Nitro-Explosives. Illustration: Danger building showing protecting mounds. See page 6. Nitro-Explosives, a practical treatise concerning the properties, manufacture, and analysis of nitrate substances, including the fulminates, smokeless powders, and celluloid, by P. Gerald Sanford, FIC, FCS. Public Analyst to the Borough of Penzance. Late Consulting Chemist to the Cotton Powder Company Limited, and formerly Resident Chemist at the Stowmarket Works of the New Explosives Company Limited, and the Hale Works of the National Explosive Company Limited. Second edition, revised and enlarged. Preface. In compiling the following treatise, my aim has been to give a brief but thoroughly practical account of the properties, manufacture, and methods of analysis of the various nitro-explosives now so largely used for mining and blasting purposes and as propulsive agents. And it is believed that the account given of the manufacture of nitroglycerin and of the gelatin dynamites will be found more complete than in any similar work yet published in this country. For many of the facts and figures contained in the chapter on smokeless powders I am indebted to, amongst others, the late Mr. J. D. Dowdall and Messrs. A. Z. Ponsonby and H. M. Chapman, FCS, and for details with regard to roburite to Messrs. H. A. Crone and W. J. Oarsman, FIC. To these gentlemen my cordial thanks are due. Among the authorities which have been consulted in the general preparation of the work may be mentioned the journals of the Chemical Society, the Society of Chemical Industry, the United States Naval Institute, and the Royal Artillery Institution. I have also referred to several volumes of the periodical publication Arms and Explosives, to various papers by Sir Frederick Abel, Bart., FRS, and General Wardell, R.A., on gun cotton, to Modern Artillery, by Captain Lloyd, R.N., and A.G. Hadcock, R.A., to the late Colonel Cundall's Dictionary of Explosives, as well as to the works of Messrs. Eisler, Berthelot, and others. The illustrations have been prepared chiefly from my own drawings. A few, however, have been taken, by permission, from the pages of Arms and Explosives, or from other sources which are acknowledged in the text. PGS The Laboratory, 20 Cullum Street, E.C. May 1896. Preface to the second edition. In the preparation of the second edition of this work, I have chiefly made use of the current technical journals, especially of the Journal of the Society of Chemical Industry. The source of my information has in every case been acknowledged. I am also indebted to several manufacturers of explosives for information respecting their special products, among others the New Explosives Company Limited, Messrs. Curtis's and Harvey Limited, the Schulze Gunpowder Company Limited, and Mr. W. D. Borland, FIC, of the E.C. Powder Company Ltd. To my friend Mr. A. Stanley Fox, FCS of Faversham, my best thanks are also due for his help in many departments, and his kindness in pointing out several references. The chapter on smokeless powders has been considerably enlarged and, as far as possible, brought up to date, but it has not always been possible to give the process of manufacture or even the composition, as these details have not, in several cases, been made public. P. Gerald Sanford. London, June 1906. Table of Contents. Chapter 1. Introduction. The nitro-explosives, substances that have been nitrate, the danger area, systems of Professors Lodge, Zenger, and Melson's for the protection of buildings from lightning, N.C. Chapter 2. Nitroglycerin. Properties of nitroglycerin, manufacture, nitration, separation, washing and filtering, drying, storing, N.C. The waste acids, their treatment, nitric acid plants. Chapter 3. Nitrocellulose, N.C. Cellulose properties, discovery of gun cotton, properties of gun cotton, varieties of soluble and insoluble gun cottons, manufacture of gun cotton, dipping and steeping, whirling out the acid, washing, boiling, pulping, compressing, the Waltham-Abbey process, Le Bouchet process, granulation of gun cotton, collodion cotton, manufacture, acid mixture used, cotton used, N.C. Nitrate gun cotton. Tonight, dangers in manufacture of gun cotton, trenches fire extinguishing compound, uses of collodion cotton, celluloid. Manufacture, N.C. Nitro starch, nitro jute, and nitromanite. Chapter 4. Dynamite. Kieselguhr dynamite, classification of dynamites, properties and efficiency of ordinary dynamite, other forms of dynamite, gelatin and gelatin dynamites, suitable guncotton for, and treatment of, other materials used, composition of gelignite, blasting gelatin, gelatin dynamite, absorbing materials, wood pulp, potassium nitrate, NC. Manufacture, NC. Apparatus used. The properties of the gelatin compounds. Chapter 5. Nitrobenzol, roburite, belite, picric acid, NC. Explosives derived from benzene, toluene and nitrobenzene, D and trinitrobenzene, roburite, properties and manufacture, belite, properties, NC. Securite, tonight number 3. Nitrotoluene, nitronaphthalene, ammonite, Sprengel's explosives, picric acid, picrates, picric powders, melanite, Abel's mixture, Brugger's powders, the fulminates, composition, formula. Preparation, danger of, NC. Detonators, sizes, composition, manufacture, fuses, NC. The fulminates. Composition, formula, preparation, danger of, NC. Detonators, sizes, composition, manufacture, fuses, NC. Chapter 6. Smokeless powders in general. Cordite, axite, ballastite, U.S. naval powder, Schultz's EC powder, indurite, Viel poudre, Walsrode and Coupe powders, amberite, Troisdorf, Bien powder, Wetterin, normal powder, maximite, picric acid powders, NC. Chapter 7. Analysis of explosives. Kieselguhr dynamite, gelatin compounds, tonite, cordite, vaseline, acetone, scheme for analysis of explosives, nitro-cotton, solubility test, non-nitrate cotton, alkalinity, ash and inorganic matter, determination of nitrogen, lunge, champion and pellets, Schulze-Tiemann, and Gjeldel's methods, celluloid, picric acid and picrates, resinous and tarry matters, sulfuric acid and hydrochloric acid and oxalic acid, nitric acid, inorganic impurities, general impurities and adulterations, potassium picrate, NC. Picrates of the alkalids, analysis of glycerin, residue, silver test, nitration, total acid equivalent, neutrality, free fatty acids, combined fatty acids, impurities, oleic acid, sodium chloride, determination of glycerin, waste acids, sodium nitrate, mercury fulminate, cap composition, table for correction of volumes of gases, for temperature and pressure. Chapter 8. Firing point of explosives, heat tests, NC. Horsley's apparatus, table of firing points, the government heat test apparatus, NC. For dynamites, nitroglycerin, nitro-cotton, and smokeless powders, Gutmann's heat test, liquefaction and exudation tests, Page's regulator for heat test apparatus, specific gravities of explosives, Will's test for nitrocellulose, table of temperature of detonation, sensitiveness, NC. Chapter 9. The determination of the relative strength of explosives. Effectiveness of an explosive, high and low explosives, theoretical efficiency, Roux and Serraul's results, Abel and Nobel's ballistic test, the mortar, pressure or crusher gauge, calculation volume of gas evolved, NC. Lead cylinders, the foot-pounds machine, Nobel's pressure gauge, Lieutenant Walk's results, calculation of pressure developed by dynamite and guncotton, McNabb's and Ristori's results of heat developed by the explosion of various explosives, composition of some of the explosives in common use for blasting, NC. Nitro-Explosives. Chapter 1. Introductory. The nitro-explosives, substances that have been nitrate, the danger area, systems of Professors Lodge, Zenger, and Melson's for the protection of buildings from lightning, NC. The manufacture of the various nitro-explosives has made great advances during late years, and the various forms of nitro compounds are gradually replacing the older forms of explosives, both for blasting purposes and also for propulsive agents, under the form of smokeless powders. The nitro-explosives belong to the so-called high explosives, and may be defined as any chemical compound possessed of explosive properties, or capable of combining with metals to form an explosive compound, which is produced by the chemical action of nitric acid, either alone or mixed with sulfuric acid, upon any carbonaceous substance, whether such compound is mechanically mixed with other substances or not. A. Footnote A. Definition given in Order of Council, No. 1, Explosives Act, 1875. The number of compounds and mixtures included under this definition is very large, and they are of very different chemical composition. Among the substances that have been nitrate are cellulose, under various forms, example, cotton, lignin, and C. Glycerin, benzene, starch, jute, sugar, phenol, wood, straw, and even such substances as treacle and horse dung. Some of these are not made upon the large scale, others are but little used. Those of most importance are nitroglycerin and nitrocellulose. The former enters into the composition of all dynamites and several smokeless powders, and the second includes gun cotton, collodion cotton, nitrate wood, and the majority of the smokeless powders, which consist generally of nitro-cotton, nitrolignin, nitrojute, and C, together with metallic nitrates, or nitroglycerin. The nitro-explosives consist generally of some organic substance in which the NO_2 group, known as nitrile, has been substituted in place of hydrogen. Thus in glycerin, OC_3H_5OO, which is a trihydric alcohol, and which occurs very widely distributed as the alcoholic or basic constituent of fats, the hydrogen atoms are replaced by the NO_2 group to form the highly explosive compound, nitroglycerin. If one atom only is thus displaced, the mononitrate is formed thus. ONO_2C_3H_5OO, and if the three atoms are displaced, C_3H_5 ONO_2_3 or the trinitrate is formed, which is commercial nitroglycerin. Another class, the nitrocelluloses, are formed from cellulose C_6H_10 O_5, which forms the groundwork of all vegetable tissues. Cellulose has some of the properties of the alcohols, and forms ethereal salts when treated with nitric and sulfuric acids. The hexanitrate, or gun cotton, has the formula C_12H_14 O_4 ONO_2_6, and collodion cotton, pyroxylin, and C, form the lower nitrates, i.e., the tetra and pentanitrates. These last are soluble in various solvents, such as ether alcohol and nitroglycerin, in which the hexanitrate is insoluble. They all dissolve, however, in acetone and acetic ether. The solution of the soluble varieties in ether alcohol is known as collodion, which finds many applications in the arts. The hydrocarbon benzene, C_6H_6, prepared from the light oil obtained from coal tar, when nitrate forms nitrobenzenes, such as mononitrobenzene, C_6H_5, NO_2, and dinitrobenzene, C_6H_4, NO_2, in which 1 and 2 atoms are replaced by the NO2 group. The latter of these compounds is used as an explosive, and enters into the composition of such well-known explosives as roburite, and C. The presence of nitro groups in a substance increases the difficulty of further nitration, and in any case not more than 3 nitro groups can be introduced into an aromatic compound, or the phenols. All aromatic compounds with the general formula C_6H_4 X_2 give, however, 3 series. They are called ortho, meta, or para compounds, depending upon the position of NO_2 groups introduced. Certain regularities have been observed in the formation of nitro compounds. If, for example, a substance contains alkyl or hydroxyl groups, large quantities of the para compound are obtained, and very little of the ortho. The substitution takes place, however, almost entirely in the meta position, if a nitro, carboxyl, or aldehyde group be present. Ordinary phenol, C_6 H_5.0 gives para and orthonitrophenol. Toluene gives para and orthonitrotoluene, but nitrobenzene forms metadinitrobenzene and benzoic acid, metanitrobenzoic acid. A. Footnote A. Organic Chemistry. Professor Gelt. Translated by J.B. Tingle, Ph.D. If the graphic formula of benzene be represented thus, number 1, then the positions 1 and 2 represent the ortho, 1 and 3 the meta, and 1 and 4 the para compounds. When the body phenol, C_6, H_5.0, is nitrate, a compound is formed known as trinitrophenol, or picric acid, C_6, H_2, No_230, which is used very extensively as an explosive, both as picric acid and in the form of picrates. Another nitro body that is used as an explosive is nitronaphthalene, C10, H_6, No_22, in roburite, securite, and other explosives of this class. The hexanitromannite C6, H_8, Ono_2_6 is formed. Illustration number 1. Illustration: metadinitrobenzene number 2. By treating a substance known as mannite C_6, H_8, O_6, an alcohol formed by the lactic acid fermentation of sugar and closely related to the sugars, with nitric and sulfuric acids. It is a solid substance, and very explosive. It contains 18.58% of nitrogen. Nitrostarch has also been used for the manufacture of an explosive. Muhlhauer has described Ding. Poly. Schuer, 73, 137–143, 3 nitric ethers of starch, the tetranitrostarch, C_12, H_16, O_6, Ono_2_4, the penta and hexanitrostarch. They are formed by acting upon potato starch dried at 100 degrees Celsius, with a mixture of nitric and sulfuric acids at a temperature of 20 degrees to 25 degrees Celsius. Rice starch has also been used in its production. Muhlhauer proposes to use this body as a smokeless powder, and to nitrate it with the spent mixed acids from the manufacture of nitroglycerin. This substance contains from 10.96 to 11.09% of nitrogen. It is a white substance, very stable and soluble even in cold nitroglycerin. The explosive bodies formed by the nitration of jute have been studied by Messrs. Cross and Bevan, and also by Muhlhauer. The former chemists give jute the formula C_12, H_18, O_9, and believe that its conversion into a nitro compound takes place according to the equation C_12, H_18, O_9, plus 3 No_3 equals 3H_2, O plus C_12, H_15, O_6, No_3. This is equivalent to a gain in weight of 44% for the trinitrate and 58% for the tetranitrate. The formation of the tetranitrate appears to be the limit of nitration of jute fiber. Messrs. Cross and Bevan say, in other words, if we represent the lignocellulose molecule by a C_12 formula, it will contain 4 hydroxyl O groups, or 2 less than cellulose similarly represented. It contains 11.5% of nitrogen. The jute nitrates resemble those of cellulose, and are in all essential points nitrates of lignocellulose. Nitrojute is used in the composition of the well-known Coop-Pal smokeless powders. Cross and Bevan are of opinion that there is no very obvious advantage in the use of lignified textile fibers as raw materials for explosive nitrates, seeing that a number of raw materials containing cellulose, chiefly as cotton, can be obtained at from 10 pounds to 25 pounds a ton, and yield also 150 to 170% of explosive material when nitrate, whereas jute only gives 154.4%, and are in many ways superior to the products obtained from jute. Nitrolignin, or nitrate wood, is, however, largely used in the composition of a good many of the smokeless powders, such as Schulze's, the Smokeless Powder Company's products, and others. The danger area. That portion of the works that is devoted to the actual manufacture or mixing of explosive material is generally designated by the term danger area, and the buildings erected upon it are spoken of as danger buildings. The best material of which to construct these buildings is of wood, as in the event of an explosion they will offer less resistance, and will cause much less danger than brick or stone buildings. When an explosion of nitroglycerin or dynamite occurs in one of these buildings, the sides are generally blown out, and the roof is raised some considerable height, and finally descends upon the blown-out sides. If, on the other hand, the same explosion had occurred in a strong brick or stone building, the walls of which would offer a much larger resistance, large pieces of brickwork would probably have been thrown for a considerable distance, and have caused serious damage to surrounding buildings. It is also a very good plan to surround all danger buildings with mounds of sand or earth, which should be covered with turf, and of such a height as to be above the roof of the buildings that they are intended to protect. See frontispiece. A. These mounds are of great value in confining the force of the explosion, and the sides of the buildings being thrown against them are prevented from traveling any distance. In gunpowder works it is not unusual to surround the danger buildings with trees or dense underwood instead of mounds. This would be of no use in checking the force of explosion of the high explosives, but has been found a very useful precaution in the case of gunpowder. Footnote A. At the Baelen factory, Belgium, the danger buildings are erected on a novel plan. They are circular in ground plan and lighted entirely from the roof by means of a patent glass having wire netting in it, and which it is claimed will not let a splinter fall, even if badly cracked. The mounds are then erected right up against the walls of the building, exceeding them in height by several meters. For this method of construction it is claimed that the force exerted by an explosion will expand itself in a vertical direction. Report on visits to certain explosive factories. H.M. Inspectors, 1905. In Great Britain it is necessary that all danger buildings should be a specified distance apart. A license also must be obtained. The application for a license must give a plan, drawn to scale, of the proposed factory or magazine, and the site, its boundaries, and surroundings, and distance the building will be from any other buildings or works, and c. also the character and construction of all the mounds, and nature of the processes to be carried on in the factory or building. A. Footnote A. Explosives Act 38 Vict. Ch. 17. Illustration, Figure 1. Section of nitroglycerin conduit. A. Lid. B. Lead lining. C. Cinders. The selection of a site for the danger area requires some attention. The purpose for which it is required, that is, the kind of explosive that it is intended to manufacture, must be taken into consideration. A perfectly level piece of ground might probably be quite suitable for the purpose of erecting a factory for the manufacture of gun-cotton or gunpowder, and such materials, but would be more or less unsuitable for the manufacture of nitroglycerin, where a number of buildings are required to be upon different levels. In order to allow of the flow of the liquid nitroglycerin from one building to another through a system of conduits. These conduits, Figure 1, which are generally made of wood and lined with lead, the space between the woodwork and the lead lining, which is generally some 4 or 5 inches, being filled with cinders, connect the various buildings, and should slope gently from one to the other. It is also desirable that, as far as possible, they should be protected by earthwork banks, in the same way as the danger buildings themselves. They should also be provided with covers, which should be whitewashed in hot weather. A great deal of attention should be given to these conduits, and they should be very frequently inspected. Whenever it is found that a portion of the lead lining requires repairing, before cutting away the lead it should be very carefully washed, for several feet on either side of the portion that it is intended to remove, with a solution of caustic soda or potash dissolved in methylated spirit and water, and afterwards with water alone. This decomposes the nitroglycerin, forming glycerin and potassium nitrate. It will be found that the mixed acids attack the lead rather quickly, forming sulfate and nitrate of lead, but chiefly the former. It is on this account that it has been proposed to use pipes made of gutta percha, but the great drawback to their use is that in the case of anything occurring inside the pipes, such as the freezing of the nitroglycerin in winter, it is more difficult to find it out, and the condition of the inside cannot be seen, whereas in the case of wooden conduits it is an easy matter to lift the lids along the whole length of the conduit. The buildings which require to be connected by conduits are of course those concerned with the manufacture of nitroglycerin. These buildings are 1. The nitrating house, 2. The separating house, 3. The filter house, 4. The secondary separator, 5. The deposit of washings, 6. The settling or precipitation house, and each of these buildings must be on a level lower than the preceding one, in order that the nitroglycerin or acids may flow easily from one building to the next. These buildings are, as far as possible, best placed together, and away from the other danger buildings, such as the cartridge huts and dynamite mixing houses, but this is not essential. All danger buildings should be protected by a lightning conductor, or covered with barbed wire, as suggested by Professor Sir Oliver J. Lodge, FRS, Professors Zenger, of Prague, and Melsons, of Brussels, and everything possible should be done to keep them as cool as possible in the summer. With this object they should be made double, and the intervening space filled with cinders. The roof also should be kept whitewashed, and the windows painted over thinly with white paint. A thermometer should be suspended in every house. It is very essential that the floors of all these buildings should be washed every day before the workpeople leave. In case any nitroglycerin is spilt upon the floors, after sponging it up as far as possible, the floor should be washed with an alcoholic solution of soda or potash to decompose the nitroglycerin, which it does according to the equation A C_3 H_5 No_3 plus 3 co equals C3 H_8 O_3 plus 3 No_3. Footnote A. See also Berthelot, Comtes Rendus, 1900, 131, 12, 519 521. Every one employed in the buildings should wear list or sewn leather shoes, which of course must be worn in the buildings only. The various houses should be connected by paths laid with cinders, or boarded with planks, and any loose sand about the site of the works should be covered over with turf or cinders, to prevent its blowing about and getting into the buildings. It is also of importance that standpipes should be placed about the works with a good pressure of water, the necessary hose being kept in certain known places where they can be at once got at in the case of fire, such as the danger area laboratory, the foreman's office, and c. It is also desirable that the above precautions against fire should be tested once a week. With regard to the heating of the various buildings in the winter, steam pipes only should be used, and should be brought from a boiler house outside the danger area, and should be covered with kieselguhr or fossil meal and tarred canvas. These pipes may be supported upon poles. A stove of some kind should be placed in the corner of each building, but it must be entirely covered in with woodwork, and as small a length of steam pipes should be within the building as possible. In the case of a factory where nitroglycerin and dynamite are manufactured, it is necessary that the workpeople should wear different clothes upon the danger area than usual, as they are apt to become impregnated with nitroglycerin, and thus not very desirable or safe to wear outside the works. It is also necessary that these clothes should not contain any pockets, as this lessens the chance of matches or steel implements being taken upon the danger area. Changing houses, one for the men, and another for the girls, should also be provided. The tools used upon the danger area should, whenever the building is in use, or contains explosives, be made of phosphor bronze or brass, and brass nails or wooden pegs should be used in the construction of all the buildings. Illustration, Figure 2. Melson's system of lightning conductors. Lightning conductors. The Explosive Substances Act, 38 Vict. Ch. 17, Clause 10 says, every factory magazine and expense magazine in a factory, and every danger building in a magazine, shall have attached thereto a sufficient lightning conductor, unless by reason of the construction by excavation or the position of such magazine or building, or otherwise, the Secretary of State considers a conductor unnecessary, and every danger building in a factory shall, if so required by the Secretary of State, have attached thereto a sufficient lightning conductor. The exact form of lightning conductor most suitable for explosive works and buildings has not yet been definitely settled. Lightning rod engineers favor what is known as the Melson's system, due to Professor Melsons, of Brussels, and Professor Zenger, of Prague, but first suggested by the late Professor Clerk Maxwell. In a paper read before the British Association, Clerk Maxwell proposed to protect powder magazines from the effects of lightning by completely surrounding or encasing them with sheet metal, or a cage of metallic conductors. There were, however, several objections to his system as he left it. Professor Melsons has, while using the idea, made several important alterations. He has multiplied the terminals, the conductors, and the earth connections. His terminals are very numerous, and assume the form of an aigrette or brush with 5 or 7 points, the central point being a little higher than the rest, which form with it an angle of 45 degrees. He employs for the most part galvanized iron wire. He places all metallic bodies, if they are of any considerable size, in communication with the conducting system in such a manner as to form closed metallic circuits. His system is illustrated in Figure 2, taken from Arms and Explosives. Footnote A. Belgian Academy of Science. This system is a near approximation to J.C. Maxwell's cage. The system was really designed for the protection of powder magazines or store buildings placed in very exposed situations. Zenger's system is identical with that of Melson's, and has been extensively tried by the Austrian military authorities, and Colonel Hess has reported upon the absolute safety of the system. Illustration, Figure 3. French system of lightning conductors. The French system of protecting powder magazines is shown in Figure 3, where there are no brush terminals or aigrettes. The French military authorities also protect magazines by erecting 2 or more lightning rods on poles of sufficient height placed close to, but not touching, the walls of the magazine. These conductors are joined below the foundations and earthed as usual. In the instructions issued by the government, it is stated that the lightning rods placed upon powder mills should be of such a height, and so situated, that no danger is incurred in igniting the powder dust in the air by the lightning discharge at the pointed rod. In such a case, a fork or aigrette of 5 or more points should invariably be used in place of a single point. Illustration, Figure 4_A_. Government system of lightning conductors for large buildings. Illustration, Figure 4_B_. Government system of lightning conductors for small buildings. In Figure 4A and B is shown the government method for protecting buildings in which explosives are made or stored. Multiple points or aigrettes would be better. Lord Kelvin and Professor Melsons favor points, and it is generally admitted that lightning does not strike buildings at a single point, but rather in a sheet. Hence, in such cases, or in the event of the globular form being assumed by the lightning, the aigrette will constitute a much more effective protection than a single point. As to the spacing of conductors, they may, even on the most important buildings, be spaced at intervals of 50 feet. There will then be no point on the building more than 25 feet from the conductor. This 25 feet rule can be adhered to with advantage in all overground buildings for explosives. Underground magazines should, whenever possible, also be protected, because, although less exposed than overground buildings, they frequently contain explosives packed in metal cases, and hence would present a line of smaller electrical resistance than the surrounding earth would offer to the lightning. The conductor should be arranged on the same system as for overground buildings, but be applied to the surface of the ground over the magazines. In all situations where several conductors are joined in one system, the vertical conductors should be connected both at the top and near the ground line. The angles and the prominent portions of a building being the most liable to be struck, the conductors should be carried over and along these projections, and therefore along the ridges of the roof. The conductors should be connected to any outside metal on the roofs and walls, and specially to the foot of rainwater pipes. All the lightning conductors should be periodically tested, to see that they are in working condition, at least every 3 months, according to Mr. Richard Anderson. The object of the test is to determine the resistance of the earth connection, and to localize any defective joints or parts in the conductors. The best system of testing the conductors is to balance the resistance of each of the earths against the remainder of the system, from which the state of the earths may be inferred with sufficient accuracy for all practical purposes. Captain Bucknell, R.E., has designed an instrument to test resistance which is based on the post office pattern resistance coil, and is capable of testing to approximate accuracy up to 200 ohms, and to measure roughly up to 2000 ohms. Mr. R. Anderson's apparatus is also very handy, consisting of a case containing 3 Leclanche cells, and a galvanometer with a tangent, scale, and certain standard resistances. Some useful articles on the protection of buildings from lightning will be found in Arms and Explosives, July, August, and September 1892, and by Mr. Anderson, Brit. Associate, 1878-80. Nitroglycerin. One of the most powerful of modern explosive agents is nitroglycerin. It is the explosive contained in dynamite, and forms the greater part of the various forms of blasting gelatins, such as gelatin dynamite and gelignite, both of which substances consist of a mixture of guncotton dissolved in nitroglycerin, with the addition of varying proportions of wood pulp and saltpetre, the latter substances acting as absorbing materials for the viscid gelatin. Nitroglycerin is also largely used in the manufacture of smokeless powders, such as cordite, ballastite, and several others. Nitroglycerol, or glycerol trinitrate, was discovered by Sobrero in the year 1847. In a letter written to M. Palaus, he says, "When glycerol is poured into a mixture of sulfuric acid of a specific gravity of 1.84 and of nitric acid of a gravity of 1.5, which has been cooled by a freezing mixture, that an oily liquid is formed. This liquid is nitroglycerol, or nitroglycerin, which for some years found no important use in the arts, until the year 1863, when Alfred Nobel first started a factory in Stockholm for its manufacture upon a large scale, but on account of some serious accidents taking place, its use did not become general. It was not until Nobel conceived the idea, in 1866, of absorbing the liquid in some absorbent earth, and thus forming the material that is now known as dynamite, that the use of nitroglycerin as an explosive became general. Among those who improved the manufacture of nitroglycerin was Mowbray, who, by using pure glycerin and nitric acid free from nitrous acid, made very great advances in the manufacture. Mowbray was probably the first to use compressed air for the purpose of keeping the liquids well agitated during the process of nitration, which he conducted in earthenware pots, each containing a charge of 17 pounds of the mixed acids and 2 pounds of glycerol. A few years later, 1872, MM Boutny and Fauché, of Vannes, proposed to prepare nitroglycerin by mixing the sulfuric acid with the glycerin, thus forming a sulfoglyceric acid, which was afterwards mixed with a mixture of nitric and sulfuric acids. They claimed for this method of procedure that the final temperature is much lower. The two mixtures are mixed in the proportions: glycerin 100, nitric acid 280, and sulfuric acid 600. They state that the rise of temperature upon mixing is limited from 10 degrees to 15 degrees Celsius, but this method requires a period of 24 hours to complete the nitration, which, considering the danger of keeping the nitroglycerin in contact with the mixed acids for so long, probably more than compensates for the somewhat doubtful advantage of being able to perform the nitration at such a low temperature. The Boutny process was in operation for some time at Pembrey Burrows in Wales, but after a serious explosion the process was abandoned. Footnote A. Comptes Rendus 75, and Dissortios. Traits sur la poudre. 684 to 686. Nitroglycerin is now generally made by adding the glycerin to a mixture of sulfuric and nitric acids. The sulfuric acid, however, takes no part in the reaction, but is absolutely necessary to combine with the water that is formed by the decomposition, and thus to keep up the strength of the nitric acid, otherwise lower nitrates of glycerin would be formed that are soluble in water, and which would be lost in the subsequent process of washing to which the nitro compound is subjected. In order to remove the excess of acids, the retention of which in the nitroglycerol is very dangerous. Nitroglycerol, which was formerly considered to be a nitro-substitution compound of glycerol, was thought to be formed thus. C_3 H_8 O_3 plus 3 No_3 equals C 3 H_5 No_2 303 plus 3H_2O. But more recent researches rather point to its being regarded as a nitric ether of glycerol, or glycerin, and to its being formed thus. C_3H_8O_3 plus 3No_3 equals C3H_5 No_3 plus 3H2O 92,227. The formula of glycerin is C_3H_8O_8 or C_3H_5OO. ono_2, and that of the mononitrate of glycerin, C_3H_5OO. ono_2, and of the trinitrate or nitroglycerin, C_3H_5 ono_2. That is, the three hydrogens of the semi-molecules of hydroxyl in the glycerin have been replaced by the No_2 group. In the manufacture upon the large scale, a mixture of 3 parts by weight of nitric acid and 5 parts of sulfuric acid are used. From the above equation it will be seen that every 1 pound of glycerol should give 2.47 pounds of nitroglycerol. 227 plus 1/92 equals 2.47, but in practice the yield is only about 2 pounds to 2.22, the loss being accounted for by the unavoidable formation of some of the lower nitrate, which dissolves in water and is thus washed away, and partly perhaps to the presence of a little water, or other non-nitrable matter, in the glycerin, but chiefly to the former, which is due to the acids having become too weak. Chapter 2. Manufacture of nitroglycerin. Properties of nitroglycerin. Manufacture of nitroglycerin. Nitration. The Nathan nitrator. Separation. Filtering and washing. The waste acids. Treatment of the waste acid from the manufacture of nitroglycerin and gun cotton. Properties of nitroglycerin. Nitroglycerol is a heavy oily liquid of specific gravity 1.6 at 15 degrees Celsius, and when quite pure is colorless. The commercial product is a pale straw yellow, but varies much according to the purity of the materials used in its manufacture. It is insoluble in water, crystallizes at 10.5 degrees Celsius, but different commercial samples behave very differently in this respect, and minute impurities prevent or delay crystallization. Solid nitroglycerol, A, melts at about 12 degrees Celsius, but requires to be exposed to this temperature for some time before melting. The specific gravity of the solid form is 1.735 at plus 10 degrees Celsius. It contracts 1/12 of its volume in solidifying. Beckerheim, B, gives the specific heat as 0.4248 between the temperatures of 9.5 degrees and 9.8 degrees Celsius, and L. De Bruyne gives the boiling point as above 200 degrees. Footnote A. Dinitromonochlorhydrin, when added to nitroglycerin up to 20%, is said to prevent its freezing. Footnote B. ISB, Chem. Tech. 22, 481 to 487. 1876. Nitroglycerin has a sweet taste, and causes great depression and vertigo. It is soluble in ether, chloroform, benzene, glacial acetic acid, and nitrobenzene, in 1.75 part of methylated spirit, very nearly insoluble in water, and practically insoluble in carbon bisulfide. Its formula is C_3H_5 No_3 and molecular weight 227. When pure, it may be kept any length of time without decomposition. Berthelot kept a sample for 10 years, and Mr. G. M. Roberts, of the Ardere factory, for 9 years, without their showing signs of decomposition. But if it should contain the smallest trace of free acid, decomposition is certain to be started before long. This will generally show itself by the formation of little green spots in the gelatin compounds, or a green ring upon the surface of liquid nitroglycerin. Sunlight will often cause it to explode. In fact, a bucket containing some water that had been used to wash nitroglycerin, and had been left standing in the sun, has in our experience been known to explode with considerable force. Nitroglycerin when pure is quite stable at ordinary temperatures, and samples have been kept for years without any trace of decomposition. It is very susceptible to heat, and even when quite pure will not stand a temperature of 100 degrees Celsius for a longer period than a few hours, without undergoing decomposition. Up to a temperature of 45 degrees Celsius. However, properly made and purified nitroglycerin will remain unchanged almost indefinitely. The percentage composition of nitroglycerin is as follows. Found. Theory for C_3, H_5, N0_2_3. Carbon 15.62, 15.86%. Hydrogen 2.40, 2.20. Nitrogen 17.90, 18.50. Oxygen 63.44. The above analysis is by Beckerheim. Sauer and Adu give the nitrogen as 18.35 to 10.54% by Dumas method, but I have never found any difficulty in obtaining percentages as high as 18.46 by the use of Lunge's nitrometer. The decomposition products by explosion are shown by the following equation. 2C_3 H_5 no_3 equals 6 co 2 plus 5 H_2 O plus 6 N plus O. That is, it contains an excess of 3.52% of oxygen above that required for complete combustion. 100 grms would be converted into carbonic acid co_2 58.15%, water 19.83, oxygen 3.52%, nitrogen 18.50. The volume of gases produced at 0 degrees and 760 millimeters, calculated from the above, is 714 liters per kilo, the water being taken as gaseous. Nitroglycerin is decomposed differently if it is ignited as dynamite, i.e., Kieselguhr dynamite, and if the gases are allowed to escape freely under a pressure nearly equal to that of the atmosphere. Serrao and Vie obtained under these conditions, for 100 volumes of gas, No 48.2%, Co 35.9, Co_2, 12.7, H 1.6%, N 1.3, CH_4 0.3. These conditions are similar to those under which a mining charge, simply ignited by the cap, burns away slowly under a low pressure, i.e., a misfire. In a recent communication, P.F. Challen, Engineering and Mining Journal, 1892, says that in practice nitroglycerin vapor, carbon monoxide, and nitrous oxide are also produced as the result of detonation, but he attributes their formation to the use of a too feeble detonator. Nitroglycerin explodes very violently by concussion. It may be burned in an open vessel, but if heated above 250 degrees Celsius, it explodes. Professor C. Monroe gives the firing point as 203°-205 degrees C, and L. De Bruyne, A., states its boiling point as 185 degrees. He used the apparatus devised by Horsley. The heat of formation of nitroglycerin, as deduced from the heat of combustion by M. Longuinin, is 432 calories for 1 grm, and the heat of combustion equals 1,576 calories for 1 grm. In the case of nitroglycerin, the heat of total combustion and the heat of complete decomposition are interchangeable terms, since it contains an excess of oxygen. According to Dr. W. H. Perkin, F.R.S., B, the magnetic rotation of nitroglycerin is 5,407, and that of trimethylene nitrate, 4.769, diff, equals 0.638. Dr. Perkin says, had nitroglycerin contained its nitrogen in any other combination with oxygen than as NO_2, as it might if its constitution had been represented as C_3, H_2, No_2,303, the rotation when compared with propyl nitrate, 4.085, would be abnormal. Footnote A. Jour SOC Chem. IND, June 1896, page 471. Footnote B. Jour Chem. SOC, W. H. Perkin, 1889, page 726. The solubility of nitroglycerin in various solvents has been investigated by H. Elliott. His results may be summarized as follows. Underscore 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 solvent cold warm underscore 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 water insoluble slightly soluble alcohol absolute soluble soluble 93% 80% slowly soluble 50% insoluble slightly soluble methyl alcohol soluble soluble amyl ether ethylic acetic, chloroform, acetone, sulfuric acid, 1.845, nitric acid, 1.400, slowly soluble. Hydrochloric acid, 1.200, insoluble, decomposed, slowly soluble acetic. Acid glacial, soluble, soluble carbolic acid, astral oil, insoluble, insoluble olive, soluble, soluble stearine oil, mineral jelly, insoluble, insoluble glycerin, benzene, soluble, soluble nitrobenzene, toluene, carbon bisulfide, insoluble, slightly affected turpentine, soluble petroleum naphtha, 71 to 76 degrees B, insoluble caustic soda, 110 solution, insoluble, insoluble, borax, 5% solution, ammonia, 0.980, slightly affected. Ammonium sulfhydrate, insoluble, sulfur, decomposed. Separates, iron sulfate solution, slightly affected, affected. Iron chloride, 1.4 grm. Fe, slowly affected, decomposed. To 10 ccN underscore 2O, tin chloride, slightly affected, affected. Underscore 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 underscore. Many attempts have been made to prepare nitroglycerin explosives capable of withstanding comparatively low temperatures without freezing, but no satisfactory solution of the problem has been found. Among the substances that have been proposed and used with more or less success are nitrobenzene, nitrotoluene, dinitromonochlorhydrin, solid nitro derivatives of toluene, are stated to lower the freezing point of nitroglycerin to -20 degrees Celsius, without altering its sensitiveness and stability. The subject has been investigated by S. Knockhoff, B., who states that nitroglycerin can be cooled to temperatures -40 degrees to -50 degrees Celsius, much below its true freezing point, without solidifying, by the addition of various substances. When cooled by means of a mixture of solid carbon, dioxide, and ether, it sets to a glassy mass, without any perceptible crystallization. The mass, when warmed to 0 degrees Celsius, first rapidly liquefies and then begins to crystallize. The true freezing point of pure nitroglycerin was found to be 12.3 degrees Celsius. The technical product, owing to the presence of dinitroglycerin, freezes at 10.5 degrees Celsius. According to Raoult's law, the lowering of the freezing point caused by mgrms of a substance with the molecular weight m, when dissolved in 100 grms of the solvent, is expressed by the formula delta equals E m/m, where E is a constant characteristic for the solvent in question. The value of E for nitroglycerin was found to be 70.5 when calculated, according to Van 't Hoff's formula, from the melting point and the latent heat of fusion of the substance. Determinations of the lowering of the freezing point of nitroglycerin by additions of benzene, nitrobenzene, dinitrobenzene, trinitrobenzene, P, nitrotoluene, O, nitrotoluene, dinitrotoluene, naphthalene, nitronaphthalene, dinitronaphthalene, ethyl acetate, ethyl nitrate, and methyl alcohol, gave results agreeing fairly well with Raoult's formula, except in the case of methyl alcohol, for which the calculated lowering of the freezing point was greater than that observed, probably owing to the formation of complex molecules in the solution. The results show that, in general, the capacity of a substance to lower the freezing point of nitroglycerin depends, not upon its freezing point, or its chemical composition or constitution, but upon its molecular weight. Nockhoff states that a suitable substance for dissolving in nitroglycerin, in order to lower the freezing point of the latter, must have a relatively low molecular weight, must not appreciably diminish the explosive power and stability of the explosive, and must not be easily volatile at relatively high atmospheric temperatures. It should, if possible, be a solvent of nitrocellulose, and in every case must not have a prejudicial influence on the gelatinization of the nitrocellulose. Footnote A.M. Pat. 25797, November 1904. Footnote B.Z. and Ju. Chem. 1905, 18, 11-22, 53-60. Manufacture of nitroglycerin. Nitroglycerin is prepared upon the manufacturing scale by gradually adding glycerin to a mixture of nitric and sulfuric acids of great strength. The mixed acids are contained in a lead vessel, which is kept cool by a stream of water continually passing through worms in the interior of the nitrating vessel, and the glycerin is gradually added in the form of a fine stream from above. The manufacture can be divided into 3 distinct operations, viz., nitration, separation, and washing, and it will be well to describe these operations in the above order. Nitration. The most essential condition of nitrating is the correct composition and strength of the mixed acids. The best proportions have been found to be 3 parts by weight of nitric acid of a specific gravity 1.525 to 1.530, and containing as small a portion of the oxides of nitrogen as possible, to 5 parts by weight of sulfuric acid of a specific gravity of 1.840 at 15 degrees Celsius, and about 97% of monohydrate. It is of the very greatest importance that the nitric acid should be as strong as possible. Nothing under a gravity of 1.52 should ever be used even to mix with stronger acid, and the nitration will be proportional to the strength of the acid used, provided the sulfuric acid is also strong enough. It is also of great importance that the oxides of nitrogen should be low, and that they should be kept down to as low as 1%, or even lower. It is also very desirable that the nitric acid should contain as little chlorine as possible. The following is the analysis of a sample of nitric acid, which gave very good results upon the commercial scale. Specific gravity 1.525 and underscore 2 O underscore 4 1.03%. Nitric acid no underscore 3 95.58%. The amount of real nitric acid monohydrate and the amount of nitric peroxide present in any sample should always be determined before it is used for nitrating purposes. The specific gravity is not a sufficient guide to the strength of the acid, as an acid having a high gravity, due to some 3 or 4% of nitric oxides in solution, will give very poor nitration results. A 10th normal solution of sodium hydroxide (NaO) with phenolphthalein as indicator will be found the most convenient method of determining the total acid present. The following method will be found to be very rapid and reliable. Weigh a 100 cc flask, containing a few cubic centimeters of distilled water, and then add from a pipette 1 cc of the nitric acid to be examined, and reweigh. This gives the weight of acid taken. Now make up to 100 cc at 15 degrees Celsius. Shake well, and take out 10 cc with a pipette, drain into a small Erlenmeyer flask, and add a little of the phenolphthalein solution, and titrate with the 10th normal soda solution. The nitric peroxide can be determined with a solution of potassium permanganate of N/10 strength. Thus, take a small conical flask, containing about 10 cc of water, and add from a burette 10 to 16 cc of the permanganate solution, then add 2 cc of the acid to be tested, and shake gently, and continue to add permanganate solution as long as it is decolorized, and until a faint pink color is permanent. Example: N/10 permanganate 3.16 grms per liter, 1 cc equals 0.0046 grm. N_2O_4 2 cc of sample of acid specific gravity 1.52 is equal to 3.04 grms. Taken for analysis. Took 20 cc permanganate solution, 0.0046 x 20 equals 0.092 grm. N_2O_4 and 0.092 by 100/3.04 equals 3.02%. N_2O_4. The specific gravity should be taken with an hydrometer that gives the specific gravity directly, or, if preferred, the 2 cc of acid may be weighed. A very good method of rapidly determining the strength of the sulfuric acid is as follows. Weigh out in a small weighing bottle, as nearly as possible, 2.45 grms. This is best done by running in 1.33 cc of the acid. 1.33 times 1.84 is equal to 2.447. Wash into a large Erlenmeyer flask, carefully washing out the bottle, and also the stopper, and c. Add a drop of phenolphthalein solution and titrate. With a half normal solution of sodium hydrate, use a 100 cc burette. Then if 2.45 grms exactly have been taken, the readings on the burette will equal percentages of H_2, SO_4 monohydrate. If not, calculate thus: 2.444 grms. Weighed, required 95.4 cc NaO. Then 2.444, 95.4, 2.45x equals 95.64%. H_2, SO_4. It has been proposed to free nitric acid from the oxides of nitrogen by blowing compressed air through it, and thus driving the gases in solution out. The acid was contained in a closed lead tank, from which the escaping fumes were conducted into the chimney shaft, and on the bottom of which was a lead pipe, bent in the form of a circle, and pierced with holes, through which the compressed air was made to pass. But the process was not found to be of a very satisfactory nature, and it is certainly better not to allow the formation of these compounds in the manufacture of the acid in the first instance. Another plan, however, is to heat the acid gently, and thus drive out the nitrous gases. Both processes involve loss of nitric acid. Having obtained nitric and sulfuric acids as pure as possible, the next operation is to mix them. This is best done by weighing the carboys in which the acids are generally stored before the acids are drawn off into them from the condensers, and keeping their weights constantly attached to them by means of a label. It is then a simple matter to weigh off as many carboys of acid as may be required for any number of mixings, and subtract the weights of the carboys. The two acids should, after being weighed, be poured into a tank and mixed, and subsequently allowed to flow into an acid egg or Mondjus, to be afterwards forced up to the nitrating house in the danger area. The Mondjus or acid egg is a strong cast iron tank, of either an egg shape or a cylinder with a round end. If of the former shape, it would lie on its side, and upon the surface of the ground, and would have a manhole at one end, upon which a lid would be strongly bolted down. But if of the latter shape, the lid, of course, is upon the top, and the mod just itself is let into the ground. In either case, the principle is the same. One pipe, made of stout lead, goes to the bottom, and another just inside to convey the compressed air, the acids flowing away as the pressure is put on, just as blowing down one tube of an ordinary wash bottle forces the water up the other tube to the jet. The pressure necessarily will, of course, vary immensely, and will depend upon the height to which the acid has to be raised and the distance to be traversed. The mixed acids having been forced up to the danger area, and to a level higher than the position of the nitrating house, should, before being used, be allowed to cool, and let in tanks of sufficient capacity to hold at least enough acid for 4 or 5 nitrations should be placed in the wooden house upon a level at least 6 or 7 feet above the nitrating house. In this house also should be a smaller lead tank, holding, when filled to a certain mark, just enough of the mixed acids for 1 nitration. The object of this tank is, that as soon as the man in charge knows that the last nitration is finished, he refills this smaller tank, which contains just enough of the mixed acids, and allows its contents to flow down into the nitrating house and into the nitrator, ready for the next nitration. The nitration is usually conducted in a vessel constructed of lead, some 4 feet wide at the bottom, and rather less at the top, and about 4 feet or so high. The size, of course, depends upon the volume of the charge it is intended to nitrate at one operation, but it is always better that the tank should be only 2/3 full. A good charge is 16 cwt of the mixed acids, in the proportion of 3 to 5, that is, 6 cwt of nitric acid, and 10 cwt of sulfuric acid, and 247 pounds of glycerin. Upon reference to the equation showing the formation of nitroglycerin, it will be seen that for every 1 pound of glycerin 2.47 pounds of nitroglycerin should be furnished, but in practice the yield is only a little over 2 pounds, the loss being accounted for by the unavoidable formation of some of the lower nitrate of glycerin, the mononitrate, which afterward dissolves in the washing waters. The lead tank, figure 5, is generally cased in woodwork, with a platform in front for the man in charge of the nitrating to stand upon, and whence to work the various taps. The top of the tank is closed in with a dome of lead, in which is a small glass window, through which the progress of the nitrating operation can be watched. From the top of this dome is a tube of lead which is carried up through the roof of the building. It serves as a chimney to carry off the acid fumes which are given off during the nitration. The interior of this tank contains at least 3 concentric spirals of at least 1-inch lead pipe, through which water can be made to flow during the whole operation of nitrating. Another lead pipe is carried through the dome of the tank, as far as the bottom, where it is bent round in the form of a circle. Through this pipe, which is pierced with small holes, about 1 inch apart, compressed air is forced at a pressure of about 60 pounds, in order to keep the liquids in a state of constant agitation during the whole period of nitration. There must also be a rather wide pipe, of say 2 inches internal diameter, carried through the dome of the tank, which will serve to carry the mixed acid to be used in the operation into the tank. There is still another pipe to go through the dome, viz., one to carry the glycerin into the tank. This need not be a large bore pipe, as the glycerin is generally added to the mixed acids in a thin stream. An injector is often used. Footnote A. Thus if 92 pounds, glycerin give 227 pounds. Nitroglycerin, 277 by 1/92 equals 2.47 pounds. Illustration, figure 5. Top of nitrator. A. Fume pipe. B. Water pipes for cooling. C. Acid mixture pipe. E. Compressed air. G. Glycerin pipe and funnel. T. Thermometer. W. Window. Before the apparatus is ready for use, it requires to have 2 thermometers fixed, one long one to reach to the bottom of the tank, and one short one just long enough to dip under the surface of the acids. When the tank contains its charge, the former gives the temperature of the bottom, and the latter of the top of the mixture. The glycerin should be contained in a small cistern, fixed in some convenient spot upon the wall of the nitrating house, and should have a pipe let in flush with the bottom, and going through the dome of the nitrating apparatus. It must of course be provided with a tap or stopcock, which should be placed just above the point where the pipe goes through the lead dome. Some method of measuring the quantity of glycerin used must be adopted. A gauge tube graduated in inches is a very good plan, but it is essential that the graduation should be clearly visible to the operator upon the platform in front of the apparatus. A large tap made of earthenware, and covered with lead, is fixed in the side of the nitrating tank just above the bottom, to run off the charge after nitration. This should be so arranged that the charge may be at option run down the conduit to the next house or discharged into a drowning tank, which may sometimes be necessary in cases of decomposition. The drowning tank is generally some 3 or 4 yards long and several feet deep, lined with cement, and placed close outside the building. The apparatus having received a charge of mixed acids, the water is started running through the pipes coiled inside the tank, and a slight pressure of compressed air is turned on, to mix the acids up well before starting. The nitration should not be commenced until the 2 thermometers register a temperature of 18 degrees Celsius. The glycerin tap is then partially opened, and the glycerin slowly admitted, and the compressed air turned on full until the contents of the apparatus are in a state of very brisk agitation. A pressure of about 40 pounds is about the minimum, if 247 pounds of glycerin and 16 cwt of acids are in the tank. If the glycerin tube is fitted with an injector, it may be turned on almost at once. The nitration will take about 30 minutes to complete, but the compressed air and water should be kept on for an additional 10 minutes after this, to give time for all the glycerin to nitrate. The temperature should be kept as low as possible, not above 18 degrees Celsius. Footnote A. At the Halton factory, Germany, cylinders of compressed carbon dioxide are connected with the air pipes so that in the event of a failure of the air supply the stirring can be continued with this gas if necessary. The chief points to attend to during the progress of the nitration are 1. The temperature registered by the 2 thermometers. 2. The color of the nitrous fumes given off, as seen through the little window in the dome of the apparatus. 3. The pressure of the compressed air as seen from a gauge fixed upon the air pipe just before it enters the apparatus. 4. The gauge showing the quantity of glycerin used. The temperature, as shown by either of the 2 thermometers, should not be at any time higher than 25 degrees Celsius. If it rises much above this point, the glycerin should be at once shut off, and the pressure of air increased for some few minutes until the temperature falls, and no more red fumes are given off. The nitration being finished, the large earthenware tap at the bottom of the tank is opened, and the charge allowed to flow away down the conduit to the next building, i.e., to the separator. The nitrating house is best built of wood, and should have a closed boarded floor, which should be kept scrupulously clean, and free from grit and sand. A wooden pail and a sponge should be kept in the house in order that the workmen may at once clean up any mess that may be made, and a small broom should be handy, in order that any sand, may be at once removed. It is a good plan for the nitrator to keep a book in which he records the time of starting each nitration, the temperature at starting and at the finish, the time occupied, and the date and number of the charge, as this enables the foreman of the danger area at any time to see how many charges have been nitrate, and gives him other useful information conducive to safe working. Edward Liebert has devised an improvement in the treatment of nitroglycerin. He adds ammonium sulfate or ammonium nitrate to the mixed acids during the operation of nitrating, which he claims destroys the nitrous acid formed according to the equation NH_4 2 so 4 plus 2 no 3 equals H_2 so 4 plus 2 N 2 plus 4 H_2 O. I am not aware that this modification of the process of nitration is in use at the present time. The newly made charge of nitroglycerin, upon leaving the nitrating house, flows away down the conduit, either made of rubber pipes, or better still, of woodwork, lined with lead and covered with lids made of wood, in short lengths, in order that by lifting them at any point the condition of the conduit can be examined, as this is of the greatest importance. And the conduit requires to be frequently washed out, and the sulfate of lead removed. This sulfate always contains nitroglycerin, and should therefore be burnt in some spot far removed from any danger building or magazine, as it frequently explodes with considerable violence. Illustration: Figure 6. Small nitrator. N. Tap for discharging. P. Water pipes. T. Thermometer. W. Windows. P. Glycerin pipe. In works where the manufacture of nitroglycerin is of secondary importance, and some explosive containing only perhaps 10% of nitroglycerin is manufactured, and where 50 or 100 pounds of glycerin are nitrate at one time, a very much smaller nitrating apparatus than the one that has been already described will be probably all that is required. In this case, the form of apparatus shown in Figure 6 will be found very satisfactory. It should be made of stout lead, all lead used for tanks, and C. must be chemical lead, and may be made to hold 50 or 100 pounds, as found most convenient. This nitrator can very well be placed in the same house as the separator. In fact, where such a small quantity of nitroglycerin is required, the whole series of operations, nitrating, separation, and washing, and C. may very well be performed in the same building. It will of course be necessary to place the nitrator on a higher level than the separator, but this can easily be done by having platforms of different heights, the nitration being performed upon the highest. The construction of this nitrator is essentially the same as in the larger one, the shape only being somewhat different. 2 water coils will probably be enough, and 1 thermometer. It will not be necessary to cover this foreman with woodwork. The Nathan nitrator. A. This nitrator is the patent of Lt. Colonel F.L. Nathan and Messrs. J.M. Thompson and W. Rintoul of Waltham Abbey, and will probably before long entirely supersede all the other forms of nitrator on account of its efficiency and economy of working. With this nitrator it is possible to obtain from 2.21 to 2.22 parts of nitroglycerin from every 1 part of glycerin. The apparatus is so arranged that the nitration of the glycerin, the separation of nitroglycerin produced, as well as the operation of after separation, are carried out in one vessel. The usual nitrating vessel is provided with an acid inlet pipe at the bottom, and a glass separation cylinder with a lateral exit or overflow pipe at the top. This cylinder is covered by a glass hood or bell jar during nitration to direct the escaping air and fumes into a fume pipe where the flow of the latter may be assisted by an air injector. The lateral pipe in the separation cylinder is in connection with a funnel leading to the pre-washed tank. The drawing, Figure 7, shows a vertical section of the apparatus, is the nitrating vessel of usual construction, having at the bottom an acid inlet pipe with 3 branches, 1 leading to the denitrating plant, C leading to the drowning tank, and D, which extends upwards and has 2 branches, E leading to the nitrating acids tank, and F to the waste acid tank. On the sloped bottom of the nitrating vessel lies a coil G of perforated pipe for blowing air, and there are in the vessel several coils H, 3 shown in the drawing, for circulation of cooling water. At the top of the vessel there is a glass cylinder I, having a lateral outlet J directed into the funnel mouth of a pipe K leading to the pre-washed tank. Over the cylinder I is a glass globe L, into which opens a pipe M for leading off fumes which may be promoted by a compressed air jet from a pipe or operating as an injector. Into an opening of the glass dome L is inserted a vessel N, which is connected by a flexible pipe P to the glycerin tank, and from the bottom of N, which is perforated and covered with a disc perforated with holes registering with those through the bottom, this disc being connected by a stem with a knob Q by which it can be turned so as to throttle or cut off passage of glycerin through the bottom. S is a thermometer for indicating the temperature of the contents of the vessel. Footnote AM. Pat. 15983, August 1901. Illustration, Figure 7. Nathan's nitrator for nitroglycerin. A. Nitrating vessel. B. To separating vessel. C. To drowning tank. E. Nitrating acids enter. F. To the waste acids. G. Coils for compressed air. H. Pipes for cooling water. I. Glass cylinder. J. Outlet to K. K. Leading to pre-wash tank. L. Glass dome. M. Pipe to lead off for escape of fumes. N. Vessel. P. Pipe conveying glycerin. Q. Knob to turn off glycerin. R. Compressed air jet. S. Thermometer. In operating with this apparatus, the nitrating acid is introduced into the nitrating vessel by opening the cock of the pipe E. The glycerin is then run in by introducing N and opening the valve at its bottom, the contents of the vessel being agitated by air blown through the perforations of the pipe G. When the glycerin is all nitrate and the temperature has slightly fallen, the circulation of the water through the coils H and the air stirring are stopped, and the glycerin supply vessel N is removed. The nitroglycerin as it separates from the acids is raised by introducing by the pipe F waste acid from a previous charge, this displacing the nitroglycerin upwards and causing it to flow by the outlet J and pipe K to the pre-washed tank. When nearly all the nitroglycerin has been separated in this manner, the acids in the apparatus may be run off by the pipe B to an after-separating vessel for further settling, thus leaving the apparatus free for another nitration, or the nitrating vessel itself may be used as an after-separating bottle displacing the nitroglycerin with waste acid as it rises to the top, or skimming off in the usual manner. When the separation of the nitroglycerin is complete, the waste acid is run off and denitrated as usual, a portion of it being reserved for the displacement of the nitroglycerin in a subsequent operation. In a further patent on Pat. 3020, 1903, the authors propose with the object of preventing the formation and separation of nitroglycerin in the waste acids, after the nitroglycerin initially formed in the nitrating vessel has been separated and removed, to add a small quantity of water to the waste acids. This is carried out as follows. A relatively small quantity of water is added, and this prevents all further separation of nitroglycerin, and at the same time the strength of the waste acids is so slightly reduced that their separation and reconcentration are not affected. After separation is thus done away with, and the nitroglycerin plant simplified and its output increased. After nitration, separation is commenced at a temperature such that when all the displacing acid has been added, and the separation of the nitroglycerin is complete, the temperature of the contents of the nitrating vessel shall not be lower than 15 degrees Celsius. A sufficient quantity of the displacing acid is then run off through the waste acid cock to allow of the remaining acids being air stirred without splashing over the top. A small quantity of water, from 2 to 3%, according to strength of acid. If waste consists of sulfuric acid monohydrate 62%, nitric acid anhydrous 33%, and water 5%, temperature 15 degrees Celsius, then 2% of water is added. If waste acids contain less than 4% of water of temperature lower than 15 degrees Celsius, from 3 to 5% of water may have to be added. The water is added slowly through the separator cylinder, and the contents of the nitrator air stirred, but not cooled, the temperature being allowed to rise slowly and regularly as the water is added, usually about 3 degrees Celsius, for each % of water added. When air agitation has been stopped, the acids are kept at rest for a short time, in order to allow of any small quantity of initially formed nitroglycerin adhering to the coils and sides of the vessel rising to the top. When this has been separated by displacement, the acids are ready for denitration, or can be safely stored without further precaution. Separation. The nitroglycerin, together with the mixed acids, flows from the nitrating house to the separating house, which must be on a lower level than the former. The separating house contains a large lead-lined tank, closed in at the top with a wooden lid, into which a lead pipe of large bore is fixed, and which is carried up through the roof of the building, and acts as a chimney to carry off any fumes. A little glass window should be fixed in this pipe in order that the color of the escaping fumes may be seen. The conduit conveying the nitroglycerin enters the building close under the roof, and discharges its contents into the tank through the pipe G, figure 8. The tank is only about 2/3 filled by the charge. There is in the side of the tank a small window of thick plate glass, which enables the workman to see the level of the charge, and also to observe the progress of the separation, which will take from 30 minutes to 1 hour. The tank should be in connection with a drowning tank, as the charge sometimes gets very dangerous in this building. It must also be connected by a conduit with the filter house, and also to the secondary separator by another conduit. The tank should also be fitted with a compressed air pipe, bent in the form of a loop. It should lie upon the bottom of the vat. The object of this is to mix up the charge in case it should get too hot through decomposition. A thermometer should of course be fixed in the lid of the tank, and its bulb should reach down to the middle of the nitroglycerin, which rests upon the surface of the mixed acids, the specific gravity of the nitroglycerin being 1.6, and that of the waste acids 1.7. The composition of the acids is now 11%, No underscore 3, 67%, H underscore 2, so underscore 4, and 22% water, and the temperature carefully watched. Illustration, Figure 8. Separator. A. Compressed air pipes. G. Nitroglycerin enters from nitrator. N. Nitroglycerin to P. L. Lantern window. W. Window inside. S. Waste acids to secondary separator. T. Tap to remove last traces of nitroglycerin. P. Lead washing tank. A. Compressed air. W. Water pipe. N. Nitroglycerin from separator. If nothing unusual occurs, and it has not been necessary to bring the compressed air into use, and so disturb the process of separation, the waste acids may be run away from beneath the nitroglycerin, and allowed to flow away to the secondary separator, where any further quantity of nitroglycerin that they contain separates out after resting for some days. The nitroglycerin itself is run into a smaller tank in the same house, where it is washed 3 or 4 times with its own bulk of water, containing about 3 pounds of carbonate of soda to neutralize the remaining acid. This smaller tank should contain a lead pipe, pierced and coiled upon the bottom, through which compressed air may be passed, in order to stir up the charge with the water and soda. After this preliminary washing, the nitroglycerin is drawn off into India-rubber buckets, and poured down the conduit to the filter house. The wash waters may be sent down a conduit to another building, in order to allow the small quantity of nitroglycerin that has been retained in the water as minute globules to settle, if thought worth the trouble of saving. This, of course, will depend upon the usual outturn of nitroglycerin in a day, and the general scale of operations. Illustration, Figure 9. Filtering and washing plant. W. Lead washing tank. WP. Water pipe. L. Lid. S. Nitroglycerin from separator. A. B. C. Filtering tanks. B2. India rubber bucket. Filtering and washing. The filter house, Figure 9, which must of course be again on a somewhat lower level than the separating house, must be a considerably larger building than either the nitrating or separating houses, as it is always necessary to be washing some 5 or 6 charges at the same time. Upon the arrival of the nitroglycerin at this house, it first flows into a lead-lined wooden tank, W, containing a compressed air pipe, just like the one in the small tank in the separating house. This tank is half filled with water, and the compressed air is turned on from half to a quarter of an hour after the introduction of the charge. The water is then drawn off, and fresh water added. 4 or 5 washings are generally necessary. The nitroglycerin is then run into the next tank, A, the top of which is on a level with the bottom of the first one. Across the top of this tank is stretched a frame of flannel, through which the nitroglycerin has to filter. This removes any solid matters, such as dirt or scum. Upon leaving this tank, it passes through a similar flannel frame across another tank, B, and is finally drawn off by a tap in the bottom of the tank into rubber buckets. The taps in these tanks are best made of vulcanite. At this stage, a sample should be taken to the laboratory and tested. If the sample will not pass the tests, which is often the case, the charge must be rewashed for 1 hour, or some other time, according to the judgment of the chemist in charge. In the case of an obstinate charge, it is of much more avail to wash a large number of times with small quantities of water, and for a short time, than to use a lot of water and wash for half an hour. Plenty of compressed air should be used, as the compound nitric ethers which are formed are thus got rid of. As 5 or 6 charges are often in this house at one time, it is necessary to have as many tanks arranged in tiers, otherwise 1 or 2 refractory charges would stop the nitrating house and the rest of the nitroglycerin plant. The chief causes of the wash material not passing the heat test are either that the acids were not clean, or they contained objectionable impurities, or more frequently, the quality of the glycerin used. The glycerin used for making nitroglycerin should conform to the following tests, some of which, however, are of greater importance than others. The glycerin should 1. have minimum specific gravity at 15 degrees Celsius of 1.261. 2. Should nitrify well. 3. Separation should be sharp within half an hour, without the separation of flocculent matter, nor should any white flocculent matter, due to fatty acids, be formed when the nitrate glycerin is thrown into water and neutralized with carbonate of soda. 4. Should be free from lime and chlorine, and contain only traces of arsenic, sulfuric acid, and C. 5. Should not leave more than 0.25% of inorganic and organic residue together when evaporated in a platinum dish without ebullition, about 160 degrees Celsius, or partial decomposition. 6. Silver test fair. 7. The glycerin, when diluted 1/2, should give no deposit or separation of fatty acids when nitric peroxide gas is passed through it. Numbers 1, 2, 3, and 5 are the most essential. The white flocculent matter sometimes formed is a very great nuisance, and any sample of glycerol which gives such a precipitate when tried in the laboratory should at once be rejected, as it will give no end of trouble in the separating house, and also in the filter house, and it will be very difficult indeed to make the nitroglycerin pass the heat test. The outturn of nitroglycerin also will be very low. The trouble will show itself chiefly in the separating operation. Very often 2 or 3 inches will rise to the surface or hang about in the nitroglycerin, and at the point of contact between it and the mixed acids, and will afterwards be very difficult to get rid of by filtration. The material appears to be partly an emulsion of the glycerin, and partly due to fatty acids, and as there appears to be no really satisfactory method of preventing its formation, or of getting rid of it, the better plan is not to use any glycerin for nitrating that has been found by experiment upon the laboratory scale to give this objectionable matter. One of the most useful methods of testing the glycerin, other than nitrating, is to dilute the sample 1/2 with water, and then to pass a current of nitric peroxide gas through it, when a flocculent precipitate of oleic acid, less soluble in glycerin than the original oleic acid, will be formed. Nitrogen peroxide, N_2O_4, is best obtained by heating dry lead nitrate. See Allen. Commercial Organic Analysis. Volume 2, 301. When a sample of nitroglycerin is brought to the laboratory from the filter house, it should first be examined to see that it is not acid. A weak solution of Congo red or methyl orange may be used. If it appears to be decidedly alkaline, it should be poured into a separating funnel, and shaken with a little distilled water. This should be repeated, and the washings, about 400 cc, run into a beaker, a drop of Congo red or methyl orange added, and a drop or so of N/2 hydrochloric acid added, when it should give, with 2 or 3 drops at most, a blue color with the Congo red, or pink with the methyl orange, and C. The object of this test is to show that the nitroglycerin is free from any excess of soda, i.e., that the soda has been properly washed out, otherwise the heat test will show the sample to be better than it is. The heat test must also be applied. Footnote AA. Leroux Bull. SOC Chim. De Bell. 19, August 1905, contends that experience does not warrant the assumption that free acid is a source of danger in nitroglycerin or nitrocellulose. Free alkali, he states, promotes their decomposition. Upon leaving the filter house, where it has been washed and filtered, and has satisfactorily passed the heat test, it is drawn off from the lowest tank in indiarubber buckets, and poured down the conduit leading to the precipitating house, where it is allowed to stand for a day, or sometimes longer, in order to allow the little water it still contains to rise to the surface. In order to accomplish this, it is sufficient to allow it to stand in covered-in tanks of a conical form, and about 3 or 4 feet high. In many works it is previously filtered through common salt, which of course absorbs the last traces of water. It is then of a pale yellow color, and should be quite clear, and can be drawn off by means of a tap of vulcanite, fixed at the bottom of the tanks, into rubber buckets, and is ready for use in the preparation of dynamite, or any of the various forms of gelatin compounds, smokeless powders, and such as cordite, ballastite, and many others. Michael Lajazak Chem. Zeit. 1904, Rep 174 states that he has prepared mono and dinitroglycerin, and believes that the latter compound will form a valuable basis for explosives, as it is unfreezable. It is stated to be an odorless, unfreezable oil, less sensitive to percussion, friction, and increase of temperature, and to possess a greater solvent power for collodion cotton than ordinary nitroglycerin. It can thus be used for the preparation of explosives of high stability, which will maintain their plastic nature even in winter. The dinitroglycerin is a solvent for trinitroglycerin. It can therefore be mixed with this substance and the various gelatin explosives in order to lower the freezing point. The waste acids. The waste acids from the separating house, from which the nitroglycerin has been as completely separated as possible, are run down the conduit to the secondary separator, in order to recover the last traces of nitroglycerin that they contain. The composition of the waste acids is generally somewhat as follows: specific gravity, 1.7075 at 15 degrees Celsius, sulfuric acid, 67.2%, nitric acid, 11.05%, and water, 21.7%, with perhaps as much as 2% of nitric oxide, and of course varying quantities of nitroglycerin, which must be separated, as it is impossible to run this liquid away, unless it can be run into the sea, or to recover the acids by distillation as long as it contains this substance. The mixture, therefore, is generally run into large circular lead-lined tanks, covered in, and very much like the nitrating apparatus in construction, that is, they contain worms coiled round inside, to allow of water being run through to keep the mixture cool, and a compressed air pipe, in order to agitate the mixture if necessary. The top also should contain a window, in order to allow of the interior being seen, and should have a leaden chimney to carry off the fumes which may arise from decomposition. It is also useful to have a glass tube of 3 or 4 inches in diameter substituted for about a foot of the lead chimney, in order that the man on duty can at any time see the color of the fumes arising from the liquid. There should also be 2 thermometers, one long one reaching to the bottom of the tank, and one to just a few inches below the surface of the liquid. The nitroglycerin, of course, collects upon the surface, and can be drawn off by a tap placed at a convenient height for the purpose. The cover of the tank is generally conical, and is joined to a glass cylinder, which is cemented to the top of this lead cover, and also to the lead chimney. In this glass cylinder is a hole into which fits a ground glass stopper, through which the nitroglycerin can be drawn off. There will probably never be more than an inch of nitroglycerin at the most, and seldom that. It should be taken to the filter house and treated along with another charge. The acids themselves may either be run to waste, or better treated by some denitration plant. This house probably requires more attention than any other in the danger area, on account of the danger of the decomposition of the small quantities of nitroglycerin, which, as it is mixed with such a large quantity of acids and water, is very apt to become hot, and decomposition, which sets up in spots where a little globule of nitroglycerin is floating, surrounded by acids that gradually get hot, gives off nitrous fumes, and perhaps explodes, and thus causes the sudden explosion of the whole. The only way to prevent this is for the workman in charge to look at the thermometers frequently, and at the color of the escaping fumes, and if he should notice a rise of temperature or any appearance of red fumes, to turn on the water and air, and stir up the mixture, when probably the temperature will suddenly fall, and the fumes cease to come off. The cause of explosions in this building is either the non-attention of the workman in charge, or the bursting of one of the water pipes, by which means, of course, the water, finding its way into the acids, causes a sudden rise of temperature. If the latter of these 2 causes should occur, the water should at once be shut off and the air turned on full, but if it is seen that an explosion is likely to occur, the tank should at once be emptied by allowing its contents to run away into a drowning tank placed close outside the house, which should be about 4 feet deep, and some 16 feet long by 6 feet wide, in fact, large enough to hold a considerable quantity of water. But this last course should only be resorted to as a last extremity, as it is extremely troublesome to recover the small quantity of nitroglycerin from the bottom of this tank, which is generally a bricked and cemented excavation some few yards from the house. It has been proposed to treat these waste acids, containing nitroglycerin in Mr. M. Prentice's nitric acid retort. In this case, they would be run into the retort, together with nitrate of soda, in a fine stream, and the small quantity of nitroglycerin, coming into contact with the hot mixture already in the retort, would probably be at once decomposed. This process, although not yet tried, promises to be a success. Several processes have been used for the denitration of these acids. Treatment of the waste acid from the manufacture of nitroglycerin and guncotton. The composition of these acids is as follows: nitroglycerin and guncotton waste acid. Sulfuric acid 70%, 78%, nitric acid 10, 12, water 20, 10. The waste acid from the manufacture of guncotton is generally used direct for the manufacture of nitric acid, as it contains a fairly large amount of sulfuric acid, and the small amount of nitrocellulose which it also generally contains decomposes gradually, and without explosion, in the retort. Nitric acid may be first distilled off, the resulting sulfuric acid being then added to the equivalent amount of nitrate of soda. Nitric acid is then distilled over and condensed in the usual way. Very often, however, the waste acid is added direct to the charge of nitrate without previously eliminating the nitric acid. The treatment of the waste acid from the manufacture of nitroglycerin is somewhat different. The small amount of nitroglycerin in this acid must always be eliminated. This is effected either by allowing the waste acid to stand for at least 24 hours in a big vessel with a conical top, where all the nitroglycerin which will have separated to the surface is removed by skimming, or, better still, the watering down process of Colonel Nathan may be employed. In Nathan's nitrator, every existing trace of nitroglycerin is separated from the acids in a few hours after the nitration, and any further formation of nitroglycerin is prevented by adding about 2% of water to the waste acids, which are kept agitated during the addition. The waste acid, now free from nitroglycerin, but which may still contain organic matter, is denitrated by bringing it into contact with a jet of steam. The waste acid is passed in a small stream down through a tower of acid-resisting stoneware, Volvic stone, which is closely packed with earthenware, and at the bottom of which is the steam jet. Decomposition proceeds as the acid meets the steam. Nitric and nitrous acids are disengaged and are passed out at the top of the tower through a pipe to a series of condensers and towers, where the nitric acid is collected. The nitrous acid may be converted into nitric acid by introducing a hot compressed air jet into the gases before they pass into the condensers. Weak sulfuric acid of SpGr 1.6 collects in a saucer in which the tower stands, and is then passed through a cooling worm. The weak sulfuric acid, now entirely free from nitric and nitrous acids, may be concentrated to SpGr 1.842 and 96%, H_2, SO_4, by any of the well-known processes, example, Kessler, Webb, Benker, Del Place, and C, and it may be used again in the manufacture of nitroglycerin or guncotton. 2 points in the manufacture of nitroglycerin are of the greatest importance, viz., the purity of the glycerin used, and the strength and purity of the acids used in the nitration. With regard to the first of these, great care should be taken, and a complete analysis and thorough examination, including a preliminary experimental nitration, should always be instituted. As regards the second, the sulfuric acid should not only be strong, 96%, but as free from impurities as possible. With the nitric acid, which is generally made at the explosive works where it is used, care must be taken that it is as strong as possible, 97%, and upwards. This can easily be obtained if the plant designed by Mr. Oscar Gutman, A, is used. Having worked Mr. Gutman's plant for some time, I can testify as to its value and efficiency. Footnote A. The manufacture of nitric acid. Jur SOC Chem. IND, March 1893. Another form of nitric acid plant, which promises to be of considerable service to the manufacturer of nitric acid for the purpose of nitrating, is the invention of the late Mr. Manning Prentice, of Stowmarket. Through the kindness of Mr. Prentice, I visited his works to see the plant in operation. It consists of a still, divided into compartments or chambers in such a manner that the fluid may pass continuously from one to the other. The nitric acid being continuously separated by distillation, the contents of each division vary, the first containing the full proportion of nitric acid, and each succeeding one less of the nitric acid, until from the overflow of the last one the bisulfate of soda flows away without any nitric acid. The nitrate of soda is placed in weighed quantities in the hopper, whence it passes to the feeder. The feeder is a miniature horizontal pug mill, which receives the streams of sulfuric acid and of nitrate, and after thoroughly mixing them, delivers them into the still, where, under the influence of heat, they rapidly become a homogeneous liquid, from which nitric acid continuously distills. Mr. Prentice says, I may point out that while the ordinary process of making nitric acid is one of fractional distillation by time, mine is fractional distillation by space. Instead of the operation being always at the same point of space, but differing by the successive points of time, I arrange for the differences to take place at different points of space, and these differences exist at one and the same points of time. It is possible with this plant to produce the full product of nitric acid of a gravity of 1.500, or to obtain the acid of varying strengths from the different stillheads. One of these stills, capable of producing about 4 tons of nitric acid per week, weighs less than 2 tons. It is claimed that there is by their use a saving of more than 2/3 in fuel, and 4/5 in condensing plant. Further particulars and illustrations will be found in Mr. Prentice's paper, Journal of the Society of Chemical Industry, 1894, page 323. Chapter 3. Nitrocellulose, N.C. Cellulose properties, discovery of guncotton, properties of guncotton, varieties of soluble and insoluble guncottons, manufacture of guncotton, dipping and steeping, whirling out the acid, washing, boiling, pulping, compressing, the Waltham Abbey process, Le Bouchet process, granulation of guncotton, collodion cotton, manufacture, acid mixture used, cotton used, N.C. Nitrate guncotton. Tonight, dangers in manufacture of guncotton, trenches fire extinguishing compound, uses of collodion cotton, celluloid. Manufacture, N.C. Nitro-starch, nitro-jute, and nitromanite. The nitrocelluloses. The substance known as cellulose forms the groundwork of vegetable tissues. The cellulose of the woody parts of plants was at one time supposed to be a distinct body, and was called lignin, but they are now regarded as identical. The formula of cellulose is C_6, H_10, O_6, X, and it is generally assumed that the molecular formula must be represented by a multiple of the empirical formula C12, H_20, O_10, being often regarded as the minimum. The assumption is based on the existence of a pentanitrate and the insoluble and colloidal nature of cellulose. Green Zeit. Farb. Text. IND 1904-397 considers these reasons insufficient, and prefers to employ the single formula C_6, H_10, O_5. Cellulose can be extracted in the pure state, from young and tender portions of plants by first crushing them, to rupture the cells, and then extracting with dilute hydrochloric acid, water, alcohol, and ether in succession, until none of these solvents remove anything more. Fine paper or cotton will yield very nearly pure cellulose by similar treatment. Cellulose is a colorless, transparent mass, absolutely insoluble in water, alcohol, or ether. It is, however, soluble in a solution of cuprammoniac solution, prepared from basic carbonate or hydrate of copper and aqueous ammonia. The specific gravity of cellulose is 1.25 to 1.45. According to Schulz, its elementary composition is expressed by the percentage numbers. Carbon 44%, 44.2%, hydrogen 6.3, 6.4, oxygen 49.7, 49.4. These numbers represent the composition of the ash-free cellulose. Nearly all forms of cellulose, however, contain a small proportion of mineral matters, and the union of these with the organic portion of the fiber or tissue is of such a nature that the ash left on ignition preserves the form of the original. It is only in the growing point of certain young shoots that the cellulose tissue is free from mineral constituents. Hofmeister. Cellulose is a very inert body. Cold concentrated sulfuric acid causes it to swell up, and finally dissolves it, forming a viscous solution. Hydrochloric acid has little or no action, but nitric acid has, and forms a series of bodies known as nitrates or nitrocelluloses. Cellulose has some of the properties of alcohols, among them the power of forming ethereal salts with acids. When cellulose in any form, such as cotton, is brought into contact with strong nitric acid at a low temperature, a nitrate or nitro product, containing nitrile, or the NO_2 group, is produced. The more or less complete replacement of the hydroxylic hydrogen by NO_2 groups depends partly on the concentration of the nitric acid used, partly on the duration of the action. If the most concentrated nitric and sulfuric acids are employed, and the action allowed to proceed for some considerable time, the highest nitrate, known as hexanitrocellulose or guncotton, C_12, H_14, O_4, O.No_2_6 will be formed, but with weaker acids and a shorter exposure to their action. The tetra and penta and lower nitrates will be formed. Footnote A. The paper by Professor Lunge, Jur. Chem. SOC, 1901, 23, 8, 527 to 579, contains valuable information on this subject. Besides the nitrate A, Luck A has proposed to use other esters of cellulose, such as the acetate, benzoate, or butyrate. It is found that cellulose acetate forms with nitroglycerin a gelatinous body without requiring the addition of a solvent. A sporting powder is proposed composed of 75 parts of cellulose nitrate, 13% or north, mixed with 13 parts of cellulose acetate. Footnote AM. Pat. 24662, November 22, 1898. The discovery of guncotton is generally attributed to Schonbein, 1846, but Brackenot, in 1832, had previously nitrate starch, and 6 years later Palaus prepared nitro-cotton and various other nitro bodies, and Dumas nitrate paper, but Schonbein was apparently the first chemist to use a mixture of strong nitric and sulfuric acids. Many chemists, such as Piobert in France, Morin in Russia, and Abel in England, studied the subject, but it was in Austria, under the auspices of Baron von Lenk, that the greatest progress was made. Lenk used cotton in the form of yarn, made up into hanks, which he first washed in a solution of potash, and then with water, and after drying dipped them in the acids. The acid mixture used consisted of 3 parts by weight of sulfuric to 1 part of nitric acid, and were prepared some time before use. The cotton was dipped 1 skein at a time, stirred for a few minutes, pressed out, steeped, and excess of acid removed by washing with water, then with dilute potash, and finally with water. Von Lenk's process was used in England at Faversham, Messrs. Hall's works, but was given up on account of an explosion, 1847. Sir Frederick Abel, working at Stowmarket and Waltham Abbey, introduced several very important improvements into the process, the chief among these being pulping. Having traced the cause of its instability to the presence of substances caused by the action of the nitric acid on the resinous or fatty substances contained in the cotton fiber, he succeeded in eliminating them, by boiling the nitro-cotton in water, and by a thorough washing, after pulping the cotton in poachers. Although guncottons are generally spoken of as nitrocelluloses, they are more correctly described as cellulose nitrates, for unlike nitro bodies of other series, they do not yield, or have not yet done so, amido bodies, on reduction with nascent hydrogen. The equation of the formation of guncotton is as follows. 2C_6, H_10, O_5, plus 6 No_3, equals C_12, H_14, O_4, No_3, 6, plus 602. Cellulose. Nitric acid. Guncotton. Water. The sulfuric acid used does not take part in the reaction, but its presence is absolutely essential to combine with the water set free, and thus to prevent the weakening of the nitric acid. The acid mixture used at Waltham Abbey consists of 3 parts by weight of sulfuric acid of 1.84 specific gravity, and 1 part of nitric acid of 1.52 specific gravity. The same mixture is also used at Stowmarket, the new explosive company's works. The use of weaker acids results in the formation of collodion cotton and the lower nitrates generally. Footnote A. Cellulose. By Cross and Bevan, edition by W. R. Hodgkinson, page 9. The nitrate which goes under the name of guncotton is generally supposed to be the hexanitrate, and to contain 14.14% of nitrogen, but a higher percentage than 13.7 has not been obtained from any sample. It is almost impossible, at any rate upon the manufacturing scale, to make pure hexanitrocellulose or guncotton. It is certain to contain several percents of the soluble forms, i.e., lower nitrates. It often contains as much as 15 or 16%, and only from 13.07 A to 13.6% of nitrogen. Footnote A. Mr. J. J. Sayers, in evidence before the court in the Cordite case, says he found 15.2 and 16.1% soluble cotton, and 13.07 and 13.08% nitrogen in 2 samples of Waltham Abbey guncotton. A whole series of nitrates of cellulose are supposed to exist, the highest member being the hexanitrate, and the lowest the mononitrate. Guncotton was at one time regarded as the trinitrate, and collodion cotton as the dinitrate and mononitrate, their respective formula being given as follows. Mononitrocellulose C_6, H_9, NO_2, O_5 equals 6.763% nitrogen. Dinitrocellulose C_6, H_8, NO_2205 equals 11.11. Trinitrocellulose C_6, H_7, NO_2305 equals 14.14. But guncotton is now regarded as the hexanitrate, and collodion cotton as a mixture of all the other nitrates. In fact, chemists are now more inclined to divide nitrocellulose into the soluble and insoluble forms, the reason being that it is quite easy to make a nitrocellulose entirely soluble in a mixture of ether alcohol, and yet containing as high a percentage of nitrogen as 12.6, whereas the dinitrate, A, should theoretically only contain 11.11%. On the other hand, it is not possible to make guncotton with a higher percentage of nitrogen than about 13.7, even when it does not contain any nitrocotton that is soluble in ether alcohol. B. The fact is that it is not at present possible to make a nitrocellulose which shall be either entirely soluble or entirely insoluble, or which will contain the theoretical content of nitrogen to suit any of the above formulae for the cellulose nitrates. Professor G. Lunge gives the following list of nitration products of cellulose. Footnote A. The pentanitrate C_12, H_15, O_5, NO_3_5 equals 12.75% nitrogen. Footnote B. In the Cordite trial, 1894, Sir F. A. Abel said, "Before 1888 there was a broad distinction between soluble and insoluble nitrocellulose, collodion cotton being soluble in ether alcohol, and guncotton insoluble." Sir H. E. Roscoe. That he had been unable to make a nitro-cotton with a higher nitrogen content than 13.7, and Professor G. Lunge said, "Guncotton always contained soluble cotton, and vice versa." These opinions were also generally confirmed by Sir E. Frankland, Sir W. Crookes, Dr. Armstrong, and others. Dodecanitrocellulose C_24, H_28, O_20, NO_212 equals 14.16% nitrogen. Equals old trinitrocellulose and decanitrocellulose C24, H_29, O_20, NO_211 equals 13.5% nitrogen. Decanitrocellulose C24, H_30, O_20, NO_210 equals 12.78% nitrogen. Any nitrocellulose C, 24, H_31, O_20, No_2, 9, equals 11.98% nitrogen. Octonitrocellulose C, 24, H_32, O_20, No_2, 8, equals 11.13% nitrogen. Equals old dinitrocellulose, heptanitrocellulose C, 24, H_33, O_20, No_2, 7, equals 10.19% nitrogen. Hexanitrocellulose C, 24, H_34, O_20, No_2, 6, equals 9.17% nitrogen. Pentanitrocellulose C, 24, H_35, O_20, No_2, 5, equals 8.04% nitrogen. Tetranitrocellulose C, 24, H_36, O_20, No_2, 4, equals 6.77% nitrogen. Equals old mononitrocellulose. It is not unlikely that a long series of nitrates exists. It is at any rate certain that whatever strength of acids may be used, and whatever temperature or other conditions may be present during the nitration, that the product formed always consists of a mixture of the soluble and insoluble nitrocellulose. Theoretically, 100 parts of cotton by weight should produce 218.4 parts of gun cotton, but in practice the yield is a good deal less, both in the case of gun cotton or collodion cotton. In speaking of soluble and insoluble nitrocellulose, it is their behavior, when treated with a solution consisting of 2 parts ether and 1 of alcohol, that is referred to. There is, however, another very important difference, and that is their different solubility in nitroglycerin. The lower nitrates or soluble form is soluble in nitroglycerin under the influence of heat, a temperature of about 50 degrees Celsius, being required. At lower temperatures the dissolution is very imperfect indeed, and after the materials have been left in contact for days, the threads of the cotton can still be distinguished. The insoluble form or gun cotton is entirely insoluble in nitroglycerin. It can, however, be made to dissolve, A. by the aid of acetone or acetic ether. Both or rather all the forms of nitrocellulose can be dissolved in acetone or acetic ether. They also dissolve in concentrated sulfuric acid, and the pentanitrate in nitric acid at about 80 degrees or 90 degrees Celsius. Footnote A, or rather to form a transparent jelly. The pentanitrate may be obtained in a pure state by the following process, devised by Eder. The gun cotton is dissolved in concentrated nitric acid at 90 degrees Celsius, and reprecipitated by the addition of concentrated sulfuric acid. After cooling to 0 degrees Celsius, and mixing with a larger volume of water, the precipitated nitrate is washed with water, then with alcohol, dissolved in ether alcohol, and again precipitated with water, when it is obtained pure. This nitrate is soluble in ether alcohol, and slightly in acetic acid, easily in acetone, acetic ether, and methyl alcohol, insoluble in alcohol. Strong potash, Co. solution converts into the dinitrate C_12, H_18, O_8, No_3_2. The hexanitrate is not soluble in acetic acid or methyl alcohol. The lower nitrates known as the tetra and trinitrates are formed together when cellulose is treated with a mixture of weak acids, and allowed to remain in contact with them for a very short time, 20 minutes. They cannot be separated from one another, as they all dissolve equally in ether alcohol, acetic ether, acetic acid, methyl alcohol, acetone, amyl acetate, and C. As far as the manufacture of explosive bodies is concerned, the 2 forms of nitrocellulose used and manufactured are gun cotton or the hexanitrate, once regarded as trinitrocellulose, which is also known as insoluble gun cotton, and the soluble form of gun cotton, which is also known as collodion, and consists of a mixture of several of the lower nitrates. It is probable that it chiefly consists, however, of the next highest nitrate to gun cotton, as the theoretical percentage of nitrogen for this body. The pentanitrate is 12.75%, and analyses of commercial collodion cotton, entirely soluble in ether alcohol, often give as high a percentage as 12.6. We shall only describe the manufacture of the two forms known as soluble and insoluble, and shall refer to them under their better known names of gun cotton and collodion cotton. The following would, however, be the formulae A and percentage of nitrogen of the complete series. Hexanitrocellulose C _ 12, H _ 14, O _ 4, No _ 3, 6, 14.14% nitrogen. Pentanitrocellulose C 12, H _ 15, O _ 5, No _ 3, 5, 12.75% nitrogen. Tetranitrocellulose C 12, H _ 16, O _ 6, No _ 3, 4, 11.11% nitrogen. Trinitrocellulose C 12, H _ 17, O _ 7, No _ 3, 3, 9.13% nitrogen. Dinitrocellulose C 12, H _ 18, O _ 8, No _ 3, 2, 7.65% nitrogen. Mononitrocellulose C 12, H _ 19, O _ 9, No _ 3, 3.8% nitrogen. Footnote A. Berthelot takes C _ 24, H _ 40, O _ 20 as the formula of cellulose, and M. Va regards the highest nitrate as C _ 24, H _ 18, No _ 3, H 1109. Comptroller Rend, 1882, page 132. Properties of gun cotton. The absolute density of gun cotton is 1.5. When in lumps, its apparent density is 0.1. If twisted into thread, 0.25. When subjected, in the form of pulp, to hydraulic pressure, 1.0 to 1.4. Gun cotton preserves the appearance of the cotton from which it is made. It is, however, harsher to the touch. It is only slightly hygroscopic. Dry gun cotton absorbs 2% of moisture from the air. It possesses the property of becoming electrified by friction. It is soluble in acetic ether, amyl acetate, and acetone, insoluble in water, alcohol, ether, ether alcohol, methyl alcohol, and C. It is very explosive, and is ignited by contact with an ignited body, or by shock, or when it is raised to a temperature of 172 degrees Celsius. It burns with a yellowish flame, almost without smoke, and leaves little or no residue. The volume of the gases formed is large, and consists of carbonic acid, carbonic oxide, nitrogen, and water gas. Compressed gun cotton, when ignited, often explodes when previously heated to 100 degrees Celsius. Gun cotton kept at 80 degrees to 100 degrees Celsius decomposes slowly, and sunlight causes it to undergo a slow decomposition. It can, however, be preserved for years without undergoing any alteration. It is very susceptible to explosions by influence. For instance, a torpedo, even placed at a long distance, may explode a line of torpedoes charged with gun cotton. The velocity of the propagation of the explosion in metallic tubes filled with pulverized gun cotton has been found to be from 5,000 to 6,000 mms per second in tin tubes, and 4,000 in leaden tubes. Sebert. Gun cotton loosely exposed in the open air burns 8 times as quickly as powder. Piobert. A thin disc of gun cotton may be fired into from a rifle without explosion, but if the thickness of the disc be increased, an explosion may occur. The effect of gun cotton in mines is very nearly the same as that of dynamite for equal weights. It requires, however, a stronger detonator, and it gives rise to a larger quantity of carbonic oxide gas. Gun cotton should be neutral to litmus, and should stand the government heat test, temperature of 150 degrees Fahrenheit. For 15 minutes, see page 249. In the French Navy, gun cotton is submitted to a heat test of 65 degrees Celsius, equals 149 degrees Fahrenheit, for 11 minutes. It should contain as small a percentage of soluble nitro cotton and of non-nitrate cotton as possible. The products of perfectly detonated gun cotton may be expressed by the following equation: 2C_12, H_14, O_4, No_3, 6 equals 18 co plus 6 co, 2 plus 14 H_2, O plus 12 N. It does not therefore contain sufficient oxygen for the complete combustion of its carbon. It is for this reason that when used for mining purposes a nitrate is generally added to supply this defect, as, for instance, in tonnite. It tends also to prevent the evolution of the poisonous gas, carbonic oxide. The success of the various gelatin explosives is due to this fact, viz., that the nitroglycerin has an excess of oxygen, and the nitro-cotton too little, and thus the two explosives help one another. In practice, the gases resulting from the explosion of gun cotton are carbonic oxide, 28.55, carbonic acid, 19.11, marsh gas, CH_4, 11.17, nitric oxide, 8.83, nitrogen, 8.56, water vapor, 21.93%. The late Mr. Yo Brown, of Woolwich Arsenal, discovered that perfectly wet and uninflammable compressed gun cotton could be easily detonated by the detonation of a priming charge of the dry material in contact with it. This rendered the use of gun cotton very much safer for use as a military or mining explosive. As a mining explosive, however, gun cotton is now chiefly used under the form of tonnite, which is a mixture of half gun cotton and half barium nitrate. This material is sometimes spoken of as nitrate gun cotton. The weight of gun cotton required to produce an equal effect either in heavy ordnance or in small arms is to the weight of gunpowder in the proportion of 1 to 3, i.e., an equal weight of gun cotton would produce 3 times the effect of gunpowder. Its rapidity of combustion, however, requires to be modified for use in firearms. Hence the lower nitrates are generally used, or such compounds as nitrolignose, nitrate wood, and C, are used. The initial pressure produced by the explosion of gun cotton is very large, equal to 18,135 atmospheres, and 8,740 kilograms per square centimeter for 1 kilo. The heat liberated being 1,075 calories, water liquid, or 997.7 calories. Water gaseous, but the quantity of heat liberated changes with the equation of decomposition. According to Berthelot, A, the heat of formation of collodion cotton is 696 calories for 1053 grms, or 661 calories for 1 kilo. The heat liberated in the total combustion of gun cotton by free oxygen at constant pressure is 2633 calories for 1143 grms, or for 1 kilo. Gun cotton 2302 calories. Water liquid, or 2,177 calories. Water gaseous. The heat of decomposition of gun cotton in a closed vessel, found by experiment at a low density of charge, 0.023, amounts to 1,071 calories for 1 kilo of the substance, dry and free from ash. To obtain the maximum effect of gun cotton, it must be used in a compressed state, for the initial pressures are thereby increased. Wet gun cotton is much less sensitive to shock than dry. Paraffin also reduces its liability to explode, so also does camphor. Footnote A. Explosives and their power. Trans. By Hake and M. Nab. The substance known as celluloid, a variety of nitrocellulose nearly corresponding to the formula C_24, H_24, No_3, H8O12, to which camphor and various inert substances are added, so as to render it non-sensitive to shock, may be worked with tools, and turned in the lathe in the same manner as ivory. Instead of which material celluloid is now largely used for such articles as knife handles, combs, and C. Celluloid is very plastic when heated towards 150 degrees Celsius, and tends to become very sensitive to shock, and in large quantities might become explosive during a fire, owing to the general heating of the mass, and the consequent evaporation of the camphor. When kept in the air bath at 135 degrees Celsius, celluloid decomposes quickly, In an experiment made by M. Berthelot, in a closed vessel at 135 degrees Celsius, and the density of the charge being 0.4, it ended in exploding, developing a pressure of 3,000 kilos. A large package of celluloid combs also exploded in the guard's van on one of the German railways a few years ago. Although it is not an explosive under ordinary circumstances, or even with a powerful detonator, considerable care should be exercised in its manufacture. The manufacture of gun cotton. The method used for the manufacture of gun cotton is that of Abel, spec number 1102, 20. 4, 65. It was worked out chiefly at Stowmarket, A, and Waltham Abbey, B, but has in the course of time undergone several alterations. These modifications have taken place, however, chiefly upon the continent, and relate more to the apparatus and machinery used than to any alteration in the process itself. The form of cellulose used is cotton waste, C, which consists of the clippings and waste material from cotton mills. After it has been cleaned and purified from grease, oil, and other fatty substances by treatment with alkaline solutions, it is carefully picked over, and every piece of colored cotton rag or string carefully removed. The next operation to which it is submitted has for its object the opening up of the material. For this purpose it is put through a carding machine, and afterwards through a cutting machine, whereby it is reduced to a state suitable for its subsequent treatment with acids, that is, it has been cut into short lengths, and the fibers opened up and separated from one another. Footnote A. The New Explosive Company Works. Footnote B. Royal Gunpowder Factory. Footnote C. Costs from £10 to £25 a ton. In his description of the preparation of cotton waste for the manufacture of smokeless powder, A. Herzog states that the German military authorities require a cotton which, when thrown into water, sinks in 2 minutes, when nitrate, does not disintegrate, when treated with ether, yields only 0.9% of fat, and containing only traces of chlorine, lime, magnesia, iron, sulfuric acid, and phosphoric acid. If the cotton is very greasy, it must be first boiled with soda lye under pressure, washed, bleached with chlorine, washed, treated with sulfuric acid or HCl, again washed, centrifugated, and dried. If very greasy indeed, a preliminary treatment with lime water is desirable. See also Inspection of Cotton Waste for Use in the Manufacture of Gun Cotton by C. Monroe Juram. Chem. SOC 1895, 17, 783. Drying the cotton. This operation is performed in either of two ways. The cotton may either be placed upon shelves in a drying house, through which a current of hot air circulates, or dried in steam-jacketed cylinders. It is very essential that the cotton should be as dry as possible before dipping in the acids, especially if a wholly insoluble nitrocellulose is to be obtained. After drying, it should not contain more than 0.5% of moisture, and less than this if possible. The more general method of drying the cotton is in steam-jacketed tubes, i.e., double cylinders of iron, some 5 feet long and 1.5 foot wide. The cotton is placed in the central chamber, figure 10, while steam is made to circulate in the surrounding jacket, and keeps the whole cylinder at a high temperature. Steam pipes may be coiled round the outside of an iron tube, and will answer equally well. By means of a pipe which communicates with the compressed air reservoir, a current of air enters at the bottom, and finds its way up through the cotton, and helps to remove the moisture that it contains. The raw cotton generally contains about 10% of moisture and should be dried until it contains only 0.5% or less. For this it will generally have to remain in the drying cylinder for about 5 hours. At the end of that time a sample should be taken from the top of the cylinder and dried in the water oven, 100 degrees C, A, for an hour to an hour and a half, and reweighed, and the moisture then remaining in it calculated. Footnote A. It is dried at 180 degrees Celsius, at Waltham Abbey, in a specially constructed drying chamber. Illustration, Figure 10. Cotton dryer. It is very convenient to have a large copper water oven, containing a lot of small separate compartments, large enough to hold about a handful of the cotton, and each compartment numbered, and corresponding to one of the drying cylinders. The whole apparatus should be fixed against the wall of the laboratory, and may be heated by bringing a small steam pipe from the boiler house. It is useful to have a series of copper trays, about 3 inches by 6 inches, numbered to correspond to the divisions in the steam oven, and exactly fitting them. These trays can then be taken by a boy to the drying cylinders, and a handful of the cotton from each placed in them, and afterwards brought to the laboratory and weighed. A boy can do this very well, placed in their respective divisions of the oven, and left for 1 to 1.5 hours, and reweighed. When the cotton is found to be dry, the bottom of the drying cylinder is removed, and the cotton pushed out from the top by means of a piece of flat wood fixed on a broom handle. It is then packed away in galvanized iron airtight cases, and is ready for the next operation. At some works the cotton is dried upon shelves in a drying house through which hot air circulates, the shelves being of canvas or of brass wire netting. The hot air must pass under the shelves and through the cotton, or the process will be a very slow one. Dipping and steeping. The dry cotton has now to be nitrate. This is done by dipping it into a mixture of nitric and sulfuric acids. The acids used must be strong, that is, the nitric acid must be at least of a gravity of 1.53 to 1.52, and should contain as little nitric oxide as possible. The sulfuric acid must have a specific gravity of 1.84 at 15 degrees Celsius, and contain about 97% of the monohydrate, H_2, SO_4. In fact, the strongest acids obtainable should be used when the product required is gun cotton, i.e., the highest nitrate. The sulfuric acid takes no part in the chemical reaction involved, but is necessary in order to combine with the water that is liberated in the reaction, and thus to maintain the strength of the nitric acid. The reaction which takes place is the following: 2 C_6 H_10 O_5 plus 6 No_3 equals C_12 H_14 No_3 6 plus 6H2O 324 378 is equal to 594 108. Cellulose. Gun cotton. Theoretically, therefore, 1 part of cellulose should form 1.8 part of gun cotton. Practically, however, this is never obtained, and 1.6 pounds, from 1 pound, of cellulose is very good working. The mixture of acids used is generally 1 to 3, or 25%, nitric acid to 75%, sulfuric acid. Footnote A, 594 by 1/324 equals 1.83. Illustration, Figure 11. Tank for dipping cotton. Illustration, Figure 12. The cooling pits. The dipping is done in cast iron tanks, Figure 11, a series of which is arranged in a row, and cooled by a stream of cold water flowing round them. The tanks hold about 12 gallons, and the cotton is dipped in portions of 1 pound at a time. It is thrown into the acids, and the workman moves it about for about 3 minutes with an iron rabble. At the end of that time he lifts it up onto an iron grating, just above the acids, fixed at the back of the tank, where by means of a movable lever he gently squeezes it, until it contains about 10 times its weight of acids. The 1 pound weighs 10 pounds. It is then transferred to earthenware pots to steep. Illustration, Figure 13. Cotton steeping pot. Steeping. The nitrate cotton, when withdrawn from the dipping tanks, and still containing an excess of acids, is put into earthenware pots of the shape shown in Figures 12 and 13. The lid is put on, and the pots placed in rows in large cooling pits, about a foot deep, through which a stream of water is constantly flowing. These pits form the floor of the steeping house. The cotton remains in these pots for a period of 48 hours, and must be kept cool. Between 18 degrees and 19 degrees Celsius is the highest temperature desirable, but the cooler the pots are kept the better. At the end of 48 hours the chemical reaction is complete, and the cotton is or should be wholly converted into nitrocellulose. That is, there should be no unnitrated cotton. Illustration, Figure 14. Hydro-extractor. Whirling out the acid. The next operation is to remove the excess of acid. This is done by placing the contents of 2 or 3 or more pots into a centrifugal hydroextractor, figure 14, making 1,000 to 1,500 revolutions per minute. The hydro-extractor consists of a machine with both an inner cylinder and an outer one, both revolving in concert and driving outwardly the liquid to the chamber, from which it runs away by a discharge pipe. The wet cotton is placed around the inner cone. The cotton, when dry, is removed and at once thrown into a large tank of water, and the waste acids are collected in a tank. Footnote A. Care must be taken in hot weather that the gun cotton does not fire, as it does sometimes, directly the workman goes to remove it after the machine is stopped. It occurs more often in damp weather. Dr. Schupfhaus of Brooklyn, USA, proposes to treat the waste acids from the nitration of cellulose by adding to them sulfuric anhydride and nitric acid. The sulfuric anhydride added converts the water liberated from the cellulose into sulfuric acid. Washing. The cotton has now to be carefully washed. This is done in a large wooden tank filled with water. If, however, a river or canal runs through the works, a series of wooden tanks, the sides and bottoms of which are pierced with holes, so as to allow of the free circulation of water, should be sunk into a wooden platform that overhangs the surface of the river in such a way that the tanks are immersed in the water, and of course always full. During the time that the cotton is in the water, a workman turns it over constantly with a wooden paddle. A stream of water, in the form of a cascade, should be allowed to fall into these tanks. The cotton may then be thrown onto this stream of water, which, falling some height, at once carries the cotton beneath the surface of the water. This proceeding is necessary because the cotton still retains a large excess of strong acids, and when mixed with water gives rise to considerable heat, especially if mixed slowly with water. After the cotton has been well washed, it is again wrung out in a centrifugal machine, and afterwards allowed to steep in water for some time. Illustration: Figure 15_A_. The beater for gun cotton. Boiling. The washed cotton is put into large iron boilers with plenty of water, and boiled for some time at 100 degrees Celsius. In some works, lead-lined tanks are used, into which a steam pipe is led. The soluble impurities of unstable character, to which Sir F. A. Abel traced the liability of gun cotton to instability, are thereby removed. These impurities consist of the products formed by the action of nitric acid on the fatty and resinous substances contained in the cotton fibers. The water in the tanks should be every now and again renewed, and after the first few boilings the water should be tested with litmus paper until they are no longer found to be acid. Illustration: Figure 15_B_. Wheel of beater. Pulping. The idea of pulping is also due to Abel. By its means a very much more uniform material is obtained. The process is carried out in an apparatus known as a beater, or hollander, figure 15 and AB. It consists of a kind of wooden tank some 2 or 3 feet deep of an oblong shape, in which a wheel carrying a series of knives is made to revolve, the floor of the tank being sloped up so as to almost touch the revolving wheels. This part of the floor, known as the craw, is a solid piece of oak, and a box of knives is fixed into it, against which the knives and the revolving wheel are pressed. The beater is divided into 2 parts: the working side, in which the cotton is cut and torn between the knife edges in the revolving cylinder and those in the box, and the running side, into which the cotton passes after passing under the cylinder. The wheel is generally boxed in to prevent the cotton from being thrown out during its revolution. The cotton is thus in constant motion, continually traveling round, and passing between the knives in the revolving cylinder and those in the box fixed in the wooden block beneath it. The beater is kept full of water, and the cotton is gradually reduced to a condition of pulp. The wheel revolves at the rate of 100 to 150 times a minute. Illustration: Figure 16_A_. Poacher for washing gun cotton. Illustration: Figure 16_B_. Plan of the poacher. Illustration: Figure 16_C_. Another form of poacher. When the gun cotton is judged to be sufficiently fine, the contents of the beater are run into another very similar piece of machinery, known as the poacher, figure 16 and A and B, C, in which the gun cotton is continuously agitated together with a large quantity of water, which can be easily run off and replaced as often as required. When the material is first run into the poacher from the beater, the water with which it is then mixed is first run away and clean water added. The paddle wheel is then set in motion, and at intervals fresh water is added. There is a strainer at the bottom of the poacher which enables the water to be drawn off without disturbing the cotton pulp. After the gun cotton has been in the poacher for some time, a sample should be taken by holding a rather large mesh sieve in the current for a minute or so. The pulp will thus partly pass through and partly be caught upon the sieve, and an average sample will be thus obtained. The sample is squeezed out by hand, bottled, and taken to the laboratory to be tested by the heat test for purity. It first, however, requires to be dried. This is best done by placing the sample between coarse filter paper, and then putting it under a hand screw press, where it can be subjected to a tolerably severe pressure for about 3 minutes. It is then rubbed up very finely with the hands, and placed upon a paper tray, about 6 inches by 4.5 inches, which is then placed inside a water oven upon a shelf of coarse wire gauze, the temperature of the oven being kept as near as possible to 120 degrees Fahrenheit, 49 degrees Celsius, the gauze shelves in the oven being kept about 3 inches apart. The sample is allowed to remain at rest for 15 minutes in the oven, the door of which is left wide open. After the lapse of 15 minutes, the tray is removed and exposed to the air of the laboratory, away from acid fumes, for 2 hours, the sample being at some point within that time rubbed upon the tray with the hand, in order to reduce it to a fine and uniform state of division. 20 grains, 1.296 grm, are used for the test. See Heat Test, page 249. If the gun cotton sample removed from the poacher stands the heat test satisfactorily, the machine is stopped, and the water drained off. The cotton is allowed some little time to drain, and is then dug out by means of wooden spades, and is then ready for pressing. The poachers hold about 2,000 pounds of material, and as this represents the products of many hundred distinct nitrating operations, a very uniform mixture is obtained. 2% of carbonate of soda is sometimes added, but it is not really necessary if the cotton has been properly washed. Compressing gun cotton. The gun cotton, in the state in which it is removed from the poacher, contains from 28 to 30% of water. In order to remove this, the cotton has to be compressed by hydraulic power. The dry compressed gun cotton is packed in boxes containing 2,500 pounds of dry material. In order to ascertain how much of the wet cotton must be put into the press, it is necessary to determine the percentage of water. This may be done by drying 2,000 grains upon a paper tray, previously dried at 100 degrees Celsius, in the water oven at 100 degrees Celsius, for 3 hours, and reweighing and calculating the percentage of water. It is then easy to calculate how much of the wet gun cotton must be placed in the hopper of the press in order to obtain a block of compressed cotton of the required weight. Various forms of presses are used, and gun cotton is sent out either as solid blocks, compressed discs, or in the form of an almost dry powder, in zinc-lined, airtight cases. The discs are often soaked in water after compression until they have absorbed 25% of moisture. Illustration, Figure 17. Old method. 100 pieces. Illustration, Figure 18. New method. 1 solid block. At the Nitro-Explosives Company Stowmarket Works, large solid blocks of gun cotton are pressed up under a new process, whereby blocks of gun cotton, for use in submarine mines or in torpedo warheads, are produced. Large charges of compressed gun cotton have hitherto been built up from a number of suitably shaped charges of small dimensions, Figure 17, as it has been impossible to compress large charges in a proper manner. The formation of large-sized blocks of gun cotton was the invention of Mr. A. Hollings. Prior to the introduction of this method, 8 or 9 pounds had been the limit of weight for a block. This process has been perfected at the Stowmarket factory, where blocks varying from the armor-piercing shell charge of a few ounces up to blocks of compressed gun cotton mechanically true, weighing 4 to 5 cwts. For torpedoes or submarine mines, are now produced. At the same time, the new process ensures a uniform density throughout the block, and permits of any required density, from 1.4 downwards, being attained. It is also possible exactly to regulate the percentage of moisture, and to ensure its uniform distribution. The maximum percentage of moisture depends, of course, upon the density. By the methods of compression gun cotton blocks hitherto employed, blocks of a greater thickness than 2 inches, or of a greater weight than 9 pounds, could not be made, but with the new process blocks of any shape, size, thickness, or weight that is likely to be required can be made readily and safely. The advantages which are claimed for the process may be enumerated as follows. 1. There is no space wasted, as in the case with built-up charges, through slightly imperfect contact between the individual blocks, and thus either a heavier charge, i.e., about 15%, more gun cotton, can be got into the same space, or less space will be occupied by a charge of a given weight. 2. The metallic cases for solid charges may be much lighter than for those built up, since with the former their function is merely to prevent the loss of moisture from wet gun cotton, or to prevent the absorption of moisture by dry gun cotton. They can thus be made lighter, as the solid charge inside will prevent deformation during transport. With built-up charges the case must be strong enough to prevent damage, either to itself or to the charge it contains. For many uses a metal case, however light, may be discarded, and one of a thin waterproof material substituted. 3. The uniform density of charges made by this process is very favorable to the complete and effective detonation of the entire mass, and to the presence of the uniform amount of moisture in every part of the charge. 4. Any required density, from the maximum downwards, may be obtained with ease, and any required amount of moisture left in the charge. These points are of great importance in cases where, like torpedo charges, it is essential to have the center of gravity of the charge in a predetermined position both vertically and longitudinally, and the charge so fixed in its containing case that the center of gravity cannot shift. The difficulty of ensuring this with a large torpedo charge built up from a number of disks and segments is well known. Even with plain cylindrical or prismatic charges, a marked saving in the process of production is effected by this new system. The charges being in one block, they are more easily handled for the usual periodical examination, and they do not break or chafe at the edges, as in the case of disks and cubes and built-up charges. A general view of the press is given in Figure 19. The gun cotton in a container is placed on a cradle fixed at an angle to the press. The mold is swiveled round, and the charge pushed into it with a rammer, and it is then swiveled back into position. The mold is made up of a number of wedge pieces which close circumferentially on the enclosed mass, which is also subjected to end pressure. Holes are provided for the escape of water. Illustration: Figure 19. A 4 cwt. Block of gun cotton being taken from hydraulic press. The Waltham Abbey process. At the Royal Gunpowder Factory, Waltham Abbey, the manufacture of gun cotton has been carried out for many years. The process used differs but little from that used at Stowmarket. The cotton used is of a good quality. It is sorted and picked over to remove foreign matters, and is then cut up by a kind of guillotine into 2-inch lengths. It is then dried in the following manner. The cotton is placed upon an endless band, which conducts it to the stove, or drying closet, a chamber heated by means of hot air and steam traps to about 180 degrees Fahrenheit. It falls upon a second endless band placed below the first. It travels back again the whole length of the stove, and so on until delivered into a receptacle at the bottom of the farther end, where it is kept dry until required for use. The speed at which the cotton travels is 6 feet per minute, and as the length of the band traveled amounts to 126 feet, the operation of drying takes 21 minutes. 1¼ pound are weighed out and placed in a tin box. A truck, fitted to receive a number of these boxes, carries it along a tramway to a cool room, where it is allowed to cool. Dipping. Mixed acids are used in the proportion of 1 to 3, specific gravity nitric acid 1.52, and sulfuric acid 1.84. The dipping tank is made of cast iron, and holds 220 pounds of mixed acids, and is surrounded on 3 sides by a water space in order to keep it cool. The mixed acids are stored in iron tanks behind the dipping tanks, and are allowed to cool before use. During the nitration, the temperature of the mixed acids is kept at 70 degrees Fahrenheit, and the cotton is dipped in quantities of 1½ pounds at a time. It is put into a tin chute at the back of the dipping tank, and raked into the acids by means of a rabble. It remains in the acids for 5 or 6 minutes, and is then removed to a grating at the back, pressed and removed. After each charge of cotton is removed from the tank, about 14 pounds of fresh mixed acids are added to replace amount removed by charge. The charge now weighs, with the acids retained by it, 15 pounds. It is now placed in the pots and left to steep for at least 24 hours, the temperature being kept as low as possible, to prevent the formation of soluble cotton, and also prevent firing. The proportion of soluble formed is likely to be higher in hot weather than cold. The pots must be covered to prevent the absorption of moisture from the air, or the accidental entrance of water, which would cause decomposition, and consequent fuming off, through the heat generated by the action of the water upon the strong acids. The excess of acids is now extracted by means of hydro-extractors, as at Stowmarket. They are worked at 1,200 revolutions per minute, and whirled for 5 minutes. 10.5 pounds of waste acids are removed from each charge dipped. The charge is then washed in a very similar manner to that previously described, and again wrung out in a centrifugal extractor, 1,200 revolutions per minute. The guncotton is now boiled by means of steam in wooden tanks for 8 hours. It is then again wrung out in the extractors for 3 minutes, boiled for 8 hours more, and again wrung out. It is then sent to the beater and afterwards to the poacher. The poachers hold 1,500 gals each, or 18 cwt of cotton. The cotton remains 6 hours in the poachers. Before molding, 500 gals of water are run into the poacher, and 500 gals of lime water containing 9 pounds of whiting and 9 gals of a caustic soda solution. This mixture is of such a strength that it is calculated to leave in the finished guncotton from 1 to 2% of alkaline matter. By means of vacuum pressure, the pulp is now drawn off and up into the stuff chest, a large cylindrical iron tank, sufficiently elevated on iron standards to allow room for the small gauge tanks and molding apparatus below. It holds the contents of 1 poacher, 18 cwt, and is provided with revolving arms to keep the pulp stirred up, so that it may be uniformly suspended in water. Recently a new process, invented by J.M. and W.T. Thompson and Pat. No. 8278, 1903, has been introduced at the Waltham Abbey factory. The object of this invention is the removal of the acids of nitration from the nitrate material after the action has been completed, and without the aid of moving machinery, such as presses, rollers, centrifugals, and the like. The invention consists in the manufacture of nitrate celluloses by removing the acids from the nitrate cellulose directly by displacement without the employment of either pressure or vacuum, or mechanical appliances of any kind, and at the same time securing the minimum dilution of the acids. It was found that if water was carefully run onto the surface of the acids in which the nitrocellulose is immersed, and the acids be slowly drawn off at the bottom of the vessel, the water displaces the acid from the interstices of the nitrocellulose without any undesirable rise in temperature, and with very little dilution of the acids. By this process almost the whole of the acid is recovered in a condition suitable for concentration, and the amount of water required for preliminary washing is very greatly reduced. The apparatus which is used for the purpose consists of a cylindrical or rectangular vessel constructed with a perforated false bottom, and a cock at its lowest point for running off the liquid. Means are also provided to enable the displacing water to be run quietly onto the surface of the nitrating acids. A. Footnote A. In a further patent N. Pat. 7269, 1903, F.L. Natham, J.M. Thompson and W.D. Thompson proposed by use of alcohol to replace the water used in washing nitrocellulose, and afterward to remove the alcohol by pressing and centrifuging. The apparatus is shown in Figure 2.0, side elevation, and in Figure 21 a plan of the nitrating vessel and its accessories is given. In Figure 20 is shown in sectional elevation one of the trough devices for enabling liquids to be added to those in the nitrating vessel without substantial disturbance. Illustration, Figure 20. Sectional elevation of Thompson's apparatus, A. Tank, B. False bottom, C. Ribs, D. Draining outlet, E. Grid, F. Troughs, with aprons G. H. Pipe, with branches H, leading to troughs, F. K. Outlet pipe of the sulfuric acid tank K. L. Water supply pipe, M. Pipe to supply of nitrating acids, O. Perforations of trough F. P. Cock to remove acid. In carrying out this invention, a rectangular lead-lined or earthenware tank is employed, having a false bottom B, supported by ribs C, over the real bottom C, which slopes down to a draining outlet pipe D, provided with a perforated grid or plate E, adapted to prevent choking of the outlet. Suitably supported near the top of the vessel are provided two troughs, F having depending aprons G. A pipe H has two branches H, leading to the troughs, F. This pipe H is adapted to be connected by a rubber pipe either to the outlet pipe K of the sulfuric acid tank K or the water supply pipe L. The nitrating acids are supplied through the pipe M. A charge of mixed nitrating acids is introduced into the vessel, say up to the level N, and the dry cellulose thrown into the acids in small quantities at a time, being pushed under the surface in the usual way. Illustration: Figure 21. Plan of Thomson's apparatus: A. Tank, B. False bottom, C. Ribs, E. Grid, F. Troughs, G. Aprons, H and H pipes to troughs F. K. Sulfuric acid tank, M. Pipe to nitrating acids tank, O. Perforations of troughs, P. Cock to remove acid. A thin layer, say half an inch, of a suitable liquid, preferably sulfuric acid, of a gravity not exceeding that of the waste acid to be produced, is run carefully on the top of the acids by means of the troughs F, which are perforated as shown at O, so that the sulfuric acid runs down the aprons G, and floats on the nitrating acids. The whole is then allowed to stand till nitration has been completed. Water is then supplied to the troughs by way of the pipes L, H, and H, and is allowed to float very gently over the surface of the sulfuric acid, and when a sufficient layer has been formed, the cock P at the bottom of the apparatus is opened, and the acid slowly drawn off, water being supplied to maintain the level constant. It is found that the rate of displacement of the acids is a factor which exerts a considerable influence on the properties of the resulting nitrocellulose, and affords a means of regulating the temperature of displacement. A rate of displacement which has been found suitable is about 2 inches in depth of the vessel per hour when treating highly nitrate celluloses, but this rate may, in some cases, be considerably increased. The flow of water at the top of the apparatus is regulated so that a constant level is maintained. By this means the water gradually and entirely displaces the acids from the interstices of the nitrocellulose, the line of separation between the acids and the water being fairly sharply defined throughout. The flow of water is continued until that issuing at the bottom is found to be free from all trace of acid. The purification of the nitrocellulose is then proceeded with as usual, either in the same vessel or another. In the process above described, the object of the introduction of a small layer of sulfuric acid is mainly to prevent the fuming which would otherwise take place, and is not essential, as it is found it can be omitted without any deleterious effect. In order to use the mixed acids in the most economical manner, the waste acid from a previous operation may be used for a first nitration of the cellulose, being afterwards displaced with fresh acids which carry the nitration to the required degree before they are in turn displaced by water. The apparatus may be used merely for the removal of the acid, in which case the nitration is carried out in other vessels in the usual way, and the nitrocellulose removed to the displacement apparatus where it is just covered with waste acid, and the displacement then proceeded with as above described. In some cases the process is carried out in an ordinary nitrating centrifugal, using the latter to effect preliminary drying after acid extraction. This gives a great advantage over the usual method of working ordinary centrifugal nitrating apparatus, because the acid being removed before the centrifugal is run, practically all danger of firing therein disappears, and a greater proportion of the waste acid is recovered. In some cases the acids and water may be supplied by perforated pipes, lying along the edges of the nitrating vessel, and these edges may, if desired, be themselves made inclined, like the sides of the troughs F. In the case of effecting nitration in centrifugals as above, the displacing sulfuric acid and water may thus be supplied round the edges of the machines, or removal troughs such as F may be used. It will be obvious that any inert liquid of suitable specific gravity may be used instead of sulfuric acid, as a separation layer. Molding. By means of the small measuring tank above referred to, the guncotton pulp is drawn off from the stuffed chest, and run into molds of the shapes and sizes required. Thence a large proportion of the water is drawn off by means of tubes connected with the vacuum engine, the molds having bottoms of fine wire gauze, in order to prevent the pulp from passing through. Hydraulic pressure of about 34 pounds on the square inch is then applied, which has the effect of compressing the pulp into a state in which it has sufficient consistency to enable it to be handled with care, and also expels a portion of the remaining water. Compressing. The molded guncotton is now taken to the press house, which is situated at some distance from the rest of the factory. Here the molds are subjected to powerful hydraulic pressure, from 5 to 6 tons per square inch, and is compressed to 1/3 of its previous bulk. The slabs or discs thus formed are kept under pressure for a short time, not exceeding a minute and a half, to give the requisite density. It should, when removed, be compact, and just sink in water, and should perceptibly yield to the pressure of the fingers. There are perforations in the press blocks, to allow of the escape of gases if formed by reason of sufficient heat being generated. The men working the press are placed under cover, behind strong rope mantlets having eye tubes which command a view of the press. Packing. The finished slabs and discs are dipped into a solution of soda and carbolic acid, and packed in special wood metal-lined cases. When it is to be sent abroad, the metal lining, which is made of tin copper, is soldered down, but both the outer wooden and inner metal cases are fitted with airtight screw plugs, so that when necessary water can be added without unfastening the cases. Reworked guncotton does not make such good discs as new pulped guncotton, probably because the fibrous tenacity of the guncotton has been destroyed by the amount of pressure it has previously undergone, so that when repulped it resembles fine dust, and a long time is required to press it into any prescribed form. It is generally boiled for 8 hours to open up the fiber and remove alkali, then broken up by hand with wooden mallets, pulped, and then used with fresh guncotton in the proportion of 1 to 5 parts. Manufacture at Le Bouchet. At Le Bouchet guncotton was made thus: 200 grms of cotton were steeped for an hour in 2 liters of a mixture of 1 volume concentrated nitric and 2 volumes sulfuric acid. The cotton was then removed and pressed, whereby 7/10 ths of the waste acids was recovered. After this it was washed for 1 to 1.5 hours in running water, strongly pressed again, allowed to lie for 24 hours in wood ash lye, then well washed in running water, pressed, and finally dried on a wide linen sheet, through which was forced air heated to 60 degrees Celsius. The average yield from 100 parts of cotton was 165 parts of guncotton. The strong pressings of the guncotton, while still impregnated with acids, caused subsequent washings to be difficult and laborious. Granulation of guncotton. Guncotton is often required in the granulated form for use either alone or with some form of smokeless powder. This is done under the patent of Sir Frederick Abel in the following manner. The guncotton from the poacher is placed in a centrifugal machine, very similar to the hydroextractors before mentioned, and used for wringing out the acids. In this machine it loses water until it only contains 33%, and is at the same time reduced to a more or less fibrous state. It is then taken to the granulating room, where it is first passed through sieves or perforations, which break up the mass into little pieces like shot. The material is then transferred to a revolving drum made of wood or stout leather, which is kept constantly revolving for some time. The material is occasionally sprinkled with water. The drum in turning, of course, carries the granules partially round with it, but the action of gravity causes them to descend constantly to the lowest point, and thus to roll over one another continually. The speed of the drum must not be too rapid. None of the granules must be carried round by centrifugal force, but it must be fast enough to carry them some little distance up the side of the drum. After removal from the drum, the granules are dried upon shelves in the drying house. Guncotton is also dissolved in acetone or acetic ether until it has taken the form of a jelly. It is then rolled into thin sheets, and when dry cut up into little squares. In the manufacture of smokeless powders from nitrocellulose, nitrolignin, and C. The various substances are mixed with the gun cotton or collodion cotton before granulating. Collodion cotton. In the manufacture of collodion or soluble cotton, the finer qualities of cotton waste are used, and the acids used in the dipping tanks are much weaker. The manufacture of collodion cotton has become of more importance than gun cotton, by reason of its use for the manufacture of the various forms of gelatin, such as gelatin dynamite, gelignite, forsyte, and C, and also on account of its extensive use in the manufacture of many of the smokeless powders. It is also used for the manufacture of collodion, which is a solution of collodion cotton in ether alcohol, for the preparation of celluloid, and many other purposes. It is less explosive than gun cotton, and consists of the lower nitrates of cellulose. It is soluble in nitroglycerin, and in a mixture of 2 parts of ether and 1 of alcohol, also in acetone, acetic ether, and other solvents. Menard and de Monti were the first to prepare a soluble gun cotton, and its investigation was carried on by Béchamp, who showed that its properties and composition were different to those of gun cotton. Manufacture. The cotton used is cotton waste. A. It is thought by some that Egyptian cotton is preferable, and especially long fiber varieties. The strength of the acids used is, however, of more importance than the quality of the cotton. The percentage composition of the acid mixture which gives the best results is as follows: nitric acid, 23%, sulfuric acid, 66%, and water, 11%, and has a specific gravity of 1.712, about. It can be made by mixing sulfuric acid of specific gravity 1.84 with nitric acid of specific gravity 1.368 in the proportions of 66% and 34%, respectively. The production of the pentanitrocellulose is aimed at if the collodion cotton is for use as an explosive. If the acids are much weaker than this, or potassium nitrate and sulfuric acid is used, the lower nitrates will be formed. The product, while being entirely soluble in ether alcohol or nitroglycerin, will have a low nitrogen content, whereas a material with as high a nitrogen as 12 or 12.6 is to be aimed at. Footnote A. Raw cotton is often used. The cotton should not be allowed to remain in the dipping tanks for more than 5 minutes, and the acid mixture should be kept at a temperature of 28 degrees Celsius, or thereabouts, and the cotton should be removed after a few minutes, and should not be pressed out, as in the case of gun cotton, but at once transferred to the pots and allowed to steep for 48 hours. Some prefer 24 hours, but there is more chance in this case of the product containing non-nitrate cellulose. When the nitration is complete, the collodion cotton is removed from the pots, and treated in exactly the same manner as described under gun cotton. The produce should be entirely soluble in ether alcohol and nitroglycerin, and contain as near 12.7% of nitrogen as possible. The theoretical nitrogen is for the pentanitrocellulose 12.75%. This will, however, seldom if ever be obtained. The following are some of the results I have obtained from different samples. Nitrogen. 1, 2, 3. German make 11.64, 11.48, 11.49%. Stowmarket 12.57, 12.60, 11.22. Walsrode 11.61, 12.07, 11.99. Faversham 12.14, 11.70, 11.60. And the following was the analysis of a sample, number 1, of German-made collodion cotton, which made very good blasting gelatin. Soluble cotton, collodion, 99.118%, nitrogen equals 11.64%, gun cotton 0.642, non-nitrate cotton 0.240, total ash 0.25. It should contain as little non-nitrate or unconverted cotton and as little gun cotton as possible, as they are both insoluble in nitroglycerol. The quality and composition of any sample of collodion cotton can be quickly inferred by determining the percentage of nitrogen by means of the nitrometer and the use of the solubility test. A high nitrogen content coupled with a high solubility is the end to be aimed at. A high nitrogen with a low solubility shows the presence of gun cotton, and a low nitrogen, together with a low solubility, the presence of unnitrated cotton. Where complete solubility is essential and the percentage of nitrogen less important, Dr. Lunge recommends nitration with a mixture of equal parts of sulfuric and nitric acids containing from 19 to 20% of water. Footnote A. See Analysis of Explosives. Mr. T.R. France claims to have invented some improvements in the manufacture of soluble nitrocellulose. His object has been to produce an article as uniform as possible. His explanation of the imperfect action of the acids is that, however uniform the mixed acids may be in strength and proportions, and however carefully the operations of nitrating, NC, may be conducted, there are variable elements found in different samples of cotton. The cotton fiber has for its protection a glazed surface. It is tubular and cellular in structure, and contains a natural semi-fluid substance composed of oil or gum, which varies in nature according to the nature of the soil upon which the cotton is grown. The tubes of the fiber seem to be open at one end only when the fiber is of normal length. When, therefore, the cotton is subjected to the action of the mixed acids, the line of least resistance seems to be taken by them, viz., the insides of the tubes constituting the fiber of the cotton, into which they are taken by capillary attraction, and are subject to change as they progress, and to the increased resistance from the oil or gum, NC, in their progress, and therefore to modified action, the result of which is slower and slower action, or chemical change. He also thinks it is possible that the power of capillary attraction is balanced in the tubes by air contained therein, after a little, sufficiently so to prevent the acids from taking full effect. To get over this, Mr. France uses his cotton in a fine state, almost dust, in fact, and then nitrates in the usual mixture of acids at 40 degrees to 90 degrees Fahrenheit, the excess of acids being removed by pressure. He says he does not find it necessary to wash this fine cotton dust in an alkaline solution previous to nitration. His mixed acids consist of 8 parts No_3 equals 42 degrees B, and 12 parts H_2 so_4 equals 66 degrees B, and he stirs in the dipping tank for 15 minutes, the temperature being 50 degrees Fahrenheit to 100 degrees Fahrenheit, the temperature preferred being 75 degrees Fahrenheit. Nitrate, gun cotton. The nitrates that are or have been mixed with gun cotton in order to supply oxygen are potassium nitrate, ammonium nitrate, and barium nitrate, tonight. The total combustion of gun cotton by potassium nitrate corresponds to the equation 10 C_24 H_18 No_3 H 1109 plus 82 No_3 equals 199 Co_2 plus 41 K_2 Co_3 plus 145 H_2 O plus 96 N_2 or 828 grms of nitrate for 1,143 grms of gun cotton, or 42% nitrate and 58% gun cotton. The explosive made at Faversham by the Cotton Powder Company, and known as Tonight No. 1, consists of very nearly half gun cotton and half barium nitrate. The relations by weight of total combustion would be 51.6 of gun cotton to 48.4 of barium nitrate. The average composition of Tonight I have found by analysis to be 51% gun cotton to 49% barium nitrate. The heat liberated is practically the same as for an equivalent weight of No_3, but the barium nitrate mixture weighs 2,223 grms. Instead of 1,971 grms, or 1/8 more. The advantage in mixing a nitrate with gun cotton is that it supplies oxygen, and by converting all the carbon into carbonic acid, prevents the formation of the poisonous gas carbonic oxide CO. The nitrates of potassium and barium are also used admixed with nitrocellulose in several of the sporting smokeless powders. The manufacture of Tonight. The explosive Tonight was patented by Messrs. Trench, Fore, and Mackey, and is manufactured at Faversham and Melling at the works of the Cotton Powder Company, and at San Francisco by the Tonight Powder Company. It consists of finely divided and macerated gun cotton incorporated with finely ground nitrate of barium which has been carefully recrystallized. It is made by acting upon carbonate of barium, A, with nitric acid. The wet and perfectly purified, Finely pulped guncotton is intimately mixed up between edge runners with about the same weight of nitrate, and the mixing and grinding continued until the whole has become an intimately mixed paste. This paste is then compressed into cartridges, formed with a recess at one end for the purpose of inserting the detonator. The whole is then covered with paraffin paper. Footnote A. Witherite BACO _3 plus 2 no _3 equals BA no _3 2 plus CO 2 plus H _2O. The tonight number 2 consisted of guncotton, nitrates of potash and soda, charcoal and sulfur. Tonight No. 3A is composed as follows: guncotton 19%, dinitrobenzol 13%, and barium nitrate 68%, or similar proportions. It is a yellowish color, and being slower in its explosive action, is better adapted for blasting soft rock. Footnote A. Tonight number 1 was patented by Messrs. Trench, 4, and Mackey, and tonight numbers 2 and 3 by Trench alone. Tonight is extensively used in torpedoes and for submarine blasting, also for quarries, and c. Large quantities were used in the construction of the Manchester Ship Canal. Among its advantages are that the English railways will take tonight on the same footing as gunpowder. It is a very dense material. If wetted, it can easily be dried in the sun. It very readily explodes by the use of a proper detonator, while it burns very slowly and without the least danger. The cartridges being waterproofed, it can be employed in wet bore holes, and it can be tamped with water, and finally, as it contains sufficient oxygen to oxidize the carbon, no carbonic oxide (CO) gas is formed, i.e., its detonation is perfect. It is a very safe explosive to use, being little susceptible to either blows or friction. Not long ago, a committee, composed of Professor P. Bedson, Drs. Drummond and Hume, Mr. T. Bell, one of H.M. inspectors of coal mines, and others, in considering the problem whether the fumes produced by the combustion of tonight were injurious to health, carried out a series of experiments in coal mines for this purpose. The air at the intake was analyzed, also the air of the return, and the smoky air in the vicinity of the shot holes. The cartridge was surrounded by the flame-extinguishing mixture, and packed in a brown paper bag. During the first experiment 19 shots were fired, equals 6.29 pounds. Tonight. The return air showed only a trace of carbonic oxide gas, CO. At the second experiment 13 shots were fired, equals 4.40 pounds. Tonight, an analysis of the air of the return showed that CO was present in traces only, whilst the fumes contained only 1.9 to 4.8 parts per 10,000. Dangers in connection with the manufacture of guncotton, and c. Of all the nitro compounds, the least dangerous to manufacture are guncotton and collodion cotton. The fact that the Stowmarket factory is within 5 minutes' walk of the town shows how safe the manufacture of this explosive is regarded. With the exception of the nitration and the compression into blocks or discs, the whole process is worked with a large excess of water, and the probability of an explosion is thus reduced to a minimum. Among the precautions that should, however, be taken are, first, the careful extraction of the resinous and soluble substances from the cotton before nitration, as it was shown many years ago by Sir F. A. Abel that the instability of the guncotton first manufactured in England and Austria was chiefly due to these compounds. They are generally removed by boiling the cotton in a soda solution. The actual nitration of cotton is not a dangerous operation, but the operations of wringing in the hydro-extractors, and washing the nitro cotton after it leaves the first centrifugal machine, are somewhat so. Great care should be taken that the wrung-out nitro cotton at once comes in contact with a large excess of water, i.e., is at once immersed entirely in the water, since at this stage it is especially liable to decomposition, which, once started, is very difficult to stop. The warmer the mixture and the less water it contains, the more liable it is to decomposition. Hence it is that on warm and damp days the centrifugal machines are most likely to fire. The commencement of decomposition may be at once detected by the evolution of red fumes. Directly the guncotton is immersed in the large quantity of water in the beater and poacher, it is safe. In order that the final product may be stable and have good keeping qualities, it is necessary that it should be washed completely free from acid. The treatment in the beater and poacher, by causing the material to assume the state of a fine pulp, in contact with a large quantity of water, does a good deal to get rid of the free acid, but the boiling process is absolutely necessary. It has been proposed to neutralize the free acid with a dilute solution of ammonia, and Dr. Weber has published some experiments bearing upon this treatment. He found that after treatment with ammonia, pyroxylene assumed a slightly yellowish tinge, which was a sure sign of alkalinity. It was then removed from the water, and roughly dried between folds of filter paper, and afterwards dried in an oven at 70 degrees Celsius. After 3 hours, however, an explosion took place, which entirely destroyed the strong copper oven in which the nitro cotton, about 1 ounce, had been drying. The explosion was in some respects remarkable. The pyroxylene was the D-nitrocellulose, or possibly the pentanitro, and the temperature was below the igniting point of this material, 40 degrees Celsius, would have been a better temperature. Dr. Weber determined the ignition point of his D-nitrocellulose, and found it to be 194 degrees to 198 degrees Celsius, and he is therefore of opinion that the explosion was due to the treatment of the partially washed material with ammonia. A certain quantity of ammonium nitrate was probably formed, and subsequently dried upon the nitrocellulose, in a state of very fine subdivision. The faintest trace of acid would then be sufficient to bring about the explosive ignition of the ammonium nitrate. The drying of gun cotton or collodion cotton is also a somewhat dangerous operation. A temperature of 40 degrees Celsius, 104 degrees Fahrenheit, should not be exceeded, and thermometers should be placed in the nitro cotton, and the temperature frequently observed. An electric alarm thermometer is also a useful adjunct to the cotton drying house. Great care must also be taken that there are no exposed hot water pipes or stoves in the drying house, as the fine gun cotton dust produced by the turning or moving of the material upon the shelves would settle upon such pipes or stoves, and becoming hot, would be very sensitive to the least friction. The floor also should be covered with linoleum or India rubber. When hot currents of air are made to pass over the surface of gun cotton, the gun cotton becomes electrified. It is important, therefore, to provide some means to carry it away. Mr. W. F. Reed, FIC, was the first to use metal frames, carriers, and sieves, upon which is secured the cloth holding the gun cotton, and to earth them. The compression of gun cotton into blocks, discs, and is also attended with considerable risk. Mr. O. Gutman, in an interesting paper upon the dangers in the manufacture of explosives, Jur. Soc. Chem. IND No. 3, Volume 11, 1892 says, "The compression of gun cotton into cartridges requires far more care than that of gunpowder, as this is done in a warm state, and gun cotton even when cold is more sensitive than gunpowder. When coming out of the centrifugal machines, the gun cotton should always pass first through a sieve, in order to detect nails or matches which may by chance have got into it. What has been said as to gunpowder presses applies still more to those for gun cotton, although the latter are always hydraulic presses. Generally the pistons fit the mold perfectly, that is to say, they make aspiration like the piston of a pump. But there is no metal as yet known which for any length of time will stand the constant friction of compression, and after some time the mold will be wider in that part where the greatest compression takes place. The best metal for this purpose has proved to be a special steel made by Krupp, but this also is only relatively better. For pistons I prefer hard cast iron. If the position of the molds and pistons is not exactly the same in all cases, what the Germans call Ecken, English binding, will take place, viz., the mold will stand obliquely to the piston, and a dangerous friction will result. Of course, it is necessary to protect the man working the hydraulic valves during compression. At Waltham Abbey they have a curtain made of ship's hawsers, which is at the same time elastic and resistant. Mr. Gutman has found that a partition wall 12 inches thick, made of 2-inch planks, and filled with ground cinders, gives very effective protection. A door in this partition enables the workman to get to the press, and a conical tube penetrates the wall, enabling the man to see the whole work from a safe standpoint. The roof, or one side of the building, should be of glass, so as to give the explosion a direction. Trench's fire-extinguishing compound is manufactured by the Cotton Powder Company at Faversham, and is the invention of Mr. George Trench, FCS, the manager of the company. The object of the invention is to surround the cartridges of tonight, when used in coal mines, with a fire-extinguishing compound. If a charge of tonight, dynamite, or gelatin dynamite is put inside a few ounces of this mixture, and then fired, not the least trace of flame can be observed, and experiments appear to show that there is no flame at all. The compound consists of sawdust impregnated with a mixture of alum and chlorides of sodium and ammonia. Figure 22 shows the manner of placing the tonight cartridge in the paper bag, and surrounding it with the fire-extinguishing compound, A. The attachment of the fuse and detonator is also shown. Illustration: Figure 22. Trench's fire-extinguishing cartridge. The following report, taken from the Faversham News, October 22, 1887, of experiments conducted in the presence of several scientific and mining men will show its value. A large wrought iron tank, of 45 cubic feet capacity, had been sunk level with the ground in the middle of the yard. To this tank the gas had been laid on, for a purpose that will be explained later on. The charges were fired by means of electricity, a small dynamo firing machine being placed from 30 to 40 yards away from the mine. Operations were commenced by the top of the tank being covered over and plastered down in order to make it airtight. Then a sufficient quantity of coal gas was placed in it to make it highly inflammable and explosive, the quantity being ascertained by a meter which had been fixed specially for the purpose. Whilst the gas was being injected, the cartridge was prepared. The first experiment was to try whether a small charge of tonight, fired without the patent extinguisher, would ignite the gas. The gas having been turned on, a miner's lamp was placed in the tank, but this was extinguished before the full quantity of gas had gone through the meter. However, the gas being in, the charge of 1 1/4 ounces tonight was placed in the mine. The detonator was connected by means of long wires to the dynamo machine, and the word was given to fire. With a tremendous report, and a flash of fire, the covering of the mine flew in all directions, clearly showing that the gas had exploded. The next cartridge, a similar charge, was prepared with the patent compound. First of all, a brown paper case of about 2 inches diameter was taken, and one of the tonight cartridges was placed in the center of it, the intervening space between the charge and the case being packed with the fire-extinguishing compound. The mine having had another supply of gas injected, the protected cartridge was placed inside and fired. The result was astonishing, the explosion not being nearly so loud, whilst there was not the least flash of fire. Protected and unprotected charges were fired at intervals, gas being turned into the tank on each occasion. Charges of tonight varying from 1 to 6 ounces were also used with the compound. The report was trifling, whilst no flash could be seen. Uses of collodion cotton. The collodion or soluble gun cotton is used for a variety of purposes. The chief use is, however, for the manufacture of the various explosive gelatin compounds, of which blasting gelatin is the type. It is also very extensively used in the manufacture of smokeless powders, both military and sporting. In fact, very few of them do not contain it. In some, however, nitrolignose or nitrate wood is used instead. This, however, is chemically the same thing, viz., nitrocellulose, the cellulose being derived from the wood fiber. It is more used in this connection than the higher nitrate gun cotton. Another use to which it has been applied very extensively, of recent years, is in the manufacture of celluloid. It is used in photography for the preparation of the films on the sensitized plates, and many other purposes. Dissolved in a solution of 2 parts ether and 1 of alcohol, it forms the solution known as collodion, used for a variety of purposes, such as a varnish, as a paint for signals, in surgery, for uniting the edges of wounds. Quite lately, Mr. Alfred Nobel, the well-known inventor of dynamite, has patented the use of nitrocellulose, hydro or oxycellulose, as an artificial substitute for indiarubber. For this purpose it is dissolved in a suitable non-volatile, or slightly volatile, solvent, such as nitronaphthalene, dinitrobenzene, nitrotoluene, or its homologues, products are obtained varying from a gelatinous consistency to the hardness of ebonite. The proportions will vary from about 20% of nitrocellulose in the finished product, forming a soft rubber, to 50% nitrating celluloid, and the solvent chosen will depend on the use to which the rubber substitute is to be put, the liquids giving a more elastic substance, whilst mixtures of solids and liquids may be employed when the product is to be used at high temperatures. By means of rollers steam heated, the incorporation may be accomplished without the aid of a volatile liquid, or the nitrocellulose may be employed wet, the water being removed after solution. It is advisable to use the cellulose nitrate only just enough to render it suitable, in order to reduce the inflammability of the finished product. Mr. W. Allen, MP, of Gateshead, proposed to use celluloid for cartridge cases, and thus to lighten ammunition and prevent jamming, for the case will be resolved into gases along with the powder. Extractors will also be done away with. Celluloid is an intimate mechanical mixture of pyroxylene, gun cotton or collodion cotton, with camphor, first made by Hyatt, of Newark, USA, and obtained by adding the pyroxylene to melted camphor, or by strongly compressing the two substances together, or by dissolving the constituents in an appropriate solvent, example, alcohol or ether, and evaporating to dryness. A combination of the two latter methods, i.e., partial solution, with pressure, is now usually adapted. The pyroxylene employed is generally the tetra and pentanitrate cellulose, the hexanitrate, gun cotton, being but seldom used on account of its explosive properties. Care is taken to prevent the formation of the hexanitrate by immersing the cellulose in only moderately strong nitric acid, or in a warm mixture of nitric and sulfuric acids. The paper, either in small pieces or in sheets, is immersed for about 25 minutes in a mixture of 2 parts of nitric acid and 5 parts of sulfuric acid, at a temperature of about 30 degrees Celsius, after which the nitrate cellulose is thoroughly washed with water to remove the last traces of free acid, pressed, and whilst still moist, mixed with the camphor. In the process of Trebouillet and de Bisancel, the cellulose, which may be in the form of paper, cotton, or linen, is twice nitrate, first in the acid mixture employed in a previous operation, and secondly, in a fresh mixture of 3 parts sulfuric acid of 1.83 specific gravity, and 2 parts concentrated nitric acid containing nitrous acid. After each nitration, the mass is subjected to pressure, and is then carefully washed with water, to which, at the last, a small quantity of ammonia or caustic soda is added to remove the final traces of acid. The impregnation of the pyroxylene with the camphor is effected in a variety of ways. The usual proportion of the constituents is 2 parts pyroxylene and 1 part camphor. In Trebouillet and de Bisancel's process, 100 parts of pyroxylene are intimately mixed with from 40 to 50 parts camphor, and molded together by strong pressure in a hot press, and afterwards dried by exposure to air, desiccated by calcium chloride or sulfuric acid. The usual method is, however, to dissolve the camphor in the least possible quantity of alcohol, and sprinkle the solution over the dry pyroxylene, which is then covered with a second layer of pyroxylene, and the whole again treated with the camphor solution, the addition of pyroxylene and camphor solution being repeated alternately until the requisite amount of celluloid mixture is obtained. The mass, which sinks together in transparent lumps, is worked for about an hour between cold iron rollers, and then for the same period between rollers which can be gently heated by steam. The layer of celluloid surrounding the rollers is then cut away and again pressed, the resulting cake, which is now about 1 centimeter thick, being cut into plates of about 70 centimeters long and 30 centimeters broad. These are placed one above the other, and strongly pressed together by hydraulic pressure at a temperature of about 70 degrees for 24 hours. The thick cakes are once more cut into plates of the desired thickness, and placed in a chamber heated from 30 degrees to 40 degrees for 8 to 14 days, whereby they become thoroughly dry, and are readily made into various articles either by being molded while warm under pressure, cut, or turned. Occasionally other liquids, example, ether and wood spirit, are used in place of alcohol as solvents for the camphor. Celluloid readily colors, and can be marbled for manufacturing purposes, and c. It is highly inflammable and not explosive even under pressure, and may be worked under the hammer or between rollers without risk. It softens in boiling water, and may be molded or pressed. Its specific gravity varies slightly with its composition and with the degree of pressure it has received. It is usually 1.35. It appears to be merely a mixture of its components, since by treatment with appropriate solvents the camphor may be readily extracted, and on heating the pyroxylene burns away while the camphor volatilizes. The manufacture of pyroxylene for the purpose of making celluloid has very much increased during recent years, and with this increase of production improved methods of manufacture have been invented. A series of interesting papers upon the manufacture of pyroxylene has been published by Mr. Walter D. Field, of New York, in the Journal of the American Chemical Society, from which the following particulars are taken. Footnote A, Volume 15, Number 3, 1893, Volume 16, Number 7, 1894, Volume 16, Number 8, 1894. Figures 19 and 20 and 21 and 22 and 23 are taken from Mr. Field's paper. Selection of the fiber. Cotton fiber, wood fiber, and flax fiber in the form of raw cotton, scoured cotton, paper, and rags are most generally used, and give the best results. As the fibers differ greatly in their structure, they require different methods of nitrating. The cotton fiber is a flat and hollow ribbon or collapsed cylindrical tube, twisted a number of times, and closed at one end to form a point. The central canal is large, and runs nearly to the apex of the fiber. Its side walls are membranous, and are readily penetrated by the mixed acids, and consequently the highest nitration results. In the flax fiber the walls are comparatively thick, the central canal small. Hence it is to be presumed that the nitration must proceed more slowly than in the case of cotton. The New Zealand flax gives the most perfectly soluble nitrates of any of the flaxes. Cotton gives a glutinous collodion, and calico a fluid collodion. One of the largest manufacturers of pyroxylene in the States uses the Memphis Star brand of cotton. This is an upland cotton, and its fibers are very soft, moist, and elastic. Its color is light creamy white, and is retained after nitration. The staple is short, and the twist inferior to other grades, the straight ribbon-like filaments being quite numerous. This cotton is used carded, but not scoured. This brand of cotton contains a large quantity of 1/2 and 3/4 ripe fiber, which is extremely thin and transparent, distributed throughout the bulk of the cotton, money. Cotton fiber, 67. Mr. Field says, "This is a significant fact when it is known that from this cotton an extremely soluble pyroxylene can be produced. Pyroxylene of an inferior grade as regards color only can be produced from the cotton wastes of the trade. They must be scoured before they are fit for nitrating. Paper made from the pulps of sulfite and sulfate processes is capable of yielding a very soluble pyroxylene. It can be nitrated at high temperatures and still yield good results. Tissue paper made from flax fiber is also used after being cut into squares. Mowbray, USB, No. 443, 105, December 3, 1890, says that a pure cotton tissue paper less than 1/500 inch in thickness, thin as it is, takes on a glutinous or collard surface, and thus requires some 30 minutes to enable the nitration to take place. With a thicker paper only the surface would be nitrate. He therefore uses a fiber that has been saturated with a solution of nitrate of soda, and afterwards dried slowly, claiming that the salt crystallizes in the fiber, or enters by the action termed osmose, and opens up the fiber to the action of the acid. This process would only be useful when the cotton is to be nitrated at a low temperature. At a high temperature it would be unnecessary. Dietz and Wayne, USB, No. 133, 969, use rami, rica, or China grass for producing a soluble pyroxylene. That made from rami is always of uniform strength and solubility, and requires a smaller quantity of solvent to dissolve it than that made from cotton. Mr. Field's experience, however, is entirely contrary to this statement. Such is the influence of the physical form of the fiber on the process of nitration, that when flax fiber and cotton fiber are nitrated with acid mixtures of exactly the same strength, and at the same temperature, the solution of the first is glutinous or thick, and the second fluid or thin. By simply nitrating at a higher temperature than the cotton, the flax will yield a pyroxylene giving an equally fluid collodion. The presence of chlorine in the fiber must be carefully avoided, as such a fiber will yield an acid product which cannot be wash neutral. The fiber must be dry before nitration, and this is best done, according to Mr. Field, by using the form of dryer used in drying wool. Nitration of the fiber. Mixed cotton and flax fiber in the form of paper, from 2/1000 to 3/1000 inch thick, and cut into 1-inch squares, is nitrated by the Celluloid Manufacturing Company, and the same paper, left in long strips, 1 inch wide, is used for nitration by the Xylonite Manufacturing Company, of North Adams, Massachusetts, USA. The Celluloid Company introduced the cut paper into the mixed acids by means of a hollow, rapidly revolving tube, flared at the lower end, and immersed in the mixed acids. The centrifugal force of the revolving tube throws the paper towards the sides of the vessel, leaving the center of the vessel ready for fresh paper. The Xylonite Company simply cut the paper into long strips, and introduce it into the mixed acids by means of forks. The arrangement used by this company for holding the mixed acids is a cylindrical vessel divided into a number of sections, the whole revolving like a turntable, thus allowing the workman to nitrate successively each lot of paper at a given point. This company did not remove the acid from the paper after its immersion, but plunged it immediately into the water, thus losing a large proportion of the waste acid. The Celluloid Company, by using the paper in smaller pieces, and more paper to a pound of acid, and wringing the mixed acid from the paper before immersion in water, had a better process of nitration. Other manufacturers use earthenware vessels, and glass or steel rods, hooked at one end, having small pieces of rubber hose pulled over the other end to prevent the hand from slipping. The form of vessel in general use is that given in Figure 23. It is large enough to nitrate 1 pound of cotton at a time. The hook at one end of the rod enables the workman to pull the pyroxylene apart, and thus ensures saturation of the fiber. In the winter, the room in which the nitrating is done must be kept at a temperature of about 70 degrees Fahrenheit, in order to secure equality in the batches. Illustration: Figure 23. Vessel for nitrating cotton or paper. The nitrating apparatus of White and Schupfau's, USB, No. 418, 237, 89, Mr. Field considers to be both novel and excellent. The cage, Figure 24, with its central perforated cylinder, Figure 25, is intended to ensure the rapid and perfect saturation of the tissue paper used for nitrating. The patentees say that no stirring is required with their apparatus. This, says Mr. Field, might be true when paper is used, or even cotton, when the temperature of nitration is from 30 degrees to 35 degrees Celsius, but would not be true if the temperature were raised to 50 degrees to 55 degrees Celsius. The process is as follows. The paper is nitrated in the cage, Figure 25, the bottom of which is formed by the flange plate C, fastened to the bottom of the internal cylinder B. After nitration, the cage is carried to a wringer, which forms the basket, and the acids removed. Finally, the cage is taken to a plunge tank, where the paper is removed from the cage by simply pulling out the central perforated cylinder B. Figure 26 shows the nitrating pot, with its automatic cover. The plunge tank is shown in plan and section in Figures 28 and 29. This apparatus is suitable for the nitration of cotton fiber in bulk at high or low temperatures. Other methods that have been patented are Mowbray's, USB, No. 434, 287, in which it is proposed to nitrate paper in continuous lengths, and Hyatt's, USB, No. 210, 611. Illustration: Figure 24. Central perforated cylinder. Illustration: Figure 25. The cage. White and Schupfau's nitrating apparatus. Illustration: Figure 26. Celluloid nitrating pot. Illustration: Figure 27. Another view. Illustration: Figures 28 and 29. Plunge tank, in plan and section. The acid mixture. Various formulae have been published for producing soluble nitrocellulose. In many instances, although the observations were correct for the single experiment, a dozen experiments would have produced a dozen different products. The composition of the acids used depends upon the substance to be nitrate, and the temperature at which the nitration will be worked. Practically, there are three formulae in general use: the one used by the celluloid manufacturers, another in which the cotton is nitrate at high temperatures, and a third in which the temperature of the immersion is low, and the time of nitration about 6 hours. Of the three, the best method is the last one, or the one in which the cotton is immersed at a low temperature, and then the reaction allowed to proceed in pots holding from 5 to 10 pounds of cotton. The formula used by the celluloid manufacturers for the production of the low form of nitrate product which they use is sulfuric acid 66 parts by weight, nitric acid 17, water 17. Temperature of immersion 30 degrees Celsius. Time 20 to 30 minutes. The cellulose is used in the form of tissue paper 2/1000 inch thick, 1 pound to 100 of acid mixture. The nitrocellulose produced by this formula is very insoluble in the compound ethers and other solvents of pyroxylene, and is seemingly only converted or gelatinized by the action of the solvent. The next formula produces a mixture of tetra and pentanitrocelluloses hardly soluble in methyl alcohol, free from acetone, but very soluble in anhydrous compound ethers, ketones, and aldehydes. Nitric acid, SpGr 1.4358 pounds, sulfuric acid, SpGr 1.8315 3/4 pounds, cotton 14 ounces. Temperature of nitration, 60 degrees Celsius. Time of immersion, 45 minutes. The 60 degrees of temperature is developed by mixing the acids together. The cotton is allowed to remain in the acid until it feels short to the rod. The following table, due to Mr. W. D. Field, shows very plainly the great variation in the time of the immersion and the temperature by seemingly very slight causes. It extends over 14 working days, during which time it rained 4 days. The formula used is that given above, except that the specific gravity of the nitric acid is somewhat lower. The product obtained differs only from that produced by using nitric acid of specific gravity 1.43 in being soluble in methyl alcohol. From 30 to 35 pounds of pyroxylene were produced in each of the 14 days. A careful examination of this table will prove very instructive. The increase in yield varies from 31% to nothing, and the loss runs as high as 10%, yet care was taken to make the product uniform in quality. On the days it rained there was a loss, with the exception of the 4th day, when there was neither a loss nor a gain. On the days it was partly clear, as just before or after rain, the table shows a loss in product. We can explain this fact by reason of the moisture-absorbing qualities of the cotton. On the rainy days it would absorb the moisture from the air until, when immersed in the acids, they were weakened, and the fiber dissolved more or less in weakened acid, producing what is known as burning in the batch. It will also be noticed that on days which show a loss, the time of the immersion was correspondingly short, as on the a loss, the time of the immersion was correspondingly short, as on the 10th, 12th, and 7th days. Underscore 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 specific gravity time underscore 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 h underscore 2 s 0 underscore 4 dot No underscore 3 dot hours minutes hours minutes underscore 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 1. Clear 1.838 1.4249 20 42 1.837 1.4249 20 2 3 Cloudy 1.837 1.4226 45 2 4 Rain 1.837 1.420 20 1 25 Clear 1.8377 1.42 1 15 2 6 Rainy 1.8391 1.422 35 1 40 7 Cloudy 1.835 1.4226 20 35 8 Clear 1.835 1.422 35 1 10 9 Partly clear 1.824 1.4271 20 1 10 1.83 1.4271 10 25 11 Cloudy 1.832 1.425 10 50 12 Rainy 1.822 1.425 10 20 13 Partly clear 1.8378 1.4257 60 1 40 14 Cloudy 1.837 1.4257 1 56 4 40 underscore 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 temp degree C percentage underscore 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 from 2 increase loss underscore 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 1 clear 57 degrees 62 degrees 31 2 60 degrees 62 degrees 18 3 cloudy 60 degrees 62 degrees 7 4 rain 60 degrees 63 degrees 0 0 5 clear 58 degrees 62 degrees 15 6 rainy 58 degrees 62 degrees 2 7 cloudy 62 degrees 65 degrees 10 8 clear 60 degrees 62 degrees 5 9 partly clear 50 degrees 60 degrees 3 10 58 degrees 60 degrees 10 11 Cloudy, 58 degrees, 60 degrees 8, 12. Rainy, 58 degrees, 60 degrees 10, 13. Partly clear, 50 degrees, 58 degrees 20, 14. Cloudy, 50 degrees, 60 degrees 16. Underscore 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 underscore. The lesson this table teaches is that it is almost impossible to nitrate cellulose in small quantities and get uniform results when the nitration is carried on at high temperatures. As regards the solubility of pyroxylene, Parkes found that nitrobenzene, aniline, glacial acetic acid, and camphor, dissolved in the more volatile solvents methyl alcohol and alcohol ether, were much the best solvents for producing a plastic, as they are less volatile, and develop greater solvent action under the influence of heat. Nitrobenzene gives a solution that is granular. It seems to merely convert the pyroxylene, and not to dissolve it, but on the addition of alcohol, a solution is at once obtained, and the granular appearance disappears, and the solution becomes homogeneous. The acid mixture and the method of nitrating have much to do with the action of the various solvents, so also has the presence of water. Dr. Schupfauss found that propyl and isobutyl alcohols with camphor were active solvents, and the ketones, palmitone, and stearone in alcohol solution, also alpha and beta naphthol, with alcohol and anthraquinone, diphenylene diketone, in alcoholic solution, and also iasovaleric aldehyde and its derivatives, amylidine dimethyl and amylidine diethyl ethers. August Sayer, USB, No. 470451, finds diethylketone, dibutylketone, dipentylketone, and the mixed ketones A. methylethyl, methylpropyl, methylbutyl, methylamyl, and ethylbutyl ketones are active solvents of pyroxylene, and Paget finds that although methylamyl oxide is a solvent, that ethylamyl oxide is not. Footnote A. Ketones are derived from the fatty acids by the substitution of the hydroxyl of the latter by a monad-positive radical. They thus resemble aldehydes in constitution. The best-known ketone is acetone CH_3, company CH_3. Mixed ketones are obtained by distilling together salts of two different fatty acids. Thus potassic butyrate and potassic acetate form propylmethylketone. C_2, H_5, H_2, company CH_3. The solvents of pyroxylene can be divided into general classes. First, those which are solvents without the aid of heat or solution in alcohol. Second, those that are solvents when dissolved in alcohol. These solvents are those which also develop a solvent action when heated to their melting point in combination with pyroxylene. Mr. W. D. Field groups the solvents of pyroxylene into classes thus: 2 of the monohydric alcohols, compound ethers of the fatty acids with monohydric alcohols, aldehydes, simple and mixed ketones of the fatty acid series. These 4 classes include the greater number of the solvents of pyroxylene. Those not included are as follows: amyl nitrate and nitrite, methylene dimethyl ether, ethidine diethyl ether, amyl chloroacetate, nitrobenzene and dinitrobenzene, coumarin, camphor, glacial acetic acid, and mono-D- and triacetin. Richard Hale uses the following solvent: amyl acetate, 4 volumes, petroleum naphtha, 4 volumes, methyl alcohol, 2 volumes, pyroxylene, 4 to 5 ounces to the gallon of solvent. Hale used petroleum naphtha to hasten the drying qualities of the varnish, so that it would set on the article to be varnished before it had a chance to run off. It is, however, the non-hygroscopic character of the solvent that makes the varnish successful. This formula is very largely used for the production of pyroxylene varnish, which is used for varnishing pens, pencils, and also brasswork and silverware. The body known as oxycellulose, A, is formed by the action of nitric acid upon cellulose when boiled with it. The quantity formed is about 30% of cellulose acted upon. When washed free from acid, it gelatinizes. It is then soluble in dilute alkalis, and can be reprecipitated from solution by alcohol, acids, or saline solutions. Messrs. Cross and Bevan assigned to it the formula C_18, H_26, O_16. It dissolves in concentrated sulfuric acid, and with nitric acid forms a nitro body of the formula C_18, H_23, O_16, 3, No_2, which is prepared as follows. The gelatinous oxycellulose is washed with strong nitric acid until free from water, and is then diffused through a mixture of equal volumes of strong sulfuric and nitric acids, in which it quickly dissolves. The solution, after standing for about an hour, is poured in a fine stream into a large volume of water, by which the nitro body is precipitated as a white flocculent mass. The product, after drying at 110 degrees Celsius, was found upon analysis to contain 6.48% nitrogen. Footnote A. On the oxidation of cellulose. By C.F. Cross and E.J. Bevan, Jur. Chem. SOC 1883, page 22. Miscellaneous Nitro-Explosives. Nitrostarch. It is only recently that, by means of the process introduced by the Aktiengesellschaft Dynamit Nobel, it has been possible to make this explosive upon the manufacturing scale. Nitrostarch has been known since 1883, when Brackenot discovered it, and called it xyloidine. Its formula is C_6, H_8, O_3, No_3_2, but Dr. Otto Mulhausen has lately succeeded in preparing higher nitrate compounds, viz. A. C_6, H_7.5, O_2.5, No_3_2.5. B. C_6, H_7, O_4, No_3_3. Or doubling the molecule of starch. Nitrogen. I. Tetranitrostarch C_12, H_16, O_6, Ono_2 for 11.11%. 2. Pentanitrostarch C12, H_15, O_5, Ono_2 5, 12.75. 3. Hexanitrostarch C12, H_14, O_4, Ono_2 6, 14.14. He regards them as true ethers, esters, of nitric acid. Thus, on treatment with sulfuric acid, these compounds yield No_3H, the residue O.No_2, thus appearing to be replaced by the sulfuric acid residue. On treatment with a solution of ferrous chloride, nitric oxide, and soluble starch are regenerated. On shaking with sulfuric acid over mercury, all the nitrogen is split off as No. Tetranitrostarch is prepared upon the large scale as follows. A quantity of potato starch is taken and exposed in some suitable desiccating apparatus at a temperature of 100 degrees Celsius, until all the moisture which it contains is completely driven off. It is then reduced to a fine powder by grinding, and dissolved in nitric acid of specific gravity 1.501. The vessel in which this solution is accomplished is made of lead, and must be provided with 2 jackets, cooled by means of water. It should further be fitted with a screw agitator, in order to keep the nitric acid circulating freely. The charge of starch is introduced through an opening in the cover of this digesting vessel, and the proportions of acid to starch are 10 kilograms of starch to 100 kilos of acid. The temperature is kept within the limits 20 degrees to 25 degrees Celsius. When the solution of the starch is complete, the liquid is conducted into a precipitating apparatus, which is also provided with a cooling jacket, for the purpose of regulating the temperature. The bottom of this vessel is double and perforated, and here is placed a layer of guncotton to act as a filter. This vessel is filled with spent nitrosulfuric acid obtained as a waste product from the nitroglycerin manufactory, and the solution of starch and nitric acid is sprayed into it through an injector worked by compressed air, whereby the nitro-starch is thrown down in the form of a fine-grained powdery precipitate. In order to precipitate 100 kilos of the acid solution of starch, it is necessary to employ 500 kilos of spent nitrosulfuric acid. As it is precipitated, the nitro-starch collects on the gun-cotton filter, and the acid liquor is run off through a tap placed beneath the perforated double bottom of the vessel, and of course below the filter pad. The precipitated starch is further cleansed from acid by repeated washings and by pressure, until all trace of acidity has been eliminated, and the substance exhibits a neutral reaction. The next step is to treat the nitro-starch with a 5% solution of soda, in contact with which it is allowed to stand for at least 24 hours. The product is then ground up until a sort of milk or emulsion is obtained, and lastly treated with a solution of aniline, so that when pressed into cake, it contains about 33% of water and 1% of aniline. Dr. Mulhausen, working on these lines in the laboratory, prepared nitro-starch which contained 10.96 and 11.09% of nitrogen. When in the state of powder, it is snow-white in color. It becomes electrified when rubbed. It is very stable and soluble even in the cold in nitroglycerin. He has also prepared a tetranitro-starch containing 10.58 and 10.5% of nitrogen by pouring water into a solution of starch in nitric acid which had stood for several days. The substance thus produced in the laboratory had all the properties of that prepared by the other process. The production of pentanitro-starch is effected by adding 20 grams of rice starch, previously dried at a temperature of 100 degrees Celsius, in order to eliminate all moisture, to a mixture of 100 grams of nitric acid, specific gravity 1.501, and 300 grams of sulfuric acid, specific gravity 1.8. Some tetranitro-starch is also formed at the same time. After standing in contact with these mixed acids for 1 hour, the starch has undergone a change, and the mass may now be discharged into a large quantity of water, and then washed, first with water, and finally with an aqueous solution of soda. The yield in Dr. Mulhausen's experiments was 147.5%. The substance thus formed is now heated with ether alcohol, the ether is distilled off, and the pentanitro-starch appears as a precipitate, whilst the tetranitro-starch, which is formed simultaneously, remains in solution in the alcohol. As obtained by this process, it contained 12.76 and 12.98% nitrogen, whilst the soluble tetranitro-starch contained 10.45%. Hexanitro-starch is the product chiefly formed when 40 grams of dry starch are treated with 400 grams of nitric acid, specific gravity 1.501, and allowed to stand in contact for 24 hours. 200 grams of this mixture are then poured into 600 cc of sulfuric acid of 66 degrees B. The result of this manipulation is a white precipitate, which contains 13.52 to 13.23 and 13.22% nitrogen, and consists, therefore, of a mixture of penta and hexanitro-starch. The experiments undertaken with these substances demonstrated that those prepared by precipitating the nitro-starch with strong sulfuric acid were less stable in character or properties than those which were precipitated by water or weak sulfuric acid. Dr. Mulhausen is of opinion that possibly in the former case a sulfo group may be formed, which in small quantity may occasion this instability. The following table shows the behavior of these substances prepared in different ways and under various conditions. Underscore 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 Samples. Underscore 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 A B C D E. Ignition point 175 degrees C, 170 degrees C, 152 degrees C, 121 degrees C, 155 degrees C. Stability, stable, stable, unstable, unstable, unstable. Percent of N, 11.02, 10.54, 12.87, 12.59, 13.52, 96%. Alcohol, sol, sol, insol, 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 ether, insol, 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 ether alcohol, sol, 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 acetic ether, sol, 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 sol. Underscore 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 underscore. These samples were prepared as follows: A. From 1 part nitric acid and 2 parts sulfuric acid, containing 70%, H_2O. B. From 1 part nitric acid and water. C. From 1 part nitric and 3 parts H_2, so_4 con. D. From 1 part nitric and 3.5 parts con. H_2, so_4. E. From 1 part nitric and 3 parts con. H_2, so_4. Dr. Mulhausen is of opinion that these compounds may be turned to practical account in the production of good smokeless powder. He recommends the following proportions and method: 6 grms of nitro jute and 2 grms of nitro starch are mixed together and moistened with acetic ether. These ingredients are then worked together into a uniform mass and dried at a temperature ranging between the limits 50 degrees to 60 degrees Celsius. He has himself prepared such a smokeless powder, which proved to contain 11.54% of nitrogen and was very stable. Further details of Dr. Mulhausen's work upon nitrostarch can be found in Dingler's Polytechnisches Journal, paper. Die Horen Salpetersäure der Stark. 1892, Band 284 s. 137-143, and a bibliography up to 1892 in Arms and Explosives, December 1892. M. Berthelot gives the heat of formation of nitrostarch as 812 calories for 1 grm, and the heat of total combustion as equal to 706.5 calories for 207 grms, or for 1 grm, 3,413 calories. The heat of decomposition could only be calculated if the products of decomposition were given, but they have not as yet been studied, and the quantity of oxygen contained in the compound is far from being sufficient for its complete combustion. Berthelot and Va found the average velocities for nitrostarch powder, density of charge about 1.2, in a tin tube 4 mm, external diameter, to be, in 2 experiments, 5,222 m, and 5,674 m, in a tin tube 5.5 mm, external diameter, the velocity was 5,815 m, and in lead tube 5,006 m, density 1.1 to 1.2. The starch powder is hygroscopic, and is insoluble in water and alcohol. When dry it is very explosive, and takes fire at about 350 degrees Fahrenheit, Mr. Alfred Nobel has taken out a patent, Eng. Pat. No. 6560-88, for the use of nitrostarch. His invention relates to the treatment of nitrostarch and nitrodextrine, for the purpose of producing an explosive powder, to be used in place of gunpowder. He incorporates these materials with nitrocellulose, and dissolves the whole in acetone, which is afterwards distilled off. A perfect incorporation of the ingredients is thus brought about. Nitro-jute. It is obtained by treating jute with nitric acid. Its properties have been studied by Messrs. Cross and Bevan, Jur. Chem. SOC, 1889, 199, and by Mulhausen. The latter used for its nitration an acid mixture composed of equal parts of nitric and sulfuric acids, which was allowed to act upon the jute for some time. He found that with long exposure, i.e., from 3 to 4 hours in the acids, there was a disintegrating of the fiber bundles, and the nitration was attended by secondary decomposition and conversion into products soluble in the acid mixture. Cross and Bevan's work upon this subject leads them to conclude that the highest yield of nitrate is represented by an increase of weight of 51%. They give jute the empirical formula C_12, H_18, O_9, C equals 47%, H equals 6%, and O equals 47%, and believe its conversion into a nitro compound to take place thus. C_12, H_18, O plus 3 No_3 equals C_12, H_15, O_6, No_3 plus 3H2O. This is equivalent to a gain in weight of 44% for the trinitrate and of 58% for the tetranitrate. The formation of the tetranitrate appears to be the limit of nitration of jute fiber. In other words, if we represent the lignocellulose molecule by AC_12 formula, it will contain 4 hydroxyl O groups, or 2 less than cellulose similarly represented. The following are their nitration results. Acids used. I. No_3 SPGR 1.43 and H_2 So_4 equals 1.84 equal parts. 2. 1 volume No_3 1.5 1 volume H_2 So_4 1.84. 3. 1 volume No_3 1.5 75 volumes H_2 So_4 1.84. I equals 144.42 equals 153.33 equals 154.4 grms, 100 grms of fiber being used in all 3 cases. Duration of exposure 30 minutes at 18 degrees Celsius. The nitrogen was determined in the products and equaled 10.5%. Theory for C_12, H_15, O_6, No_3 equals 9.5%, and for C12, H_15, O_6, No_3 equals 11.5%. These nitrates resemble those of cellulose, and are in all essential points nitrates of lignocellulose. Mulhausen obtained a much lower yield, and probably, as pointed out by Cross and Bevan, a secondary decomposition took place, and his products, therefore, probably approximate to the derivatives of cellulose rather than to those of lignocellulose, the more oxidizable, non-cellulose, or lignone constituents having been decomposed. In fact, he regards his product as cellulose pentanitrate, C_12, H_16, O_5, Ono_2_5. The Chemiker-Zeitung, 21, page 163, contains a further paper by Mulhausen on the explosive nitro-jute. After purifying the jute fiber by boiling it with a 1% solution of sodium carbonate and washing with water, he treated 1 part of the purified jute with 15 parts of nitrosulfuric acid, and obtained the following results with different proportions of nitric to sulfuric acids. Yield ignition nitrogen. Percent point. Experiment I.1. No_3 H_2 so_ 4 129.5 170 degrees Celsius 11.96%. 2 132.2 167 degrees Celsius 12.15%. 3 135.8 169 degrees Celsius 11.91%. An experiment made with fine carded jute and the same mixture of acids as in No.2 gave 145.4% nitro jute, which ignited at 192 degrees Celsius and contained 12% nitrogen. This explosive is not at present manufactured upon the large scale, and Messrs. Cross and Bevan are of opinion that there is no very obvious advantage in the use of lignified textile fiber as raw materials for explosive nitrates, seeing that a large number of raw materials containing cellulose, chiefly as cotton, can be obtained at a cheaper rate, and yield also 150 to 170% of explosive material when nitrate, and are in many ways superior to the products obtained hitherto from jute. Nitromannite is formed by the action of nitric acid on mannite, a hex-acid alcohol closely related to sugar. It occurs abundantly in manna, which is the partly dried sap of the manna ash, Fraxinus ornis. It is formed in the lactic acid fermentation of sugar, and by the action of nascent hydrogen on glucose and cellulose, or on invert sugar. Its formula is C_6, H_8O6, and that of nitromannite C6, H_8, No_3_6. Mannite crystallizes in needles or rhombic prisms, which are soluble in water and alcohol, and have a sweet taste. Nitromannite forms white needle-shaped crystals, insoluble in water, but soluble in ether or alcohol. When rapidly heated, they ignite at about 374 degrees Fahrenheit, and explode at about 590 degrees Fahrenheit. It is more susceptible to friction and percussion than nitroglycerin, and unless pure it is liable to spontaneous decomposition. It is considered as the nitric ether of the hexatomic alcohol mannite. It is formed by the action of a mixture of nitric and sulfuric acids upon mannite. C_6, H_8O6 plus 6 No3 equals C_6, H_8, No_3 6 plus 6H2O. Its products of explosion are as shown in the following equation. C_6, H_8, O6 equals 6 Co2 plus 4H_2, O plus 3N_2, plus O_2. Its percentage composition is as follows: carbon, 15.9%, hydrogen, 1.8%, nitrogen, 18.6%, and oxygen, 63.7%. Its melting point is 112 to 113 degrees Celsius, and it solidifies at 93 degrees. When carefully prepared and purified by recrystallization from alcohol, and kept protected from sunlight, it can be kept for several years without alteration. Nitromannite is more dangerous than nitroglycerin, as it is more sensitive to shock. It is intermediate in its shattering properties between nitroglycerin and fulminate of mercury. It explodes by the shock of copper on iron or copper, and even of porcelain on porcelain, provided the latter shock be violent. Its heat of formation from its elements is plus 156.1 calories. It is not manufactured upon the commercial scale. Besides the nitro compounds already described, there are many others, but they are of little importance, and are none of them made upon the large scale. Among such substances are nitro-coal, which is made by the action of nitric acid on coal, nitro-coal, a product which results from the action of nitric acid on isinglass or gelatin, soaked in water. It is then treated with the usual acids. Another method is to place strong glue in cold water until it has absorbed the maximum amount of the latter. The mixture is solidified by the addition of nitric acid, nitrate in the usual way, and well washed. Abel's glyoxylene is only nitrate gun cotton impregnated with nitroglycerin. Nitrolignin is only nitrocellulose made from wood instead of cotton, and nitro straw is also only nitrocellulose. The explosive known as Kiel's explosive contains nitroglucose. Nitromolasses, which is a liquid product, has also been proposed, and nitrosaccharose, the product obtained by the nitration of sugar. It is a white, sandy, explosive substance, soluble in alcohol and ether. When made from cane sugar, it does not crystallize, but if made from milk sugar, it does. It has been used in percussion caps, being stronger and quicker than nitroglycerin. It is, however, very sensitive and very hygroscopic, and very prone to decomposition. Nitrotar, made from crude tar oil, by nitration with nitric acid of a specific gravity of 1.53 to 1.54. Nitrotoluol is used, mixed with nitroglycerin. This list, however, does not exhaust the various substances that have been nitrate and proposed as explosives. Even such unlikely substances as horse dung have been experimented with. None of them are very much used, and very few of them are made upon the manufacturing scale. Chapter 4. Dynamite and Gelatins. Kieselguhr dynamite, classification of dynamites, properties and efficiency of ordinary dynamite, other forms of dynamite, gelatin and gelatin dynamites, suitable guncotton for, and treatment of, other materials used, composition of gelignite, blasting gelatin, gelatin dynamite, absorbing materials, wood pulp, potassium nitrate, and C. Manufacture and apparatus used. And properties of gelatin dynamites, cordite, composition and manufacture. Dynamite. Dynamite consists of nitroglycerin either absorbed by some porous material, or mixed with some other substance or substances which are either explosives or merely inert materials. Among the porous substances used is kieselguhr, a siliceous earth which consists chiefly of the skeletons of various species of diatoms. This earth occurs in beds chiefly in Hanover, Sweden, and Scotland. The best quality for the purpose of manufacturing dynamite is that which contains the largest quantity of the long tubular bacillary, and less of the round and lancet-shaped forms, such as pleurosigmata and diclyoche, as the tube-shaped diatoms absorb the nitroglycerin better, and it becomes packed into the center of the siliceous skeleton of the diatoms, the skeleton acting as a kind of tamping, and increasing the intensity of the explosion. Dynamites are classified by the late Colonel Kundil, R.A., in his Dictionary of Explosives, as follows. 1. Dynamites with an inert base, acting merely as an absorbent. 2. Dynamites with an active base, i.e., an explosive base. Number 2 may be again divided into 3 minor classes, which contain as base A. Charcoal. B. Gunpowder or other nitrate, or chlorate mixture. C. Guncotton or other nitro compound, nitrobenzol, and C. The first of these, viz., charcoal, was one of the first absorbents for nitroglycerin ever used. The second is represented by the well-known Atlas powder, and the last includes the well-known and largely used gelatin compounds, viz., gelignite and gelatin dynamite, and also tonite number 3 and C. In the year 1867, Nobel produced dynamite by absorbing the nitroglycerin in an inert substance, forming a plastic mass. In his patent he says, "This invention relates to the use of nitroglycerin in an altered condition, which renders it far more practical and safe for use. The altered condition of the nitroglycerin is effected by causing it to be absorbed in porous unexplosive substances, such as charcoal, silica, paper, or similar materials, whereby it is converted into a powder, which I call dynamite, or Nobel's safety powder. By the absorption of the nitroglycerin in some porous substance it acquires the property of being in a high degree insensible to shocks, and it can also be burned over a fire without exploding. Ordinary dynamite consists of a mixture of 75% of nitroglycerin and 25% of kieselguhr. The gur is imported. Messrs. A. Hock and Company are the chief importers, contains from 20 to 30% of water and organic matter. The water may be very easily estimated by drying a weighed quantity in a platinum crucible at 100 degrees Celsius for some time and reweighing, and the organic matter by igniting the residue strongly over a Bunsen burner. Before the gur can be used for making dynamite, it must be calcined, in order not only to get rid of moisture, but also the organic matter. A good gur should absorb 4 times its weight of nitroglycerin, and should then form a comparatively dry mixture. It should be pale pink, red-brown, or white. The pink is generally preferred, and it should be as free as possible from grit of all kinds, quartz particles, and should have a smooth feeling when rubbed between the finger and thumb, and should show a large quantity of diatoms when viewed under the microscope. The following was the analysis of a dried sample of kieselguhr: silica 94.30, magnesia 2.10, oxide of iron and alumina 1.3, organic matter 0.40, moisture 1.9%. The gur is generally dried in a reverberatory muffle furnace. It is spread out on the bottom to the thickness of 3 or 4 inches, and should every now and then be turned over and raked about with an iron rabble or hoe. The temperature should be sufficiently high to make the gur red hot, or the organic matter will not be burned off. The time occupied in calcining will depend, of course, upon the quality of the gur being operated upon. Those containing a high percentage of water and organic matter will, of course, take longer than those that do not. A sample of the calcined gur should not contain more than 0.5% of moisture and organic matter together. After the gur is dry, it requires to be sifted and crushed. The crushing is done by passing it between iron rollers fixed at the bottom of a cone or hopper, and revolving at a moderate speed. Beneath the rollers a fine sieve should be placed, through which the gur must be made to pass. The kieselguhr, having been dried, crushed, and sifted, should be packed away in bags, and care should be taken that it does not again absorb moisture, as if it contains anything above about 0.5% of water it will cause the dynamite made with it to exude. The gur thus prepared is taken up to the danger area, and mixed with nitroglycerin. The nitroglycerin used should be quite free from water, and clear, and should have been standing for a day or 2 in the precipitating house. The gur and nitroglycerin are mixed in lead tanks, about 1.5 foot deep, and 2 to 3 feet long, in the proportions of 75 of the nitroglycerin to 25 of the gur, unless the gur is found to be too absorbent, which will cause the dynamite to be too dry and to crumble. In this case, a small quantity of barium sulfate, say about 1%, should be added to the gur. This will lessen its absorbing powers, or a highly absorptive sample of gur may be mixed with one of less absorptive power, in the proportions found by experiment to be the best suited to make a fairly moist dynamite, but one that will not exude. The mixing itself is generally performed in a separate house. In a series of lead-lined tanks the gur is weighed, placed in a tank, and the nitroglycerin poured onto it. The nitroglycerin may be weighed out in india-rubber buckets. The whole is then mixed by hand, and well rubbed between the hands, and afterwards passed through a sieve. At this stage the dynamite should be dry and powdery, and of a uniform color. It is now ready to be made up into cartridges, and should be taken over to the cartridge huts. These are small buildings surrounded with mounds, and contain a single cartridge machine. Each hut requires 3 girls, 1 to work the press, and 2 to wrap up the cartridges. The cartridge press consists of a short cylinder of the diameter of the cartridge that it is intended to make. Into this cylinder a piston, pointed with ivory or lignum vitae wood, works up and down from a spring worked by a lever. Round the upper edge of the cylinder is fastened a canvas bag, into which the powdery dynamite is placed by means of a wooden scoop, and the descending piston forces the dynamite down the cylinder and out of the open end, where the compressed dynamite can be broken off at convenient lengths. The whole machine should be made of gunmetal, and should be upright against the wall of the building. The 2 girls, who sit at tables placed on each side of the press, wrap the cartridges in parchment paper. From these huts the cartridges are collected by boys every 10 minutes or a quarter of an hour, and taken to the packing room, where they are packed in 5-pound cardboard boxes, which are then further packed in deal boxes lined with india-rubber, and fastened down airtight. The wooden lids are then nailed down with brass or zinc nails, and a label pasted on the outside giving the weight and description of the contents. The boxes should then be removed to the magazines. It is well to take a certain number of cartridges from the packing house at different times during the day, say 3 or 4 samples, and to test them by the heat test. A sample cut from a cartridge, about 1 inch long, should be placed under a glass shade, together with water, a large desiccator, in fact, and left for some days. A good dynamite should not, under these conditions, show any signs of exudation, even after weeks. A. Footnote A. For analysis of dynamite, see chapter on Analysis, an author's article in Chem. News, September 23, 1892. Properties of Kieselguhr dynamite. 1 cubic foot of dynamite weighs 76 pounds. 4 ounces the specific gravity of 75%. Dynamite is, however, 1.50. It is a red or gray color, and rather greasy to the touch. It is much less sensitive to shock than nitroglycerin, but explodes occasionally with the shock of a rifle bullet, or when struck. The addition of a few % of camphor will considerably diminish its explosive qualities to such an extent that it can be made non-explosive except to a very strong fulminate detonator. The direct contact of water disintegrates dynamite, separating the nitroglycerin, hence great caution is necessary in using it in wet places. It freezes at about 40 degrees Fahrenheit, 4 degrees Celsius, and remains frozen at temperatures considerably exceeding that point. When frozen, it is comparatively useless as an explosive agent, and must be thawed with care. This is best done by placing the cartridges in a warming pan, which consists of a tin can, with double sides and bottom, into which hot water, 130 degrees Fahrenheit, can be poured. The dynamite will require to be left in for some considerable time before it becomes soft. On no account must it be placed on a hot stove or near a fire, as many serious accidents have occurred in this way. Frozen dynamite is a hard mass, with altered properties, and requires 1.5 grm of fulminate instead of 0.5 grm to explode it. Thawing may also cause exudation of the nitroglycerin, which is much more sensitive to shock, and if accidentally struck with an iron tool, may explode. It is a dangerous thing to cut a frozen cartridge with a knife. Ramming is even more dangerous. In fact, it is not only dangerous, but wasteful, to use dynamite when in a frozen state. Dynamite explodes at a temperature of 360 degrees Fahrenheit, and is very sensitive to friction when hot. In hot countries it should never be exposed to the rays of the sun. It should, however, not be kept in a damp or moist place, as this is liable to cause exudation. Sunlight, if direct, can cause a slow decomposition, as with all nitro and nitric compounds. Electric sparks ignite, without exploding it, at least when operating in the open air. Dynamite, when made with neutral nitroglycerin, appears to keep indefinitely. Sodium or calcium carbonate to the extent of 1% is often added to dynamite to ensure its being neutral. If it has commenced to undergo change, however, it rapidly becomes acid, and sometimes explodes spontaneously, especially if contained in resisting envelopes. Nevertheless, neutral and well-made dynamite has been kept for years in a magazine without loss of its explosive force. If water is brought into contact with it, the nitroglycerin is gradually displaced from the silica, Gur. This action tends to render all wet dynamite dangerous. It has been observed that a dynamite made with wood sawdust can be moistened and then dried without marked alteration, and from 15 to 20% of water may be added to cellulose dynamite without depriving it of the power of exploding by strong detonator. This is similar to wet gun cotton. It is, however, rendered much less sensitive to shock. With regard to the power of No. 1 dynamite, experiments made in lead cylinders give the relative value of No. 1 dynamite, 1.0, blasting gelatin, 1.4, and nitroglycerin, 1.4. The heat liberated by the sudden explosion of dynamite is the same as its heat of combustion, A, and proportionate to the weight of nitroglycerin contained in the mixture. The gases formed are carbonic acid, water, nitrogen, and oxygen. Footnote A. Berthelot. Explosives and their power. The explosive wave of Berthelot for dynamite is about 5,000 liters per second. At this rate, the explosion of a cartridge a foot long would only occupy 1/24,000th part of a second, while a ton of dynamite cartridges about 7/8 diameter, laid end to end, and measuring 1 mile in length, would be exploded in 1/4 of a second by detonating a cartridge at either end. Mr. C. Napier Hake, FIC, the Inspector of Explosives for the Victorian Government, in his paper, Notes on Explosives, says, "The theoretical efficiency of an explosive cannot in practice be realized in useful work for several reasons, as for instance in blasting rock. 1. Incomplete combustion. 2. Compression and chemical changes induced in surrounding material. 3. Energy expended in cracking and heating of the material which is not displaced. 4. The escape of gas through the blast hole and the fissures caused by the explosion. The useful work consists partly in displacing the shattered masses. The proportion of useful work obtainable has been variously estimated at from 14 to 33% of the theoretical maximum potential." Footnote A. C. N. Hake, Notes on Explosives. Jure Soc Chem. IND, 1889. Among the various forms of dynamite that are manufactured is carbo-dynamite, the invention of Messrs. Walter F. Reed and W. D. Borland. The base is nitroglycerin, and the absorbent is carbon in the form of burnt cork. It is as cheap as ordinary dynamite, and has greater explosive force, seeing that 90% of the mixture is pure nitroglycerin, and the absorbent itself is highly combustible. It is also claimed that if this dynamite becomes wet, no exudation takes place. Atlas powder is a dynamite chiefly manufactured in America at the Repano Chemical Works, Philadelphia. It is a composition of nitroglycerin, wood pulp, nitrate of soda, and carbonate of magnesia. This was the explosive used in the outrages committed in London by the so-called dynamiters. Different varieties contain from 20 to 75% of nitroglycerin. The Rhenish dynamite, considerably used in the mines of Cornwall, is composed of 70 parts of a solution of 2 to 3% of naphthalene in nitroglycerin, 3 parts of chalk, 7 parts of sulfate of barium, and 20 of kieselguhr. Kieselguhr dynamites are being largely given up in favor of gelatin explosives. The late Colonel Kundell, in his Dictionary of Explosives, gives a list of about 125 kinds of dynamites. Many of these, however, are not manufactured. Among the best known after the ordinary number 1 dynamite are forsyte, ammonia dynamite, lithofractor, rindoc, atlas powder, giant powder, and the various explosive gelatins. They all contain nitroglycerin, mixed with a variety of other substances, such as absorbent earths, wood pulp, nitrocotton, carbon in some form or other, nitrobenzol, paraffin, sulfur, nitrates, or chlorates, NC. Blasting gelatin and gelatin dynamite. The gelatin explosives chiefly in use are known under the names of blasting gelatin, gelatin dynamite, and gelignite. They all consist of the variety of nitrocellulose known as collodion cotton, i.e., a mixture of the penta and tetranitrates dissolved in nitroglycerin, and made up with various proportions of wood pulp, and some nitrate, or other material of a similar nature. As the gun cotton contains too little oxygen for complete combustion, and the nitroglycerin in excess, a mixture of the two substances is very beneficial. Blasting gelatin consists of collodion cotton and nitroglycerin without any other substance, and was patented by Mr. Alfred Nobel in 1875. It is a clear, semi-transparent, jelly-like substance, of a specific gravity of 1.5 to 1.55, slightly elastic, resembling indie-rubber, and generally consists of 92% to 93% of nitroglycerin and 7 to 8% of nitrocotton. The cotton from which it is made should be of good quality. The following is the analysis of a sample of nitrocellulose which made very good gelatin. Soluble cotton 99.118%, gun cotton 0.642, non-nitrate cotton 0.240, nitrogen 11.64, total ash 0.25. The soluble cotton, which is a mixture of the tetra and pentanitrates, is soluble in ether alcohol, and also in nitroglycerin, and many other solvents, whereas the hexanitrate, gun cotton, C_12, H_14, O_4, Ono_2, 6, is not soluble in the above liquids, although it is soluble in acetone or acetic ether. It is very essential, therefore, that the nitro cotton used in the manufacture of the gelatin explosives should be as free as possible from gun cotton, otherwise little lumps of undissolved nitro cotton will be left in the finished gelatin. The non-nitrate or unconverted cotton should also be very low, in fact considerably under 0.5%. The nitro cotton and the nitroglycerin used should always be tested before use by the heat test, because if they do not separately stand this test, it cannot be expected that the gelatin made from them will do so. It often occurs, however, that although both the ingredients stand this test separately before being mixed, that after the process of manufacture one or other or both fail to do so. The nitro cotton most suitable for gelatin making is that which has been finely pulped. If it is not already fine enough, it must be passed through a fine brass wire sieve. It will be found that it requires to be rubbed through by hand, and will not go through at all if in the least degree damp. It is better, therefore, to dry it first. The percentage of nitrogen in the nitrate cotton should be over 11%. It should be as free as possible from sand or grit, and should give but little ash upon ignition, not more than 0.25%. The cotton, which is generally packed wet in zinc-lined wooden boxes, will require to be dried, as it is very essential indeed that none of the materials used in the manufacture of gelatin should contain more than the slightest trace of water. If they do, the gelatin subsequently made from them will most certainly exude, and become dangerous and comparatively valueless. It will also be much more difficult to make the nitro cotton dissolve in the nitroglycerin if either contains water. In order to find out how long any sample of cotton requires to be dried, a sample should be taken from the center of several boxes, well mixed, and about 1000 grams. Spread out on a paper tray, weighed, and the whole then placed in the water oven at 100 degrees Celsius, and dried for an hour or so, and again weighed, and the percentage of moisture calculated from the loss in weight. This will be a guide to the time that the cotton will probably require to be in the drying house. Samples generally contain from 20 to 30% of water. After drying for a period of 48 hours, a sample should be again dried in the oven at 100 degrees Celsius, and the moisture determined, and so on at intervals until the bulk of the cotton is found to be dry, i.e., to contain from 0.25 to 0.5% of moisture. It is then ready to be sifted. During the process of removing to the sifting house and the sifting itself, the cotton should be exposed to the air as little as possible, as dry nitro cotton absorbs as much as 2% of moisture from the air at ordinary temperatures and average dryness. The drying house usually consists of a wooden building, the inside of which is fitted with shelves, or rather framework to contain drawers, made of wood, with brass or copper wire netting bottoms. A current of hot air is made to pass through the shelves and over the surface of the cotton, which is spread out upon them to the depth of about 2 inches. This current of air can be obtained in any way that may be found convenient, such as by means of a fan or roots blower, the air being passed over hot bricks, or hot water pipes before entering the building. The cotton should also be occasionally turned over by hand in order that a fresh surface may be continually exposed to the action of the hot air. The building itself may be heated by means of hot water pipes, but on no account should any of the pipes be exposed. They should all be most carefully covered over with woodwork, because when the dry nitro cotton is moved, as in turning it over, very fine particles get into the air, and gradually settling on the pipes, window ledges, and may become very hot, when the slightest friction might cause explosion. It is on this account that this house should be very carefully swept out every day. It is also very desirable that the floor of this house should be covered with oilcloth or linoleum, as being soft, it lessens the friction. List shoes should always be worn in this building, and a thermometer hung up somewhere about the center of the house, and one should also be kept in one of the trays to give the temperature of the cotton, especially the bottom of the trays. The one nearest to the hot air inlet should be selected. If the temperature of the house is kept at about 40 degrees Celsius, it will be quite high enough. The building must of course be properly ventilated, and it will be found very useful to have the walls made double, and the intervening space filled with cinders, and the roof covered with felt, as this helps to prevent the loss of heat through radiation, and to preserve a uniform temperature, which is very desirable. The dry cotton thus obtained, if not already fine enough, should be sifted through a brass sieve and packed away ready for use in zinc airtight cases or in India rubber bags. The various gelatin compounds, gel-ignite, gelatin dynamite, and blasting gelatin, are manufactured in exactly the same way. The forms known as gelatin dynamite differ from blasting gelatin in containing certain proportions of wood pulp and potassium nitrate, and c. The following are analyses of some typical samples of the three compounds. Gelatin blasting gel-ignite. Dynamite. Gelatin. Nitroglycerin 60.514 71.128 92.94%. Nitrocellulose 4.8887 7.6327.06. Wood pulp 7.1784 4.259. Potassium nitrate 27.420 16.720. Water 0.261. The gel-ignite and gelatin dynamites consist, therefore, of blasting gelatin, thickened up with a mixture of absorbing materials. Although the blasting gelatin is weight for weight more powerful, it is more difficult to make than either of the other two compounds, it being somewhat difficult to make it stand the exudation and melting tests. The higher percentage of nitro cotton, too, makes it expensive. When the dry nitro cotton, which has been carefully weighed out in the proportions necessary either for blasting gelatin or any of the other gelatin explosives, is brought to the gelatin making house, it is placed in a lead-lined trough, and the necessary quantity of pure dry nitroglycerin poured upon it. The whole is then well stirred up, and kept at a temperature of from 40 degrees to 45 degrees Celsius. It should not be allowed to go much above 40 degrees Celsius, but higher temperatures may be used if the nitro cotton is very obstinate, and will not dissolve. Great caution must, however, be observed in this case. The mixture should be constantly worked about by the workman with a wooden paddle for at least half an hour. At a temperature of 40 degrees to 45 degrees the nitroglycerin acts upon the nitro cotton and forms a jelly. Without heat the gelatinization is very imperfect indeed, and at temperatures under 40 degrees Celsius, takes place very slowly. Footnote A. Generally due to the nitro cotton being damp. Illustration, Figure 30. Werner, Fleiderer, and Perkins mixing machine. The limit of temperature is 50 degrees Celsius, or thereabouts. Beyond this the jelly should never be allowed to go, and to 50 degrees only under exceptional circumstances. The tank in which the jelly is made is double-lined, in order to allow of the passage of hot water between its inner and outer linings. A series of such tanks are generally built in a wooden framework, and the double linings are made to communicate, so that the hot water can flow from one to the other consecutively. The temperature of the water should be about 60 degrees Celsius, if it is intended to gelatinize at 45 degrees Celsius, and about 80 degrees if at 50 degrees Celsius. But this point must, of course, be found by experiment for the particular plant used. An arrangement should be made to enable the workman to at once cut off the supply of hot water and pass cold water through the tanks in case the explosive becomes too hot. Illustration, Figure 31. Mr. M. Roberts mixer for gelatin explosives. The best way to keep the temperature of the water constant is to have a large tank of water raised upon a platform, some 5 or 6 feet high, outside the building, which is automatically supplied with water, and into which steam is turned. A thermometer stuck through a piece of cork and floated upon the surface of the tank will give the means of regulating the temperature. When the jelly in the tanks has become semi-transparent and the cotton has entirely dissolved, the mixture should be transferred to the mixing machine. The mixing machines are specially designed for this work, and are built in iron, with steel or bronze kneading and mixing blades, according to requirements. A suitable machine for the purpose is that known as the Nitro-Universal Incorporator, shown in Figure 30, which has been specially constructed by Messrs. Werner, Fleiderer, and Perkins, Limited, after many years' experience in the mixing of explosive materials, and is now almost exclusively adopted in both government and private factories. Mr. George M. Roberts, a mixing machine, however, which is shown in Figure 31, is still used in some factories for dynamite jelly. Footnote A. See Jour SOC Chem. IND 1890, 267. If it is intended to make gelignite, or gelatin dynamite, it is at this point that the proper proportions of wood pulp, A, and potassium nitrate should be added, and the whole well mixed for at least half an hour, until the various ingredients are thoroughly incorporated. Footnote A. Most of the wood pulp used in England is obtained from pine trees, but poplar, lime, birch, and beech wood are also used. It is chiefly imported as wood pulp. The pulp is prepared as follows. The bark and roots are first removed, and the logs then sawn into boards, from which the knots are removed. The pieces of wood are afterwards put through a machine which breaks them up into small pieces about an inch long, which are then crushed between rollers. These fragments are finally boiled with a solution of sodium bisulfite, under a pressure of about 90 pounds per square inch, the duration of the boiling being from 10 to 12 hours. Sulfurous acid has also been used. Pinewood yields about 45%, and birch about 40%, of pulp when treated by this process. The pulp is afterwards bleached and washed, and c. birch, beech, lime, pine, poplar, cellulose 55.52, 45.47, 53.09, 56.99, 62.77%. Resin 1.14, 0.41, 3.93, 0.97, 1.37. Aqueous extract 2.65, 2.47, 3.56, 1.26, 2.88. Water 12.48, 12.57, 10.10, 13.87, 12.10. Lignin 28.21, 39.14, 29.32, 26.91, 20.88. The following analysis of woods is by Dr. H. Muller. These mixing machines can either be turned by hand, or a shaft can be brought into the house and the machine worked by means of a belt at 20 to 30 revolutions per minute. The bearings should be kept constantly greased and examined, and the explosive mixture carefully excluded. When the gelatin mixture has been thoroughly incorporated, and neither particles of nitrate or wood meal can be detected in the mass, it should be transferred to wooden boxes and carried away to the cartridge-making machines to be worked up into cartridges. Illustration: Figure 32. Plan of the box containing the explosive, in M. Roberts' machine. The application of heat in the manufacture of the jelly from collodion cotton and nitroglycerin is absolutely necessary, unless some other solvent is used besides the nitroglycerin, such as acetone, acetic ether, methyl, or ethyl alcohol. They are all too expensive, with the exception of acetone and methyl alcohol, for use upon the large scale. These liquids not only dissolve the nitrocellulose in the cold, but render the resulting gelatin compound less sensitive to concussion, and reduce its quickness of explosion, as in cordite. They also lower the temperature at which the nitroglycerin becomes congealed, i.e., they lower the freezing point, A, of the resulting gelatin. Footnote A. It has been proposed to mix dynamite with amyl alcohol for this purpose. Dinitromonochlorhydrin has also been proposed. The finished gelatin paste, upon entering the cartridge huts, is at once transferred to the cartridge-making machine, which is very like an ordinary sausage-making machine, A. Figure 33. The whole thing must be made of gunmetal or brass, and it consists of a conical case containing a shaft and screw. The revolutions of the shaft cause the thread of the screw to push forward the gelatin introduced by the hopper on the top to the nozzle, the apex of the cone-shaped case, from whence the gelatin issues as a continuous rope. The nozzle is of course of a diameter according to the size of cartridge required. Footnote A. G. M. Roberts, Jur. Soc. Chem. IND, March 31, 1890, page 266. Illustration: Figure 33. Cartridge-making machine for gelatin explosives. The issuing gelatin can of course be cut off at any length. This is best done with a piece of hardwood planed down to a cutting edge, i.e., wedge-shaped. Mr. Trench has devised a kind of brass frame, into which the gelatin issuing from the nozzle of the cartridge machine is forced, finding its way along a series of grooves. When the frame is full, a wooden frame, which is hinged to one end of the bottom frame, and fitted with a series of brass knives, is shut down, thereby cutting the gelatin up into lengths of about 4 inches. It is essential that the cartridge machines should have no metallic contacts inside. The bearing for the screw shaft must be fixed outside the cone containing the gelatin. One of these machines can convert from 5 to 10 cwt of gelatin into cartridges per dm, depending upon the diameter of the cartridges made. After being cut up into lengths of about 3 inches, the gelatin is rolled up in cartridge paper. Waterproof paper is generally used. The cartridges are then packed away in cardboard boxes, which are again packed in deal boxes lined with India rubber, and screwed down airtight, brass screws or zinc or brass nails being used for the purpose. These boxes are sent to the magazines. Before the boxes are fastened down, a cartridge or so should be removed and tested by the heat test, the liquefaction test, and the test for liability to exudation. Appendix, page 6, Explosives Act, 1875. A cartridge also should be stored in the magazine in case of any subsequent dispute after the bulk of the material has left the factory. The object of the liquefaction test is to ensure that the gelatin shall be able to withstand a fairly high temperature, such as it might encounter in a ship's hold, without melting or running together. The test is carried out as follows. A cylinder of the gelatin dynamite is cut from the cartridge of a length equal to its diameter. The edges must be sharp. This cylinder is to be placed on end on a flat surface, such as paper, and secured by a pin through the center, and exposed for 144 consecutive hours to a temperature of 85 degrees to 90 degrees Fahrenheit, and during such time the cylinder should not diminish in height by more than 1/4 of an inch, and the cut edges should remain sharp. There should also be no stain of nitroglycerin upon the paper. The exudation test consists in freezing and thawing the gelatin 3 times in succession. Under these conditions there should be no exudation of nitroglycerin. All the materials used in the manufacture of gelatin explosives should be subjected to analytical examination before use, as success largely depends upon the purity of the raw materials. The wood pulp, for instance, must be examined for acidity. Properties of the gelatin compounds. Blasting gelatin is generally composed of 93 to 95 parts nitroglycerin and 5 to 7 parts of nitrocellulose, but the relative proportions of explosive base and nitroglycerin, NC, in the various forms of the gelatin explosives do not always correspond to those necessary for total combustion, either because an incomplete combustion gives rise to a greater volume of gas, or because the rapidity of decomposition and the law of expansion varies, according to the relative proportions and the conditions of application. The various additions to blasting gelatin generally have the effect of lowering the strength by reducing the amount of nitroglycerin, but this is sometimes done in order to change a shattering agent into a propulsive force. If this process be carried too far, we of course lose the advantages due to the presence of nitroglycerin. There is therefore a limit to these additions. A. Footnote A. Mica is said to increase the rapidity of explosion when mixed with gelatin. The homogeneousness and stability of the mixture are of the highest importance. It is highly essential that the nitroglycerin should be completely absorbed by the substances with which it is mixed, and that it should not subsequently exude when subjected to heat or damp. It is also important that there should be no excess of nitroglycerin, as this may diminish instead of augment the strength, owing to a difference in the mode of the propagation of the explosive wave in the liquid and in the mixture. Nitroglycerin at its freezing point has a tendency to separate from its absorbing material, in fact to exude. When frozen, too, it requires a more powerful detonation to explode it, but it is less sensitive to shock. The specific gravity of blasting gelatin is 1.5, i.e., nearly equal to that of nitroglycerol. That of guncotton, dry, is 1.0. Blasting gelatin burns in the air when unconfined without explosion, at least in small quantities and when not previously heated, but it is rather uncertain in this respect. It can be kept at a moderately high temperature, 70 degrees Celsius, without decomposition. At higher temperatures the nitroglycerin will partially evaporate. When slowly heated, it explodes at 204 degrees Celsius. If, however, it contains as much as 10% of camphor, it burns without exploding. According to Berthelot, A. gelatin composed of 91.6%, nitroglycerin and 8.4% of nitrocellulose, which are the proportions corresponding to total combustion, produces by explosion 177 Co_2 plus 143H_2 O plus 8N_2. Footnote A. Berthelot. Explosives and their powers. He takes C_24 H_22 No_3 H9 O11 as the formula of the nitrocellulose, and 51 C_3 H_2 No_3 H3 plus C 24 H_22 No_3 H9 O11 as the formula of the gelatin itself, its equivalent weight being 12,360 grams. The heat liberated by its explosion is equal to 19,381 calories, or for 1 kilo, 1,535 calories. Volume of gases reduced temperature equals 8,950 liters. The relative value, A, of blasting gelatin to nitroglycerin is as 1.4 to 1.45, Kieselguhr dynamite being taken as 1.0. Footnote A. Roux and Saran. Chapter 5. Nitrobenzol, robierite, bellite, picric acid, and C. Explosives derived from benzene, toluene and nitrobenzene, D and trinitrobenzene, robierite, properties and manufacture, bellite, properties, and C. Securite, tonight number 3. Nitrotoluene, nitronaphthalene, ammonite, Sprengel's explosives, picric acid, picrates, picric powders, melanite, Abel's mixture, Brewer's powders, the fulminates, composition, formula, preparation, danger of, and C. Detonators, sizes, composition, manufacture, fuses, and C. The explosives derived from benzene. There is a large class of explosives made from the nitrate hydrocarbons, benzene, C_6, H_6, toluene, C_7, H_8, naphthalene, C_10, H_8, and also from phenol, or carbolic acid, C_6, H_5O. The benzene hydrocarbons are generally colorless liquids, insoluble in water, but soluble in alcohol and ether. They generally distill without decomposition. They burn with a smoky flame, and have an ethereal odor. They are easily nitrate and sulfurated. Mono, D, and tri-derivatives are readily prepared, according to the strength of the acids used. It is only the H atoms of the benzene nucleus which enter into reaction. Benzene was discovered by Faraday in 1825, and detected in coal tar by Hoffman in 1845. It can be obtained from that portion of coal tar which boils at 80 degrees to 85 degrees by fractionating or freezing. A. The ordinary benzene of commerce contains thiophene, C_4, H_4S, from which it may be freed by shaking with sulfuric acid. Its boiling point is 79 degrees Celsius. Specific gravity at 0 degrees equals 0.9. It burns with a luminous smoky flame, and is a good solvent for fats, resins, sulfur, phosphorus, and C. Toluene was discovered in 1837, and is prepared from coal tar. It boils at 110 degrees Celsius, and is still liquid at 28 degrees Celsius. Footnote A. It may be prepared chemically pure by distilling a mixture of benzoic acid and lime. The mono-, chloro-, bromo-, and iodobenzenes are colorless liquids of peculiar odor. Dichloro-, dibromobenzenes, tri- and hexachloro and bromobenzenes are also known, and monochloro-, C_6, H_4, Cl, CH_3, and bromotoluenes, together with D derivatives in the ortho, meta, and para modifications. The nitrobenzenes and toluenes are used as explosives. The following summary is taken from D.R.A. Bernstein's Organic Chemistry. Summary. underscore 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 C underscore 6 H underscore 5 N0 underscore 2 nitrobenzene liquid B.pt 206 degrees Celsius. C underscore 6 H underscore 4 no underscore 2 2 ortho dash meta dash and para dinitrobenzenes. Solid. MP 118 degrees 90 degrees and 172 degrees Celsius. C 6 H underscore 3 no underscore 3 underscore 3s trinitrobenzene. Solid. MP 121 degrees Celsius. Underscore 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 C underscore 6 H underscore 4 CH underscore 3 no underscore 2 ortho dash meta dash and para nitrotoluenes. BP 218 degrees, 230 degrees, and 234 degrees Celsius, para compound solid. Underscore 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 C underscore 6 H underscore 3 CH underscore 3 2 no 2 nitroxylene liquid underscore 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 C underscore 6 H underscore 2 CH underscore 3 3 no 2 nitromethylene solid underscore 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 C underscore 6 H underscore 3 CH underscore 3 no underscore 2 underscore 2 dinitrotoluenes. Underscore 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 C underscore 6 H underscore 4 Cl no underscore 2 nitrochlorobenzenes C underscore 6 Br underscore 4 no underscore 2 underscore 2 tetrabromodinitrobenzene underscore 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 underscore. The nitro compounds are mostly pale yellow liquids, which distill unchanged, and volatilize with water vapor, or colorless or pale yellow needles or prisms. Some of them, however, are of an intense yellow color. Many of them explode upon being heated. They are heavier than water, and insoluble in it, but mostly soluble in alcohol, ether, and glacial acetic acid. Nitrobenzene, C_6, H_5, No_2, was discovered in 1834 by Mitscherlich. It is a yellow liquid, with a melting point of +3 degrees Celsius. It has an intense odor of bitter almonds. It solidifies in the cold. In dinitrobenzene, the two nitro groups may be in the meta, ortho, or para position, the meta position being the most general, see figure, page 4. By recrystallizing from alcohol, pure metadinitrobenzene may be obtained in long colorless needles. The ortho compound crystallizes in tables, and the para in needles. They are both colorless. When toluene is nitrate, the para and ortho are chiefly formed, and a very little of the meta compound. Nitro compounds of benzene and toluene. The preparation of the nitro derivatives of the hydrocarbons of the benzene series is very simple. It is only necessary to bring the hydrocarbon into contact with strong nitric acid, when the reaction takes place, and one or more of the hydrogen atoms of the hydrocarbon are replaced by the nitro group, No_2. Thus, by the action of nitric acid on benzene, or benzol, mononitrobenzene is formed. C_6, H_6, plus No_3 equals C_6, H_5, No_2, plus H_2O, mononitrobenzene. By the action of another molecule of nitric acid, the dinitrobenzene is formed. C_6, H_5, No_2, plus No_3 equals C_6, H_4, No_2, 2, plus H2O, dinitrobenzene. These nitro bodies are not acids, nor are they ethereal salts of nitrous acid, as nitroglycerin is of glycerin. They are regarded as formed from nitric acid by the replacement of hydroxyl by benzene radicals. Mononitrobenzene is made by treating benzene with concentrated nitric acid, or a mixture of nitric and sulfuric acids. The latter, as in the case of the nitration of glycerin, takes no part in the reaction, but only prevents the dilution of the nitric acid by the water formed in the reaction. Small quantities may be made thus. Take 150 cc of H_2, SO_4, and 75 cc No_3, or 1 part nitric to 2 parts sulfuric acid, and put in a beaker standing in cold water. then add 15 to 20 cc of benzene, drop by drop, waiting between each addition for the completion of the reaction, and shake well during the operation. When finished, pour contents of beaker into about a liter of cold water. The nitrobenzol will sink to the bottom. Decant the water, and wash the nitrobenzol 2 or 3 times in a separating funnel with water. Finally, dry the product by adding a little granulated calcium chloride, and allowing to stand for some little time. It may then be distilled. Nitrobenzene is a heavy oily liquid which boils at 205 degrees Celsius, has a specific gravity of 1.2, and an odor like that of oil of bitter almonds. In the arts it is chiefly used in the preparation of aniline. Dinitrobenzene is a product of the further action of nitric acid on benzene or nitrobenzene. It crystallizes in long fine needles or thin rhombic plates, and melts at 89.9 degrees Celsius. It can be made thus. The acid mixture used consists of equal parts of nitric and sulfuric acids, say 50 cc of each, and without cooling add very slowly 10 cc of benzene from a pipette. After the action is over, boil the mixture for a short time, then pour into about half a liter of water, filter off the crystals thus produced, press between layers of filter paper, and crystallize from alcohol. Dinitrobenzene, or metadinitrobenzene, as it is sometimes called, enters into the composition of several explosives, such as tonnite No. 3, roburite, securite, bellite. Nitrobenzene is manufactured upon the large scale as follows. Along a bench a row of glass flasks, containing 1 gallon each, 1 to 2 pounds, benzene, are placed, and the acids added in small portions at a time, the workman commencing with the first, and adding a small quantity to each in turn, until the nitration was complete. This process was a dangerous one, and is now obsolete. The first nitrobenzene made commercially in England, by Messrs. Simpson, Mall, and Nicholson, of Kennington, in 1856, was by this process. Now, however, vertical iron cylinders, made of cast iron, are used for the nitrating operation. They are about 4 feet in diameter and 4 feet deep, and a series are generally arranged in a row, at a convenient height from the ground, beneath a line of shafting. Each cylinder is covered with a cast iron lid having a raised rim all round. A central orifice gives passage to a vertical shaft, and 2 or more other conveniently arranged openings allow the benzene and the mixed acids to flow in. Each of these openings is surrounded with a deep rim, so that the whole top of the cylinder can be flooded with water some inches in depth, without any of it running into the interior of the nitrator. The lid overhangs the cylinder somewhat, and in the outer rim a number of shot holes or tubes allow the water to flow down all over the outside of the cylinder into a shallow cast iron dish, in which it stands. By means of a good supply of cold water, the top, sides, and bottom of the whole apparatus is thus cooled and continually flooded. The agitator consists of cast iron arms keyed to a vertical shaft, with fixed arms or dash plates secured to the sides of the cylinder. The shaft has a miter wheel keyed on the top, which works into a corresponding wheel on the horizontal shafting running along the top of the converters. This latter is secured to a clutch, and there is a feather on the shaft, so that any one of the converters can if necessary be put either in or out of gear. This arrangement is necessary, as riggers or belts of leather, cotton, or India rubber will not stand the atmosphere of the nitrobenzol house. Above and close to each nitrator stands its acid store tank, of iron or stoneware. The building in which the nitration is carried out should consist of 1 story, have a light roof, walls of hard brick, and a concrete floor of 9 to 12 inches thick, and covered with pitch, to protect its surface from the action of the acids. The floor should be inclined to a drain, to save any nitrobenzol spilt. Fire hydrants should be placed at convenient places, and it should be possible to at once fill the building with steam. A 2-inch pipe, with a cock outside the building, is advisable. The building should also be as far as possible isolated. The acids are mixed beforehand, and allowed to cool before use. The nitric acid used has a specific gravity of 1.388, and should be as free as possible from the lower oxides of nitrogen. The sulfuric acid has a specific gravity of 1.845, and contains from 95 to 96% of monohydrate. A good mixture is 100 parts of nitric to 140 parts of sulfuric acid, and 78 parts of benzene, or 128 parts No_3, 179 of H_2, SO_4, and 100 of benzene, C_6, H_6. The benzene having been introduced into the cylinder, the water is turned on and the apparatus cooled, the agitators are set running, and the acid cock turned on so as to allow it to flow in a very thin stream into the nitrator. Should it be necessary to check the machinery even for a moment, the stream of acid must be stopped and the agitation continued for some time, as the action proceeds with such vigor that if the benzene being nitrate comes to rest and acid continues to flow, local heating occurs, and the mixture may inflame. Accidents from this cause have been not infrequent. The operation requires between 8 to 10 hours, agitation and cooling being kept up all the time. When all the acid is added, the water is shut off, and the temperature allowed to rise a little, to about 100 degrees Celsius. When it ceases to rise, the agitators are thrown out of gear, and the mixture allowed some hours to cool and settle. The acid is then drawn off, and the nitrobenzene is well washed with water, and sometimes distilled with wet steam, to recover a little unconverted benzene and a trace of paraffin, about 0.5%, together. At many English works, 100 to 200 gallons, or 800 to 1,760 pounds, are nitrate at a time, and toluene is often used instead of benzene, especially if the nitrobenzene is for use as essence of merbane. The waste acids, specific gravity 1.6 to 1.7, contain a little nitrobenzene in solution and some oxalic acid. They are concentrated in cast iron pots and used over again. Dinitrobenzene is obtained by treating a charge of the hydrocarbon benzene with double the quantity of mixed acids in 2 operations, or rather in 2 stages, the second lot of acid being run in directly after the first. The cooling water is then shut off, and the temperature allowed to rise rapidly, or nitrobenzene already manufactured is taken and again nitrate with acids. A large quantity of acid fumes come off, and some of the nitro and dinitrobenzol produced comes off at the high temperature which is attained, and a good condensing apparatus of stoneware must be used to prevent loss. The product is separated from the acids, washed with cold water and then with hot. It is slightly soluble in water, so that the washing waters must be kept and used over again. Finally, it is allowed to settle, and run while still warm into iron trays, in which it solidifies in masses 2 or 4 inches thick. It should not contain any nitrobenzol, nor soil a piece of paper when laid on it, should be well crystallized, fairly hard, and almost odorless. The chief product is metadinitrobenzene, melting point 89.8, but orthodinitrobenzene, melting point 118 degrees, and paradinitro, melting point 172 degrees are also produced. The melting point of the commercial product is between 85 degrees to 87 degrees Celsius. Dinitrotoluene is made in a similar manner. The trinitrobenzene can only be made by using a very large excess of the mixed acids. Nitrobenzene, when reduced with iron, zinc, or tin, and hydrochloric acids, forms aniline. Roburite. This explosive is the invention of a German chemist, Dr. Karl Roth, English patent 267A, 1887, and is now manufactured in England, at Gathurst, near Wigan. It consists of 2 component parts, non-explosive in themselves, Sprengel's principle, but which, when mixed, form a powerful explosive. The 2 substances are ammonium nitrate and chlorinated dinitrobenzol. Nitronaphthalene is also used. Nitrate of soda and sulfate of ammonium are allowed to be mixed with it. The advantages claimed for the introduction of chlorine into the nitro compound are that chlorine exerts a loosening effect upon the No_2 groups, and enables the compound to burn more rapidly than when the nitro groups alone are present. The formula of chlorodinitrobenzol is C_6, H_3Cl, No_2. The theoretical percentage of nitrogen, therefore, is 13.82, and of chlorine 17.53. Dr. Roth states that, from experiments he has made, the dynamic effect is considerably increased by the introduction of chlorine into the nitro compound. Roburite burns quickly, and is not sensitive to shock. It must be used dry. It cannot be made to explode by concussion, pressure, friction, fire, or lightning. It does not freeze. It does not give off deleterious fumes, and it is to all intents and purposes flameless, and when properly tamped and fired by electricity, can be safely used in fiery mines, neither fine dust nor gases being ignited by it. The action is rending and not pulverizing. Compared to gunpowder, it is more powerful in a ratio ranging from 2.5 to 4 to 1, according to the substance acted upon. It is largely used in blasting, pit sinking, quarrying, and sea, but especially in coal mining. According to Dr. Roth, the following is the equation of its decomposition. C_6 H_3 Cl NO_2 plus 9 HN 4 NO_3 equals 6 CO_2 plus 20 N plus HCl. In appearance, roburite is a brownish yellow powder, with the characteristic smell of nitrobenzol. Its specific gravity is 1.40. The company's statement that the fumes of roburite were harmless having been questioned by the miners of the Garswood Coal and Iron Works colliery, a scientific committee was appointed by the management and the men jointly for the purpose of settling the question. The members of this committee were Dr. Hanna, Dr. D.J. Mounsey, and Professor H.B. Dixon, FRS, of Owens College. After a protracted investigation, a long and technical report was issued, completely vindicating the innocuousness of roburite when properly used. In the words of the Iron and Coal Trades Review, May 24, 1889, the verdict, though not on every point in favor of the use in all circumstances of roburite in coal mines, is yet of so pronounced a character in its favor as an explosive that it is impossible to resist the conclusion that the claims put forward on its behalf rest on solid grounds. Roburite was also one of the explosives investigated by the committee appointed in September 1889 by the Durham Coal Owners and Miners Associations, for the purpose of determining whether the fumes produced by certain explosives are injurious to health. Both owners and workmen were represented on the committee, which elected Mr. T. Bell, H.M. Inspector of Mines, as its chairman, with Professor P.P. Bedson and D.R.S. Drummond and Hume as professional advisors. The problem considered was whether the fumes produced by the combustion of certain explosives, one of which was roburite, were injurious to health. The trial comprised the chemical analysis of the air at the intake, and of the vitiated air during the firing of the shots at the return, and also of the smoky air in the vicinity of the shot holes. 5.5 pounds of roburite were used in 23 shots. It had been asserted that the fumes from this explosive contained carbon monoxide (CO), but no trace of this gas could be discovered after the explosion. On another occasion, however, when 4.7 pounds of roburite were exploded in 23 shots, the air at the return showed traces of CO gas to the extent of 0.042 to 0.019%. The medical report which Dr.S. Hume and Drummond presented to the committee shows that they investigated every case of suspected illness produced by exposure to fumes, and they could find no evidence of acute illness being caused. They say, "No case of acute illness has, throughout the inquiry, been brought to our knowledge, and we are led to the conclusion that such cases have not occurred." Manufacture. As now made, roburite is a mixture of ammonium nitrate and chlorinated D-nitrobenzol. The nitrate of ammonia is first dried and ground, and then heated in a closed steam-jacketed vessel to a temperature of 80 degrees Celsius, and the melted organic compound is added, and the whole stirred until an intimate mixture is obtained. On cooling, the yellow powder is ready for use, and is stored in straight canisters or made up into cartridges. Owing to the deliquescent nature of the nitrate of ammonia, the finished explosive must be kept out of contact with the air, and for this reason the cartridges are waterproofed by dipping them in melted wax. Roburite is made in Germany, at Witten, Westphalia, and also at the English company's extensive works at Gathurst, near Wigan, which have been at work now for some 18 years, having started in 1888. These works are of considerable extent, covering 30 acres of ground, and are equal to an output of 10 tons a day. A canal runs through the center, separating the chemical from the explosive portions of the works, and the Lancashire and Yorkshire Railway runs up to the doors. Besides sending large quantities of roburite itself abroad, the company also export to the various colonies the two components, as manufactured in the chemical works, and which separately are quite non-explosive, and which, having arrived at their destination, can be easily mixed in the proper proportions. Among the special advantages claimed for roburite are, first, that it is impossible to explode a cartridge by percussion, fire, or electric sparks. If a cartridge or layer be struck with a heavy hammer, the portion struck is decomposed, owing to the large amount of heat developed by the blow. The remaining explosive is not in the least affected, and no detonation whatever takes place. If roburite be mixed with gunpowder, and the gunpowder fired, the explosion simply scatters the roburite without affecting it in the least. In fact, the only way to explode roburite is to detonate it by means of a cap of fulminate, containing at least 1 gram of fulminate of mercury. Secondly, its great safety for use in coal mines. Roburite has the great advantage of exploding by detonation at a very low temperature, indeed so low that a very slight amount of tamping is required when fired in the most explosive mixture of air and cold gas possible, and not at all in a mixture of air and cold dust, a condition in which the use of gunpowder is highly dangerous. Mr. W. J. Orsman, F.I.C., in a paper read at the University College, Nottingham, in 1893, gives the temperature of detonation of roburite as below 2100 degrees Celsius, and of ammonium nitrate as 1130 degrees Celsius, whereas that of blasting gelatin is as much as 3220 degrees Celsius. With regard to the composition of the fumes formed by the explosion of roburite, Mr. Orsman says, with certain safety explosives, roburite, for instance, an excess of the oxidizing material is added, namely, nitrate of ammonia, but in this case the excess of oxygen here causes a diminution of temperature, as the nitrate of ammonia on being decomposed absorbs heat. This excess of oxygen effectually prevents the formation of carbon monoxide (CO) and the oxides of nitrogen. The following table, A, also from Mr. Orsman's paper, gives the composition of 5 prominent explosives, and shows the composition of the gases formed on explosion. The gases were collected after detonating 10 grms of each in a closed strong steel cylinder, having an internal diameter of 5 inches. With respect to the influence of ammonium nitrate in lowering the temperature of explosion of the various substances to which it is added, it was found by a French commission that, when dry and finely powdered, ammonium nitrate succeeds in depreciating the heat of decomposition without reducing the power of the explosive below a useful limit. The following table, B, shows the composition of the explosives examined, and the temperatures which accompanied their explosion. A underscore 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 composition of gases. Volume. Underscore 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 explosive of gas formed co underscore 2 dot company ch underscore 4n and h underscore 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 per cc cent gunpowder niter 75 parts sulfur tin 2214 51.3 3.5 3.5 41.7 charcoal 15 gel ignite nitroglycerin 56.5 parts nitro cotton 3.5 4980 25 7 67 wood meal 8.0 no underscore 3 32.0 tonight nitro cotton 3750 38 62 barium nitrate roburite ammonium nitrate 86 parts dinitrochlorobenzyl 14 4780 32 68 carbonite nitroglycerin 25 parts woodmeal 40 2100 19 15 26 potas nitrate 34 underscore 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 B underscore 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 original percentage final explosive temperature NH underscore 4.no underscore 3 temperature coefficient added coefficient underscore 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 nitroglycerin 3200 blasting gelatin 8% gun cotton 3090 88 1493 dynamite 25% silica 2940 80 1468 gun cotton 1 2650 2060 90.5 1450 ammonium nitrate 1130 underscore 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 Bellite is the patent of Mr. Carl Lamb, Managing Director of the Rotebro Explosive Company, of Stockholm, and is licensed for manufacture in England. It consists of a mixture of nitrate of ammonia with D or trinitrobenzol. It has a specific gravity of 1.2 to 1.4 in its granulated state, and 1 liter weighs 800 to 875 grams. Heated in an open vessel, bellite loses its consistency at 90 degrees Celsius, but does not commence to separate before a temperature of 200 degrees Celsius is reached, when it evaporates without exploding. If heated suddenly, it burns with a sooty flame, somewhat like tar, but if the source of heat is removed, it will cease burning and assume a caramel-like structure. It absorbs very little moisture from the air after it has been pressed, and if the operation has been performed while the explosive is hot, the subsequent increase of weight is only 2%. When subjected to the most powerful blow with a steel hammer upon an iron plate, it neither explodes nor ignites. A rifle bullet fired into it at 50 yards distance will not explode it. Granulated bellite explodes fully by the aid of fulminating mercury. 15 grms. Of bellite fired by means of fulminate, projected a shot from an ordinary mortar, weighing 90 pounds, a distance of 75 yards, 15 grms. Of gunpowder, under the same conditions, throwing it only 12 yards. A weight of 7.5 pounds, falling 145 centimeters, failed to explode 1 grm. Of bellite. Various experiments and trials have been made with this explosive by Professor P.T. Cleve, and P.F. Challen, C.N. Hake, and by a committee of officers of the Swedish Royal Artillery. It is claimed that it is a very powerful and extremely safe explosive, that it cannot be made to explode by friction, shock, or pressure, nor by electricity, fire, lightning, and that it is specially adapted for use in coal mines, and that it can only be exploded by means of a fulminate detonator, and is perfectly safe to handle and manufacture, that it does not freeze, can be used as a filling for shells, and lastly, can be cheaply manufactured. Securite consists of 26 parts of metadinitrobenzol and 74 parts of ammonium nitrate. It is a yellow powder, with an odor of nitrobenzol. It was licensed in 1886. It sometimes contains trinitrobenzol and trinitronaphthalene. The equation of its combustion is given as C_6 H_4 NO_2 2 plus 10 NH4 NO_3 equals 6 CO_2 plus 22 H_2 O plus 11 N_2. And like bellite and roburite, it is claimed to be perfectly safe to use in the presence of fire, damp, and coal dust. The variety known as flameless securite consists of a mixture of nitrate and oxalate of ammonia and dinitrobenzol. Footnote A. See paper by S.B. Coxon, Northaven. INST Mining and Mech. Eng. 11-287. Kintite. A few years ago an explosive called kintite was introduced, but is not manufactured in England. It was the patent of Messrs. Petrie and Fallenstein, and consisted of nitrobenzol, thickened or gelatinized by the addition of some collodion cotton, incorporated with finely ground chloride of potash and precipitated sulfate of antimony. An analysis gave the following percentages: nitrobenzol, 19.4%, chloride of potash, 76.9%, sulfate of antimony, nitro-cotton, 3.7%. Footnote A.V. Watson Smith, Jur. Soc. Chem. IND, January 1887. It requires a very high temperature to ignite it, and cannot, under ordinary circumstances, when unconfined, be exploded by the application of heat. It is little affected by immersion in water, unless prolonged, when the chlorate dissolves out, leaving a practical inexplosive residue. It was found to be very sensitive to combined friction and percussion, and to be readily ignited by a glancing blow of wood upon wood. It was also deficient in chemical stability, and has been known to ignite spontaneously both in the laboratory and in a magazine. It is an orange-colored plastic mass, and smells of nitrobenzol. Footnote A. Colonel Cundill R.A. Dict. Of explosives says, if, however, it be exposed to moist and dry air alternately, the chlorate crystallizes out on the surfaces, and renders the explosive very sensitive. Tonight No. 3 contains 10 to 14% of nitrobenzol, see tonight. Trench's flameless explosive contains 10% of dinitrobenzol, together with 85% of nitrate of ammonia and 5% of a mixture of alum and the chlorides of sodium and ammonia. Trinitrotoluene. Toluene, C_7, H_8, now chiefly obtained from coal tar, was formerly obtained by the dry distillation of tolu balsam. It may be regarded as methylbenzene, or benzene in which one hydrogen is replaced by methyl, CH_3, thus C_6, H_5, CH_3, or as phenylmethane, or methane in which one hydrogen atom is replaced by the radical phenyl, C_6, H_5, thus CH_3, C_6, H_5. Toluene is a colorless liquid, boiling at 110 degrees Celsius, has a specific gravity of 0.8824 at 0 degrees Celsius, and an aromatic odor. Trinitrotoluene is formed by the action of nitric acid on toluene. According to Hosserman, it is more advantageous to start with the orthopyridinitrotoluene, which is prepared by allowing a mixture of 75 parts of 91 to 92% nitric acid and 150 parts of 95 to 96% sulfuric acid to run in a thin stream into 100 parts of paranitrotoluene, while the latter is kept at a temperature between 60 degrees to 65 degrees Celsius, and continually stirred. When the acid has all been run in, this mixture is heated for half an hour to 80 degrees Celsius, and allowed to stand till cold. The excess of nitric acid is then removed. The residue after this treatment is a homogeneous crystalline mass of orthopyridinitrotoluene, of which the solidifying point is 69.5 degrees Celsius. To convert this mass into trinitro derivative, it is dissolved by gently heating it with 4 times its weight of sulfuric acid, 95 to 96%, and it is then mixed with 1.5 times its weight of nitric acid, 90 to 92%, the mixture being kept cool. Afterwards it is digested at 90 degrees to 95 degrees Celsius, with occasional stirring, until the evolution of gas ceases. This takes place in about 4 or 5 hours. The operation is now stopped, the product allowed to cool, and the excess of nitric acid separated from it. The residue is then washed with hot water and very dilute soda solution, and allowed to solidify without purification. The solidifying point is 70 degrees Celsius, and the mass is then white, with a radiating crystalline structure. Bright sparkling crystals, melting at 81.5 degrees Celsius, may, however, be obtained by recrystallization from hot alcohol. The yield is from 100 parts dinitrotoluene, 150 parts of the trinitro derivative. Hosserman states also that 1:2:4:6 trinitrotoluene can be obtained from ordinary commercial dinitrotoluene melting at 60 degrees to 64 degrees Celsius. But when this is used, greater precautions must be exercised, for the reactions are more violent. Moreover, 10% more nitric acid is required, and the yield is 10% less. He also draws attention to the slight solubility of trinitrotoluene in hot water, and to the fact that it is decomposed by dilute alkalis and alkaline carbonates, facts which must be borne in mind in washing the substance. This material is neither difficult nor dangerous to make. It behaves as a very stable substance when exposed to the air under varying conditions of temperature, -10 degrees to +50 degrees Celsius, for several months. It cannot be exploded by flame, nor by heating it in an open vessel. It is only slightly decomposed by strong percussion on an anvil. A fulminate detonator produces the best explosive effect with trinitrotoluene. It can be used in conjunction with ammonium nitrate, but such admixture weakens the explosive power, but even then it is stated to be stronger than an equivalent mixture of dinitrobenzene and ammonium nitrate. Mowbray patented a mixture of 3 parts nitrotoluol to 7 of nitroglycerin, also in the proportions of 1 to 3, which he states to be a very safe explosive. Faversham powder, one of the explosives on the permitted list, coal mines, is extensively used and is manufactured by the Cotton Powder Company Limited at Faversham. It is composed of trinitrotoluol 11 parts, ammonium nitrate 93 parts, and moisture 1 part. This explosive must be used only when contained in a case of an alloy of lead, tin, zinc, and antimony thoroughly waterproof. It must be used only with a detonator or electric detonator of not less strength than that known as number 6. Nitronaphthalene. Nitronaphthalene is formed by the action of nitric acid on naphthalene, C_10, H_8. Its formula is C_10, H_7, NO_2, and it forms yellow needles, melting at 61 degrees Celsius, and of dinitronaphthalene, C_10, H_6, NO_2, melting 216 degrees Celsius. There are also trinitro and tetranitro and alpha and beta derivatives of nitronaphthalene. It is the dinitronaphthalene that is chiefly used in explosives. It is contained in roburite, securite, romit, Volney's powder, and C. Fevin has patented an explosive consisting of 10 parts of nitronaphthalene mixed with the crude ingredients of gunpowder as follows: nitronaphthalene, 10 parts, saltpetre, 75 parts, charcoal, 12.5 parts, and sulfur, 12.5 parts. He states that he obtains a mononitronaphthalene, containing a small proportion of dinitronaphthalene, by digesting 1 part of naphthalene, with or without heat, in 4 parts of nitric acid, specific gravity 1.40, for 5 days. Quite lately a patent has been taken out for a mixture of nitronaphthalene or dinitrobenzene with ammonium nitrate, and consists in using a solvent for one or other or both of the ingredients, effected in a wet state, and then evaporating off the solvent, care being taken not to melt the hydrocarbon. In this way a more intimate mixture is ensured between the particles of the components, and the explosive thus prepared can be fired by a small detonator, viz. by 0.54 grms of fulminate. Faver's explosive also contains mononitronaphthalene, 8.5 parts, together with 91.5 parts of nitrate of ammonia. This explosive is made in England by the Miners' Safety Explosive Company. A variety of roburite contains chloronitronaphthalene. Romit consists of 100 parts ammonium nitrate and 7 parts potassium chlorate mixed with a solution of 1 part nitronaphthalene and 2 parts rectified paraffin oil. Ammonite. This explosive was originally made at Vilvoorde in Belgium, under the title of the Faver explosive, consisting of a compressed hollow cylinder composed of 91.5% of nitrate of ammonia and 8.5% of mononitronaphthalene filled inside with loose powder of the same composition. The cartridges were wrapped in paper saturated with paraffin wax, and afterwards dipped in hot paraffin to secure their being watertight. The Miners' Safety Explosives Company, when making this explosive at their factory at Stamford-le-Hope, Essex, abandoned after a short trial the above composition, and substituted dinitronaphthalene 11.5% for the mononitronaphthalene, and used thin lead envelopes filled with loose powder slightly pressed in place of the compressed cylinders containing loose powder. The process of manufacture is shortly as follows: 132 3/4 pounds of thoroughly dried nitrate of ammonium is placed in a mill pan, heated at the bottom with live steam, and ground for about 20 minutes until it becomes so dry that a slight dust follows the rollers. Then 17.5 pounds of thoroughly dried dinitronaphthalene is added, and the grinding continued for about 10 minutes. Cold water is then circulated through the bottom of the pan until the material appears of a lightish color and falls to powder. While the pan is hot, the whole mass looks slightly plastic and of a darker color than when cold. A slide in the bottom of the pan is then withdrawn, the whole mass working out until the pan is empty. It is now removed to the sifting machine, brushed through a wire sieve of about 12 holes to the inch, and is then ready for filling into cartridges. The hard core is returned from the sifting machine and turned into one of the pans a few minutes before the charge is withdrawn. The ammonite is filled into the metallic cartridges by means of an Archimedean screw working through a brass tube, pushing off the cartridges as the explosive is fed into them against a slight back pressure, a cover is screwed on, and they then go to the dipping room, where they are dipped in hot wax to seal the ends. They are then packed in boxes of 5 pounds each and are ready for delivery. The dinitronaphthalene is made at the factory. Mononitronaphthalene is first made as follows: 12 parts of commercial nitrate of soda are ground to a fine powder, and further ground with the addition of 15 parts of refined naphthalene until thoroughly incorporated. It is then placed in an earthenware pan, and 30 parts of sulfuric acid of 66 degrees B added, 2 parts at a time, during 48 hours. The rate of adding H_2 4 depends on the condition of the charge, and keeping it in a fluid state, with frequent agitation, day and night. During the first 3 or 4 days, afterwards 3 or 4 times a day. In all, 14 days are occupied in the nitration process. It is then strained through an earthenware strainer, washed with warm water, drained, and dried. For the purpose of producing this material in a granulated condition, which is found more convenient for drying, and further nitrification, it is placed in a tub, and live steam passed through, until brought up to the boiling point. The tub should be about half full. Cold water is then run in whilst violently agitating the contents until the naphthalene solidifies. It can then be easily drained and dried. For the further treatment to make dinitronaphthalene, 18 parts of nitronaphthalene are placed in an earthenware pan, together with 39 parts of sulfuric acid of 66 degrees B. Then 15 parts of nitric acid of 40 degrees B are added, in small quantities at a time, stirring the mixture continually. This adding of nitric acid is controlled by the fuming, which should be kept down as much as possible. The operation takes 10 to 12 days, when 100 times the above quantities, taken in kilograms, are taken. At the end of the nitration, the dinitronaphthalene is removed to earthenware strainers, allowed to drain, washed with hot water and soda until all acid is removed, washed with water and dried. The dinitronaphthalene gives some trouble in washing, as some acid is held in the crystals, which is liable to make its appearance when crushed. To avoid this, it should be ground and washed with carbonate of soda before drying. An excess of carbonate of soda should not, however, be used. Electronite. This is a high explosive designed to afford safety in coal getting. This important end has been attained by using such ingredients, and so proportioning them, as will ensure on detonation a degree of heat insufficient under the conditions of a blown-out shot to ignite fire, damp, or coal dust. It is of the nitrate of ammonium class of permitted explosives. It contains about 75% of nitrate of ammonium, with the addition of nitrate of barium, wood meal, and starch. The gases resulting from detonation are chiefly water in the gaseous form, nitrogen, and a little carbon dioxide. It is granulated with the object of preventing misfires from ramming, to which nitrate of ammonium explosives are somewhat susceptible. This explosive underwent some exhaustive experiments at the experimental station near Wigan in 1895, when 8 ounces or 12 ounces charges were fired unstemmed into an admixture of coal dust and 10% of gas, without any ignition taking place. It is manufactured by Messrs. Curtis's and Harvey Limited at their factory, Tunbridge, Kent. Sprengel's explosives. This is a large class of explosives. The essential principle of them all is the admixture of an oxidizing with a combustible agent at the time of, or just before, being required for use, the constituents of the mixture being very often non-explosive bodies. This type of explosive is due to the late Dr. Hermann Sprengel, FRS. Following up the idea that an explosion is a sudden combustion, he submitted a variety of mixtures of oxidizing and combustible agents to the violent shock of a detonator of fulminate. These mixtures were made in such proportions that the mutual oxidation or deoxidation should be theoretically complete. Among them are the following: 1. 1 chemical equivalent of nitrobenzene to equivalents of nitric acid. 2. 5 equivalents of picric acid to 13 equivalents of nitric acid. 3. 87 equivalents of nitronaphthalene to 413 equivalents of nitric acid. 4. Porous cakes, or lumps of chloride of potash, exploded violently with bisulfide of carbon, nitrobenzol, carbonic acid, sulfur, benzene, and mixtures of these substances. Number 1 covers the explosive known as Hellhoffite, and number 2 is really oxenite, and number 4 resembles rakarok, an explosive invented by Mr. S.R. Devine, and consisting of a mixture of chloride of potash and nitrobenzol. Roburite, belite, and securite should perhaps be regarded as belonging to the Sprengel class of explosives, otherwise this class is not manufactured or used in England. The principal members are known as hellhoffite, consisting of a mixture of nitropetroleum or nitrotar oils and nitric acid, or of metadinitrobenzol and nitric acid, oxenite, consisting of picric and nitric acids, and panclastite, a name given to various mixtures, proposed by M. Turpin, such as liquid nitric peroxide, with bisulfide of carbon, benzol, petroleum, ether, or mineral oils. Picric acid, trinitrophenol, or carbazotic acid. Picric acid, or a trinitrophenol, C_6, H_2, No_2_2_302:4:6, is produced by the action of nitric acid on many organic substances, such as phenol, indigo, wool, aniline, resins, and C. At one time a yellow gum from Botany Bay, Xanthorrhea hastilis, was chiefly used. 1 part of phenol, carbolic acid, C_6, H_5O, is added to 3 parts of strong fuming nitric acid, slightly warmed, and when the violence of the reaction has subsided, boiled till nitrous fumes are no longer evolved. The resinous mass thus produced is boiled with water. The resulting picric acid is converted into a sodium salt by a solution of sodium carbonate, which throws down sodium picrate in crystals. Phenol sulfuric acid is now, however, more generally used, and the apparatus employed for producing it closely resembles that used in making nitrobenzol. It is also made commercially by melting carbolic acid and mixing it with strong sulfuric acid, then diluting the sulfocarbolic acid with water, and afterwards running it slowly into a stone tank containing nitric acid. This is allowed to cool, where the crude picric acid crystallizes out, and the acid liquid, which contains practically no picric acid, but only sulfuric acid, with some nitric acid, being poured down the drains. The crude picric acid is then dissolved in water by the aid of steam, and allowed to cool when most of the picric acid recrystallizes. The mother liquor is transferred to a tank and treated with sulfuric acid, when a further crop of picric acid crystals is obtained. The crystals of picric acid are further purified by recrystallization, drained, and dried at 100 degrees Fahrenheit, on glazed earthenware trays by the aid of steam. It can also be obtained by the action of nitric acid on orthonitrophenol, paranitrophenol, and dinitrophenol, 2:4 and 2:6, but not from metanitrophenol, a fact which indicates its constitution. B. Footnote AO and P. Phenolsulfonic acids. C_3H_4O.so_3H+3 no_3 equals C_6H_2 no_2 3O plus H2 so_4 plus 2H_2O. Picric acid. Footnote B. Carey Leah Amer. Jure Science 2, 32. 180. Picric acid crystallizes in yellow shining prisms or laminae having an intensely bitter taste, and is poisonous. It melts at 122.5 degrees Celsius, sublimes when cautiously heated, dissolves sparingly in cold water, more easily in hot water, still more in alcohol. It stains the skin an intense yellow color, and is used as a dye for wool and silk. It is a strong acid, forming well crystallized yellow salts, which detonate violently when heated, some of them also by percussion. The potassium salt, C_6H_2 no_2 3 crystallizes in long needles very slightly soluble in water. The sodium, ammonium, and barium salts are, however, easily soluble in water. Picric acid, when heated, burns with a luminous and smoky flame, and may be burned away in large quantity without explosion, but the mere contact of certain metallic oxides with picric acid in the presence of heat develops powerful explosives, which are capable of acting as detonators to an indefinite amount of the acid, wet or dry, which is within reach of their detonative influence. The formula of picric acid is C_6H_2NO_2_3O, which shows its formation from phenol C_6H_5O, 3 hydrogen atoms being displaced by the NO_2 group. The equation of its formation from phenol is as follows: C_6H_5 DATO plus 3 NO_3 equals C_6H_2 NO_2 3O plus 3H2O. According to Berthelot, its heat of formation from its elements equals 49.1 calories, and its heat of total combustion by free oxygen is equal to plus 618.4 calories. It hardly contains more than half the oxygen necessary for its complete combustion. 2C_6H_2 NO_2 3O plus O10 equals 12 CO_2 plus 3H_2 plus 3N_2. The percentage composition of picric acid is nitrogen 18.34, oxygen 49.22, hydrogen 1.00, and carbon 31.44, equal to 60.26% of NO_2. The products of decomposition are carbonic acid, carbonic oxide, carbon, hydrogen, and nitrogen, and the heat liberated, according to Berthelot, would be 130.6 calories, or 570 calories per kilogram. The reduced volume of the gases would be 190 liters per equivalent, or 829 liters per kilogram. To obtain a total combustion of picric acid, it is necessary to mix with it an oxidizing agent, such as a nitrate, chlorate, and C. It has been proposed to mix picric acid, 10 parts, with sodium nitrate, 10 parts, and potassium bichromate, 8.3 parts. These proportions would furnish a third of oxygen in excess of the necessary proportion. Picric acid was not considered to be an explosive, properly so called, for a long time after its discovery, but the disastrous accident which occurred at Manchester, Vede Gov. Rep. No. 81, by Colonel, now Sir V.D. Magendie C.B., and some experiments made by Dr. Dupré and Colonel Magendie to ascertain the cause of the accident, conclusively proved that this view was wrong. The experiments of Berthelot Bull. De la Soc. Chim. de Paris, 49, page 456, on the explosive decomposition of picric acid are also deserving of attention in this connection. If a small quantity of picric acid be heated in a moderate fire, in a crucible, or even in an open test tube, it will melt at 120 degrees Celsius. Commercial acid then give off vapors which catch fire upon contact with air, and burn with a sooty flame, without exploding. If the burning liquid be poured out upon a cold slab, it will soon go out. A small quantity carefully heated in a tube, closed at one end, can even be completely volatilized without apparent decomposition. It is thus obvious that picric acid is much less explosive than the nitric ethers, such as nitroglycerol and nitrocellulose, and very considerably less explosive than the nitrogen compounds and fulminates. It would, however, be quite erroneous to assume that picric acid cannot explode when simply heated. On the contrary, Berthelot has proved that this is not the case. If a glass tube be heated to redness, and a minute quantity of picric acid crystals be then thrown in, it will explode with a curious characteristic noise. If the quantity be increased so that the temperature of the tube is materially reduced, no explosion will take place at once, but the substance will volatilize and then explode, though with much less violence than before, in the upper part of the tube. Finally, if the amount of picric acid be still further increased under these conditions, it will undergo partial decomposition and volatilize, but will not even deflagrate. Nitrobenzene, dinitrobenzene, and mono-D- and trinitronaphthalines behave similarly. The manner in which picric acid will decompose is thus dependent upon the initial temperature of the decomposition, and if the surrounding material absorb heat as fast as it is produced by the decomposition, there will be no explosion and no deflagration. If, however, the absorption is not sufficient to prevent deflagration, This may so increase the temperature of the surrounding materials that the deflagration will then end in explosion. Thus, if an explosion were started in an isolated spot, it would extend throughout the mass, and give rise to a general explosion. In the manufacture of picric acid, the first obvious and most necessary precaution is to isolate the substance from other chemicals with which it might accidentally come into contact. If pure materials only are used, the manufacture presents no danger. The finished material, however, must be carefully kept from contact with nitrates, chlorates, or oxides. If only a little bit of lime or plaster become accidentally mixed with it, it may become highly dangerous. A local explosion may occur which might have the effect of causing the explosion of the whole mass. Picric acid can be fired by a detonator, 5-grain fulminate, NM. Turpin patented the use of picric acid, unmixed with any other substance, in 1885. The detonation of a small quantity of dry picric acid is sufficient to detonate a much larger quantity containing as much as 17% of water. It is chiefly due to French chemists, and to Dr. Sprengel, that picric acid has come to the front as an explosive. Melinite, a substance used by the French government for filling shells, was due to M. Turpin, and is supposed to be little else than fused picric acid mixed with guncotton dissolved in some solvent, acetone or ether alcohol. Sir F. A. Abel has also proposed to use picric acid, mixed with nitrate of potash, 3 parts, and picrate of ammonia, 2 parts, as a filling for shells. This substance requires a violent blow and strong confinement to explode it. I am not aware, however, that it has ever been officially adopted in this country. Messrs. Designols and Bruguera have introduced military powders, consisting of mixtures of potassium and ammonium picrates with nitrate of potassium. M. Designols introduced 3 kinds of picrate powders, composed as follows: underscore 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 4 torpedoes, 4 guns, 4 small, and shells. Ordinary, heavy, arms. Underscore 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 picrate of potash 55 to 50 16.49.6 9 28.6 to 22.9 saltpetre 45 to 50, 74.4 to 79.7, 80, 65.0 to 69.4, charcoal, 9.2 to 10.7, 11, 6.47.7. Underscore 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 underscore. They were made much like ordinary gunpowder, 6 to 14% of moisture being added when being milled. The advantages claimed over gunpowder are greater strength, and consequently greater ballistic or disruptive effect, comparative absence of smoke, and freedom from injurious action on the bores of guns, owing to the absence of sulfur. Brewer's powder is composed of ammonium picrate and niter, the proportions being 54% picrate of ammonia and 46% potassic nitrate. It is stable, safe to manufacture and handle, but expensive. It gives good results in the Shaspo rifle, very little smoke, and its residue is small, and consists of carbonate of potash. It is stated that 2.6 grms used in a rifle gave an effect equal to 5.5 grms of ordinary gunpowder. Footnote A. The British lyddite and the Japanese Shermose are said to be identical with melanite. Turpin has patented various mixtures of picric acid, with gum arabic, oils, fats, collodion jelly, and C, when the last named substance is diluted in the proportion of from 3 to 5%. In a mixture of ether and alcohol, he states that the blocks of picric acid molded with it will explode in a closed chamber with a priming of from 1 to 3 grams of fulminate. He also casts picric acid into projectiles, the cast acid having a density of about 1.6. In this state it resists the shock produced by the firing of a cannon, when contained in a projectile, having an initial velocity of 600 meters. It is made in the following way. The acid is fused in a vessel provided with a false bottom, heated to 130 degrees to 145 degrees Celsius, by a current of steam under pressure, or simply by the circulation under the false bottom of a liquid, such as oil, chloride of zinc, glycerin, and C, heated to the same temperature. The melted picric acid is run into molds of a form corresponding to that of the blocks required, or it may be run into projectiles, which should be heated to a temperature of about 100 degrees Celsius, in order to prevent too rapid solidification. When cresilic acid, or cresol, C_6, H_4, CH_3O, is acted upon by nitric acid, it produces a series of nitro compounds very similar to those formed by nitric acids on phenol, such as sodium dinitrocresylate, known in the arts as Victoria yellow. Naphthol, a phenol-like body obtained from naphthalene, under the same conditions, produces sodium dinitronaphthalic acid, C_10, H_6, NO_2, The explosive known as roburite contains chloronitronaphthalene, and romit, a Swedish explosive, nitronaphthalene. Trinitrocresol, C_7, H_4, NO_2, a body very similar to trinitrophenol, crystallizes in yellow needles, slightly soluble in cold water, rather more so in boiling water, alcohol, and ether. It melts at about 100 degrees Celsius. In France it is known as chrysolite, and mixed with melanite, is used for charging shells. By neutralizing a boiling saturated solution of trinitrocresol with ammonia, a double salt of ammonium and nitrocresol crystallizes out upon cooling, which is similar to ammonium picrate. This salt is known as ecrasite, and has been used in Austria for charging shells. It is a bright yellow solid, greasy to the touch, melts at 100 degrees Celsius, is unaffected by moisture, heat, or cold, ignites when brought into contact with an incandescent body or open flame, burning harmlessly away unless strongly confined, and is insensitive to friction or concussion. It is claimed to possess double the strength of dynamite, and requires a special detonator, not less than 2 grms of fulminate, to provoke its full force. Notwithstanding the excellent properties attributed to this explosive, Lieutenant W. Walk, Lectures on Explosives, page 181 says, several imperfectly explained and unexpected explosions have occurred in loading shells with this substance, and have prevented its general adoption up to the present time. The fulminates are salts of fulminic acid, C_2, N_2, O_2, H_2. Their constitution is not very well understood. Diary, Divers, FRS, and Mr. Kawakita, Chem. SOC Jour, 1884, pages 13 to 19, give the formulae of mercury and silver fulminates as OC equals N/N/. backslash, backslash HG, O and O backslash, forward slash, forward slash C equals N AGC equals N. Whereas Drhe Armstrong, FRS, would prefer to write the formula of fulminic acid. On.C.O, C and .O. And AF Holloman Bericht v. 26, page 1403, assigns to mercury fulminate the formula C N.OHG, C N.O. NR Scholl BR v. 23, page 3505. C no, Hg. C no. They are very generally regarded as isonitroso compounds. The principal compound of fulminic acid is the mercury salt commonly known as fulminating mercury. It is prepared by dissolving mercury in nitric acid, and then adding alcohol to the solution, 1 part of mercury and 12 parts of nitric acid of specific gravity 1.36, and 5.5 parts of 90%, alcohol being used. As soon as the mixture is in violent reaction, 6 parts more of alcohol are added slowly to moderate the action. At first the mixture blackens from the separation of mercury, but this soon vanishes, and is succeeded by crystalline flocks of mercury fulminate which fall to the bottom of the vessel. During the reaction, large quantities of volatile oxidation products of alcohol, such as aldehyde, ethylic nitrate, and C, are evolved from the boiling liquid, whilst others, such as glycolic acid, remain in solution. The mercury fulminate is then crystallized from hot water. It forms white silky, delicate needles, which are with difficulty soluble in cold water. In the dry state it is extremely explosive, detonating on heating, or by friction or percussion, as also on contact with concentrated sulfuric acid. The reaction that takes place upon its decomposition is as follows. C_2 N_2 O_2 Hg equals Hg plus 2 Co plus N_2 284. According to this equation 1 grm of the fulminate should yield 235.8 cc, equals 66.96 liters for 284 grms. Berthelot and Vassil have obtained a yield of 234.2 cc, equal to 66.7 liters for 1 equivalent 284 grms. Dry fulminate explodes violently when struck, compressed, or touched with sulfuric acid, or as an incandescent body. If heated slowly, it explodes at 152 degrees Celsius, or if heated rapidly, at 187 degrees Celsius. It is often used mixed with potassium chlorate in detonators. The reaction which takes place in this case is 3C_2 N_2 O_2 Hg plus 2 Clo_3 equals 3 Hg plus 6 Co_2 plus 3 N_2 plus 2 KCl. On adding copper or zinc to a hot saturated solution of the salt, fulminate of copper or zinc is formed. The copper salt forms highly explosive green crystals. There is also a double fulminate of copper of ammonia, and of copper and potassium. Silver fulminate C_2 N_2 O_2 Ag_2 is prepared in a similar manner to the mercury salt. It separates in fine white needles, which dissolve in 36 parts of boiling water, and are with difficulty soluble in cold water. At above 100 degrees Celsius, or on the weakest blow, it explodes with fearful violence. Even when covered with water, it is more sensitive than the mercury salt. It forms a very sensitive double salt with ammonia and several other metals. With hydrogen, it forms the acid fulminate of silver. It is used in crackers and bonbons, and other toy fireworks, in minute quantities. Gay-Lussac found it to be composed as follows: carbon, 7.92%, nitrogen, 9.24%, silver, 72.19%, oxygen, 10.65%, and he assigned to it the formula C_2 N_2 Ag_2 O_2. Laurent and Gerhardt give it the formula C_2 N No_2 Ag_2, and thus suppose it to contain nitrile No_2. On adding potassium chloride to a boiling solution of argentic fulminate, as long as a precipitate of argentic chloride forms, there is obtained on evaporation brilliant white plates, of a very explosive nature, of potassic argentic fulminate C, No_2, CAG.CN, from whose aqueous solution nitric acid precipitates a white powder of hydric argentic fulminate C, No_2, HAG.CN. All attempts to prepare fulminic acid, or nitroacetonitrile C, No_2, H_2, from the fulminates have failed. There is a fulminate of gold, which is a violently explosive buff precipitate, formed when ammonia is added to terchloride of gold, and fulminate of platinum, a black precipitate formed by the addition of ammonia to a solution of oxide platinum, in dilute sulfuric acid. Fulminating silver is a compound obtained by the action of ammonia on oxide of silver. It is a very violent explosive. Pure mercury fulminate may be kept an indefinite length of time. Water does not affect it. It explodes at 187 degrees Celsius, and on contact with an ignited body. It is very sensitive to shock and friction, even that of wood upon wood. It is used for discharging bullets in saloon rifles. Its inflammation is so sudden that it scatters black powder on which it is placed without igniting it, but it is sufficient to place it in an envelope, however weak, for ignition to take place, and the more resisting the envelope the more violent is the shock, a circumstance that plays an important part in caps and detonators. The presence of 30% of water prevents decomposition, 10% prevents explosion. This is, however, only true for small quantities, and does not apply to silver fulminate, which explodes under water by friction. Moist fulminates slowly decompose on contact with the oxidizable metals. The reduced volume of gases obtained from 1 kilo is, according to Berthelot, 235.6 liters. The equation of its decomposition is C_2 HGN_2 O_2 equals 2 Co plus N_2 plus Hg. Fulminate of mercury is manufactured upon the large scale by two methods. One of these, commonly known as the German method, is conducted as follows. 1 part of mercury is dissolved in 12 parts of nitric acid of a specific gravity of 1.375, and to this solution 16.5 parts of absolute alcohol are added by degrees, and heat is then slowly applied to the mixture until the dense fumes first formed have disappeared. And when the action has become more violent, some more alcohol is added, equal in volume to that which has already been added. This is added very gradually. The product obtained, which is mercury fulminate, is 112% of the mercury employed. Another method is to dissolve 10 parts of mercury in 100 parts of nitric acid of a gravity of 1.4, and when the solution has reached a temperature of 54 degrees Celsius, to pour it slowly through a glass funnel into 83 parts of alcohol. When the effervescence ceases, it is filtered through paper filters, washed, and dried over hot water, at a temperature not exceeding 100 degrees Celsius. The fulminate is then carefully packed in paper boxes, or in corked bottles. The product obtained by this process is 130% of the mercury taken. This process is the safest, and at the same time the cheapest. Fulminate should be kept, if possible, in a damp state. Commercial fulminate is often adulterated with chlorate of potash. Detonators, or caps, are metallic capsules, usually of copper, and resemble very long percussion caps. The explosive is pure fulminate of mercury, or a mixture of that substance with nitrate or chlorate of potash, gunpowder, or sulfur. The following is a common cap mixture: 100 parts of fulminate of mercury and 50 parts of potassium nitrate, or 100 parts of fulminate and 60 parts of meal powder. Silver fulminate is also sometimes used in caps. There are 8 sizes made, which vary in dimensions and in amount of explosive contained. They are further distinguished as singles, doubles, trebles, and C, according to their number. Colonel Kundal R.A. Dict. Of explosives, gives the following list. Number 1 contains 300 grms of explosive per 1,000. 2 403. 540. 4 650, 5 806, 1007, 1500, 8 2000. Trebles are generally used for ordinary dynamite, 5, 6, or 7 for gun cotton, blasting gelatin, roburite, and C. In the British service, percussion caps, fuses, and C are formed of 6 parts by weight of fulminate of mercury, 6 of chloride of potash, and 4 of sulfate of antimony. Time fuses of 4 parts of fulminate, 6 of potassium chlorate, 4 of sulfate of antimony, the mixture being damped with a varnish consisting of 645 grains of shellac dissolved in a pint of methylated spirit. Abel's fuse, number 1, consists of a mixture of sulfate of copper, phosphide of copper, chloride of potash, and number 2 of a mixture of gun cotton and gunpowder. They are detonated by means of a platinum wire heated to readiness by means of an electric current. Bain's fuse mixture is a mixture of subphosphide of copper, sulfate of antimony, and chloride of potash. In the manufacture of percussion caps and detonators, the copper blanks are cut from copper strips and stamped to the required shape. The blanks are then placed in a gunmetal plate, with the concave side uppermost, a tool composed of a plate of gunmetal, in which are inserted a number of copper points, each of the same length, and so spaced apart as to exactly fit each point into a cap when inverted over a plate containing the blanks. The points are dipped into a vessel containing the cap composition, which has been previously moistened with methylated spirit. It is then removed and placed over the blanks, and a slight blow serves to deposit a small portion of the cap mixture into each cap. A similar tool is then dipped into shellac varnish, removed and placed over the caps, when a drop of varnish from each of the copper points falls into the caps, which are then allowed to dry. This is a very safe and efficacious method of working. At the works of the Cotton Powder Company Limited, at Faversham, the fulminate is mixed wet with a very finely ground mixture of gun cotton and chloride of potash, in about the proportions of 6 parts fulminate, 1 part gun cotton, and 1 part chlorate. The water in which the fulminate is usually stored is first drained off, and replaced by displacement by methyl alcohol. While the fulminate is moist with alcohol, the gun cotton and chlorate mixture is added, and well mixed with it. This mixture is then distributed in the detonators standing in a frame, and each detonator is put separately into a machine for the purpose of pressing the paste into the detonator shell. At the 11th annual meeting of the representatives of the Bavarian chemical industries at Regensburg, attention was drawn to the unhealthy nature of the process of charging percussion caps. Numerous miniature explosions occur, and the air becomes laden with mercurial vapors, which exercise a deleterious influence upon the health of the operatives. There is equally just cause for apprehension in respect to the poisonous gases which are evolved during the solution of mercury in nitric acid, and especially during the subsequent treatment with alcohol. Many methods have been proposed for dealing with the waste products arising during the manufacture and manipulation of fulminate of mercury, but according to Kammerer, only one of comparatively recent introduction appears to be at all satisfactory. It is based upon the fact that mercuric fulminate, when heated with a large volume of water under high pressure, splits up into metallic mercury and non-explosive mercurial compounds of unknown composition. In mixing the various ingredients with mercury fulminate to form cap mixtures, they should not be too dry. In fact, they are generally more or less wet, and mixed in small quantities at a time, in a special house, the floors of which are covered with carpet, and the tables with felt. Felt shoes are also worn by the workpeople employed. All the tools and apparatus used must be kept very clean. For granulating, hair sieves are used, and the granulated mixture is afterwards dried on light frames, with canvas trays the bottoms of which are covered with thin paper, and the frames fitted with india-rubber cushions, to reduce any jars they may receive. The windows of the building should be painted white to keep out the rays of the sun. Mr. H. Maxim, of New York, has lately patented a composition for detonators for use with high explosives, which can also be thrown from ordnance in considerable quantities with safety. The composition is prepared as follows. Nitroglycerin is thickened with pyroxylene to the consistency of roll rubber. This is done by employing about 75 to 85% of nitroglycerin and 15 to 25% of pyroxylene, according to the stiffness or elasticity of the compound desired. Some solvent that dissolves the nitro cotton is also used. The product thus formed is a kind of blasting gelatin, and should be in a pasty condition, in order that it may be mixed with fulminate of mercury. The solvent used is acetone, and the quantity of fulminate is between 75 to 85% of the entire compound. If desired, the compound can be made less sensitive to shocks by giving it a spongy consistency by agitating it with air while it is still in a syrupy condition. The nitroglycerin, especially in this latter case, may be omitted. In some cases, when it is desirable to add a deterring medium, nitrobenzene or some suitable gum is added. Illustration, Figure 34. Method of preparing the charge. The method of preparing a blasting charge is as follows. A piece of Bickford fuse of the required length is cut clean and is inserted into a detonator until it reaches the fulminate. The upper portion of the detonator is then squeezed round the fuse with a pair of nippers. The object of this is not only to secure that the full power of the detonator may be developed, but also to fix the fuse in the cap, Figure 34. When the detonator, NC, is to be used under water, or in a damp situation, grease or tallow should be placed round the junction of the cap with the fuse, in order to make a watertight joint. A cartridge is then opened and a hole made in its upper end, and the detonator pushed in nearly up to the top. Gun cotton or tonite cartridges generally have a hole already made in the end of the charge. Small charges of dry gun cotton, known as primers, are generally used to explode wet gun cotton. The detonators, which are often fired by electrical means, are placed inside these primers, Figure 35. Illustration, Figure 35. Primer. One of the forms of electric exploders used is shown in Figure 36. This apparatus is made by Messrs. John Davis and Son, and is simply a small hand dynamo, capable of producing a current of electricity of high tension. This firm are also makers of various forms of low-tension exploders. A charge having been prepared, as in Figure 34, insert into the borehole one or more cartridges as judged necessary, and squeeze each one down separately with a wooden rammer, so as to leave no space round the charge, and above this insert the cartridge containing the fuse and detonator. Now fill up the rest of the borehole with sand, gravel, water, or other tamping. With gelatin dynamites a firm tamping may be used, but with ordinary dynamite loose sand is better. The charge is now ready for firing. Illustration, Figure 36. Electric exploder. Chapter 6. Smokeless powders. Smokeless powder in general, cordite, axite, ballastite, U.S. naval powder, Schulze's E.G. powder, indurite, Viel poudre, riflite, cannonite, Walsrode, Kupal powders, amberite, Troisdorf, maximite, picric acid powders, NC. The progress made in recent years in the manufacture of smokeless powders has been very great. With a few exceptions, nearly all these powders are nitro compounds, and chiefly consist of some form of nitrocellulose, either in the form of nitro-cotton or nitrolignin, or else contain, in addition to the above, nitroglycerin, with very often some such substance as camphor, which is used to reduce the sensitiveness of the explosive. Other nitro bodies that are used, or have been proposed, are nitrostarch, nitrojute, nitrate paper, nitrobenzene, dinitrobenzene, mixed with a large number of other chemical substances, such as nitrates, chlorates, NC. And lastly, there are the picrate powders, consisting of picric acid, either alone or mixed with other substances. The various smokeless powders may be roughly divided into military and sporting powders. But this classification is very rough, because although some of the better-known purely military powders are not suited for use in sporting guns, nearly all the manufacturers of sporting powders also manufacture a special variety of their particular explosive, fitted for use in modern rifles or machine guns, and occasionally, it is claimed, for big guns also. Of the purely military powders, the best known are cordite, ballastite, and the French Bien powder, the German smokeless, which contains nitroglycerin and nitro-cotton, and among the general powders, two varieties of which are manufactured either for rifles or sporting guns, Schulze's, the EC powders, Walsrode powder, cannonite, Kupal powder, amberite, NC. Cordite, the smokeless powder adopted by the British government, is the patent of the late Sir F. A. Abel and Sir James Dewar, and is somewhat similar to blasting gelatin. It is chiefly manufactured at the Royal Gunpowder Factory at Waltham Abbey, but also at 2 or 3 private factories, including those of the National Explosives Company Limited, the New Explosives Company Limited, the Cotton Powder Company Limited, Messrs. Kynox, and C. As first manufactured, it consisted of guncotton 37%, nitroglycerin 58%, and Vaseline 5%, but the modified cordite now made consists of 65% guncotton, 30% of nitroglycerin, and 5% of Vaseline. The guncotton used is composed chiefly of the hexanitrate, A, which is not soluble in nitroglycerin. It is therefore necessary to use some solvent such as acetone in order to form the jelly with nitroglycerin. The process of manufacture of cordite is very similar, as far as the chemical part of the process is concerned, to that of blasting gelatin, with the exception that some solvent for the guncotton, other than nitroglycerin, has to be used. Both the nitroglycerin and the guncotton employed must be as dry as possible, and the latter should not contain more than 0.6% of mineral matter and not more than 10% of soluble nitrocellulose, and a nitrogen content of not less than 12.5%. The dry guncotton, about 1% of moisture, is placed in an incorporating tank, which consists of a brass-lined box. Some of the acetone is added, and the machine, Figure 29, is started. After some time, the rest of the acetone is added, 20%, in all, and the paste needed for 3.5 hours. At the end of this time, the Vaseline is added, and the kneading continued for a further 3.5 hours. The kneading machine, Figure 29, consists of a trough, composed of 2 halves of a cylinder, in each of which is a shaft which carries a revolving blade. These blades revolve in opposite directions, and one makes about half the number of revolutions of the other. As the blades very nearly touch the bottom of the trough, any material brought into the machine is divided into 2 parts, kneaded against the bottom, then pushed along the blade, turned over, and completely mixed. During kneading, the acetone gradually penetrates the mixture, and dissolves both the nitrocellulose and nitroglycerin, and a uniform dough is obtained which gradually assumes a buff color. During kneading, the mass becomes heated, and therefore cold water is passed through the jacket of the machine to prevent heating the mixture above the normal temperature, and consequent evaporation of the acetone. The top of the machine is closed in with a glass door, in order to prevent as far as possible the evaporation of the solvent. When the various ingredients are formed into a homogeneous mass, the mixture is taken to the press house, where in the form of a plastic mass it is placed in cylindrical molds. The mold is inserted in a specially designed press, and the cordite paste forced through a die with 1 or more holes. The paste is pressed out by hydraulic pressure, and the long cord is wound on a metal drum, Figure 38, or cut into lengths. In either case, the cordite is now sent to the drying houses, and dried at a temperature of about 100 degrees Fahrenheit, from 3 to 14 days, the time varying with the size. This operation drives off the acetone, and any moisture the cordite may still contain, and its diameter decreases somewhat. In case of the finer cordite, such as the rifle cordite, the next operation is blending. This process consists in mounting 10 of the metal drums on a reeling machine similar to those used for yarns, and winding the 10 cords onto one drum. This operation is known as 10-stranding. Furthermore, 6 10-stranded reels are afterwards wound upon one, and the 60-stranded reel is then ready to be sent away. This is done in order to obtain a uniform blending of the material. With cordite of a larger diameter, the cord is cut into lengths of 12 inches. Every lot of cordite from each manufacturer has a consecutive number, numbers representing the size and 1 or more initial letters to identify the manufacturer. These regulations do not apply to the Royal Gunpowder Factory, Waltham Abbey. The finished cordite resembles a cord of gutta percha, and its color varies from light to dark brown. It should not look black or shriveled, and should always possess sufficient elasticity to return to its original form after slight bending. Cordite is practically smokeless. On explosion, a very thin vapor is produced, which is dissipated rapidly. This smokelessness can be understood from the fact that the products of combustion are nearly all non-condensable gases, and contain no solid products of combustion which would cause smoke. For the same muzzle velocity, a smaller charge of cordite than gunpowder is required owing to the greater amount of gas produced. Cordite is very slow in burning compared to gunpowder. For firing blank cartridges, cordite chips containing no Vaseline is used. The rate at which cordite explodes depends in a measure upon the diameter of the cords, and the pressure developed upon its mechanical state. The sizes of cordite used are given by Colonel Barker, R.A., as follows. For the .303 rifle, 0.0375 inch diameter. 12 PRBL gun, .05, .075, 4.7 inch QF gun, .100, 6 inch QF gun, .300, heavy guns, .40 to .50. For rifles, the cordite is used in bundles of 60 strands, in field guns in lengths of 11 to 12 inches, and the thicker cordite is cut up into 14-inch lengths. Colonel Barker says that the effect of heat upon cordite is not greater as regards its shooting qualities than upon black powder, and in speaking of the effect that cordite has upon the guns in which it is used, RAINST said that they had at Waltham Abbey a 4.7-inch QF gun that had fired 40 rounds of black powder and 249 rounds of cordite, 58%, nitroglycerin, and was still in excellent condition, and showed very little sign of action, and also a 12-pound BL gun that had been much used and was in no wise injured. Footnote A. The gun cotton used contains 12% of soluble gun cotton, and a nitrogen content of not less than 12.8 to 13.1%. Illustration: Figure 37 scale, 1 inch equals 1 foot. Single strand reel. Illustration: Figure 38. 10 stranding. In some experiments made by Captain Sir A. Noble, A., with the old cordite containing 58% nitroglycerin, a charge of 5 pounds, 10 ounces of cordite of 0.2-inch diameter was fired. The mean chamber crusher gauge pressure was 13.3 tons per square inch, maximum 13.6, minimum 12.9, or a mean of 2,027 atmospheres, max 2,070. Min 1970. The muzzle velocity was 2,146 foot-seconds, and the muzzle energy 1,437 foot-tons. A gram of cordite generated 700 cc of permanent gases at 0 degrees Celsius, and 760 millimeters pressure. The quantity of heat developed was 1,260 gram units. In the case of cordite, as also with ballastite, a considerable quantity of aqueous vapor has to be added to the permanent gases formed. A similar trial, in which 12 pounds of ordinary pebble powder was used, gave a pressure of 15.9 tons per square inch, or a mean of 2,424 atmospheres. It gave a 45-pound projectile a mean muzzle velocity of 1,839 foot-seconds, thus developing a muzzle energy of 1,055 foot-tons. A gram of this powder at 0 degrees Celsius, and 760 millimeters, generates 280 cc of permanent gases, and develops 720 grm. Units of heat. Footnote A. Prop Roy. SOC, Volume 52, Number 315. In a series of experiments conducted by the War Office Chemical Committee on Explosives in 1891, it was conclusively shown that considerable quantities of cordite may be burnt away without explosion. A number of wooden cases, containing 500 to 600 pounds, each of cordite, were placed upon a large bonfire of wood, and burned for over a quarter of an hour without explosion. At Woolwich in 1892, a brown paper packet containing 10 cordite cartridges was fired into with a rifle, .303, loaded with cordite, without the explosion of a single one of them, which shows its insensibility to shock. With respect to the action of cordite upon guns, Sir A. Noble points out that the erosion caused is of a totally different kind to that of black powder. The surface of the barrel in the case of cordite appears to be washed away smoothly by the gases, and not pitted and eaten into as with black powder. The erosion also extends over a shorter length of surface, and in small arms it is said to be no greater than in the case of black powder. Sir A. Noble says in this connection, "It is almost unnecessary to explain that freedom from rapid erosion is of very high importance in view of the rapid deterioration of the bores of large guns when fired with charges developing very high energies. As might perhaps be anticipated from the higher heat of ballastite, its erosive power is slightly greater than that of cordite, while the erosive power of cordite is again slightly greater than that of brown prismatic. Amide powder, on the other hand, possesses the peculiarity of eroding very much less than any other powder with which I have experimented, its erosive power being only 1/4 of that of the other powders enumerated." Table giving some of Sir A. Noble's experiments. Underscore 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 velocities obtained. Underscore 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 in a 40, in a 50, in a 75, in a 100, cow gun, cow gun, cow gun, cow gun. Underscore 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 foot sex, foot sex, foot seas, foot sex, with cordite 0.4 inches. Diameter 2,794, 2,940, 3,166, 3,286, 0.3, 2,469, 2,619, 2,811, 2,905. Ballastite 0.3 inches. Cubes 2,416, 2,537, 2,713, 2,806. French Bien 4, 6-inch guns, 2,249, 2,360, 2,536, 2,616. Prismatic amide, 2,218, 2,342, 2,511, 2,574. Underscore 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 energies represented by above velocities. Underscore 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 foot tons foot tons foot tons foot tons cordite 0.4 inch 5,413, 5,994, 6,950, 7,478, ballastite 0.3 inch cubes, 4,227, 4,754, 5,479, 5,852, French bien, 4,047, 4,463, 5,104, 5,460, prismatic amide, 3,507, 3,862, 4.460, 4,745. Underscore 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 underscore. And again, in speaking of his own experiments, he says, one 4.7-inch gun has fired 1,219 rounds, and another 953, all with full charges of cordite, while a 6-inch gun has fired 588 rounds with full charges, of which 355 were cordite. In the whole of these guns, so far as I can judge, the erosion is certainly not greater than with ordinary powder, and differs from it remarkably in appearance. With ordinary powder, a gun, when much eroded, is deeply furrowed, these furrows having a great tendency to develop into cracks, and presents much the appearance in miniature of a very roughly plowed field. With cordite, on the contrary, the surface appears to be pretty smoothly swept away, while the length of the surface eroded is considerably less. Illustration: Figure 39. Comparative pressure curves of cordite and black powder. A. Charge 48 pounds. Powder. B. Charge 13 pounds. 4 ounces cordite. C. Charge 13 pounds. 4 ounces powder. Weight of projectile 100 pounds. In 6-inch gun. MB cordite equals 1960 feet seconds. The pressures given by cordite compared with those given by black powder in the 6-inch gun will be seen upon reference to Figure 39, which is taken from Professor V. B. Lewis's paper, Read Before the Society of Arts, and due to Dr. W. Anderson, FRS, the Director General of Ordnance Factories. It has been found that the erosive effect is in direct proportion to the nitroglycerin present. The cordite MD, which contains only 30% nitroglycerin, gives only about half the erosive effect of the old service cordite. With regard to the heating effect of cordite and cordite MD on a rifle, Mr. T. W. Jones made some experiments. He fired 50 rounds of .303 cartridges in 15 minutes in the service rifle. Cordite raised the temperature of the rifle 270 degrees Fahrenheit, and cordite MD 160 degrees Fahrenheit. only. With regard to the effect of heat upon cordite, there is some difference of opinion. Dr.W. Anderson FRS says that there is no doubt that the effect of heat upon cordite is greater than upon black powder. At a temperature of 110 degrees Fahrenheit, the cordite used in the 4.7-inch gun is considerably affected as regards pressure. Colonel Barker, R.A., in reply to a question raised by Colonel Trench, R.A., at the Royal Artillery Institution, concerning the shooting qualities of cordite heated to a temperature of 110 degrees Fahrenheit, said, "Heating cordite and firing it hot undoubtedly does disturb its shooting qualities, but as far as we can see, not much more than gunpowder. I fear that we must always expect abnormal results with heated propellants, either gunpowder or cordite, and when fired hot, the increase in pressure and velocities will depend upon the heat above the normal or average temperature at which firing takes place." Colonel Barker also, in referring to experiments that had been made in foreign climates, said, "Climatic trials have been carried out all over the world, and they have so far proved eminently satisfactory. The Arctic cold of the winter in Canada, with the temperature below zero, and the tropical sun of India, have as yet failed to shake the stability of the composition, or abnormally injure its shooting qualities." Dr. Anderson is of opinion that cordite should not be stored in naval magazines near to the boilers. Professor Vivian B. Lewis, in his recent Cantor lectures before the Society of Arts, suggests that the magazines of warships should be water-jacketed, and maintained at a temperature that does not rise above 100 degrees Fahrenheit. Axite. This powder is manufactured by Messrs. Kynoch Limited, at their works at Whitton, Birmingham. The main constituents of cordite are retained although the proportions are altered, ingredients are added which impart properties not possessed by cordite, and the methods of its manufacture have been modified. The form has also been altered. Axite is made in the form of a ribbon, the cross-section being similar in shape to a double-headed rail. It is claimed for this powder that it does not corrode the barrel in the way cordite does, that with equal pressure it gives greatly increased velocity, and therefore flatter trajectory. That the effect of temperature on the pressure and velocity with axite is only half that with cordite. That the maximum flame temperature of axite is considerably less than that of cordite, and the erosive effect is therefore considerably less. That the deposit left in the barrel after firing axite cartridges reduces the friction between the bullet and the barrel. It is therefore practicable to use axite cartridges giving higher velocities than can be employed with cordite, as with such velocities the latter would nickel the barrel by excessive friction. It is also claimed that the accuracy is greatly increased. The following results have been obtained with this same time, and under the same conditions. Axite cartridges with 200 grain bullets. Velocity 2726 fs, pressure 20.95 tons. Axite cartridges with 215 grain bullets. Velocity 2498 fs, pressure 19.24 tons. Axite service cartridges. Velocity 2179 fs, pressure 15.76 tons. Cordite service cartridges. Velocity 2010 fs, pressure 15.67 tons. 5 rounds from the service axite and service cordite were placed in an oven and heated to a temperature of 110 degrees Fahrenheit for 1 hour, and were then fired for pressure. The following results were obtained. Axite, cordite, before heating 15.76 tons per square in. 15.67 tons per square in. After 16.73, 17.21, underscore 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 underscore. Increase 0.97 equals 6.1%, 1.54 equals 9.8%. Average velocities. Before heating 2150 fs, 2030 fs after 2180, 2090. Underscore 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 underscore. Increase 30 fs equals 1.5%, 60.0 fs equals 3%. In order to show the accuracy given by axite, 7 rounds were fired from a machine rest at a target fixed at 100 yards from a rifle. 6 of the 7 shots could be covered by a penny piece, the other being just outside. In order to ascertain the relative heat imparted to a rifle by the explosion of axite and cordite, 10 rounds each of axite and cordite cartridges were fired from a .303 rifle, at intervals of 10 seconds, the temperature of the rifle barrel being taken before and after each series. The rise in temperature of the rifle barrel with axite was 71 degrees Fahrenheit. With cordite was 89 degrees Fahrenheit. Difference in favor of axite 18 degrees Fahrenheit, equals 20.2%. The lubricating action of axite is shown by the fact that a series of cordite cartridges fired from a .303 rifle in the ordinary way, followed by a second series, the barrel being lubricated between each shot by firing an axite cartridge alternately with the cordite cartridge. The mean velocity of the first series of cordite cartridges was 1,974 feet per second. The mean velocity of the second series was 2,071 feet per second. The increased velocity due to the lubricating effect of axite therefore was 97 feet per second. This powder, it is evident, has very many very excellent qualities, and considerable advantages over cordite. It is understood that axite is at present under the consideration of the British government for use as the service powder. Ballastite. Nobel's powder, known as ballastite, originally consisted of a camphorated blasting gelatin, and was made of 10 parts of camphor and 100 parts of nitroglycerin, to which 200 parts of benzol were then added, and 50 parts of nitro-cotton, soluble, were then steeped in this mixture, which was then heated to evaporate off the benzol, and the resulting compound afterwards passed between steam-heated rollers, and formed into sheets, which were then finally cut up into small squares or other shapes as convenient. The camphor contained in this substance was, however, found to be a disadvantage, and its use discontinued. The composition is now 50% of soluble nitro-cotton and 50% of nitroglycerin. As nitroglycerin will not dissolve its own weight of nitro-cotton, even the soluble variety, benzol is used as a solvent, but is afterwards removed from the finished product, just as the acetone is removed from cordite. About 1% of diphenylamine is added for the purpose of increasing its stability. The color of ballastite is a darkish brown. It burns in layers when ignited, and emits sparks. The size of the cubes into which it is cut is a 0.2-inch cube. Its density is 1.6. It is also, by means of a special machine, prepared in the form of sheets, after being mixed in a wooden trough fitted with double zinc plates, and subjected to the heating process by means of hot water pipes. It is passed between hot rollers, and rolled into sheets, which are afterwards put through a cutting machine and granulated. Sir A. Nobel's experiments, with this powder gave the following results. The charge used was 5 pounds, 8 ounces, the size of the cubes being 0.2 inch. The mean crusher gauge pressure was 14.3 tons per square inch, maximum 2,210, minimum 2,142, and average pressure 2,180 atmospheres. The muzzle velocity was 2,140 foot-seconds, and the muzzle energy 1,429 foot-tons. A gram of ballastite generates 615 cc of permanent gases, and gives rise to 1,365 grm. Units of heat. Ballastite is manufactured at Ardare in Scotland, at Chilworth in Surrey, and also in Italy, under the name of phyllite, which is in the form of cords instead of cubes. The ballastite made in Germany contained more nitrocellulose, and the finished powder was coated with graphite. Its use has been discontinued as the service powder in Germany, but it is still the service powder in Italy. Footnote A. Prop. Roy. SOC, Volume 52, page 315. U.S. Naval Smokeless Powder. This powder is manufactured at the U.S. Naval Torpedo Station for use in guns of all calibers in the U.S. Navy. It is a nitrocellulose powder, a mixture of insoluble and soluble nitrocellulose together with the nitrates of barium and potassium, and a small percentage of calcium carbonate. The proportions in the case of the powder for the 6-inch rapid-fire gun are as follows: mixed nitrocellulose, soluble and insoluble, 80 parts, barium nitrate 15 parts, potassium nitrate 4 parts, and calcium carbonate 1 part. The percentage of nitrogen contained in the insoluble nitrocellulose must be 13.30 plus or minus 0.15, and in the soluble 11.60 plus or minus 0.15, and the mean nitration strength of the mixture must be 12.75% of nitrogen. The solvent used in making the powder is a mixture of ether, SPGR 0.720, 2 parts, and alcohol, 95%, by volume, 1 part. The process of manufacture is briefly as follows. Frowny face A. The soluble and insoluble nitrocellulose are dried separately at a temperature from 38 degrees to 41 degrees Celsius, until they do not contain more than 0.1% of moisture. The calcium carbonate is also finely pulverized and dried, and is added to the mixed nitrocelluloses after they have been sifted through a 16-mesh sieve. The nitrates are next weighed out and dissolved in hot water, and to this solution is added the mixture of nitrocelluloses and calcium carbonate with constant stirring until the entire mass becomes a homogeneous paste. This pasty mass is next spread upon trays and re-dried at a temperature between 38 degrees and 48 degrees Celsius, and when thoroughly dry it is transferred to the kneading machine. The ether-alcohol mixture is now added, and the process of kneading begun. It has been found by experiment that the amount of solvent required to secure thorough incorporation is about 500 cc to each 500 grms of dried paste. To prevent loss of solvent due to evaporation, the kneading machine is made vapor light. The mixing or kneading is continued until the resulting grayish-yellow paste is absolutely homogeneous so far as can be detected by the eye, which requires from 3 to 4 hours. The paste is next treated in a preliminary press, known as the block press, and is actuated by hydraulic power, where it is pressed into a cylindrical mass of uniform density and of such dimensions as to fit it for the final or powder press. The cylindrical masses from the block press are transferred to the final press, whence they are forced out of a die under a pressure of about 500 pounds per square inch. As it emerges from the final press, the powder is in the form of a ribbon or sheet, the width and thickness of which is determined by the dimensions of the powder chamber of the gun in which the powder is to be used. On the inner surface of the die are ribs extending in the direction of the powder as it emerges from the press, the object of these ribs being to score the sheets or ribbons in the direction of their length, so that the powder will yield uniformly to the pressure of the gases generated in the gun during the combustion of the charge. The ribbon or sheet is next cut into pieces of a width and length corresponding to the chamber of the gun for which it is intended, the general rule being that the thickness of the grain, when perfectly dry, shall be 15 1/1000ths (0.015) of the caliber of the gun, and the length equal to the length to fit the powder chamber. Thus, in case of the 6-inch rapid-fire gun, the thickness of the grain, or sheet, is 0.09 of an inch and the length 32 inches. The sheets are next thoroughly dried, first between sheets of porous blotting paper under moderate pressure and at a temperature between 15 degrees Celsius and 21.5 degrees Celsius, for 3 days, and then exposed to free circulation of the air at about 21.5 degrees Celsius, for 7 days, and finally subjected for a week or longer to a temperature not exceeding 38 degrees Celsius, until they cease to lose weight. Footnote A. Lieutenant W. Walk. Lectures on Explosives. Page 330. The sheets, when thoroughly dried, are of a uniform yellowish-gray color, and of the characteristic colloidal consistency. They possess a perfectly smooth surface, and are free from internal blisters or cracks. The temperature of ignition of the finished powder should not be below 172 degrees Celsius, and when subjected to the heat or stability test, it is required to resist exposure to a temperature of 71 degrees Celsius for 30 minutes without causing discoloration of the test paper. W.A. Powder. This powder is made by the American Smokeless Powder Company, and it was proposed for use in the United States Army and Navy. It is made in several grades according to the ballistic conditions required. It consists of insoluble gun cotton and nitroglycerin, together with metallic nitrates and an organic substance used as a deterrent or regulator. The details of its manufacture are very similar to those of cordite, with the exception that the nitroglycerin is dissolved in a portion of the acetone before it is added to the gun cotton. The powder is pressed into solid threads, or tubular cords or cylinders, according to the caliber of the gun in which the powder is to be used. As the threads emerge from the press, they are received upon a canvas belt, which passes over steam-heated pipes and deposited in wire baskets. The larger cords or cylinders are cut into the proper lengths and exposed upon trays in the drying house. The powder for small arms is granulated by cutting the threads into short cylinders, which are subsequently tumbled, dusted, and if not perfectly dry, again placed upon trays in the drying house. Before being sent away from the factory, from 5 to 10 lots of 500 pounds, each are mixed in a blending machine, in order to obtain greater uniformity. The color of the WA powder is very light gray, the grains are very uniform in size, dry and hard. The powder for larger guns is of a yellowish color, almost translucent, and almost as hard as vulcanite. The powder is said to be unaffected by atmospheric or climatic conditions, to be stable, and to have given excellent ballistic results. It is not sensitive to the impact of bullets, and when ignited burns quietly, unless strongly confined. Turning now to the smokeless powders, in which the chief ingredient is nitrocellulose in some form, either gun cotton or nitrolignin, and c. One of the first of these was Prentice's gun cotton, which consisted of nitrate paper 15 parts, mixed with 85 parts of unconverted cellulose. It was rolled into a cylinder. Another was Punchin's gun cotton powder, which consisted of gun cotton soaked in a solution of sugar, and then mixed with a nitrate, such as sodium or potassium nitrate. Barium nitrate was afterwards used, and the material was granulated, and consisted of nitrate gun cotton. The explosive known as tonite, made at Faversham, was at first intended for use as a gunpowder, but is now only used for blasting. The Schulze powder, one of the earliest of the successful powders introduced into this country, was Schulze's powder, the invention of Colonel Schulze, of the Prussian artillery, and is now manufactured by the Schulze Gunpowder Company Limited, of London. The composition of this powder, as given in the Dictionary of Explosives, by the late Colonel Kundal, is as follows. Soluble nitrolignin 14.83%, insoluble 23.36, lignin unconverted 13.14, nitrates of K and Ba 32.35, paraffin 3.65, matters soluble in alcohol 0.11, moisture 2.56. This powder was the first to solve the difficulty of making a smokeless, or nearly smokeless powder which could be used with safety and success in small arms. Previously, gun cotton had been tried in various forms, and in nearly every instance disaster to the weapon had followed, owing to the difficulty of taming the combustion to a safe degree. But about 1866 Colonel Schulze produced, as the result of experiments, a nitrate wood fiber which gave great promise of being more pliable and more easily regulated in its burning than gun cotton, and this was at once introduced into England, and the Schulze Gunpowder Company Limited was formed to commence its manufacture, which it did in the year 1868. During the years from its first appearance, Schulze gunpowder has passed through various modifications. It was first made in a small cubical grain formed by cutting the actual fiber of timber transversely, and then breaking this veneer into cubes. Later on improvements were introduced, and the wood fiber so produced was crushed to a fine degree, and then reformed into small irregular grains. Again, an advance was made in the form of the wood fiber used, the fiber being broken down by the action of chemicals under high temperature, and so producing an extremely pure form of woody fiber. The next improvement was to render the grains of the powder practically waterproof and less affected by the atmospheric influences of moisture and dryness, and the last improvement to the process was that of hardening the grains by means of a solvent of nitrolignin, so as to do away with the dust that was often formed from the rubbing of the grains during transit. Minor modifications have from time to time also been made, in order to meet the gradual alteration which has taken place during this long period in the manufacture of sporting guns and cartridge cases to be used with this powder, but through all its evolution this company has adhered to the first idea of using woody fiber in preference to cotton as the basis of their smokeless powder. as experience has confirmed the original opinion that a powder can be thus made less sensitive to occasional differences in loading, and more satisfactory all round than when made from the cotton base. The powder has always been regulated so that bulk for bulk it occupies the same measure as the best black powder, and as regards its weight, just 1/2 of that of black. The process of manufacture of this powder is briefly as follows. Wood of clean growth is treated by the well-known sulfite process for producing pure woody fiber, which is very carefully purified, and this, after drying, is steeped in a mixture of nitric and sulfuric acids, to render it a nitro compound and the explosive base of the powder. This nitro compound is carefully purified until it stands the very high purity requirements of the Home Office, and is then ground with oxygen-bearing salts, NC, and the whole is formed into little irregular shaped grains of the desired size, which grains are dried and hardened by steeping in a suitable solvent for the nitro compound, and after finally drying, sifting, NC. The powder is stored in magazines for several months before it is issued. When issued, a very large blend is made of many tons weight, which ensures absolute uniformity in the material. There is in England a standard load adopted by every one for testing a sporting powder. This charge is 42 grains of powder and 1 1/8 ounces No. 6 shot. This shot fired from a 12-bore gun, patterns being taken at 40 yards, the velocity at any required distance. The standard muzzle velocity of Schulze gunpowder is 1,220 feet per second. The mean 40 yards ditto is 875 feet per second. The mean 20 yards ditto is 1,050 feet per second. The internal pressure not to exceed 3.5 tons. This company also manufactures a new form of powder, known as Imperial Schulze. It is a powder somewhat lighter in gravity. 33 grains occupies the bulk charge, as compared with the 42 grains of the old. It follows in its composition much the lines of the older powder, but it is quite free from smoke, and leaves no residue whatever. The E.G. powder. This is one of the oldest of the nitro powders. It was invented by Reed and Johnson in 1882. It is now manufactured by the E.G. Powder Company Limited, at their factory near Dartford, Kent, and in America by the Anglo-American E.G. Powder Company, at New Jersey. The basis of this powder is a fine form of cellulose, derived from cotton, carefully purified, and freed from all foreign substances, and carefully nitrate. Its manufacture is somewhat as follows. Pure nitro cotton, in the form of a fine powder, is rotated in a drum, sprinkled with water, and the drum rotated until the nitro cotton has taken the form of grains. The grains are then dried and moistened with ether alcohol, whereby the moisture is gelatinized, and afterwards colored with orine, which gives them an orange color. They are then dried and put through a sieve, in order to separate the grains which may have stuck together during the gelatinizing process. Since its introduction soon after 1881, E.G. powder has undergone considerable modifications, and is now a distinctly different product from a practical point of view. It is now and has been since 1897 what is known as a 33-grain powder, that is to say, the old standard charge of 3 drams by measure for a 12-bore gun weighs 33 grains, as compared with 42 grains for the original E.G. and other nitro powders. This improvement was effected by a reduction of the barium nitrate and the use of nitrocellulose of a higher degree of nitration, and also more gelatinization in manufacture. The granules are very hard, and resist moisture to an extent hitherto unattainable by any bulk powder. Irregularities of pressure and loading have also a minimum effect by reason of the hardness of the grains. The coloring matter used is orine, and the small quantity of nitrate used is the barium salt. The powder is standardized for pressure velocity with Boulogne chronograph, a pattern and gravimetric density by elaborate daily tests, and is continually subjected to severe trials for stability under various conditions of storage, the result being that it may be kept for what in practice amount to indefinite periods of time, either in cartridges or in bulk without any alteration being feared. The EC powders are used in sporting guns. No. 1 and No. 2 EC are not at present manufactured, EC No. 3 having taken their place entirely. Since 1890 these powders have been manufactured under the Borland-Johnson patents, these improved powders being for some time known as the JB powders. The EC No. 1 was superseded by the EC No. 2, made under the Borland-Johnson patents, and this in its turn by the EC No. 3, in 1897. Footnote A, invented in 1869 by Major Le Belange, Belgian artillery. It is intended to record the mean velocity between any 2 points, and from its simplicity and accuracy is largely employed. Other forms have been invented by Captain Brieger, French Artillerie de la Marine, and Captain Holden R.A. Indurite is the invention of Professor C. Monroe, of the U.S. Naval Torpedo Station. It is made from insoluble nitro-cotton, treated in a particular manner by steam, and mixed with nitrobenzene. The DuPont powder is very similar to Indurite. M.E. Leonard, of the United States, invented a powder consisting of 75 parts of nitroglycerin, 25 parts of guncotton, 5 parts of lycopodium powder, and 4 parts of urea crystals dissolved in acetone. The French smokeless powder, Viel Poudre, Poudre B, used in the Lebel rifle, is a mixture of nitrocellulose and tannin, mixed with barium and potassium nitrates. It gives a very feeble report, and very little bluish smoke. The Nobel Company is said to be perfecting a smokeless powder in which the chief ingredients are nitroamido and trinitrobenzene. C.O. Lundholm has patented, U.S. Pat. 701,591, 1901, a smokeless powder containing nitroglycerin 30, nitrocellulose 60, diamylphthalate 10, or diamylphthalate 5, and mineral jelly 5. The diamylphthalate is added, with or without the mineral jelly, to nitroglycerin and nitrocellulose. Walsrode powder. The smokeless powder known as Walsrode powder consists of absolutely pure gelatinized nitrocellulose, grained by a chemical, not a mechanical process. Consequently, the grains do not need facing with gelatin to prevent their breaking up, as is the case with many nitro powders. For this same reason, as well as from the method of getting rid of the solvent used, the Walsrode has no tendency whatever to absorb moisture. In fact, it can lie in water for several days, and when taken out and dried again at a moderate temperature will be found as good as before. Nor is it influenced by heat, whether dry or damp, and it can be stored for years without being in the least affected. It is claimed also that it heats the barrels of guns much less than black powder, and does not injure them. The standard charge is 30 grains, and it is claimed that with this charge Walsrode powder will prove second to none. A large cap is necessary, as the grains of this powder are very hard, and require a large flame to properly ignite them. In loading cartridges for sporting purposes, an extra felt wad is required to compensate for the small space occupied by the charge, but for military use the powder can be left quite loose. The gas pressure of this powder is low, in several military rifles only 1/2 that of other nitros, and the recoil consequently small, and it is claimed that with the slight increase of the charge, from 29 to 30 grs, both penetration and initial velocity will be largely increased, whilst the gas pressure and recoil will not be greater. This powder was used at Bisley, at the National Rifle Association's meeting, with satisfactory results. It is made by the Walsrode Smokeless and Waterproof Gunpowder Company. The nitro-cotton is gelatinized by means of acetic ether, and the skin-produced retards burning. The nitro-cotton is mixed with acetic ether, and when the gelatinization has taken place, the plastic mass is forced through holes in a metal plate into strips, which are then cut up into pieces the size of grains. The MH Walsrode powder is a leaflet powder, light in color, about 40 grains of which give a muzzle velocity of 1,350 feet and a pressure of 3 tons. It is, like the other Walsrode powders, waterproof and heatproof. Coupal powder is manufactured by Messrs. Coupal and Company at their extensive powder works in Belgium. It consists of nitro-jute or nitro-cotton, with or without nitrates, treated with a solvent to form a gelatinized mass. There are a great many varieties of this powder. One kind is in the form of little squares. Another, for use in Hotchkiss guns, is formed into 3 mm cubes, and is black. Other varieties are colored with aniline dyes of different colors. Amberite is a nitrocellulose powder of the 42-grain type of sporting gunpowders, and is manufactured by Messrs. Curtis's and Harvey Limited, at their smokeless powder factory, Tunbridge, Kent. It consists of a mixture of nitrocellulose, paraffin, barium, nitrate, and some other ingredients. It is claimed for this powder that it combines hard shooting with safety, great penetration, and moderate strain on the gun. It is hard and tough in grain, and may be loaded like black powder, and subjected to hard friction without breaking into powder, that it is smokeless, and leaves no residue in the gun. The charge for 12 bores is 42 grains by weight, and 1 1/8 ounces or 1 1/16 ounces shot. The powders known as Cannonite, A, and Ruby powder, also manufactured by Messrs. Curtis's and Harvey Limited, are analogous products having the same general characteristics. Footnote A. For further details of Cannonite, see first edition, page 181. Smokeless diamond, also manufactured by the above-mentioned firm, is a nitrocellulose powder of the 33-grain type of sporting gunpowders. It was invented by Mr. H. M. Chapman. The manufacture of smokeless diamond, as carried out at Tunbridge, is shortly as follows. The gun cotton, which is the chief ingredient of this powder, is first stoved, then mixed with certain compounds which act as moderators, and after the solvents are added, is worked up into a homogeneous plastic condition. It then undergoes the processes of granulation, sifting, dusting, drying, and glazing. In order to ensure uniformity, several batches are blended together and stored for some time before being issued for use. It is claimed for this powder that it is quick of ignition, the quickness being probably due to the peculiar structure of the grains which, when looked at under the microscope, have the appearance of coke. The charge for a 12-bore is 33 grains and 1 1/16 ounces shot, which gives a velocity of 1,050 feet per second and a pressure of 3 tons per square inch. Grainer's powder consists of nitrocellulose, nitrobenzol, graphite, and lampblack. B.N. Powder. This powder is of a light gray or drab color, perfectly opaque, and rough to the touch. It consists of a mixture, nitrocellulose, and the nitrates of barium and potassium. Its composition is as follows. Insoluble nitrocellulose 29.13 parts, soluble nitrocellulose 41.31. Barium nitrate 19.00. Potassium nitrate 7.97. Sodium carbonate 2.03. Volatile matter 1.43. This powder is a modification of the poudre B, or Vieille's powder invented for use in the Lebel rifle, and which consisted of a mixture of the nitrocelluloses with paraffin. Vaughan Foster's powder contains nothing but pure gelatinized nitrocellulose, together with a small quantity of carbonate of lime. The German Troisdorf powder is a mixture of gelatinized nitrocellulose, with or without nitrates. Maximite is the invention of Mr. Hudson Maxim, and is a nitro compound, the base being gun cotton. The exact composition and method of manufacture are, however, kept secret. It is made by the Columbia Powder Manufacturing Company, of New York, and in 2 forms, one for use as a smokeless rifle powder, and the other for blasting purposes. Wetteren powder. This powder was manufactured at the Royal Gunpowder Factory at Wetteren, and used in the Belgian service. Originally it was a mixture of nitroglycerin and nitrocellulose, with amyl acetate as solvent. Its composition has, however, been altered from time to time. One variety consists chiefly of nitrocellulose, with amyl acetate as solvent. It is of a dark brown color, and of the consistency of indiarubber. It is rolled into sheets and finally granulated. Henrite is a nitrocellulose powder. Normal powder, the Swedish powder known as normal. Smokeless powder, and manufactured by the Swedish Powder Manufacturing Company, of Landskrona, Sweden, and used for some years past in the Swiss Army, is made in 4 forms. For field guns of 8.4 caliber, it is used in the form of cylindrical grains of a yellow color, of a diameter of 0.8 to 0.9 mm and density of 0.790. About 840 grains of it go to 1 gun. For rifles, it is used in the form of gray squares, density 0.750, and 1 grm. Equals about 1,014 grains. 100 rounds of this powder, fired in 18 minutes, raised the temperature of the gun barrel 284 degrees Fahrenheit. A nitroglycerin powder, fired under the same conditions, gave a temperature of 464 degrees Fahrenheit. This powder is said to keep well. A sample kept 3.5 years gave as good results as when first made, is easy to make, very stable, ignites easily, not very sensitive to shock or friction, is very light, and c. 800 rounds fired from a heavy gun produced no injury to the interior of the weapon. Samples kept for 11 months in the moist atmosphere of a cellar, when fired gave a muzzle velocity of 1,450 feet seconds, and pressure of 1,312 atmospheres, and the moisture was found to have risen from 1.2 to 1.6%. After 23 months in the damp it contained 2% moisture, gave a muzzle velocity of 1,478 feet seas, and pressure of 1,356 atmospheres. In a 7.5 mm rifle, 13.8 grm bullet, and charge of 2 grms, it gives a muzzle velocity of 2,035 feet seconds, and a pressure of 2,200 atmospheres. In the 8.4 cm field gun, with charge of 600 grms, and projectile of 6.7 kilograms, muzzle velocity was equal to 1,640 feet seconds, and pressure 1,750. A sample of the powder for use in the .303 m rifle, lately analyzed by the author, gave the following result. Gun cotton 96.21%, soluble cotton 1.80, non-nitrate cotton trace, resin and other matters 1.99, underscore 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 100.00. The various forms of powder invented and manufactured by Mr. C.F. Hengst are chiefly composed of nitrate straw that has been finely pulped. The straw is treated first with acids and afterwards with alkalis, and the result is a firm fibrous substance which is granulated. It is claimed that this powder is entirely smokeless and flameless, that it does not foul the gun nor heat the barrel, and is at the same time 150% stronger than black powder. The German Troisdorf powder consists of nitrocellulose that has been gelatinized together with a nitrate. Kauf's powder is also gelatinized with nitrocellulose. The powders invented by Mr. E. J. Rives contain nitroglycerin, nitrocotton, castor oil, paper pulp, and carbonate of magnesia. Maxim powder contains both soluble and insoluble nitrocellulose, nitroglycerin, and carbonate of soda. The smokeless powder made by the Dynamite Aktiengesellschaft Nobel consists of nitrostarch 70 to 99 parts, and of D or trinitrobenzene 1 to 30 parts. An American wood powder, known as Brackett's sporting powder, consists of soluble and insoluble nitrolignin, mixed with charred lignin, humus, and nitrate of soda. Mr. F. H. Snyder, of New York, is the inventor of a shell powder known as the Snyder-Explosive, consisting of 94% nitroglycerin, 6% of soluble nitrocotton, and camphor, which is said to be safe in use. Experiments were made with it in a 6-inch rifled gun, fired at a target 220 yards away, composed of 12 1-inch steel plates welded together, and backed with 12-inch and 14-inch oak beams, and weighing 20 tons. The shots entirely destroyed it. The charge of explosive used was 10 pounds in each shell. Comparative tests of black and nitro powders from American Field. The results given in table below were obtained at the German Shooting Association's grounds at Köpenick, Berlin. Penetration was calculated by placing frames, each holding 5 cards of 1 mm in thickness, equals .03937 inch, and 3 inches apart, in a B-line, at distances of 20 inches. Velocity, pattern, and penetration were taken at 40 yards from the muzzle of a 12-gauge chokebore double-barrel gun. Gas pressure was taken by a special apparatus. All shells were loaded with 1 1/8 ounces of number 3 shot, equal to 120 pellets, and the number given below represents the average number in the 30-inch pattern. The number of sheets passed through gives the average penetration. 1 atmosphere equals pressure equal to 1 kilogram, 2.2 pounds, on the square centimeter, hence 1,000 atmospheres equal 2,200 pounds, on the square centimeter. The EC, Schulze, and Walsrode powders were loaded in LC's special shells, 2.5 inches long. The averages were taken from a large number of shots, and the same series of shots fired under precisely the same conditions. Underscore 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 gas, pressure, velocity, pattern, penetration. Underscore 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 atmospheres, meters, sheets, fine-grained black, powder, standard, charge, 514.2, 280, 78.6 equals 66%, 19.0, coarse-grained, black powder, standard charge, 473.4, 281.4, 78.2 equals 65%, 19.4, Schulze powder, 42 grains, 921.0, 290.0, 64.2 equals 54%, 20.2, Schulze powder, 45 grains, 1052.8, 305.8, 52.2 equals 42%, 20.6, e.g. smokeless, 42 grains, 920.2, 298.4, 81.4 equals 67%, 18.8. Walsrode, 29 grains, 586.4, 280.6, 83.0 equals 69%, 19.0. Underscore 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 barometer 760 millimeters, thermometer 30 degrees Celsius, hydrometer equals 65, wind SW. Picric powders. The chief of these is melinite, the composition of which is not known with certainty. It is believed to be melted picric acid together with guncotton dissolved in acetone or ether alcohol. Walk gives the following proportions: 30 parts of trinitrocellulose dissolved in 45 parts of ether alcohol, 2:1, and 70 parts of fused and pulverized picric acid. The ether alcohol mixture is allowed to evaporate spontaneously, and the resulting cake granulated. The French claim, however, that the original invention has been so modified and perfected that the melinite of today cannot be recognized in the earlier product. Melinite has a yellow color, is almost without crystalline appearance, and when ignited by a flame or heated wire, it burns with a reddish-yellow flame, giving off copious volumes of black smoke. Melinite as at present used is said to be a perfectly safe explosive, both as regards manufacture, handling, and storage. Lyddite A, the picric acid explosive used in the British service, is supposed to be identical with the original melinite, but its composition has not been made public. Footnote A. Skymos, the Japanese powder, is stated to be identical with lyddite and melinite chem. Center, 1906, 1, 1196. Picrates are more often used than picric acid itself in powders. One of the best known is Brugger's powder, which is a mixture of 54 parts of picrate of ammonia and 45 parts of saltpetre. It is stable and safe to manufacture. It has been used in the Shaspo rifle with good results, gives little smoke, and a small residue only of carbonate of potash. The next in importance is Designol's powder, made at Buchan, consisting of picrate of potash, saltpetre, and charcoal. It was made in 3 varieties, viz., for rifles, big guns, and torpedoes and shells. These powders are made much in the same way as gunpowder. The advantages claimed for them over gunpowder are greater strength, comparative absence of smoke, and freedom from injurious action on the bores of guns. Emmonsite is the invention of Dr. Stephen Emmons, of the United States. The Emmons crystals are produced by treating picric acid with fuming nitric acid of specific gravity of 1.52. The acid dissolves with the evolution of red fumes. The liquid, when cooled, deposits crystals stated to be different to picric acid, and lustrous flakes. These flakes, when heated in water, separate into 2 new bodies. One of these enters into solution and forms crystals unlike the first, while the other body remains undissolved. The acid crystals are used mixed with the nitrate. Emmonsite has been subjected to experiment by the direction of the U.S. Secretary for War, and found satisfactory. A sample of emmonsite, in the form of a coarse powder, was first tried in a pistol, and proved superior in propelling power to ordinary gunpowder. When tested against explosive gelatin, it did very good work in shattering iron plates. It is claimed for this explosive that it enjoys the distinction of being the only high explosive which may be used both for firearms and blasting. This view is supported by the trials made by the American War Office authorities, and shows emmonsite to be a useful explosive both for blasting and as a smokeless powder. Its explosive power, as tested, is 283 tons per square inch, and its specific gravity is 1.8. Abel proposed to use picric acid for filling shells. His picric powder consisted of 3 parts of saltpetre, and 2 of picrate of ammonia. Victorite consists of chloride of potash, picric acid, and olive oil, and with occasionally some charcoal. It has the form of a coarse yellowish-gray powder, and leaves an oily stain on paper, and it is very sensitive to friction and percussion. The composition is as follows: Clo_3 equals 80 parts, picric acid 110 parts, saltpetre 10 parts, charcoal 5 parts. It is not manufactured in England. Skyner's powder is very similar to Victorite in composition, but contains resin. A list of the chief picric powders will be found in the late Colonel J. P. Cundall, R.A.'s Dictionary of Explosives. Chapter 7. Analysis of Explosives. Kieselguhr dynamite, gelatin compounds, tonite, cordite, vaseline, acetone, scheme for analysis of explosives, nitro-cotton, solubility test, non-nitrate cotton, alkalinity, ash and inorganic matter, determination of nitrogen, lunge, champion and pellets, Schulze-Tiemann, and Kjeldal's methods, celluloid, picric acid and picrates, resinous and tarry matters, sulfuric acid and hydrochloric acid and oxalic acid, nitric acid, inorganic impurities, general impurities and adulterations, potassium picrate, and C. Picrates of the alkalids, analysis of glycerin, residue, silver test, nitration, total acid equivalent, neutrality, free fatty acids, combined fatty acids, impurities, oleic acid, sodium chloride, determination of glycerin, waste acids, sodium nitrate, mercury fulminate, cap composition, table for correction of volumes of gases, for temperature and pressure. Kieselguhr dynamite. The material generally consists of 75% of nitroglycerin and 25% of the infusorial earth kieselguhr. The analysis is very simple, and may be conducted as follows: weigh out about 10 grams of the substance, and place over calcium chloride in a desiccator for some 6 to 8 days, and then reweigh. The loss of weight gives the moisture. This will generally be very small, probably never more than 1%, and usually less. Mr. James O. Handy, in order to save time, proposes to dry dynamite in the following manner. He places 1 grm of the material in a porcelain crucible 1 inch in diameter. The crucible is then supported at the bottom of an extra wide-mouthed bottle of about 600 cc capacity. Air, which has been dried by bubbling through strong sulfuric acid, is now drawn over the surface of the sample for 3 hours by means of an ordinary aspirator. The air should pass approximately at the rate of 10 cc per second. The tube by which the dry air enters the bottle extends to within 1 inch of the crucible containing the dynamite. An empty safety bottle is connected with the inlet, and another with the outlet of the wide-mouthed bottle. The first guards against the mechanical carrying over by the air current of sulfuric acid from the acid bottle into the sample, whilst the second prevents spasmodic outbursts of water from the exhaust from reaching the sample. The method also gave satisfactory results with nitroglycerin. The dry substance may now be wrapped in filter paper, the whole weighed, and the nitroglycerin extracted in the Soxhlet apparatus with ether. The ether should be distilled over at least 24 times. I have found, however, that much quicker, and quite as accurate, results may be obtained by leaving the dynamite in contact with ether in a small Erlenmeyer flask for 24 hours. Leaving it overnight is better, and decanting, and again allowing the substance to remain in contact with a little fresh ether for an hour, and finally filtering through a weighed filter, drying at 100 degrees Celsius, and weighing. This gives the weight of the kieselguhr. The nitroglycerin must be obtained by difference, as it is quite useless to evaporate down the ethereal solution to obtain it, as it is itself volatile to a very considerable extent at the temperature of evaporation of the ether, and the result, therefore, will always be much too low. The dry guhr can, of course, be examined, either qualitatively or quantitatively, for other mineral salts, such as carbonate of soda, and c. An actual analysis of dynamite No. 1 made by the author at Hale gave moisture 0.92%, kieselguhr 26.15%, and nitroglycerin 72.93%, the last being obtained by difference. Nitroglycerin. It is sometimes desired to test an explosive substance for nitroglycerin. If an oily liquid is oozing from the substance, soak a drop of it in filter paper. If it is nitroglycerin, it will make a greasy spot. If the paper is now placed upon an iron anvil, and struck with an iron hammer, it will explode with a sharp report. If lighted, it burns with a yellowish to greenish flame, emitting a crackling sound, and placed upon an iron plate and heated from beneath, it explodes sharply. If a few drops of nitroglycerin are placed in a test tube, and shaken up with methyl alcohol, previously tested with distilled water, to see that it produces no turbidity, and filtered, on the addition of distilled water, the solution will become milky, and the nitroglycerin will separate out, and finally collect at the bottom of the tube. If to a solution of a trace of nitroglycerin in methyl alcohol, a few drops of a solution, composed of 1 volume of aniline, and 40 volumes sulfuric acid, 1.84, be added, a deep purple color will be produced. This color changes to green upon the addition of water. If it is necessary to determine the nitroglycerin quantitatively in an explosive, the scheme on page 213 may be followed. Ether is the best solvent to use. Nitrogen should be determined in the nitrometer. Gelatin compounds. The simplest of these compounds is, of course, blasting gelatin, as it consists of nothing but nitrocotton and nitroglycerin, the nitrocellulose being dissolved in the glycerin to form a clear jelly, the usual proportions being about 92% of nitroglycerin to 8% nitrocotton, but the cotton is found as high as 10% in some gelatins. Gelatin dynamite and gelignite are blasting gelatins, with varying proportions of wood pulp and saltpetre, No_3, mixed with a thin blasting gelatin. The method of analysis is as follows: weigh out 10 grams of the substance, previously cut up into small pieces with a platinum spatula, and place over calcium chloride in a desiccator for some days. Reweigh. The loss equals moisture. This is generally very small. Or Handy's method may be used. The dried sample is then transferred to a small thistle-headed funnel which has been cut off from its stem, and the opening plugged with a little glass wool, and round the top rim of which a piece of fine platinum wire has been fastened, in order that it may afterwards be easily removed from the sock-slit tube. The weight of this funnel and the glass wool must be accurately known. It is then transferred to the sock-slit tube and exhausted with ether, which dissolves out the nitroglycerin. The weighed residue must afterwards be treated in a flask with ether alcohol to dissolve out the nitro-cotton. But the more expeditious method, and one quite as accurate, is to transfer the dried gelatin to a conical Erlenmeyer flask of about 500 cc capacity, and add 250 cc of a mixture of ether alcohol, 2 ether to 1 alcohol, and allow to stand overnight. Sometimes a further addition of ether alcohol is necessary. It is always better to add another 300 cc, and leave for 20 minutes or so after the solution has been filtered off. The undissolved portion, which consists of wood pulp, potassium nitrate, and other salts, is filtered off through a linen or paper filter, dried and weighed. Solution. The ether alcohol solution contains the nitro-cotton and the nitroglycerin in solution. A. To this solution add excess of chloroform. About 100 cc will be required, when the nitrocellulose will be precipitated in a gelatinous form. This should be filtered off through a linen filter, and allowed to drain. It is useless to attempt to use a filter pump, as it generally causes it to set solid. The precipitated cotton should then be redissolved in ether alcohol, and again precipitated with chloroform. 20 cc of ether alcohol should be used. This precaution is absolutely necessary if the substance has been treated with ether alcohol at first instead of ether only, otherwise the results will be much too high, owing to the gelatinous precipitate retaining very considerable quantities of nitroglycerin. The precipitate is then allowed to drain as completely as possible, and finally allowed to dry in the air bath at 40 degrees Celsius, until it is easily detached from the linen filter by the aid of a spatula, and is then transferred to a weighed watch glass, replaced in the oven, and dried at 40 degrees Celsius, until constant in weight. The weight found, calculated upon the 10 grams taken, gives the percentage of nitrocellulose. Footnote A. If the substance has been treated with ether alone in the sock-slit, the nitroglycerin will of course be dissolved out first, and the ether alcohol solution will only contain the nitrocellulose. The residue left after treating the gelatin with ether alcohol is, in the case of blasting gelatin, very small, and will probably consist of nothing but carbonate of soda. It should be dried at 100 degrees Celsius, and weighed, but in the case of either gelignite or gelatin dynamite this residue should be transferred to a beaker and boiled with distilled water, and the water decanted some 8 or 10 times, and the residue finally transferred to a tarred filter and washed for some time with hot water. The residue left upon the filter is wood pulp. This is dried at 100 degrees Celsius, until constant, and weighed. The solution and washings from the wood are evaporated down in a platinum dish, and dried at 100 degrees Celsius. It will consist of the potassium nitrate, and any other mineral salts, such as carbonate of soda, which should always be tested for by adding a few drops of nitric acid and a little water to the residue, and again evaporating to dryness and reweighing. From the difference in weight the soda can be calculated, sodium nitrate having been formed. Thus, Na_2 Co_3 plus 2 No_3 equals 2 Nano_3 plus Co_2 plus H_2O mole. Weight equals 106 equals 170. 170 minus 106 is equal to 64, and x equals 106xd/64, where x equals grams of sodium carbonate in residue, and d equals the difference in weight of residue before and after treatment with nitric acid. The nitroglycerin is best found by difference, but if desired, the solutions from the precipitation of the nitrocellulose may be evaporated down upon the water bath at 30 degrees to 40 degrees Celsius, and finally dried over CaCl_2 until no smell of ether or chloroform can be detected, and the nitroglycerin weighed. It will, however, always be much too low. An actual analysis of a sample of gelatin dynamite gave the following result. Nitrocellulose, collodion, 3.819%, nitroglycerin 66.691. Wood pulp 16.290. No_3, 12.890. Na_2, Co_3 nil. Water 0.340. This sample was probably intended to contain 30% of absorbing material to 70% of explosive substances. Many dynamites contain other substances than the above, such as paraffin, resin, sulfur, wood, coal dust, charcoal, also mineral salts, such as carbonate of magnesia, chloride of potash, and C. In these cases, the above described methods must of course be considerably modified. Paraffin, resin, and most of the sulfur will be found in the ether solution if present. The solution should be evaporated, and in this case the explosive should in the first case be treated with ether only, and not ether alcohol, and the residue weighed, and then treated on the water bath with a solution of caustic soda. The resin goes into solution, and is separated by decantation from the residue, and precipitated by hydrochloric acid, and collected on a tarred filter, dried at 100 degrees Celsius, and dried at 100 degrees Celsius, and weighed. The nitroglycerin residue is treated with strong alcohol, decanted, and the residue of paraffin and sulfur washed with alcohol, dried, and weighed. To separate the paraffin from the sulfur, the residue is heated with a solution of ammonium sulfate. After cooling, the paraffin collects as a crust upon the surface of the liquid, and by pricking a small hole through it with a glass rod, the liquid underneath can be poured off, and the paraffin then washed with water, dried, and weighed. Sulfur is found by difference. Mr. F. W. Smith, Schurhammer. Chem. SOC, 1901, 23, 8, 585 to 589, determines the sulfur in dynamite gelatin as follows: about 2 grams are warmed in a 100 cc silver crucible on the water bath with an alcoholic solution of sodium hydroxide, and where the nitroglycerin is decomposed, the liquid is evaporated to dryness. The residue is fused with 40 grams of Co and 5 grams of potassium nitrate, the mass dissolved in dilute acetic acid and filtered, and the sulfates precipitated in the usual way. If camphor is present, it can be extracted with bisulfide of carbon after the material has been treated with ether alcohol. In that case, the sulfur, paraffin, and resin will also be dissolved. The camphor, being easily volatile, can be separated by evaporation. Let the weight of the extract, freed from ether alcohol before treatment with bisulfide of carbon, equal A, and the weight of extract after treatment with CS_2, and evaporation of the same equal B, and weight of the residue which is left after evaporation of the CS_2, and the camphor in solution equals C. The percentage of camphor will be ABC. The residue C may contain traces of nitroglycerin, resin, or sulfur. Camphor may be separated from nitroglycerin by means of CS_2. If the solution of camphor in nitroglycerin be shaken with CS_2, the camphor and a little of the nitroglycerin will dissolve. The bisulfide solution is decanted, or poured into a separating funnel and separated from the nitroglycerin. The two solutions are then heated on the water bath to 20 degrees Celsius, and then to 60 degrees Celsius, and afterwards in a vacuum over CaCl_2, until the CS_2 has evaporated from them. The camphor evaporates, and leaves the small quantity of nitroglycerin which had been dissolved with it. The other portion is the nitroglycerin, now free from CS_2. The two are weighed and their weights added together, and equals the nitroglycerin present. There is a loss of nitroglycerin, it being partly evaporated along with the CS_2. Captain Hess has shown that it is equal to about 1.25%, This quantity should therefore be added to that found by analysis. Morton Leibschutz, in a paper in the Moniteur Scientifique for January 1893, very rightly observes that the variety of dynamites manufactured is very great, all of them having a special composition which, good or bad, is sometimes of so complicated a nature that the determination of their elements is difficult. The determination of nitroglycerin in simple dynamite number 1 is easy, but not so when the dynamite contains substances soluble in ether, such as sulfur, resin, paraffin, and naphthalene. After detailing at length the methods he employs, he concludes with the observation that the knowledge of the use of acetic acid, in which nitroglycerin dissolves, for the determination of nitroglycerin may be serviceable. Mr. F. W. Smith, A., gives the following indirect method of determining nitroglycerin in gelatin dynamite, Nc. About 15 grams of the sample are extracted with chloroform in a Soxhlet apparatus, and the loss in weight determined. In a second portion the moisture is determined. A third portion of about 2 grams is macerated with ether in a small beaker, the ethereal extract filtered, and the process of extraction repeated 3 or 4 times. The united filtrates are allowed to evaporate spontaneously, and the residue warmed gently on the water bath with 5 cc of ammonium sulfate solution and 10 cc of alcohol until the nitroglycerin is decomposed, after which about 250 cc of water and sufficient hydrochloric acid to render the liquid strongly acid are added, and the liquid filtered. The precipitate is washed free from acid, and then washed through the filter with strong alcohol and chloroform into a weighed platinum dish, which is dried to constant weight at 50 degrees Celsius. The contents of the dish are now transferred to a silver crucible, and the sulfur determined. This amount of sulfur, deducted from the weight of the contents of the platinum dish, gives the quantity of substances soluble in chloroform with the exception of the nitroglycerin, moisture, and sulfur. The amount of the former substances plus the moisture and sulfur, deducted from the total loss on extraction with chloroform, gives the quantity of nitroglycerin. Nitrobenzene may be detected, according to J. Marpergo, in the following manner. In a porcelain basin are placed 2 drops of liquid phenol, 3 drops of water, and a fragment of potash as large as a pea. The mixture is boiled, and the aqueous solution to be tested then added. On prolonged boiling, nitrobenzene produces at the edge of the liquid a crimson ring, which on the addition of a solution of bleaching powder turns emerald green. And nitroglycerin in ether solution, by placing a few drops of the suspected solution, together with a drop or 2 of aniline, upon a watchglass, evaporating off the ether, and then adding a drop of concentrated sulfuric acid to the residue, when, if nitroglycerin is present, the H_2, so_4, will strike a crimson color, due to the action of the aniline sulfate upon the nitric acid liberated from the nitroglycerin. Footnote A. Notes on the analysis of explosives. Schurhammer. Chem. SOC, 1901, 23 8, 585 to 589. Tonight, the analysis of this explosive is a comparatively easy matter, and can be performed as follows: weigh out 10 grams, or a smaller quantity, and boil with water in a beaker, decanting the liquid 4 or 5 times, and filter. The aqueous solution will contain the nitrate of barium. Then put the residue on the filter, and wash 2 or 3 times with boiling water. Evaporate the filtrate to dryness in a platinum dish. Dry and weigh. This equals the BA, No_3_2. If the sample is tonight number 3, and contains dinitrobenzol, treat first with ether to dissolve out this substance. Filter into a dish, and evaporate off the ether, and weigh the dinitrobenzol, and afterwards treat residue with water as before. The residue is dried and weighed, and equals the guncotton present. It should then be treated with a solution of ether alcohol in a conical flask, allowed to stand some 3 hours, then filtered through a weighed filter paper, dried at 40 degrees Celsius, and weighed. This will give the guncotton, and the difference between this last weight and the previous one will give the collodion cotton. A portion of the residue containing both the guncotton and the soluble cotton can be tested in the nitrometer, and the nitrogen determined. Cordite. This explosive consists of gun cotton, with a little collodion cotton in it as impurity, nitroglycerin, and Vaseline, the proportions being given as 30% nitroglycerin, 65% gun cotton, and 5% Vaseline. Its analysis is performed by a modification of the method given for gelatins. 5 grms may be dissolved in ether alcohol in a conical flask, allowed to stand all night, and then filtered through a linen filter. The residue is washed with a little ether, pressed, and dried at 40 degrees Celsius, and weighed. It equals the gun cotton. The solution contains the nitroglycerin, soluble cotton, and Vaseline. The cotton is precipitated with chloroform, filtered off, dried, and weighed. The two ether alcohol solutions are mixed, and carefully evaporated down in a platinum dish upon the water bath at a low temperature. The residue is afterwards treated with strong 80% acetic acid, which dissolves out any nitroglycerin left in it. The nitroglycerin is then obtained by difference, or the method suggested to me privately by Mr. W. J. Williams may be used. The residue obtained by evaporation of the ether alcohol solution, after weighing, is treated with alcoholic potash to decompose the nitroglycerin, water is added and the alcohol evaporated off. Some ether is then added, and the mixture shaken, and the ether separated and evaporated, and the residue weighed as Vaseline. The moisture should, however, be determined by the method devised by Mr. Arthur Marshall, FIC, of the Royal Gunpowder Works, Waltham Abbey, which is carried out as follows. The cordite or other explosive is prepared in the manner laid down for the able heat test, that is to say, it is ground in a small mill, and that portion is selected which passes through a sieve having holes of the size of No. 8 wire gauge, but not through one with holes No. 14 wire gauge. Illustration, Figure 40. Marshall's apparatus for moisture in cordite. The form of apparatus used is shown in Figure 40. It consists of an aluminium dish A, having the dimensions shown, and the glass cone B weighing not more than 30 grms. 5 grms of the cordite are weighed into the aluminium dish A. This is covered with the cone B, and the whole is accurately weighed, and is then placed upon a metal plate heated by steam from a water bath. It is left upon the bath until all the moisture has been driven off, then it is allowed to cool for about half an hour in a desiccator, and is weighed. The loss in weight gives accurately the moisture of the sample. For cordite of the original composition, 1 hour's heating is sufficient to entirely drive off the moisture. For modified cordite containing 65% of gun cotton, 2 hours is enough, provided that there be not more than 1.3% of moisture present. If the proportion of nitroglycerin be higher, a longer heating is necessary. The aluminium dish must not be shallower than shown in the figure, for if the distance between the substance and the edge of the glass cone be less than half an inch, some nitroglycerin will be lost. Again, the sample must not be ground finer than stated, else some of the moisture will be lost in the grinding and sieving operations, and the result will be too low. In order to be able to drive off all the moisture in the times mentioned, it is essential that the glass cone shall not fit too closely on the aluminium dish, consequently the horizontal ledge round the top of the dish should be bent, so as to render it slightly untrue, and leave a clearance of about 0.02 inch in some places. If these few simple precautions be taken, the method will be found to be very accurate. Duplicate determinations do not differ more than 0.01%. A. Footnote A. Determination of moisture in nitroglycerin explosives. By A. Marshall, Schuer SOC Chem. IND, February 29, 1904, page 154. The Vaseline, C_16, H_34, or petroleum jelly, used has a flash point of 400 degrees Fahrenheit. It must not contain more than 0.2% volatile matter when heated for 12 hours on the water bath, and should have a specific gravity of 0.87 at 100 degrees Fahrenheit, and a melting point of 86 degrees Fahrenheit. It is obtained during the distillation of petroleum, and consists mainly of the portions distilling above 200 degrees Celsius. It boils at about 278 degrees Celsius. Acetone, CH_3, company CH_3 or dimethyl ketone is formed when isopropyl alcohol is oxidized with potassium bichromate and sulfuric. It is also produced in considerable quantities during the dry distillation of wood and many other organic compounds. Crude wood spirit, which has been freed from acetic acid, consists in the main of a mixture of acetone and methyl alcohol. The two substances may be roughly separated by the addition of calcium chloride, which combines with the methyl alcohol. On subsequent distillation, crude acetone passes over and may be purified by conversion into the bisulfite compound. Acetone is usually prepared, however, by the dry distillation of crude calcium or barium acetate. CH_3.Cu2 Ca equals CH3. Company CH_3 plus CaCO_3. The distillate is fractionated, and the portion, boiling between 50 degrees and 60 degrees Celsius, mixed with strong solution of sodium bisulfite. The crystalline cake of acetone sodium bisulfite, which separates on standing, is well pressed, to free it from impurities, decomposed by distillation with dilute sodium carbonate, and the aqueous distillate of pure acetone dehydrated over calcium chloride. Acetone is a colorless, mobile liquid of SPGR. 792 at 20 degrees Celsius. It boils at 56.5 degrees Celsius, has a peculiar, pleasant, ethereal odor, and is mixable with water, alcohol, and ether in all proportions. The acetone used in the manufacture of cordite should conform to the following specification. Specification for acetone. 1. The acetone to be not more than 0.802 specific gravity at 60 degrees Fahrenheit. When mixed with distilled water, it must show no turbidity, and must leave no residue on evaporation at 212 degrees Fahrenheit. On distillation, 4/5 by volume of the quantity taken must distill over at a temperature not exceeding 138 degrees Fahrenheit. The residual matter left after this distillation must not contain, besides acetone, any ingredient that is not a byproduct incidental to the manufacture of acetone. 2. 1 cc of 0.1% solution in distilled water of pure permanganate of potash, added to 100 cc of the acetone, must retain its distinctive color for not less than 30 minutes. This test should be made at a temperature of 60 degrees Fahrenheit. 3. The acetone tested by the following method must not show more than 0.005% of acid, calculated to acetic acid. To 50 cc of the sample diluted with 50 cc of distilled water, with 2 cc of phenolphthalein solution, 1 gram to 1000 cc of 50% alcohol, added as an indicator, add from a burette and /100 sodium hydrate solution, 1 cc 0.0006 gram acetic acid, and calculate to acetic acid in the usual manner. The water used for the dilution of the acetone must be carefully tested for acidity, and the pipettes used for measuring should not be blown out, as it would be possible thus to neutralize nearly 2 cc of the soda solution. The presence of water in a sample of acetone may be detected by Schweitzer and Lungwitz's method Chem. Zeit. 1895-19, page 1384, which consists in shaking together equal volumes of acetone and petroleum ether, boiling point, 40 degrees to 60 degrees Celsius, when if present a separation of the liquid in layers will take place. Estimation of acetone. Kebler, Jurammer. Chem. SOC 1897-19, 316-320, has improved Squibb's modification of Robineau and Rollin's method. The following solutions are required. 1. A 6% solution of hydrochloric acid. 2. A decinormal solution of sodium thiosulfate. 3. Alkaline potassium iodide solution prepared by dissolving 250 grams of potassium iodide in water, made up to a liter, dissolving 257 grams of sodium hydroxide by alcohol in water, likewise made up to a liter. After allowing the latter to stand, 800 cc of the clear solution are added to the liter of key. 4. Sodium hypochlorite solution, 100 grams of bleaching powder, 35%, are mixed with 400 cc of water. To this is added a hot solution of 120 grams of crystallized sodium carbonate in 400 cc of water. After cooling, the clear liquid is decanted, the remainder filtered, and the filtrate made up to a liter. To each liter is added 25 cc of sodium hydroxide solution, SPGR 1.29. 5. An aqueous solution of the acetone, containing 1 or 2% of acetone. 6. Bicarbonate starch solution prepared by treating 0.125 grm of starch with 5 cc of cold water, then adding 20 cc of boiling water, boiling a few minutes, cooling, and adding 2 grms of sodium bicarbonate. To 20 cc of the potassium iodide solution are added 10 cc of the diluted aqueous acetone. An excess of the sodium hypochlorite solution is then run in from a burette and well shaken for a minute. The mixture is then acidified with the hydrochloric acid solution, and while agitated, an excess of sodium thiosulfate solution is added, the mixture being afterwards allowed to stand a few minutes. The starch indicator is then added, and the excess of thiosulfate retitrated. The relation of the sodium hypochlorite solution to the sodium thiosulfate being known, the percentage of acetone can be readily calculated. A. Footnote A.C. The testing of acetone. Conroy, Jure SOC Chem. IND, March 31, 1900, Volume 19. DRS Jam, Ald has recently, Jure Chem. SOC, February 15, 1906, Volume 25. Worked out a volumetric method for the estimation of acetone, depending on the formation of bromoform, and its subsequent hydrolysis with alcoholic potash. The hydrolysis is probably expressed thus: 3 CHBr underscore 3 plus 9 Co plus C underscore 2 H underscore 5 O equals 3 Co plus C underscore 2 H underscore 4 plus 9 KBr plus 7 H underscore 2 O. As it has been shown by Hermann and Long that exactly 3 volumes of carbon monoxide to 1 of ethylene are evolved. The residual potassium bromide is estimated by means of standard silver nitrate solution. Bromoform is specially suitable for this purpose for several reasons. It is very readily formed by the action of bromine and potash on acetone, and although very volatile in steam, it is not liable to loss due to its own evaporation. Further, its high molecular weight and large percentage of bromine conduce to accurate results, 58 grms of acetone being responsible for the formation of 357 grms of KBr. The method of carrying out the analysis is as follows. A known quantity of the solution to be tested, containing acetone to the extent of 0.1 to 0.2 grm, is pipetted into a 500 cc round-bottom flask, diluted with a little water, and mixed with 20 to 30 cc of a 10% solution of caustic potash. The flask is connected with a long reflex condenser, and is also fitted with a dropping funnel containing a solution of bromine and potassium bromide, 200 grms of Br and 250 grms of KBr to 1 liter of water. The bromine solution is allowed to flow into the mixture until it has acquired a faint yellow tinge, the flask and its contents being then heated on the water bath at about 70 degrees Celsius for half an hour. Bromine solution is added drop by drop until the slight coloration is permanent, excess of bromine being got rid of by boiling for a minute or two with a little more caustic potash. The mixture is then distilled until the distillate is free from bromoform, halogen being tested for in the usual manner. Water is added to the contents of the flask if necessary. It may be here observed that no acetone can be detected in the distillate by means of the mercuric oxide test, and free bromine is also absent. The condenser having been washed out with a little alcohol, in order to remove any traces of bromoform which may have collected, the distillate and washings are mixed with 50 cc of alcohol and sufficient solid caustic potash to make an approximately 10% solution. The mixture is then heated on the water bath under a reflux condenser until the bromoform is completely decomposed. This generally occupies about 3/4 of an hour. The liquid is allowed to cool, evaporated to smaller bulk if necessary, and exactly neutralized with dilute nitric acid. It is then diluted with water to 500 cc, and an aliquot part titrated with N/10 silver nitrate solution, using potassium chromate as indicator. 240 parts of bromine correspond to 58 parts of acetone. The complete analysis can be performed in 1.5 to 2 hours. It is imperative that the bromine used should be pure, as crude bromine frequently contains bromoform. The method is suitable for the estimation of acetone in wood spirit, the spirit being diluted to 10 times its volume, and 5 cc of this solution employed for the determination. For example, 1. 3 cc of a solution containing 9.61% acetone gave 1.7850 grm. kbr. Acetone found equals 9.66%. 2. 10 cc of a solution containing 0.96% acetone gave 0.5847 grm. kbr. Acetone found equals 0.95%. Nitro-cotton. The first thing upon opening a case of wet cotton, or in receiving a sample from the poacher, that requires to be determined is the percentage of water that it contains. It is best done by weighing out about 1000 grams. Upon a paper tray, which has been previously dried in the oven at 100 degrees Celsius, for some time, and become constant in weight. The trayful of cotton is then placed in a water oven, kept at 100 degrees Celsius, and dried as long as it loses water. The loss gives the percentage of water. It varies from 20 to 30%, as a rule in wet cotton. Outline scheme for the analysis of nitro-explosives. Underscore 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 exhaust dried substance with anhydrous ether and Soxhlet's fat extraction apparatus. Underscore 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 solution divide into two parts A and B. Underscore 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 A. Allow ether to evaporate spontaneously. Dry residue in vacuole over H underscore 2, so underscore 4, and weigh equals nitroglycerin, resin, camphor, and paraffin. The nitroglycerin in this residue may be decomposed by heating, with a solution of alcoholic potash. Water may then be added, and the alcohol evaporated off on the water bath. From this solution, the resin may be precipitated by HCl, filtered off, dried, and weighed. Solution containing the paraffin is treated with AMS solution and heated. On cooling, the paraffin separates, and may be separated. Residue may be shaken with CS_2 to remove camphor. Underscore 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 B. Add phenolphthalein and titrate with alcoholic potash, 1 cc normal. Co equals 0.330 grm. Resin, and add considerably more Co. Evaporate, dissolve residue in water, shake with ether, and separate. Underscore 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 ethereal solution evaporated leaves paraffin. Underscore 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 aqueous solution. Add bromide, acidify with HCl, separate any resin and precipitate. Filtrate with Backel underscore 2, Baso underscore 4, X.1373 equals sulfur. Underscore 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 residue, dry away, and exhaust with water, preferably in sockslit. Underscore 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 solution residue contains metallic, dry away, and agitate an aliquot part with nitrates, chlorates, with H underscore 2, SO underscore 4, and Hg in nitrometer. If soluble carbonates, nitrocellulose is present, treat remainder of, the sum of which, residue with ether alcohol. Except AMCO underscore 3. underscore 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 can be determined by evaporating down at solution 100 degrees Celsius to dryness, evaporate and weigh. Residue consists of and weighing soluble nitrocellulose. Nitrates can be underscore 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 determined by residue, dry and weigh and determine hexanitro, cellulose and nitrometer, if present. Exhaust, remainder with acetic ether. Underscore 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 note dot camphor is found by difference. Sulfur is only partially soluble in ether. It is better, therefore, to extract some of the original substance with water and treat residue with alcoholic co. Add bromide, acidify, and precipitate as baso. The solubility test. The object of this test is to ascertain, in the case of gun cotton, the percentage of soluble, penta and lower nitrates, cotton that it contains, or in the case of soluble cotton, the quantity of gun cotton. The method of procedure is as follows: 5 grms of the sample which has been previously dried at 100 degrees Celsius, and afterwards exposed to the air for 2 hours, is transferred to a conical flask, and 250 cc ether alcohol added, 2 ether to 1 alcohol. The flask is then corked and allowed to digest, with repeated shaking, for 2 or 3 hours. The whole is then transferred to a linen filter, and when the solution has passed through the filter, is washed with a little ether, and pressed in a hand screw press between folds of filter paper. The sample is then returned to the flask, and the previous treatment repeated, but it will be sufficient for it to digest for 1 hour the second time. The filter is then again pressed, first gently by hand, then in the press, and afterwards opened up and the ether allowed to evaporate. The gum cotton is then removed from the filter and transferred to a watch glass, and dried in the water oven at 100 degrees Celsius. When dry, it is exposed to the air for 2 hours and weighed. It equals the amount of gun cotton and unconverted cotton in the 5 grms. The unconverted cotton must be determined in a separate 5 grms and deducted. The method of determining the soluble cotton now used in the government laboratories is as follows: 50 grains of the nitro cotton are dissolved in 150 cc of ether alcohol, and allowed to stand, with frequent shakings, in a 200 cc stoppered measure for 6 hours. 75 cc of the clear solution are then drawn off by the aid of a pipette and evaporated in a dish on the water bath, and finally in the water oven at 120 degrees Fahrenheit, 49 degrees Celsius, until constant in weight. The weight found equals the quantity of soluble cotton in the 75 cc, which, multiplied by 4, equals the percentage. Thus, suppose that 2.30 grains was the weight found, then 2.3 by 150/75 equals 4.6 and 50 is equal to 9.20%. A method for the determination of soluble nitrocellulose in gun cotton and smokeless powder has been published by K.B. Quinn in Schur-Ammer. Chem. SOC 23 4 258. In this method, about 1 grm of the finely divided dry sample to be analyzed is placed in an aluminium cup 1.9 inch in diameter and 4 1/8 inch deep. It is then covered and well stirred with 50 cc of alcohol, 100 cc of ether are then added, and the mixture is stirred for several minutes. After removing the stirrer, the cup is lightly covered with an aluminium lid, and is then placed in the steel cup of a centrifugal machine, which is gradually got up to a speed of 2,000 revolutions per minute. The total centrifugal force at the position occupied by the cups, which become horizontal when in rapid rotation, is about 450 pounds. They are rotated at the full speed for 10 to 12 minutes, and the machine is then gradually stopped. By this time the whole of the insoluble matter will be at the bottom of the cup, and the supernatant solution will be clear. It is drawn off to within 1/4 of an inch of the bottom, without disturbing the sediment, with the aid of a pipette. Care must be taken that the solution thus withdrawn is perfectly clear. About 10 to 15 cc of colloid solution and a film of insoluble matter remain at the bottom of the cup. These are stirred up well. The stirrer is rinsed with ether alcohol. About 50 cc of fresh ether alcohol are added. The mixture is again treated in the centrifugal apparatus for about 8 minutes. The whole washing process is then repeated until all soluble matter has been removed. This may require about 7 or 8, or for samples with much insoluble matter 10 or 12 or more, washings, but as the extraction proceeds, the period of rotation may be somewhat reduced. After extraction is completed, the insoluble matter is transferred to a gouge crucible with the usual asbestos pad, dried at 100 degrees Celsius, and weighed. The residue may, if wished, be dried and weighed in the aluminium cup, but then it cannot be ignited. The whole time for an analysis exclusive of that required for drying is from 1 to 2 hours, average time 1 to 1/4 hour. The results are satisfactory both as to accuracy and rapidity. Acetone-soluble nitrocellulose may be determined by the same method. The unconverted or non-nitrate cotton, however well the cotton has been nitrate, it is almost certain to contain a small quantity of non-nitrate or unconverted cotton. This can be determined thus: 5 grams of the sample are boiled with a saturated solution of sodium sulfate, and then allowed to stand for 48 hours, and afterwards filtered or decanted, and again boiled with fresh solutions of sulfate, and again filtered, washed first with dilute HCl and then with water, dried, and weighed. The residue is the cellulose that was not nitrate, plus ash, and C. It should be ignited, and the weight of the ash deducted from the previous weight. Acetone and acetic ether, ethyl acetate, may also be used as solvents for the nitrocellulose. Another process is to boil the guncotton, NC, in a solution of sodium stannate made by adding caustic soda to a solution of stannous chloride until the precipitate first formed is just redissolved. This solution dissolves the cellulose nitrates, but does not affect the cellulose. Dr. Lunge found the following process more satisfactory in the case of the more highly nitrate products. The reagent is an alcoholic solution of sodium methylate prepared by dissolving 2 to 3 grams of sodium in 100 cc of 95% alcohol, and mixing the filtered solution with 100 cc of acetone. It has no effect upon cellulose, but decomposes nitrocellulose with the formation of a reddish-brown compound, which is soluble in water. In the determination, 5 grams of guncotton are heated to 40 degrees or 50 degrees Celsius, on the water bath with 150 cc of the reagent, the liquid being shaken at intervals for 20 to 30 minutes, or the mixture may be allowed to stand for a few hours at the ordinary temperature. The brown-red solution is decanted from the undissolved residue, and the latter washed with alcohol and with water, by decantation, and then on the filter with hot water, to which a little hydrochloric acid is added for the final washings. For ordinary work this cellulose is dried immediately and weighed, but in exact determinations it is washed with alcohol, again treated with 50 cc of the reagent, and separated and washed as before. The cellulose thus obtained gives no trace of gas in the nitrometer, and duplicate determinations agree within 0.1 to 0.2%, when the weight of unchanged cellulose amounts to about 0.2 grm. Guncotton, which is completely soluble in acetone, contains only traces of cellulose, and when as much as 0.85% is present, it does not dissolve entirely. This method is not applicable to the determination of cellulose in lower nitrate products, and Dr. Lunge attributes this to the fact that these, being prepared with less concentrated acid, invariably contain oxycellulose. Alkalinity 5 grams of the air-dried and very finely divided sample are taken from the center of the slabs or discs, and digested with about 20 cc of N/2 hydrochloric acid, and diluted with water to about 250 cc, and shaken for about 15 minutes. The liquid is then decanted, and washed with water until the washings no longer give an acid reaction. The solution, together with the washings, are titrated with N/4 sodium carbonate, using litmus as indicator. Ash and inorganic matter. This is best determined by mixing 2 or 3 grams of the nitro cotton in a platinum crucible with shavings of paraffin, heating sufficiently to melt the paraffin, and then allowing the contents of the crucible to catch fire and burn away quietly. The temperature is then raised, and the carbonaceous residue incinerated, cooled, weighed, and the percentage of ash calculated. Stirring proceeds in the following way. He takes 5 grams of the nitro cotton in a large platinum crucible. He then moistens it with a mixture of alcohol and ether, in which paraffin has been dissolved to saturation, and filtered and mixed with 1/4 of its volume of water. Some fragments of solid paraffin are then added, and the ether set on fire. Whilst this is in progress, the crucible is kept in an oblique position, and is rotated so that the gun cotton may absorb the paraffin uniformly. The partially charred residue is now rubbed down with a rounded glass rod, and the crucible is covered and heated for from 15 to 20 minutes over the blowpipe, the lid being occasionally removed. The residue is soon converted into ash, which is weighed, and then washed out into a porcelain basin and treated with hydrochloric acid heated to 90 degrees Celsius. The oxide of iron, alumina, lime, and magnesia are thus dissolved, and the silica remains as insoluble residue. The rest of the analysis is conducted according to the well-known methods of separation. The percentage of ash as a whole is generally all that is required. Examination of nitrate celluloses with polarized light. DRG. Lunge, Schur-Ammer. Chem. SOC, 1901, 23, 8, 527, has formed the following conclusions. The most highly nitrate products appear blue in polarized light, but those containing between 13.9 and 13% of nitrogen cannot be distinguished from each other by polarization. As the percentage of nitrogen rises, the blue color becomes less intense, and here and there gray fibers can be observed, though not in proportion to the increase in the nitrogen. Below 12.4% of nitrogen, the fibers show a gray luster, which usually appears yellow when the top light is cut off. Below 10% of nitrogen, the structure is invariably partially destroyed and no certain observations possible. It is only possible to distinguish with certainty, firstly, any unchanged cellulose by its flashing up in variegated, rainbow, colors, and secondly, highly nitrate products, from 12.75% and upwards, by their flashing up less strongly in blue colors. The purple transition stage in the fibers containing over 11.28% of N-Chardonnay was not observed by Dr. Lunge. Determination of nitrogen by Lunge nitrometer. The determination of the percentage of nitrogen in a sample of gun cotton or collodion is perhaps of more value, and affords a better idea of its purity and composition than any of the foregoing methods of examination, and taken in conjunction with the solubility test. It will generally give the analyst a very fair idea of the composition of his sample. If we regard gun cotton as the hexanitrocellulose, the theoretical amount of nitrogen required for the formula is 14.14%, and in the same way for collodion cotton, which consists of the lower nitrates, chiefly, however, of the pentanitrate, the theoretical nitrogen is 12.75%. So that if in a sample of nitro cotton the nitrogen falls much lower than 14%, it probably contains considerable quantities of the lower nitrates, and perhaps some non-nitrate cellulose as well. C_6, H_10, O_5, X, which of course would also lower the percentage of nitrogen. The most expeditious method of determining the nitrogen in these nitro bodies is by the use of Lunge's nitrometer, figure 41, and the best way of working the process is as follows: weigh out with the greatest care 0.6 grm of the previously dried substance in a small weighing bottle of about 15 cc capacity, and carefully add 10 cc of concentrated sulfuric acid from a pipette, and allow to stand until all the cotton is dissolved. The nitrometer should be of a capacity 150 to 200 cc, and should contain a bulb of 100 cc capacity at the top, and should be fitted with a Grainer and Friedrichs 3-way tap. When the nitro cotton has entirely dissolved to a clear solution, raise the pressure tube of the nitrometer so as to bring the mercury in the measuring tube close up to the tap. Open the tap in order to allow of the escape of any air bubbles, and clean the surface of the mercury and the inside of the cup with a small piece of filter paper. Now close the tap and pour the solution of the nitro cotton into the cup. Rinse out the bottle with 15 cc of sulfuric acid contained in a pipette, pouring a little of the acid over the stopper of the weighing bottle in case some of the solution may be on it. Now lower the pressure tube a little, just enough to cause the solution to flow into the bulb of the measuring tube, when the tap is slightly opened. When the solution has run in almost to the end, turn off the tap, wash down the sides of the bottle, and add to the cup of the nitrometer. Allow it to flow in as before, and then wash down the sides of the cup with 10 cc of sulfuric acid, adding little by little, and allowing each portion added to flow into the bulb of the nitrometer before adding the next portion. Great care is necessary to prevent air bubbles obtaining admission, and if the pressure tube is lowered too far, the acid will run with a rush and carry air along with it. Illustration, figure 41. Ordinary form of lunge nitrometer. The solution being all in the measuring tube, the pressure tube is again slightly raised, and the tube containing the nitro cotton solution shaken for 10 minutes with considerable violence. It is then replaced in the clamp, and the pressure relieved by lowering the pressure tube, and the whole apparatus allowed to stand for 20 minutes, in order to allow the gas evolve to assume the temperature of the room. A thermometer should be hung up close to the bulb of the measuring tube. At the end of the 20 minutes, the levels of the mercury in the pressure and measuring tubes are equalized, and the final adjustment obtained by slightly opening the tap on the measuring tube, very slightly, after first adding a little sulfuric acid to the cup, and observing whether the acid runs in or moves up. This must be done with very great care. When accurately adjusted, it should move either way. Now read off the volume of the no gas in cubic centimeters from the measuring tube. Read also the thermometer suspended near the bulb, and take the height of the barometer in millimeters. The calculation is very simple. Example, collodion cotton. 0.6 a grm. Taken. Reading on measuring tube equals 114.6 cc no. Barometer, 758 millimeters. Temperature, 15 degrees Celsius. Footnote A 0.5 grm. Is enough in the case of gun cotton. Since 1 cc no equals 0.6272 mg N, and correcting for temperature and pressure by the formula 760x, 1 plus d caret, 2, d equals 0.003665, for temperature 15 degrees equals 801.78 a. Then 114.6 by 100 by 750x.6272 / 801.7x 6 equals 11.22%. Nitrogen. Footnote A, see table, page 244. The nitrogen in nitroglycerin may of course be determined by the nitrometer, but in this case it is better to take a much smaller quantity of the substance. From 0.1 to 0.2 grm is quite sufficient. This will give from 30 to 60 cc of gas, and therefore a measuring tube without a 100 cc bulb must be used. Example: 0.1048 grm. Nitroglycerin taken gave 32.5 cc no. Barometer, 761 millimeters. Temperature, 15 degrees Celsius. Therefore, 3.25 by 100 by 761 x.6272 /801.78 x.1048 equals 18.46%. N. Theory equals 18.5%. Professor Lunge has devised another form of nitrometer, figure 42, very useful in the nitrogen determination in explosives. It consists of a measuring tube, which is widened out in the middle to a bulb, and is graduated above and below into 1/10 cc. The capacity of the whole apparatus is 130 cc, that of each portion of the tube being 30 cc, and of the bulb 70 cc. The upper portion of the graduated tube serves to measure small volumes of gas, whilst larger volumes are read off on the lower part. Illustration, Figure 42, Figure 43, some new forms of nitrometer. F.M. Horn, Zeitschrift für Angewandte Chemie, 1892, page 358, has devised a form of nitrometer, figure 43, which he has found especially useful in the examination of smokeless powders. The tap H is provided with a wide bore through which a weighed quantity of the powder is dropped bodily into the bulb K, from 4 to 5 cc of sulfuric acid which has been heated to 30 degrees Celsius, are then added through the funnel T, the tap H being immediately closed. When the powder has dissolved, a process which may be hastened by warming the bulb very carefully, the thick solution is drawn into the nitrometer tube N, and the bulb rinsed several times with fresh acid, after which operation the analysis is proceeded with in the usual way. Dr. Lunge's method of using a separate nitrometer in which to measure the no gas evolved to the one in which the reaction has taken place, the gas being transferred from the one to the other by joining them by means of india-rubber tubing, and then driving the gas over by raising the pressure tube of the one containing the gas, the taps being open, I have found to be a great improvement. 1 cc no gas at 0 degrees and 760 millimeters equals 0.6272 milligrams N nitrogen. 1.343 nitric oxide. 2.820 No_3 nitric acid. 3.805 Nano_3 sodium nitrate. 4.523 No_3 potassium nitrate. Champion and pellets method. This method is now very little used. It is based upon the fact that when nitrocellulose is boiled with ferrous chloride and hydrochloric acid, all the nitrogen is disengaged as nitric oxide, No. It is performed as follows. A vacuum is made in a flask, fitted with a funnel tube, with a glass stopper on the tube, a delivery tube that can also be closed, and which dips under a solution of caustic soda contained in a trough, and the end placed under a graduated tube, also full of caustic soda. From 0.12 to 0.16 grm. Cotton dissolved in 5 to 6 cc of sulfuric acid is allowed to flow into the flask, which contains the ferrous chloride and hydrochloric acid, and in which a vacuum has been formed by boiling, and then closing the taps. The solution is then heated, the taps on the delivery tube opened, and the end placed under the collecting tube, and the no evolved collected. The no gas is not evolved until the solution has become somewhat concentrated. Eder substituted a solution of ferrous sulfate in HCl for ferrous chloride. Care must be taken that the flask used is strong enough to stand the pressure, or it will burst. The same chemists, Comptre-Leroux, 83. 707, also devised the following method for determining the No_2 in nitroglycerin. A known quantity of a solution of ferrous sulfate of previously ascertained reducing power is placed in a flask, acidified with hydrochloric acid, and its surface covered with a layer of petroleum oil. About 0.5 grm of the nitroglycerin is then introduced, and the flask heated on the water bath. When the sample is completely decomposed, the liquid is heated to boiling to remove nitric oxide, and the excess of ferrous sulfate ascertained by titration with standard permanganate, 56 of iron, Fe, oxidized by the sample correspond to 23 of No_2 in the sample of nitroglycerin. The Schulze-Tiemann method for determining nitrogen in nitro-explosives, especially nitrocellulose and nitroglycerin. The figure, number 44, shows the general arrangement of the apparatus. I am indebted for the following description of the method of working it to my friend, Mr. William Bate, of Hale. To fill the apparatus with the soda solution, the gas burette is put on the India rubber stopper of basin W, and firmly clamped down. Then the taps A and C are opened, and B closed. When the burette is filled with soda solution halfway up the funnel Y, A and C are closed, and B opened. The arrows show the inlet and outlet for the cooling water that is kept running through the water jacket round the nitrometer tube. To collect the gas, raise the nitrometer off the rubber stopper, and place the gas tube from the decomposition apparatus in the glass dish W and under the opening of the nitrometer. Illustration, Figure 44, Schulze-Tiemann apparatus. For the estimation of nitrogen in nitrocellulose, take 0.5 to 0.65 grm, and place in the decomposition flask F, Figure 45, washing in with about 25 cc of water by alternately opening clips D and E. The air in the flask is driven out by boiling, whilst the air is shut off by the tube by dipping into the basin W, which is filled with the soda lye. And tube K is placed in the test tube R, which contains a few cc of water. As soon as all the air is completely driven out, clips D and E are closed, and the gas jet is taken away. This flask must be a strong one, or it will burst. Into test tube R, 25 cc of concentrated solution of protochloride of iron and 10 to 15 cc concentrated hydrochloric acid are poured, which are sucked up into the developing flask F by opening clip E, air being carefully kept from entering. The clip E is now closed, and tube I is put underneath the burette, and the development of no gas is commenced by heating the contents of the flask F. When the pressure of the gas in the flask has become greater than the pressure of the atmosphere, the connecting tube begins to swell at I, whereupon clip D is opened, and the boiling continued with frequent shaking of the bulb, until no more nitrous gas bubbles rise up into the soda lye. The distilling over of the HCl causes a crackling noise, the clip D is closed, and E opened. The burette is again put hermetically on the India rubber stopper in basin W, and the apparatus is left to cool until the water discharged through P shows the same temperature as the water flowing through, into the cooling jacket, Z. If the level of the soda solution in the tube X is now put on exactly the same level as that in the burette by lowering or elevating the tube X as required. The volume of NO obtained in cc can be read off within 1/10 cc, and the percentage of nitrogen calculated by the usual formula. Illustration, Figure 45. Decomposition flask for Schulze-Tiemann method. The solution of protochloride of iron is obtained by dissolving iron nails, and C, in concentrated HCl, the iron being in excess. When the development of hydrogen ceases, it is necessary to filter warm through a paper filter, and acidify filtrate with a few drops of HCl. The soda solution used has a SPGR of 1.210 to 1.260, equals 25 degrees to 30 degrees B. The nitrocellulose is dried in quantities of 2 grms at 70 degrees Celsius, during 8 to 10 hours, and then 3 hours in an exsicator over H_2, so_4. The results obtained with this apparatus are very accurate. The reaction is founded upon that of Champion and Pellet's method. The Gerald method of determining nitrogen. This method, which has been so largely used by analysts for the determination of nitrogen in organic bodies, more especially perhaps in manures, was proposed by J. Gerald, A., of the Carlsberg Laboratory of Copenhagen. It was afterwards modified by Jabelbauer, of Munich, B., and applied to the analysis of nitro-explosives by M. Chenel, of the Laboratoire Central de Poudres, whose method of procedure is as follows: 0.5 grm of the finely powdered substance is digested in the cold with a solution of 1.2 grm of phenol and 0.4 grm phosphoric anhydride and 30 cc of sulfuric acid. The mixture is kept well shaken until the solution is complete. From 3 to 4 grms of zinc dust is then cautiously and gradually added, the temperature of the mass being kept down until complete reduction has been effected. Finally, 0.7 grm of mercury is added, and the process continued in the usual way, according to Gerald, that is, The liquid is distilled until all the ammonia has passed over and is absorbed in the standard acid. The distillate is then titrated with standard ammonia. Footnote A.J. Gerald, Zeitschrift Anal. Chem. 1883, 22, page 366. Footnote B. Jodelbauer, Chemisches Centralblatt, 1886, pages 434 to 484. See also Arms and Explosives, 1893, page 87. The NO_2 group is at the moment of solution fixed upon the phenol with the production of mononitrophenol, which is afterwards reduced by the action of the zinc dust into the amido derivative. During the subsequent combustion, the nitrogen of the amidophenol becomes fixed in the state of ammonia. M. Chenel is perfectly satisfied with the results obtained, but he points out that the success of the operation depends upon the complete conversion of the phenol into the mononitro derivatives. This takes place whenever the organic compound forms a clear solution in the cold sulfuric acid mixture. Substances like collodion or guncotton must be very finely divided for successful treatment. The following table shows some of the results obtained by M. Chenel. Underscore 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 total nitrogen. Substances analyzed. Underscore 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 calculated. Found. Underscore 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 Saltpetre, no underscore 3, 13.86, 13.91, 13.82, 13.73, 13.96, ammonium nitrate 35.00, 35.31, 34.90, 34.96, barium nitrate 10.72, 10.67, 10.62, nitroglycerol 18.50, 18.45, dinitrobenzol A 16.67, 16.78, 16.57, paranitrophenol 10.07, 10.03, picric acid A 18.34, 18.42, 18.43, ammonium picrate 22.76, 22.63, 22.67, dinitroorthocresol 14.14, 14.10, 13.98, trinitrometacresol 17.28, 17.57, 17.27, underscore 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 underscore. Footnote A. Dr. Bernard Dyer obtained 18.39% for picric acid and 16.54% for dinitrobenzol. Jurchem. SOC, August 1895. When Chenel endeavored to apply Jodelbauer's modification of Gscheldel's process to the examination of the tri- and tetranitrate naphthalenes, he found that good results were not obtainable, because these compounds do not dissolve completely in the cold sulfuric acid. It may, however, be used if they are previously converted into the naphthylamines, according to the plan proposed by Diaguiar and Lotman, Bull. SOC Chim. Volume 3, New Series, page 256. This is rapidly effected as follows: 12 grms of iodine are gradually added to a solution of 2 grms of phosphorus in about 15 or 20 cc of bisulfide of carbon, this solution being contained in a flask of 250 cc capacity. The flask and its contents are heated on the water bath at 100 degrees Celsius, with constant attention, until the last traces of the carbon bisulfide have distilled away. It is then cooled, and the iodide of phosphorus is detached from the sides of the flask by shaking, but not expelled. The next step is to add about 0.5 to 0.6 grm of the substance that is to be analyzed, after which 8 grms of water are introduced, and the flask is agitated gently 2 or 3 times. As soon as the reaction becomes lively, the contents of the flask are well shaken. It is usually finished about 1 minute after the addition of the water. The flask is now cooled, and 25 cc of sulfuric acid, together with 0.7 grm of mercury, are gradually added. Hydriodic acid, high, forms, and the temperature of the flask must be raised sufficiently to expel it. The remaining part of the operation is as in the ordinary Kjeldahl process. M. Channel has found this process the best for the analysis of the nitronaphthalines, and for impervious substances like collodion or guncotton. Personally, I have never been able to obtain satisfactory results with this process in the analysis of nitrocellulose, and I am of opinion that the process does not possess any advantage over the nitrometer method, at any rate for the analysis of guncotton. Table giving the percentages of nitrogen and oxide of nitrogen in various substances used in or as explosives. Name formulae: nitrogen No_2%. Nitroglycerin C_3, H_5, ono_2, 318.50 is equal to 60.70 hexanitrocellulose C12, H_14, O_4, ono_2, 6, 14.14 is equal to 46.42 pentanitrocellulose C6, H_8, O_5, ono_2, 5, 11.11 is equal to 36.50 nitrobenzene C6, H_5, no_2, 11.38 is equal to 37.39 dinitrobenzene C_6, H_4, no_2, 16.67 is equal to 54.77 trinitrobenzene C6, H_3, no_2, 3, 19.24 is equal to 63.22 nitrotoluene C7, H_7, no_2, 10.21 is equal to 33.49 nitronaphthalene C_10, H_7, no_2, 8.09 is equal to 26.53 dinitronaphthalene C_10, H_6, no_2, 12.84 is equal to 42.12 nitro. Mannite C6, H_7, no_3, 6, 23.59 is equal to 77.37 nitrostarch C6, H_8, O_4, no_3, 6.76 is equal to 22.18 picric acid, trinitrophenol, C_6, H_2, O, no_2, 3. 18.34 is equal to 60.15 chloronitrobenzene C6, H_3, Cl, no_2, 13.82 is equal to 45.43 ammonium nitrate NH4, no_3, 35.00 equals sodium nitrate nano_3, 16.47 equals potassium nitrate no_3, 13.86 equals nitric acid no_3, 22.22 equals barium nitrate Ba, no_3, 2, 10.72 equals. Analysis of celluloid. The finely divided celluloid is well stirred, by means of a platinum wire, with concentrated sulfuric acid in the cup of a lunge nitrometer, and when dissolved the nitrogen determined in the solution in the usual way. To prevent interference from camphor, the following treatment is suggested by H. Zonshirm, Chem. Zeit, 14, 905. Dissolve a weighed quantity of the celluloid in a mixture of ether alcohol, mixed with a weighed quantity of washed and ignited asbestos, or pumice stone, dry, and disintegrate the mass, and afterwards extract the camphor with chloroform, dry, and weigh, then extract with absolute methyl alcohol, evaporate, weigh, and examine the nitrocellulose in the nitrometer. Picric acid and picrates. Picric acid is soluble in hot water, and to the extent of 1 part in 100 in cold water, also in ether, chloroform, glycerin, 10%, soda solution, alcohol, amylic alcohol, carbon bisulfide, benzene, and petroleum. If a solution of picric acid be boiled with a strong solution of potassium cyanide, a deep red liquid is produced, owing to the formation of potassium isopurpurate, which crystallizes in small reddish-brown plates with a beetle-green luster. This, by reaction with ammonium chloride, gives ammonium isopurpurate, NH_4C_8, H_4, N_5O_6, or artificial murexide, which dyes silk and wool a beautiful red color. On adding barium chloride to either of the above salts, a vermilion red precipitate was formed, consisting of barium isopurpurate. With ammonium sulfate of copper, solutions of picric acid give a bright green precipitate. Mr. H. Allen gives the following methods for the assay of commercial picric acid, in his Commercial Organic Analysis. Resinous and tarry matters are not unfrequently present. They are left insoluble on dissolving the sample in boiling water. The separation is more perfect if the hot solution be exactly neutralized by caustic soda. Sulfuric acid, hydrochloric acid, and oxalic acid, and their salts are detected by adding to the filtered aqueous solution of the sample solutions of the picrates of barium, silver, and calcium. These salts are readily made by boiling picric acid with the carbonates of the respective metals and filtering. Other soluble salts of these methods may be substituted for the picrates, but they are less satisfactory. Nitric acid may be detected by the red fumes evolved on warming the sample with copper turnings. Inorganic impurities and picrates of potash and sodium, and C, leave residues on cautious ignition. General impurities and adulterations may be detected and determined by shaking 1 grm of the sample of acid in a graduated tube with 25 cc of ether. The pure acid dissolves, while any oxalic acid, nitrates, picrates, boric acid, alum, sugar, and C will be left insoluble, and after removal of the ethereal liquid, may be readily identified and determined. For the detection and determination of water and of oxalic acid, 50 cc of warm benzene may be advantageously substituted for ether. Sugar may be separated from the other impurities by treating the residue insoluble in ether or benzene with rectified spirit, in which sugar and boric acid alone will dissolve. If boric acid be present, the alcoholic solution will burn with a green flame. Mono and dinitrophenic acids lower the melting point, 122 degrees Celsius. Their calcium salts are less soluble than the picrate, and may be approximately separated from it by fractional crystallization, or by precipitating the hot saturated solution of the sample with excess of lime water. Picric acid may be determined by extracting the acidulated aqueous solution by agitation with ether or benzene, and subsequently removing and evaporating off the solvent. It may also be precipitated as the potassium salt. Potassium picrate Kc_6 H_2 No_2_30. When a strong solution of picric acid is neutralized by carbonate of potash, this salt is thrown down in yellow crystalline needles, which require 260 parts of cold or 14 parts of hot water for their solution. In alcohol it is much less soluble. Ammonium picrate is more soluble in water than the above, and sodium picrate is readily soluble in water, but nearly insoluble in solution of sodium carbonate. Picrates of the alkalids. Picric acid forms insoluble salts with many of the alkalids, and picric acid may be determined in the following manner. To the solution of picric acid, or a picrate, add a solution of sulfate of cinchonine acidulated with H_2, So_4. The precipitated picrate of cinchonine, C_20, H_24, N_2, O_C_6, H_2, N_3, O_7_2 is washed with cold water, rinsed off the filter into a porcelain crucible or dish, the water evaporated on the water bath, and the residual salt weighed. Its weight, multiplied by 0.6123, gives the quantity of picric acid in the sample taken. Analysis of glycerin. A glycerin that is to be used for the manufacture of nitroglycerin should have a minimum specific gravity of 1.261 at 15 degrees Celsius. This can be determined either by the aid of a Sartorius specific gravity balance, or by using an ordinary specific gravity bottle. 1 of 10 or 25 cc capacity is very convenient. Footnote A. See also Sulman and Berry, Analyst, 11, 12-34, and Allen's Commercial Organic Analysis. Volume 2, Part 1. Residue A left upon evaporation should not be more than 0.25%. To determine this, take 25 grams of the glycerin and evaporate it at a temperature of about 160 degrees Celsius in a platinum basin and finish in an air bath. Weigh until constant weight is obtained. Afterwards incinerate over a Bunsen burner and weigh the ash. Footnote A. Organic matter up to 0.6% is not always prejudicial to the nitrating quantities of a glycerin. Silver test. A portion of the sample of glycerin to be tested should be put in a small weighing bottle, and a quarter of its bulk of N/10 silver nitrate solution added to it, then shake it, and place in a dark cupboard for 15 minutes. It must be pronounced bad if it becomes black or dark brown within that time, acrolein, formic, and butyric acids. The German official test for glycerin for pharmaceutical purposes is much more stringent. 1 cc of glycerin heated to boiling with 1 cc of ammonia solution and 3 drops of silver nitrate solution must give either color or precipitate within 5 minutes. Nitration. 50 grams of the glycerin are poured from a beaker into a mixture of concentrated nitric acid, specific gravity 1.53, and sulfuric acid, 1.84, mixed in the proportions of 3 to 5 H_2, so_4, about 400 cc of mixed acids. The mixed acids should be put into a rather large beaker, and held in the right hand in a basin of water, and the glycerin slowly poured into them from a smaller one held in the left. A constant rotatory motion should be given to the beaker in which the nitration is performed. When all the glycerin has been added, and the mixture has been shaken for a few minutes longer, it is poured into a separator, and allowed to stand for some time. It should, if the glycerin is a good one, have separated from the mixed acids in 10 minutes, and the line of demarcation between the nitroglycerin and the acid should be clear and sharp, either should there be any white flocculent matter suspended in the liquid. The excess of acids is now drawn off, and the nitroglycerin shaken once or twice with a warm solution of carbonate of soda, and afterwards with water alone. The nitroglycerin is then drawn off into a weighed beaker, the surface dried with a piece of filter paper, and weighed. 100 parts of a good glycerin should yield about 230 of nitroglycerin. A quicker method is to take only 10 cc of the glycerin, of which the specific gravity is already known, nitrate as before, and pour into a burette. Read off the volume of nitroglycerin in cc and multiply them by 1.6, the specific gravity of nitroglycerin, thus, 10 grams. Gave 14.5 cc nitroglycerin, and 14.5 times 1.6 is equal to 23.2 grams. Therefore 100 would give 232 grams. Nitroglycerin. The points to be noted in the nitration of a sample of glycerin are: the separation should be sharp, and within half an hour or less, and there should be no white flocculent matter formed, especially when the carbonate of soda solution is added. Total acid equivalent. Mr. G. Barton, Schur-Ammer. Chem. SOC 1895, proposes to determine thus: 100 cc of glycerin are diluted to 300 cc in a beaker, a few drops of a 1% solution of phenolphthalein and 10 cc of normal caustic soda solution are added. After boiling, the liquid is titrated with normal hydrochloric acid. Fatty acids are thus indicated and roughly determined. Neutrality. The same chemist determines the neutrality of glycerin, thus, 50 cc of glycerin mixed with 100 cc of water and a few drops of alcoholic phenolphthalein, A, are titrated with hydrochloric acid or sodium hydroxide. Not more than 0.3 cc normal hydrochloric acid or normal soda solution should be required to render the sample neutral. Raw glycerins contain from 0.5 to 1% of sodium carbonate. Footnote A. Sulman and Berry prefer litmus as indicator. Determination of free fatty acids. A weighed quantity of the glycerin is shaken up with some neutral ether in a separating funnel, the glycerin allowed to settle, drawn off, and the ether washed with 3 separate lots of water. The water must have been recently boiled, and be quite free from CO_2. All the free fatty acid is now in the ether, and no other soluble acid. A drop of phenolphthalein is now added, a little water, and the acidity determined by titration with decinormal baryta solution, and the baryta solution taken calculated as oleic acid. Combined fatty acid, about 30 grams, of the glycerin are placed in a flask, and to it is added about half a grm of caustic soda in solution. The mixture is heated for 10 minutes at 150 degrees Celsius. After cooling, some pure ether is added to it, and enough dilute H_2, so_4, to render it distinctly acid. It is well shaken. All the fatty acids go into the ether. The aqueous solution is then removed, and the ether well washed to remove all H_2, so_4. After the addition of phenolphthalein, the acid is titrated, and the amount used calculated into oleic acid. From this total amount of fatty acids, the free fatty acid is deducted, and the quantity of combined fatty acids thus obtained. Impurities. The following impurities may be found in bad samples of glycerin: lead, arsenic, lime, chlorine, sulfuric acid, thiosulfates, sulfides, cyanogen compounds, organic acids, especially oleic acid and fatty acids, rosin products, and other organic bodies. It is also said to be adulterated with sugar and glucose dextrine. Traces of sulfuric acid and arsenic may be allowed, also very small traces indeed of lime and chlorine. Footnote A. These substances often cause trouble in nitrating, white flocculent matter being formed during the process of washing. The organic acids, formic and butyric acids, may be detected by heating a sample of the glycerin in a test tube with alcohol and sulfuric acid, when, if present, compound ethers, such as ethylic formate and butyrate, the former smelling like peaches and the latter of pineapple, will be formed. Oleic acid, if present in large quantity, will come down upon diluting the sample with water, but smaller quantities may be detected by passing a current of nitrogen peroxide, N_2O_4, obtained by heating lead nitrate, through the diluted sample, when a white flocculent precipitate of oleic acid, which is less soluble than oleic acid, will be thrown down. By agitating glycerol with chloroform, fatty acids, rosin oil, and some other impurities are dissolved, while certain others form a turbid layer between the chloroform and the supernatant liquid. On separating the chloroform and evaporating it to dryness, a residue is obtained which may be further examined. Sodium chloride can be determined in 100 cc of the glycerin by adding a little water, neutralized with sodium carbonate, and then titrated with a decinormal solution of silver nitrate, using potassium chromate as indicator. Organic impurities of various kinds occur in crude glycerin, and are mostly objectionable. There some may be determined with fair accuracy by Sulman and Berry's method, 50 grams of the sample are diluted with twice its measure of water, carefully neutralized with acetic acid, and warmed to expel carbonic acid. When cold, a solution of basic lead acetate is added in slight but distinct excess, and the mixture well agitated. The formation of an abundant precipitate, which rapidly subsides, is an indication of considerable impurity in the sample. To ascertain its amount, the precipitate is first washed by decantation, and then collected on a tared, or preferably a double counterpoised filter, where it is further washed, dried at 100 degrees to 105 degrees Celsius, and weighed. The precipitate and filter paper are then ignited separately in porcelain, at a low red heat, The residues moistened with a few drops of nitric acid and reignited. The weight of the lead oxide deducted from that of the original precipitate gives the weight of the organic matter precipitated by the lead. Raw glycerins contain from 0.5 to 1% albuminous matters. An approximate determination of the albuminous matters may be made by precipitating with basic lead acetate as already described, and determining the nitrogen by the Kjeldal method. The nitrogen multiplied by 6.25 gives the amount of albuminous matter in the precipitate. The determination of glycerin. The acetone method of Benedict and Canton depends upon the conversion of glycerin into triacetone, and the saponification of the latter, and reduces the estimation of glycerin to an asymmetric method. About 1.5 grm of crude glycerin is heated to boiling with 7 grms of acetic anhydride and 3 to 4 grms of anhydrous sodium acetate under an upright condenser for 1.5 hours. After cooling, 50 cc of water are added, and the mixture heated until all the triacetone has dissolved. The liquid is then filtered into a large flask. The residue on the filter is well washed with water, the filtrate quite cooled, phenolphthalein is added and the fluid exactly neutralized with a dilute, 2 to 3%, solution of alkali. 25 cc of a 10% caustic soda solution, which must be accurately standardized upon normal acid, are then pipetted into the liquid, which is heated to boiling for 10 minutes to saponify the triacetone, and the excess of alkali is then titrated back with normal acid. 1 cc of normal acid corresponds to 0.03067 grm of glycerin. Precautions. The heating must be done with a reflux condenser, the triacetone being somewhat volatile. The sodium acetate used must be quite anhydrous, or the conversion of the glycerin to triacetyl is imperfect. Triacetone in contact with water gradually decomposes. After acetylation is complete, therefore, the operations must be conducted as rapidly as possible. It is necessary to neutralize the free acetic acid very cautiously, and with rapid agitation, so that the alkali may not be locally in excess. The lead oxide method, 2 grms of sample are mixed with about 40 grms of pure litharge, and heated in an air bath to 130 degrees Celsius, until the weight becomes constant, care being taken that the litharge is free from such lead compounds and other substances as might injuriously affect the results, and that the heating of the mixture takes place in an air bath free from carbonic acid. The increase in weight in the litharge, minus the weight of substance not volatilizable from 2 grms of glycerin at 160 degrees Celsius, multiplied by the factor 1.243, is taken as the weight of glycerin in the 2 grms of sample. The glycerin must be fairly pure, and free from resinous substances, and so _3, to give good results by this process. Analysis of the waste acids, from the manufacture of nitroglycerin or guncotton. Determine the specific gravity by the specific gravity bottle or hydrometer, and the oxides of nitrogen by the permanganate method described under nitroglycerin. Now determine the total acidity of the mixture by means of a 10th normal solution of sodium hydrate, and calculate it as nitric acid, No_3, then determine the nitric acid by means of lunge nitrometer, and subtract percentage found from total acidity, and calculate the difference into sulfuric acid thus. Total acidity equals 97.46%. 11.07%, No_3 equals 86.39%, then 86.39 by 49/63 equals 67.2%, H_2, so_4. Then analysis of sample will be: sulfuric acid equals 67.2%, nitric acid equals 11.07. Specific gravity equals 1.7075. Water equals 12.73. This method is accurate enough for general use in the nitric acid factory. The acid mixture may be taken by volume for determining nitric oxide in nitrometer. 2 cc is a convenient quantity in the above case, then 2 by 1.7075, specific gravity, equals 3.414 grms. Taken, gave 145 cc No, barometer equals 748 millimeters, and temperature equals 15 degrees Celsius. Equals 134.9 cc, CORR. And as 1 cc No equals 0.0282 grm. No underscore 3, 135 times 0.0282 is equal to 0.378 grm. Equals 11.07%, nitric acid. Sodium nitrate. Determine moisture and chlorine by the usual methods, and the total, nano underscore 3, by means of nitrometer 0.45 grm. Is a very convenient quantity to work on, gives about 123 cc gas. Grind very fine, and dissolve in a very little hot water in the cup of the nitrometer. Use about 15 cc concentrated H_2, so 4. 1 cubic cent of No equals 0.003805 grm. Of nano_3. The insoluble matter, both organic and inorganic, should also be determined, also sulfate of soda and lime tested for. Analysis of mercury fulminate, Divers and Kawakita's method. A weighed quantity of mercury fulminate is added to excess, but measured quantity of fuming hydrochloric acid contained in a retort connected with a receiver holding water. After heating for some time, the contents of the retort and receiver are mixed and diluted, and the mercury is precipitated by hydrogen sulfide. By warming and exposure to the air in open vessels, the hydrogen sulfide is for the most part dissipated. The solution is then titrated with potassium hydroxide (CO), as well as another quantity of hydrochloric acid, equal to that used with the fulminate. As the mercury chloride is reconverted into hydrochloric acid by the hydrogen sulfide, and as the hydroxylamine does not neutralize to litmus the hydrochloric acid combined with it, there is an equal amount of hydrochloric acid free or available in the two solutions. Any excess of acid in the one which has received the fulminate will therefore be due to the formic acid generated from the fulminate. Dr. Divers and M. Kawakita, working by this method, have obtained 31.31% formic acid instead of 32.40 required by theory. Jure-Chem. SOC, page 17, 1884. Divers and Kawakita proceed thus: 2.351 grms. Dissolved, as already described, in HCl, and afterwards diluted, gave mercury sulfide equal to 70.4%. Mercury. The same solution, after removal of mercury, titrated by iodine for hydroxylamine, gave nitrogen equal to 9.85%, and when evaporated with hydroxyl ammonium chloride equal to 9.55%, a solution of 2.6665 grms. Fulminate in HCl of known amount, after removal of mercury by hydrogen sulfide, gave by titration with potassium hydrate, formic acid equal to 8.17% of carbon. Collecting and comparing with calculation from formula we get Calc I 2. 3. Mercury 70.42 70.40, nitrogen 9.86 9.85 9.55, carbon 8.45. 8.17 oxygen 11.27, underscore 100.00. The analysis of cap composition. Messrs. F. W. Jones and F. A. Wilcox, Chem. News, December 11, 1896, have proposed the following process for the analysis of this substance. Cap composition usually consists of the ingredients, potassium chlorate, antimony sulfide, and mercury fulminate, and to estimate these substances in the presence of each other by ordinary analytical methods is a difficult process. Since the separation of antimony sulfide and mercury fulminate in the presence of potassium chlorate necessitates the treatment of the mixture with hydrochloric acid, and this produces an evolution of hydrogen sulfide from the sulfide, and a consequent precipitation of sulfur, and potassium chlorate cannot be separated from the other ingredients by treatment with water, owing to the appreciable solubility of mercury fulminate in cold water. In the course of some experiments on the solubility of mercury fulminate, Messrs. Jones and Wilcox observed that this body was readily soluble in acetone and other ethereal solvents when they were saturated with ammonia gas, and that chloride of potash and sulfate of antimony were insoluble in pure acetones saturated with ammonia. These observations at once afforded a simple method of separating the three ingredients of cap composition. By employing this solution of acetone and ammonia, an analysis can be made in a comparatively short time, and yields results of sufficient accuracy for all technical purposes. The following are the details of the process. A tared filter paper is placed in a funnel to the neck of which has been fitted a piece of rubber tubing provided with a clip. The paper is moistened with a solution of acetone and ammonia. The cap composition is weighed off directly onto the filter paper and is then covered with the solution of acetone and ammonia and allowed to stand 34 hours. It is then washed repeatedly with the same solution until the washings give no coloration with ammonium sulfate, and afterwards washed with acetone until washings give no residue on evaporation, dried and weighed. The paper is again put in the funnel and washed with water until free from potassium chlorate, dried and weighed. If C equals weight of composition taken, D equals filter paper, A equals. After first extraction, B equals second extraction, then C plus DA equals weight of fulminate, C plus DB equals Clo_3, BD equals sulfate of antimony. The composition should be finely ground in an agate mortar. The results of the analysis by this method of two mixtures of known composition are given below. Underscore 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 A B percentage 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 taken found taken found underscore 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 antimony sulfate 36.47 36.25 37.34 37.22 potassium chlorate 33.25 33.71 46.03 46.43 mercury fulminate 30.27 30.02 16.61 16.34 underscore 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 Dr. H. W. Brownsden's Schuer SOC Chem. IND 24. April 1905. Process is as follows. The cap composition is removed by squeezing the cap with pliers, while held over a porcelain basin of about 200 cc capacity, and removing the loosened foil and broken composition by means of a pointed wooden chip. Composition adhering to the shell or foil is loosened by alcohol, and washed into the dish by means of alcohol in a small wash bottle. The shell and foil are put to one side and subsequently weighed when dry. The composition in the dish is broken down quite fine with a flat-headed glass rod, and the alcohol evaporated on the water bath till the residue is moist, but not quite dry. 25 cc of water are then added, and the composition well stirred from the bottom. After the addition of 0.5 grm of pure sodium thiosulfate, the contents of the dish is well stirred for 2.5 minutes. 1 drop of methyl orange is then added, and the solution titrated with N/20 sulfuric acid, which has been standardized against weighings of 0.05 to 0.1 grm. Fulminate, to which 25 cc of water is added in a porcelain dish, then 0.5 grm of thiosulfate, and after stirring for 2.5 minutes, titrated with N/20 sulfuric acid. The small amount of antimony sulfide present does not interfere with the recognition of the end point. After titration, the solution is filtered through a small 5.5 cm filter paper, which retains the antimony sulfide. The filter paper containing the SB_2, S_3 is well washed and then transferred to a large 6x1 test tube. 5 cc of strong hydrochloric acid are added, and the contents of the tube boiled gently for a few seconds until the sulfate is dissolved and all the H_2 S driven off or decomposed. 2 to 3 cc of a saturated solution of tartaric acid are added, and the contents of the tube washed into a 250 cc Erlenmeyer flask. The solution is then nearly neutralized with sodium carbonate, excess of bicarbonate added, and after the addition of some starch solution titrated with N/20 iodine solution. This method for small quantities of stibnite is both quick and accurate, the error being about plus or minus 0.0003 grm. SB_2, S_3 at the outside. The tendency of this method is to give slightly low figures for the fulminate, but since these are uniform within a negligible error, it does not affect the value of the results as a criterion of uniformity. The following test results were obtained by Dr. Brownsdon. Underscore 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 fulminate taken. Fulminate found. Error. GRM. 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 0.0086, 0.0083. minus 0.0003, 0.0082, 0.0081, minus 0.0001, 0.0074, 0.0071, minus 0.0003, 0.0068, 0.0066, minus 0.0002. Underscore 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 stibnite taken. SB_2, S_3 found. Error. GRM. 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 0.0085, 0.0084, minus 0.0001. 0.0098, 0.0099, plus 0.0001, 0.0160, 0.0157, minus 0.0003, 0.0099, 0.0100. plus 0.0001 underscore 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 table for correction of volumes of gases for temperature, giving the divisor for the formula. V underscore 1 equals Vxb slash 760x 1 plus dt, d equals 0.003665, 1 plus dt from 0 degrees to 30 degrees Celsius. Underscore 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 T 760x 1 plus dt T 760x 1 plus dt T 760x 1 plus dt underscore 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 degree C 0.0 750.000 1.7 764.7352 3.4 769.4704 4.1 760.2785, 0.8, 765.0137, 0.5, 769.7489.2, 760.5571, 0.9, 765.2923, 0.6, 770.0274.3, 760.8356, 2.0, 765.5708, 0.7, 770.3060.4, 761.1142, 0.1, 765.8493, 0.8, 770.5845.5, 761.3927, 0.2, 766.1279, 0.9, 770.8631.6, 761.6712, 0.3, 766.4064, 4.0, 771.1416.7, 761.9498, 0.4, 766.6850, 0.1, 771.4201.8, 762.2283, 0.5, 766.9635, 0.2, 771.6987.9, 762.5069, 0.6, 767.2420, 0.3, 771.97721.0, 762.7854, 0.7, 767.5206, 4, 772.2558.1, 763.0639.8, 767.7991.5, 772.5343.2, 763.3425.9, 768.0777.6, 772.8128.3, 763.6210, 3.0, 768.3562.7, 773.0914.4, 763.8996.1, 768.6347.8, 773.3699.5, 764.1781.2, 768.9133.9, 773.6485.6, 764.4566.3, 769.1918, 5.0, 773.9270 underscore 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 T 760x 1 plus dt T 760x 1 plus dt T 760x 1 plus dt underscore 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 degree C degree C degree C 5.1 774.2055.9 787.5755.7 800.9454.2 774.4841 10.0 787.8540.8 801.2239.3 774.7626.1 788.1325.9 801.5025.4 775.0412.2 788.4111 15.0 801.7810.5 775.3197.3 788.6896.1 802.0595.6 775.5982.4 788.9682.2 802.3381.7 775.8768.5 789.2467.3 802.6166.8, 776.1553.6, 789.5252.4, 802.8952.9, 776.4339.7, 789.8038.5, 803.17376.0, 776.7124.8, 790.0823.6, 803.4522.1, 776.9909.9, 790.3609. 7, 803.7308.2, 777.2695, 11.0, 709, T, 760x, 1 plus dt. T, 760x, 1 plus dt. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Degree C. Degree C. Degree C. 19.5. 814.3153, 23.0, 824.0642.5, 833.8131.6, 814.5938.1, 824.3427.6, 834.0916.7, 814.8724.2, 824.6213.7, 834.3702.8, 815.1500.3, 824.8998.8, 834.648.7.9, 815.4925.4, 825.1784.9, 834.927320.0, 815.7080.5, 825.4569, 27.0, 835.2058.1, 815.9865.6, 825.7354.1, 835.4843.2, 816.2651.7, 826.0140.2, 835.7629.3, 816.5436.8, 826.2925.3, 836.0414.4, 816.8222.9, 826.5711.4, 836.3200.5, 817.1007, 24.0, 826.8496.5, 836.5985.6, 817.3792.1, 827.1281.6, 836.8770.7, 817.6578.2, 827.4067.7, 837.1556.8, 817.9363.3, 827.6852.8, 837.4341.9, 818.2149.4, 827.9638.9, 837.712721.0, 818.4934.5, 828.2423, 28.0, 837.9912.1, 818.7719.6, 828.5208.1, 838.2697.2, 819.0505.7, 828.7994.2, 838.5483.3, 819.3290.8, 829.0779.3, 838.8268.4, 819.6076.9, 829.3565.4, 839.1054.5, 819.8861, 25.0, 829.6350.5, 839.3839.6, 820.1646.1, 829.9135.6, 839.6624.7, 820.4432.2, 830.1921.7, 839.9410.8, 820.7217.3, 830.4706.8, 840.2195.9, 821.0003.4, 830.7492.9, 840.498122.0, 821.2788.5, 831.0277.29.0, 840.7766.1, 821.5573.6, 831.3062.1, 841.0551.2, 821.8859.7, 831.5848.2, 841.3337.3, 822.1144.8, 831.8633.3, 841.6122.4, 822.3930.9, 832.1419.4, 841.8908.5, 822.6715, 26.0, 832.4204.5, 842.1693.6, 822.9500.1, 832.6989.6, 842.4478.7, 823.2286.2, 832.9775.7, 842.7264.8, 823.5071.3, 833.2560.8, 843.0049.9, 823.7857.4, 833.5346.9, 843.2835, 30.0, 843.5620 underscore 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 underscore. Chapter 8. Firing point of explosives, heat tests, and C. Horsley's apparatus. Table of firing points. The government heat test apparatus for dynamites, nitroglycerin, nitro-cotton, and smokeless powders. Liquefaction and exudation tests. Page's regulator for heat test apparatus. Specific gravities of explosives. Table of temperature of detonation, sensitiveness, and C. The firing point of explosives. The firing point of an explosive may be determined as follows. A copper dish, about 3 inches deep, and 6 or more wide, and fitted with a lid, also of copper, is required. The lid contains several small holes, into each of which is soldered a thick copper tube about 5 millimeters in diameter, and 3 inches long, with a rather larger one in the center in which to place a thermometer. The dish is filled with Rose's metal, or paraffin, according to the probable temperature required. The firing point is then taken thus. After putting a little piece of asbestos felt at the bottom of the center tube, the thermometer is inserted, and a small quantity of the explosive to be tested is placed in the other holes. The lid is then placed on the dish containing the melted paraffin or metal, in such a way that the copper tubes dip below the surface of the liquid. The temperature of the bath is now raised until the explosive fires, and the temperature noted. The initial temperature should also be noted. The firing point of various explosives by C. E. Monroe. Horsley's apparatus used. Underscore 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 degree C. Nitroglycerin, 5 years old, a single drop taken, 203 to 205 gun cotton. Compressed military cotton, SPGR 1.5, 192 to 201 air-dried gun cotton, stored for 4 years, 179 to 187 ditto, stored for 1 year, 187 to 189 air-dried collodion cotton, long staple. Red Island cotton, 3 years old, 186 to 191 air-dried collodion, 3 years old, stored wet, 197 to 199 hydronitrocellulose, 201 to 213 Kieselguhr dynamite, number 1, 197 to 200 explosive gelatin, 203 to 209 mercury fulminate, 175 to 181 gunpowder shell, 278 to 287 Hills picric powder, shells, been in store 10 years. 273 to 283 ditto, musket, composed of 282 to 290 ammonium picrate 42.18%, potassium picrate 53.79, charcoal, alder 3.85, underscore 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 99.82, for site, number 1. 187 to 200 Atlas powder, 75% ing, 175 to 185 emmensite, number 1 sample had been stored in, 167 to 184 magazine for some months in a wooden box, number 2 stored in tin case, 165 to 177, number 5. 205 to 217 underscore 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 degree C. Powder used in Chassepot rifle 191 by Leg and Champion. French gunpowder 295, rifle powder pick rate 358, cannon 380. Underscore 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 underscore. Horsley's apparatus consists of an iron stand with a ring support, holding a hemispherical iron vessel or bath in which solid paraffin is put. Above this is another movable support, from which a thermometer is suspended, and so adjusted that its bulb is immersed in the material contained in the iron vessel. A thin copper cartridge case, 5/8 inch in diameter and 1 15/16 inch long, is suspended over the bath by means of a triangle, so that the end of the case is just 1 inch below the surface of the molten material. On beginning the experiment of determining the firing point of any explosive, the material in the bath is heated to just above the melting point. The thermometer is inserted in it, and a minute quantity of the explosive is placed in the bottom of the cartridge case. The initial temperature is noted, and then the cartridge case containing the explosive is inserted in the bath. The temperature is quickly raised until the contents of the cartridge case flash off or explode, when the temperature is noted as the firing point. Illustration: Figure 46. Heat test apparatus. Professor C. Monroe, of the U.S. Torpedo Station, has determined the firing point of several explosives by means of this apparatus. The Government Heat Test, Explosives Act, 1875 apparatus required: a water bath, consisting of a spherical copper vessel, Figure 46, of about 8 inches diameter, and with an aperture of about 5 inches. The bath is filled with water to within 1/4 inch of the edge. It has a loose cover of sheet copper about 6 inches in diameter, B, and rests on a tripod stand about 14 inches high, C, which is covered with coarse wire gauze, E, and is surrounded with a screen of thin sheet copper, D. Within the latter is placed an argan burner, F, with glass chimney. The cover, B, has 4 holes arranged, as seen in Figure 2, number 4 to contain a pages, A, or skybliss regulator, number 3 the thermometer, numbers 1 and 2 the test tubes containing the explosive to be tested. Around the holes 1 and 2 on the underside of the cover are soldered 3 pieces of brass wire with points slightly converging, Figure 3. These act as springs, and allow the test tubes to be easily placed in position and removed. Footnote A. See Chem. SOC Jour, 1876, I. 24, FJM page. Test tubes, from 5 1/4 to 5 1/2 inches long, and of such a diameter that they will hold from 20 to 22 cubic centimeters of water when filled to a height of 5 inches. Rather thick glass is preferable. India rubber stoppers, fitting the test tubes, and carrying an arrangement for holding the test papers, viz. a narrow glass tube passing through the center of the stopper, and terminating in a platinum wire hook. A glass rod drawn out and the end turned up to form a hook is better. The thermometer should have a range from 30 degrees to 212 degrees Fahrenheit, or from 1 degree to 100 degrees Celsius. A minute clock is useful. Test paper. The test paper is prepared as follows: 45 grains, 2.9 grams, of white maize starch, corn flour, previously washed with cold water, are added to 8½ ounces of water. The mixture is stirred, heated to boiling, and kept gently boiling for 10 minutes. 15 grains, 1 grm, of pure potassium iodide, previously recrystallized from alcohol, absolutely necessary, are dissolved in 8.5 ounces of distilled water. The two solutions are thoroughly mixed and allowed to get cold. Strips or sheets of white English filter paper, previously washed with water and re-dried, are dipped into the solution thus prepared, and allowed to remain in it for not less than 10 seconds. They are then allowed to drain and dry in a place free from laboratory fumes and dust. The upper and lower margins of the strips or sheets are cut off, and the paper is preserved in well-stoppered or corked bottles, and in the dark. The dimensions of the pieces of test paper used are about 4/10 inch by 8/10 inch, 10 mm, by 20 mm. Footnote A. When the paper is freshly prepared, and as long as it remains in good condition, a drop of diluted acetic acid put on the paper with a glass rod produces no coloration. In process of time it will become brownish, when treated with the acid, especially if it has been exposed to sunlight. It is then not fit for use. In Germany, zinc iodide starch paper is used, which is considered to be more sensitive than potassium iodide. Standard tint paper. A solution of caramel in water is made of such concentration that when diluted 100 times, 10 cc made up to 1 liter, the tint of this diluted solution equals the tint produced by the Nessler test in 100 cc water containing 0.000075 grm of ammonia, or 0.00023505 grm. Amcal. With this caramel solution, lines are drawn on strips of white filter paper, previously well washed with distilled water, to remove traces of bleaching matter, and dried by means of a quill pen. When the marks thus produced are dry, the paper is cut into pieces of the same size as the test paper previously described, in such a way that each piece has a brown line across it near the middle of its length, and only such strips are preserved in which the brown line has a breadth varying from 1/2 mm to 1 mm, 1/50 of an inch to 1/25 of an inch. Testing dynamite, blasting gelatin, and gelatin dynamite, nitroglycerin preparations, from which the nitroglycerin can be extracted in the manner described below, must satisfy the following test, otherwise they will not be considered as manufactured with thoroughly purified nitroglycerin, viz. 15 minutes at 160 degrees Fahrenheit, 72 degrees Celsius. Apparatus required: a funnel 2 inches across, d, a cylindrical measure divided into grains, e, figure 47. Mode of operation: about 319.4 grms to 400 grains, 26 grms of dynamite, b, finely divided, are placed in the funnel, which is loosely plugged by freshly ignited asbestos, A. The surface is smoothed by means of a flat-headed glass rod or stopper, and some clean washed and dried kieselguhr, C, is spread over it to the depth of about 1/8 inch. Water is then poured on from a wash bottle, and when the first portion has been soaked up, more is added. This is repeated until sufficient nitroglycerin has collected in the graduated measure, E. If any water should have passed through, it must be removed from the nitroglycerin by filter paper, or the nitroglycerin may be filtered. Illustration: Figure 47. Apparatus for separating the nitroglycerin from dynamite. Illustration: Figure 48. Test tube arranged for heat test. Application of test. The thermometer is fixed so as to be inserted through the lid of the water bath into the water, which is maintained at 160 degrees Fahrenheit, 72 degrees Celsius, to a depth of 2 3/4 inches. 50 grains equals 3.29 grms of nitroglycerin to be tested are weighed into the test tube, in such a way as not to soil the sides of the tube. Use a pipette. A test paper is fixed on the hook of the glass rod, so that when inserted into the tube it will be in a vertical position. A sufficient amount of a mixture of half distilled water and half glycerin, to moisten the upper half of the paper, is now applied to the upper edge of the test paper by means of a glass rod or camel's hair pencil. The cork carrying the rod and paper is fixed into the test tube, and the position of the paper adjusted so that its lower edge is about halfway down the tube. The latter is then inserted through one of the holes in the cover to such a depth that the lower margin of the moistened part of the paper is about 5/8 inch above the surface cover. The test is complete when the faint brown line, which after a time makes its appearance at the line of boundary between the dry and moist part of the paper, equals in tint the brown line of the standard tint paper. Blasting gelatin, gelatin dynamite, gel ignite, and C. 50 grains, equals 3.29 grms. Of blasting gelatin are intimately mixed with 100 grains, equals 6.5 grms. Of French chalk. This is done by carefully working the two materials together with a wooden pestle and a wooden mortar. The mixture is then gradually introduced into the test tube, with the aid of gentle tapping upon the table between the introduction of successive portions of the mixture into the tube, so that when the tube contains all the mixture it shall be filled to the extent of 1 3/4 inch of its height. The test paper is then inserted as above described for nitroglycerin. The sample tested must stand a temperature of 160 degrees Fahrenheit for a period of 10 minutes before producing a discoloration of the test paper corresponding in tint to the standard paper. NB. Non-gelatinized nitroglycerin preparations, from which the nitroglycerin cannot be expelled by water, are tested without any previous separation of the ingredients, the temperature being as above 160 degrees Fahrenheit, and the time being 7 minutes. Gun cotton, Schulze gunpowder, EC powder, and C.A. compressed gun cotton. Sufficient material to serve for 2 or more tests is removed from the center of the cartridge by gentle scraping, and if necessary, further reduced by rubbing between the fingers. The fine powder thus produced is spread out in a thin layer upon a paper tray 6 inches by 4.5 inches, which is then placed inside a water oven, kept as nearly as possible at 120 degrees Fahrenheit. 49 degrees Celsius. The wire gauze shelves of the oven should be about 3 inches apart. The sample is allowed to remain at rest for 15 minutes in the oven, the door of which is left wide open. After the lapse of 15 minutes, the tray is removed and exposed to the air of the room for 2 hours, the sample being at some point within that time rubbed upon the tray with the hand, in order to reduce it to a fine and uniform state of division. The heat test is performed as before, except that the temperature of the bath is kept at 170 degrees Fahrenheit, 66 degrees Celsius, and regulator set to maintain that temperature. 20 grains, 1.296 grm, are used, placed in the test tube, gently pressed down until it occupies a space of as nearly as possible 1 5/10 inch in the test tube of dimensions previously specified. The fine cotton adhering to the sides of the tube can be removed by a clean cloth or silk handkerchief. The paper is moistened by touching the upper edge with a drop of the 50% glycerin solution, the tube inserted in the bath to a depth of 2.5 inches, measured from the cover, the regulator and thermometer being inserted to the same depth. The test paper is to be kept near the top of the test tube, but clear of the cork, until the tube has been immersed for about 5 minutes. A ring of moisture will about this time be deposited upon the sides of the test tube, a little above the cover of the bath. The glass rod must then be lowered until the lower margin of the moistened part of the paper is on a level with the bottom of the ring of moisture and the tube. The paper is now closely watched. The test is complete when a very faint brown coloration makes its appearance at the line of boundary between the dry and moist parts of the paper. It must stand the test for not less than 10 minutes at 170 degrees Fahrenheit. The time is reckoned from the first insertion of the tube in the bath until the appearance of a discoloration of the test paper. B. Schulze powder, EC powder, collodion cotton, and C. The sample is dried in the oven as above for 15 minutes, and exposed for 2 hours to the air. The test as above for compressed gun cotton is then applied. C. Cordite must stand a temperature of 180 degrees Fahrenheit for 15 minutes. The sample is prepared as follows. Pieces half an inch long are cut from one end of every stick selected for the test. In the case of the thicker cordites, each piece so cut is further subdivided into about 4 portions. These cut pieces are then passed once through the mill, the first portion of material which passes through being rejected on account of the possible presence of foreign matter from the mill. The ground material is put on the top sieve of the nest of sieves, and sifted. That portion which has passed through the top sieve and been stopped by the second is taken for the test. If the mill is properly set, the greater portion of the ground material will be of the proper size. If the volatile matter in the explosive exceeds 0.5%, the sifted material should be dried at a temperature not exceeding 140 degrees Fahrenheit, until the proportion does not exceed 0.5%. After each sample has been ground, the mill must be taken to pieces and carefully cleaned. The sieves used consist of a nest of 2 sieves with holes drilled in sheet copper. The holes in the top sieve have a diameter equals 14 bwg, those in the second equals 21 bwg. If too hard for the mill, the cordite may be softened by exposure to the vapor of acetone, A, or reduced to the necessary degree of subdivision by means of a sharp moderately coarse rasp. Should it have become too soft in the acetone vapor for the mill, it should be cut up into small pieces, which may be brought to any desired degree of hardness by simple exposure to air. Explosives which consist partly of gelatinized collodion cotton and partly of ungelatinized gun cotton are best reduced to powder by a rasp, or softened by exposure to mixed ether and alcohol vapor at a temperature of 40 degrees Fahrenheit to 100 degrees Fahrenheit. Footnote A. Mr. W. Cullen, Jur. Soc. Chem. IND, January 31, 1901 says, "Undoubtedly the advent of the horny smokeless powders of modern times has made it a little difficult to give the test the same scope as it had when first introduced. As a rule, a simple explanation can be found for every apparently abnormal result, and in the accidental retention of a portion of the solvent used in the manufacture, will frequently be found an explanation of the trouble experienced. Ballastite. In the case of ballastite, the treatment is the same, except that when it is in a very finely granulated condition, it need not be cut up." Gutman's heat test. This test was proposed by Mr. Oscar Gutman in a paper read before the Society of Chemical Industry, Volume 16, 1897, in the place of the potassium iodide starch paper used in the Abel test. The filter paper used is wetted with a solution of diphenylamine, A, in sulfuric acid. The solution is prepared as follows. Take 0.100 grm of diphenylamine crystals, put them in a wide-necked flask with a ground stopper, add 50 cc of dilute sulfuric acid, 10 cc of concentrated sulfuric acid to 40 cc of water, and put the flask in a water bath at between 50 degrees and 55 degrees Celsius. At this temperature the diphenylamine will melt, and at once dissolve in the sulfuric acid, when the flask should be taken out, well shaken, and allowed to cool. After cooling, add 50 cc of Price's double distilled glycerin, shake well, and keep the solution in a dark place. The test has to be applied in the following way. The explosives that have to be tested are finely subdivided: gun cotton, nitroglycerin, dynamite, blasting gelatin, and C, in the same way as at present directed by the Home Office regulations. Smokeless powders are all to be ground in a bell-shaped coffee mill as finely as possible, and sifted as hitherto. 1.5 grm of the explosive, from the second sieve in the case of smokeless powder, is to be weighed off and put into a test tube as hitherto used. Strips of well-washed filter paper, 25 mm wide, are to be hung on a hooked glass rod as usual. A drop of the diphenylamine solution is taken up by means of a clean glass rod, and the upper corners of the filter paper are touched with it, so that when the 2 drops run together about a quarter of the filter paper is moist. This is then put into the test tube, and this again into the water bath, which has been heated to 70 degrees Celsius. The heat test reaction should not show in a shorter time than 15 minutes. It will begin by the moist part of the paper acquiring a greenish-yellow color, and from this moment the paper should be carefully watched. After 1 or 2 minutes a dark blue mark will suddenly appear on the dividing line between the wet and dry part of the filter paper, and this is the point that should be taken. Footnote A. DRG. Spica, Revista, August 1897, proposes to use hydrochloride of metaphenylenediamine. Exudation and liquefaction test for blasting gelatin, gelatin dynamite, and C. A cylinder of blasting gelatin, and C, is to be cut from the cartridge to be tested, the length of the cylinder to be equal to its diameter, and the ends being cut flat. The cylinder is to be placed on end on a flat surface without any wrapper, and secured by a pin passing vertically through its center. In this condition the cylinder is to be exposed for 144 consecutive hours, 6 days and nights, to a temperature ranging from 85 degrees to 90 degrees Fahrenheit, inclusive. And during such exposure the cylinder shall not diminish in height by more than 1/4 of its original height, and the upper cut surface shall retain its flatness and the sharpness of its edge. Exudation test. There shall be no separation from the general mass of the blasting gelatin or gelatin dynamite of a substance of less consistency than the bulk of the remaining portion of the material under any conditions of storage, transport, or use, or when the material is subjected 3 times in succession to alternate freezing and thawing, or when subjected to the liquefaction test before described. Picric acid. The material shall contain not more than 0.3 part of mineral or non-combustible matter in 100 parts by weight of the material dried at 160 degrees Fahrenheit. It should not contain more than a minute trace of lead. 100 parts of the dry material shall not contain more than 0.3 part of total, free and combined, sulfuric acid, of which not more than 0.1 part shall be free sulfuric acid. Its melting point should be between 248 degrees and 253 degrees Fahrenheit. Ammonite, bellite, roburite, and explosives of similar composition, these are required to stand the same heat test as compressed nitrocellulose, guncotton, and C. Chlorid mixtures. The material must not be too sensitive, and must show no tendency to increase in sensitiveness in keeping. It must contain nothing liable to reduce the chlorit. Chlorides calculated as potassium chloride must not exceed 0.25%. The material must contain no free acid, or substance liable to produce free acid. Explosives of this class containing nitro compounds will be subject to the heat test. Page's regulator. The most convenient gas regulator to use in connection with the heat test apparatus is the one invented by Professor F.J.M. Page, Bachelors of Science, A, Figure 49. It is not affected by variations of the barometric pressure, and is simple and easy to fit up. It consists of a thermometer with an elongated glass bulb 5/8 inch diameter and 3 inches long. The stem of the thermometer is 5 inches long and 1/8 inch to 3/16 inch internal diameter. 1.5 inch from the top of the stem is fused in at right angles a piece of glass tube, 1 inch long, of the same diameter as the stem, so as to form a T. A piece of glass tube, A, about 7/16 inch external diameter and 1.5 inch long, is fitted at one end with a short, sound cork, see Figure 50. Through the center of this cork a hole is bored, so that the stem of the thermometer just fits into it. The other end of this glass tube is closed by a tightly fitting cork, preferably of India rubber, I, which is pierced by a fine bradawl through the center. Into the hole thus made is forced a piece of fine glass tube, B, 3 inches long, and small enough to fit loosely inside the stem of the thermometer. Footnote A. Chemical SOC Jour, 1876, I. 24. The thermometer is filled by pouring in mercury through a small funnel until the level of the mercury, when the thermometer is at the desired temperature, is about 1.5 inch below the T. The piece of glass tube A, closed at its upper extremity by the cork I, through which the fine glass tube B passes into the stem of the thermometer, is now filled by means of the perforated cork at its lower extremity on the stem of the thermometer. The gas supply tube is attached to the top of the tube A, the burner to the T, so that the gas passes in at the top, down the fine tube B, rises in the space between B and the inside wall of the stem of the thermometer, and escapes by the T. The regulator is set for any given temperature by pushing the cork C, and consequently the tubes A and B, which are firmly attached to it, up or down the stem of the thermometer, until the regulator just cuts off the gas at the desired temperature. Illustration, Figure 49. Page's regulator. Illustration, Figure 50. Page's gas regulator, showing bypass and cutoff arrangement. As soon as the temperature falls, the mercury contracts, and thus opens the end of the tube B. The gas is thus turned on, and the temperature rises until the regulator again cuts off the gas. In order to prevent the possible extinction of the flame by the regulator, the brass tube which carries the gas to the regulator is connected with the tube which brings the gas from the regulator to the burner by a small brass tap, Figure 2. This tap forms an adjustable bypass, and thus a small flame can be kept burning, even though the regulator be completely shut off. It is obvious that the quantity of gas supplied through the bypass must always be less than that required to maintain the desired temperature. This regulator, placed in a beaker of water on a tripod, will maintain the temperature of the water during 4 or 5 hours within 0.2 degrees Celsius, and an air bath during 6 weeks within 0.5 degrees Celsius. To sum up briefly the method of using the regulator: being filled with mercury to about 1/2 inch below the T, attach the gas supply as in diagram, figure 2, the brass tap being open, and the tube be unclosed by the mercury. Allow the gas to completely expel the air in the apparatus. Push down the tube so that the end of B is well under the surface of the mercury. Turn off the tap of the bypass until the smallest bead of flame is visible. Raise A and B, and allow the temperature to rise until the desired point is attained. Then push the tubes A and B slowly down until the flame is just shut off. The regulator will then keep the temperature at that point. Will's test for nitrocellulose. The principle of Dr. W. Will's test, A, may be briefly described as follows. The regularity with which nitrocellulose decomposes under conditions admitting of the removal of the products of decomposition immediately following their formation is a measure of its stability. As decomposing agent, a sufficiently high temperature, 135 degrees Celsius, is employed, the explosive being kept in a constantly changing atmosphere of carbon dioxide, heated to the same temperature. The oxides of nitrogen which result are swept over red-hot copper, and are then reduced to nitrogen, and finally, the rates of evolution of nitrogen are measured and compared. Dr. Will considers that the best definition and test of a stable nitrocellulose is that it should give off at a high temperature equal quantities of nitrogen in equal times. For the purposes of manufacture, it is specially important that the material should be purified to its limit, i.e., the point at which further washing produces no further change in its speed of decomposition measured in the manner described. Footnote A. W. Will Mitt. A. D. Centralstelle F. Wissenschaft. Techn. Untersuchungen no Babelsberg Berlin, 1902, 5-24. The sample of gun cotton, 2.5 grms, is packed into the decomposition tube 15 mm wide and 10 cm high, and heated by an oil bath to a constant temperature. The oxides so produced are forced over ignited copper, where they are reduced, and the nitrogen retained in the measuring tubes. Care must be taken that the acid decomposition products do not condense in any portion of the apparatus. The air in the whole apparatus is first displaced by a stream of carbon dioxide issuing from a carbon dioxide generator, or gas holder, and passing through scrubbers, and this stream of gas is maintained throughout the whole of the experiment, the gas being absorbed at the end of the system by strong solution of caustic potash. To guard against the danger of explosions, which occasionally occur, the decomposition tube and oil bath are surrounded by a large casing with walls composed of iron plate and strong glass. Dr. Will's apparatus has been modified by Dr. Robertson, A., of the Royal Gunpowder Factory, Waltham Abbey. The form of the apparatus used by him is shown in Figure 51. Co_2 holders. Although objection has been taken to the use of compressed Co_2 in steel cylinders on account of the alleged large and variable amount of air present, it has, nevertheless, been found possible to obtain this gas with as little as 0.02% of air. Frequent estimations of the air present in the Co_2 of a cylinder show that even with the commercial article, after the bulk of the Co_2 has been removed, the residual gas contains only a very small amount of air, which decreases in a gradual and perfectly regular manner. For example, one cylinder which gave 0.03% of air by volume, after 3 months' constant use gave 0.02%. The advantage of using Co_2 from this source is obvious when compared with the difficulty of evolving a stream of gas of constant composition from a Kipps or Finkner apparatus. A micrometer screw, in addition to the main valve of the Co_2 cylinder, is useful for governing the rate of flow. A blank experiment should be made to ascertain the amount of air in the Co_2 and the correction made in the readings afterwards. Footnote A. Jour Soc Chem. IND, June 30, 1902, page 819. Illustration, figure 51. Will's apparatus for testing nitrocellulose. Measurement of pressure and rate of flow. Great attention is paid to the measurement of the rate of flow of gas, which is arrived at by counting with a stopwatch the number of bubbles of gas per minute in a small sulfuric acid wash bottle. A mercury manometer is introduced here, and is useful for detecting a leak in the apparatus. The rate of flow that gives the most satisfactory results is 1000 cc per hour. If too rapid, it does not become sufficiently preheated in the glass spiral, and if too slow, there is a more rapid decomposition of the nitrocellulose by the oxides of nitrogen which are not removed. Decomposition tube. This is of the form and dimensions given by Dr. Will, 15 mm wide and 10 cm high, the preheating worm being of the thinnest hydrometer stem tubing. The ground and exit tube is kept in position by a small screw clamp with trunnion bearings. Bath. To permit of 2 experiments being carried on simultaneously, the bath is adapted for 2 decomposition tubes, and is on the principle of Lothar-Meyer's air bath, that is, the bath proper filled with a high-flashing hydrocarbon oil, and fitted with a lid perforated with 2 circular holes for the spiral tubes, is surrounded by an asbestos-covered envelope, in the interior of which circulate the products of combustion of numerous small gas jets. The stirrer, agitated by a water motor or, better still, a hot air engine, has a series of helical blades curved to give a thorough mixing to the oil. Great uniformity and constancy of temperature are thus obtained. The bath is fitted also with a temperature regulator and thermometer. Reduction tube. This is of copper, and consists of 2 parts, the outer tube and an inner reaching to nearly the bottom of the former. Into the inner tube fits a spiral of reduced copper gauze, and into the annular space between the tubes is fitted a tightly packed reduced copper spiral. At the bottom, the inlet tube dips into a layer of copper oxide asbestos, on the top of which is a layer of reduced copper asbestos. Through the india rubber cork passes a glass tube, which leads the CO_2 and nitrogen out of the reduction tube. As the portion of the tube containing the spirals is heated to readiness, water jackets are provided on both inner and outer tubes to protect the india rubber cork. Nitrogen measuring apparatus. The measuring tube with zigzag arrangement is used, having been found very economical in potash. It is most convenient to take readings by counterbalancing the column of potash solution and reading off the volume of gas at atmospheric pressure. For this purpose, the tap immediately in front of the measuring tube is momentarily closed, this having been proved to be without ill effect on the progress of the test. In all experiments done by this test, the air correction is subtracted from each reading, and the remainder brought to milligrams of nitrogen with the usual corrections. As objection has frequently been taken to the test on the ground of difficulty in interpreting the results obtained, Dr. Robertson made a series of experiments for the purpose of standardizing the test, and at the same time of arriving at the condition under which it could be applied in the most sensitive and efficient manner. A variety of nitrocelluloses having been tested, there were chosen as typical, of stable and unstable products, service gun cotton on the one hand, and an experimental gun cotton, Z, on the other. The first point brought out by these experiments was the striking uniformity of service gun cotton, first in regard to the rectilinear nature of the curve of evolution of nitrogen, and secondly in regard to the small range within which a large number of results is included, 15 samples lying between 6.6 and 8.7 mg/ms of nitrogen evolved in 4 hours. In the case of service gun cotton, little difference in the rate of evolution of nitrogen evolved is obtained on altering the rate of passage of CO_2 gas through the wide range of 500 cc per hour to 2500 cc per hour. With Z gun cotton, see figure 52, however, the case is very different. Operating at a rate of 1000 cc of CO_2 per hour, a curve of nitrogen evolution is obtained, which is bent and forms a good representation of the inherent instability of the material as proved to exist from other considerations. Operating at the rate of 1500 cc per hour, as recommended by Dr. Will, the evolution of nitrogen is represented by a straight line, steeper, however, than that of service gun cotton. The rate of passage of CO_2 was therefore chosen at 1000 cc per hour, or 2/3 of the rate of Dr. Will, and this rate, besides possessing the advantage claimed of rendering diagnostic the manner of nitrogen evolution in Z-gun cotton, has in other cases been useful in bringing out relationships, which the higher rate would have entirely masked. Illustration, Figure 52. Dr. Robertson's results. Illustration, Figure 53. Service gun cotton for cordite made at a private factory. Readings are taken 30 minutes from the time the nitrocellulose is heated, and are taken at intervals of 15 minutes for about 4 hours. Fresh caustic potash is added every 30 minutes or so. It is convenient to plot the results in curves. The curves given in Figure 53 are from gun cotton manufacturers in England at a private factory. The rate of evolution of nitrogen is as follows: in 1 hour, in 2 hours, in 3 hours, in 4 hours, n in milligrams. 1.25, 2.55, 4.55, 0.75, 1.53, 0.25, 5.25, 6.75. These results are very satisfactory. The gun cotton was of a very good quality. Several hours are necessary to remove all the air from the apparatus. Dr. Will stated 15 minutes in his original paper, but this has not been found sufficient. It has not been satisfactorily proved that Will's test can be applied to gelatinized nitrocellulose powders. It is convenient to plot the results in curves. The nitrogen is generally given in cubic centimeters or in milligrams, and readings taken every 15 minutes. The steepness of the curve is a measure of the stability of the nitrocellulose which is being examined. The steeper the curve, the more nitrogen is evolved per unit of time, and the less stable the nitrocellulose. In the case of unstable nitrocelluloses heated under the conditions described, the separation of nitrogen is much greater at first than at a later period. If the nitrocellulose be very unstable, explosions are produced. If the separation of nitrogen is uniform during the prolonged heating, then the nitrocellulose may be regarded as normal. If it be desired to determine the absolute amount of nitrogen separated from a nitrocellulose, the following conditions must be observed: 1. Accurate weighing of the nitrocellulose. 2. Determination of the amount of air in the co-2, and deduction of this from the volume of gas obtained. 3. Reduction of the volume of the gas to the volume at 0 degrees Celsius. And 760 millimeters. Pressure, A. Footnote A. See also Jour SOC Chem. IND, December 1902. Pages 1545 to 1555, on the stability of nitrocellulose and examination of nitrocellulose. Dr. Will. Bergernan and Junk, A. describe a test for nitrocellulose that has been in use in the Prussian testing station for some years. The apparatus consists of a closed copper bath provided with a condenser and 10 countersunk tubes of 20 centimeters length. By boiling amyl alcohol in the bath, the tubes can be kept at a constant temperature of 132 degrees Celsius. The explosive to be tested is placed in a glass tube 35 centimeters long and 2 centimeters wide, having a ground neck into which an absorption bulb is fitted. The whole apparatus is surrounded by a shield, in case of explosion. In carrying out the tests, 2 grams of the explosive are placed in the glass tube and well pressed down. The absorption bulb is half filled with water, and fitted into the ground neck of the glass tube, which is then placed in one of the tubes in the bath previously brought to the boiling point, 132 degrees Celsius. The evolved oxides of nitrogen are absorbed in the water in the bulb, and at the end of 2 hours the tubes are removed from the bath, and on cooling, the water from the bulb flows back and wets the explosive. The contents of the tube are filtered and washed. The filtrate is oxidized with permanganate, and the nitrogen determined as nitric oxide by the Schulze-Tiemann method. The authors conclude that a stable gun cotton does not evolve more than 2.5 cc of nitric oxide per grm. On being heated to 132 degrees Celsius for 2 hours, and a stable collodion cotton not more than 2 cc under the same conditions. The percentage of moisture in the sample to be tested should be kept as low as possible. A sample of nitrocellulose containing 1.97% of moisture gave an evolution of 2.6 cc per grm, while the same sample with 3.4% moisture gave an evolution of over 50 cc per grm. Sodium carbonate added to an unstable nitrocellulose diminishes the rate of decomposition, but if sodium carbonate be intimately mixed with a stable nitrocellulose, the rate of decomposition will be increased. Calcium carbonate and mercury chloride have no influence. If an unstable nitrocellulose be extracted with alcohol, a stable compound is produced. The percentage solubility of a nitrocellulose in ether alcohol rises on heating to 132 degrees Celsius. A sample which before heating had a solubility of 4.7% had its solubility increased to 82.5% after 6 hours heating. Footnote A. Jour SOC Chem. IND 23. October 15, 1904, page 953. Mr. APSY Schurhammer. Chem. SOC 1903 describes a new stability test for nitrocellulose which he terms the elastic limit of powder resistance to heat. The test consists in heating the powder on a watch glass in an oven to a temperature of 115 degrees Celsius. After 8 hours, the watch glass and powder are weighed and the process repeated daily for 6 days or less. He claims that the powder is tested in its natural state. All the products of decomposition are taken into account, whilst in the old tests only the acid products are shown, and in the wool test only nitrogen, that it affords an indication of the effect of small quantities of added substances or foreign matters on the stability, and that it is simple, and not subject to the variations of the old tests. Obermuller, Jour SOC Chem. IND, April 15, 1905, considers Bergman and Junk's test is too complicated and occupies too much time. He proposes to heat guncotton to 140 degrees Celsius in vacuo, and to measure continuously by means of a mercury manometer the pressure exerted by the evolved gases, the latter being maintained at constant volume. The rate at which the pressure increases is a measure of the rate of decomposition of the nitrocellulose. Specific gravities of explosives, and c. Nitroglycerin 1.6 guncotton, dry, 1.06. 25% water. 1.32 dynamite number 1 1.62 blasting gelatin 1.54 gelatin dynamite 1.55 ballastite 1.6 forsite 1.51 tonite 1.28 robierite 1.40 bellite 1.2 to 1.4 carbodynamite 1.5 terpenes cast picric acid 1.6 nitromanite 1.6 nitrostarch 1.5 emancite 1.8 mononitrobenzene 1.2 metadinitrobenzene 1.575 at 18 degrees Celsius. Orthodinitrobenzene 1.590. Paradinitrobenzene 1.625. British gunpowder, EXC 1.80. SBC 1.85 cannonite, powder, 1.60. Celluloid 1.35 cellulose 1.45 ammonium nitrate 1.707 mercury fulminate 4.42. Table of the temperature of detonation. Blasting gelatin 3220 degrees nitroglycerin 3170 degrees dynamite 2940 degrees guncotton 2650 degrees tonite 2648 degrees picric acid 2620 degrees robierite 2100 degrees ammonia nitrate 1130 degrees. Relative Sensitiveness to Detonation, by Professor C. Monroe, U.S. Naval Torpedo Station. Underscore 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 maximum distance at which detonation occurred. Centimeter, guncotton, 10, nitroglycerin 86.5 nitrocotton, 9.5 camphor 4%, explosive gelatin, 20, NH_4, no_3, 5 parts, camphorated, C_6, H_4, N0_3, 2, 1 part. Judson powder, RRP, 25, emancite number 25930, Racaroc, 32, Clo 379 parts, C_6, H_5, no_2, 21 parts. Bellite, 50, Forsyte number 1, 61, Kieselguhr dynamite number 1, 64, 75%, nitroglycerin. Atlas powder number 1, 74. Underscore 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 underscore. Chapter 9. Determination of the relative strength of explosives. Effectiveness of an explosive, high and low explosives, theoretical efficiency, MMRU and Serraul's results. Abel and Nobel's ballistic test, the mortar, pressure, or crusher gauge, Leeds cylinders, the foot-pounds machine, Nobel's pressure gauge, Lieutenant Walk's results, calculation of pressure developed by dynamite and guncotton, McNabb's and Ristori's results of heat developed by the explosion of various explosives, composition of some of the explosives in common use for blasting, and c. The determination of the relative strength of explosives. Explosives may be roughly divided into two divisions, viz., those which when exploded produce a shattering force, and those which produce a propulsive force. Explosives of the first class are generally known as the high explosives, and consist for the most part of nitro compounds, or mixtures of nitro compounds with other substances. Any explosive whose detonation is very rapid is a high explosive, but the term has chiefly been applied to the nitro-explosives. The effectiveness of an explosive depends upon the volume and temperature of the gases formed, and upon the rapidity of the explosion. In the high explosives the chemical transformation is very rapid, hence they exert a crushing of shattering effect. Gunpowder, on the other hand, is a low explosive, and produces a propelling or heaving effect. The maximum work that an explosive is capable of producing is proportionate to the amount of heat disengaged during its chemical transformation. This may be expressed in kilogram meters by the formula 425Q, where Q is the number of units of heat evolved. The theoretical efficiency of an explosive cannot, however, be expected in practice for many reasons. In the case of blasting rock, for instance, frowny face A, 1. Incomplete combustion of the explosive. 2. Compression and chemical changes induced in the surrounding material operated on. 3. Energy expended in the cracking and heating of the material which is not displaced. 4. The escape of gas through the blast hole, and the fissures caused by the explosion. The proportion of useful work has been estimated to be from 14 to 33% of the theoretical maximum potential. Footnote A. C.N. Hake, Government Inspector of Explosives, Victoria, Jure SOC Chem. IND, 1889. For the purposes of comparison, manufacturers generally rely more upon the practical than the theoretical efficiency of an explosive. These, however, stand in the same relation to one another, as the following table of Messrs. Roux and Serrault will show. Mechanical equivalent of explosives. Theoretical work relative in kilos. Value. Blasting powder, 62%. No_3, 242,335 1.0 dynamite 75%. Nitroglycerin, 548,252.26 blasting gelatin, 92%. Nitroglycerin. 766,813 3.16 nitroglycerin 794,563 3.28. Experiments made in lead cylinders give dynamite 1.0 blasting gelatin 1.4 nitroglycerin 1.4. Sir Frederick Abel and Captain W. H. Noble, R.A., have shown that the maximum pressure exerted by gunpowder is equal to 486 foot-tons per pound of powder, or that when 1 kilo of the powder gases occupy the volume of 1 liter, the pressure is equal to 6,400 atmospheres. And Berthelot has calculated that every gram of nitroglycerin exploded gives 1,320 units of heat. M. Roux and Serrao, of the Dépôts Centrales de Poudres, Paris, by means of calorimetric determinations, have shown that the following units of heat are produced by the detonation of nitroglycerin 1,784 heat units, guncotton 1,123, potassic picrate 840, which, multiplied by the mechanical equivalent per unit, gives nitroglycerin 778 megatons per kilogram, guncotton 489, picrate of potash 366. Nobel's ballistic test. Alfred Nobel was the first to make use of the mortar test to measure the ballistic power of explosives. The use of the mortar for measuring the relative power of explosives does not give very accurate results, but at the same time the information obtained is of considerable value from a practical point of view. The mortar consists of a solid cylinder of cast iron, one end of which has been bored to a depth of 9 inches, the diameter of the bore being 4 inches. At the bottom of the borehole is a steel disc 3 inches thick, in which another hole has been bored 3 inches by 2 inches. The mortar, figure 54, itself is fitted with trunnions, and firmly fixed in a very solid wooden carriage, which is securely bolted down to the ground. The shot used should weigh 28 pounds, and be turned accurately to fit the bore of the mortar. Down its center is a hole through which the fuse is put. The following is the method of making an experiment. A piece of hard wood is turned in the lathe to exactly fit the hole in the steel disc at the bottom of the bore. This wooden cylinder itself contains a small cavity into which the explosive is put. 10 grams is a very convenient quantity. Before placing in the mortar, a hole may be made in the explosive by means of a piece of glass rod of such a size that the detonator to be used will just fit into it. After placing the wooden cylinder containing the explosive in the cavity at the bottom of the bore, the shot, slightly oiled, is allowed to fall gently down onto it. A piece of fuse about a foot long, and fitted with the detonator, is now pushed through the hole in the center of the shot until the detonator is embedded in the explosive. The fuse is now lighted, and the distance to which the shot is thrown is carefully measured. The range should be marked out with pegs into yards and fractions of yards, especially at the end opposite to the mortar. The mortar should be inclined at an angle of 45 degrees. In experimenting with this apparatus, the force and direction of the wind will be found to have considerable influence. Illustration: Figure 54. Mortar for measuring the ballistic power of explosives. A. Shot. B. Steel disc. C. Section of mortar, cast iron. D. Wooden plug holding explosive. E. F. Fuse. Mr. T. Johnson made some ballistic tests. He used a steel mortar and a shot weighing 29 IBS, and he adopted the plan of measuring the distance to which a given charge, 5 grms, would throw the shot. He obtained the following results. Range in feet. Blasting gelatin, 90%, nitroglycerin and nitrocellulose, 392 ammonite, 60%, No_3 and 10%, nitronaphthalene, 310 gelignite, 60%, nitrogelatin and guncotton, 306 robierite, No_3, and chloronitrobenzol, 294 No. 1 dynamite, 75%, nitrogelatin, 264 stonite, 68%, nitrogelatin and 32%, woodmeal, 253 guncotton, 234 tonite, guncotton and nitrates, 223 carbonite, 25%, nitrogelatin, 40%, woodmeal, and 30% nitrates, 198 securite, No_3, and nitrobenzol, 183 gunpowder 143. Calculation of the volume of gas evolved in an explosive reaction. The volume of gas evolved in an explosive reaction may be calculated, but only when they are simple and stable products, such calculations being made at 0 degrees and 760 millimeters. Let it be required, for example, to determine the volume of gas evolved by 1 gram molecule of nitroglycerin. The explosive reaction of nitroglycerin may be represented by the equation C_3H_5 O_3 No_2 3 equals 3 co 2 plus 2-1/2H_2 O plus 1-1/2 N_2 plus 1/4 O_2 by weight 227 is equal to 132 plus 45 plus 42 plus 8 by volume 2 is equal to 3 plus 2.5 plus 1.5 plus 1/4. The weights of the several products of the above reactions are calculated by multiplying their specific gravities by the weight of 1 liter of hydrogen at 0 degrees Celsius and 760 millimeters, 0.0896 grm. Thus, 1 liter of CO_2 is equal to 22 times 0.0896 equals 1.9712 grm. H_2 O equals 9x equals 0.8064 and _2 equals 14x equals 1.2544 O_2 equals 16x equals 1.4336. The volume of permanent gases at 0 degrees and 760 millimeters is constant, and assuming the gram as the unit of mass, is found to be 22.32 liters. Thus, volume of 44 of CO_2 at 0 degrees and 760 millimeters equals 44 divided by 1.9712 is equal to 22.32 liters. 18 H_2 O equals 18 divided by 0.8044 is equal to 22.32, 28, N_2 equals 28 divided by 1.2544 is equal to 22.32, 32, O_2 equals 32 divided by 1.4366 is equal to 22.32. Therefore, 132 grms of CO_2 at 0 degrees Celsius and 760 millimeters is equal to 22.32 times 3 equals 66.96 liters. 45 H_2 O equals 22.32 times 2 minus 1 divided by 2 is equal to 55.80. 42 N_2 equals 22.32 times 1 minus 1 divided by 2 is equal to 33.48. 8 O_2 is equal to 22.32 times 1/4 equals 5.58. Underscore 161.82. Therefore 1 gram molecule or 227 grms of nitroglycerin when exploded produces 161.82 liters of gas at 0 degrees Celsius and 760 millimeters. To determine the volume of gas at the temperature of explosion, we simply apply the law of Charles. A thus, V T or V equals VT/T, in which V represents the original volume, V, new volume, T, original temperature on the absolute scale, T, new temperature of the same scale in the present case T equals 6001 degrees. Therefore substituting we have V equals 161.82 times 6001 divided by 273 is equal to 3,557 liters. Or at the temperature of explosion 1 gram molecule of nitroglycerin produces 3,557 liters of permanent gas. Footnote A. According to the law of Charles, the volume of any gas varies directly as its temperature on the absolute scale, provided the pressure remains constant. Knowing the temperature on the centigrade scale, the corresponding temperature on the absolute scale is obtained by adding 273 to the degrees centigrade. Pressure or crusher gauge. There are many forms of this instrument. As long ago as 1792, Count Rumford used a pressure gauge. The so-called crusher gauge was, however, first used by Captain Sir Andrew Noble in his researches on powder. Other forms are the Rodman, A. Punch Ucacius Eprouvet, and the crusher gauge of the English Commission on Explosives. They are all based either upon the size of an indent made upon a copper disc by a steel punch fitted to a piston, acted upon by the gases of the explosive, or upon the crushing or flattening of copper or lead cylinders. Footnote A. Invented by General Rodman, United States Engineers. Illustration, Figure 55. Pressure gauge. Berthelot uses a cylinder of copper, as also did the English Commission, but in a simpler form of apparatus mostly used by manufacturers. Lead cylinders are used. This form of apparatus, Figure 55, consists of a base of iron to which 4 uprights are fixed, set round the circumference of a 4-inch circle. The lead plug rests upon the steel base let into the solid iron block. A ring C holds the uprights D together at the top. The piston B, which rests upon the lead plug, is a cylinder of tempered steel 4 inches in diameter and 5 inches in length. It is turned away at the sides to lighten it as much as possible. It should move freely between the uprights D. In the top of this cylinder is a cavity to hold the charge of explosive. The weight of this piston is 12 1/4 pounds. The shot E is of tempered steel, and 4 inches in diameter and 10 inches in length, and weighs 34 1/2 pounds. It is bored through its axis to receive a capped fuse. The instrument is used in the following manner: a plug of lead 1 inch long and 1 inch in diameter, and of a cylindrical form, is placed upon the steel plate between the uprights A, the piston placed upon it, the carefully weighed explosive placed in the cavity, and the shot lowered gently upon the piston. A piece of fuse, with the detonator fixed at one end, is then pushed through the hole in the shot until it reaches the explosive contained in the cavity in the piston. The fuse is lighted. When the charge is exploded, the shot is thrown out, and the lead cylinder is more or less compressed. The lead plugs must be of a uniform density and homogeneous structure, and should be cut from lead rods that have been drawn, and not cast separately from small masses of metal. Illustration, Figure 56. B. Steel punch. C. Lead cylinder for use with pressure gauge. The strength of the explosive is proportional to the work performed in reducing the height of the lead, or copper, plug, and to get an expression for the work done it is necessary to find the number of foot-pounds, or kilogram-meters, required to produce the different amounts of compression. This is done by submitting exactly similar cylinders of lead to a crushing under weights acting without initial velocity, and measuring the reduced heights of the cylinders. From these results a table is constructed establishing empirical relations between the reduced heights and the corresponding weights. The cylinders are measured both before and after insertion in the pressure gauge by means of an instrument known as the micrometer calipers, Figure 57.A. Footnote A. An instrument called a foot-pounds machine has been invented by Lieutenant Quinnen, U.S. Army. It consists of 3 boards, connected so as to form a slide 16 feet high, in which a weight, the shot of the pressure gauge, can fall freely. One of the boards is graduated into feet and half feet. The horizontal board at the bottom, upon which the others are nailed, rests upon a heavy post set deep in the ground, upon which is placed the piston of the gauge, which in this case serves as an anvil on which to place the lead cylinders. The shot is raised by means of a pulley, fixed at the top of the structure, to any desired height, and let go by releasing the clutch that holds it. The difference between the original length and the reduced length gives the compression caused by the blow of the shot in falling, and gives the value in foot-pounds required to produce the different amounts of compression. V. Jure, U.S. Naval INST, 1892. Illustration, Figure 57. Micrometer calipers for measuring diameter of lead cylinders. The use of lead cylinders. The method of using lead cylinders to test the strength of an explosive is a very simple affair, and is conducted as follows. A solid cast lead cylinder, of any convenient size, is bored down the center for some inches, generally until the borehole reaches to about the center of the block. The volume of this hole is then accurately measured by pouring water into it from a graduated measure, and its capacity in cubic centimeters noted. The borehole is then emptied and dried, and a weighed quantity, say 10 grams, of the explosive pressed well down to the bottom of the hole. A hole is then made in the explosive, if dynamite, with a piece of clean and rounded glass rod, large enough to take the detonator. A piece of fuse, fitted with the detonator, is then inserted into the explosive and lighted. After the explosion, a large pear-shaped cavity will be found to have been formed, the volume of which is then measured in the same way as before. The results thus obtained are only relative, but are of considerable value for comparing dynamites among themselves, or gun-cottons. Experiments in lead cylinders gave the relative values for nitroglycerin 1.4, blasting gelatin 1.4, and dynamite 1.0. Figure 58 shows sections of lead cylinders before and after use. Illustration: Figure 58. Lead cylinders before and after use. Standard regulations for the preparation of lead cylinders may be found in the Chem. Zeit. 1903, 27, 74, 898. They were drawn up by the 5th International Congress of Abchem, Berlin. The cylinder of lead should be 200 mm in height and 200 mm in diameter. In its axis is a borehole, 125 mm deep and 25 mm in diameter. The lead used must be pure and soft, and the cylinder used in a series of tests must be cast from the same melt. The temperature of the cylinders should be 15 degrees to 20 degrees throughout. 10 grams of explosives should be used and wrapped in tinfoil. A detonator with a charge of 2 grams, to be fired electrically, is placed in the midst of the explosive. The cartridge is placed in the borehole, and gently pressed against the bottom, the firing wires being kept in central position. The borehole is then filled with dry quartz sand, which must pass through a sieve of 144 meshes to the square centimeter, the wires being 0.35 mm diameter. The sand is filled in evenly, any excess being leveled off. The charge thus prepared is then fired electrically. The lead cylinder is then inverted, and any residues removed with a brush. The number of cc of water required to fill the cavity, in excess of the original volume of the borehole, is a measure of the strength of the explosive. The results are only comparable if made with the same class of explosive. A result is to be the mean of at least 3 experiments. The accuracy of the method depends on a. The uniform temperature of the lead cylinder, 15 degrees to 20 degrees Celsius. 7. B. On the uniformity of the quartz sand. C. On the uniformity of the measurements. Illustration: Figure 59. Noble's pressure gauge. Noble's pressure gauge. The original explosive vessels used by Captain Sir A. Noble in his first experiments were practically exactly similar to those that he now employs, which consists of a steel barrel A, Figure 59, open at both ends, which are closed by carefully fitted screw plugs, furnished with steel gas checks to prevent any escape past the screw. The action of the gas checks is exactly the same as the leathers used in hydraulic presses. The pressure of the gas acting on both sides of the annular space presses these sides firmly against the cylinder and against the plug, and so effectually prevents any escape. In the firing plug F is a conical hole closed by a cone fitting with great exactness, which, when the vessel is prepared for firing, is covered with fine tissue paper to act as an insulator. The 2 firing wires GG, one in the insulated cone, the other in the firing plug, are connected by a very fine platinum wire passing through a glass tube filled with meal powder. The wire becomes red hot when connection is made with a Leclanche battery, and the charge which has previously been inserted into the vessel is fired. The crusher plug is fitted with a crusher gauge H for determining the pressure of the gases at the moment of explosion, and in addition there is frequently a second crusher gauge apparatus screwed into the cylinder. When it is desired to allow the gases to escape for examination, the screw J is slightly withdrawn. The gases then pass into the passage I, and can be led to suitable apparatus in which their volume can be measured, or in which they can be sealed for subsequent chemical analysis. The greatest care must be exercised in carrying out experiments with this apparatus. It is particularly necessary to be sure that all the joints are perfectly tight before exploding the charge. Should this not be the case, the gases upon their generation will cut their way out, or completely blow out the part improperly secured, in either case destroying the apparatus. The effect produced upon the apparatus when the gas has escaped by cutting a passage for itself is very curious. The surface of the metal where the escape occurred presents the appearance of having been washed away in a state of fusion by the rush of the highly heated products. The pressure gauge. The pressure is found by the use of a little instrument known as the pressure gauge, which consists of a small chamber formed of steel, inside of which is a copper cylinder, and the entrance being closed by a screw gland, in which a piston, having a definite sectional area, works. There is a gas check E, figure 60, placed in the gland, and over the piston, which prevents the admission of gas to the chamber. When it is desired to find the pressure in the chamber of a gun, one or more of these crushers are made up with or inserted at the extreme rear end of the cartridge, in order to avoid their being blown out of the gun when fired. This, however, often takes place, in which case the gauges are usually found a few yards in front of the muzzle. The copper cylinders which register the pressure are made 0.5 inch long from specially selected copper, the diameters being regulated to give a sectional area of either 1/12 or 1/24 square inch. Illustration, figure 60. Crusher gauge. E gas check. Hollow copper cylinders are manufactured with reduced sectional areas for measuring very small pressures. It has been found that these copper cylinders are compressed to definite lengths for certain pressures with remarkable uniformity. Thus, a copper cylinder having a sectional area of 1/12 square inch, and originally half an inch long, is crushed to a length of 0.42 inch by a pressure of 10 tons per square inch. By subsequently applying a pressure of 12 tons per square inch, the cylinder is reduced to a length of 0.393 inch. Before using the cylinders, whether for experimenting with closed vessels or with guns, it is advisable to first crush them by a pressure a little under that expected in the experiment. Captain Sir A. Noble used in his experiments a modification of Rodman's gauge. Ordnance Department, USA, 1861. By calculation. To calculate the pressure developed by the explosion of dynamite in a borehole 3 centimeters in diameter, charged with 1 kilogram of 75% dynamite, Messrs. VA and Serrao employed the following formula. P equals V underscore O 1 plus Q/273 C/VV, where V underscore O equals the volume, reduced to 0 degrees and 760 millimeters, of the gases produced by a unit of weight of the explosive, Q the number of calories disengaged by a unit of weight of the explosive, C equals the specific heat at constant volume of the gases, V the volume in cubic centimeters of a unit of weight of the explosive, V the volume occupied by the inert materials of the explosive. The volume of gas produced by the explosion of 1 kilogram of nitroglycerin, at 0 degrees and 760 millimeters, is 467 liters. V underscore O will therefore equal 0.75 times 467 equals 350.25. The specific heat C is, according to Serrao, 0.220 C, and according to Bunsen, 1 kilogram of dynamite number 1 disengages 1,290 Q calories. The density of dynamite is equal to 1.5, therefore. V equals 1/1.5 equals 0.666. If we take the volume of the Kieselguhr as 0.1, we find from above formula that P equals 350, 1 plus 1290/273 by 0.222 /.600.1 equals 13,900 atmospheres, which is equal to 14,317 kilograms per square centimeter. The pressure developed by 1 kilogram of pure nitroglycerin equals 18,533 atmospheres, equals 19,151 kilograms. Applying this formula to gun cotton, and taking after Berthelot, Q equals 1,075, and after VA and Serrao, V underscore O equals 671 liters, and C as 0.2314, and the density of the nitrocellulose as 1.5, we have V equals 0. P equals 671, 1 plus 1075/273 by 0.2314, /.666 equals 18,135 atmospheres. To convert this into pressure of kilograms per square centimeter, it is necessary to multiply it by the weight of a column of mercury 0.760 m high, and 1 square centimeter in section, which is equal to increasing it by January 30th. It thus becomes P(K) equals 1 plus 1/30th. P(K) equals 18,135 x 1.033 is equal to 18,733 kilograms. The following tables, taken from Messrs. William McNabbs and E. Ristori's paper, Prop. Roy. SOC 56, 8-19. Researches on modern explosives, are very interesting. They record the results of a large number of experiments made to determine the amount of heat evolved, and the quantity and composition of the gases produced when certain explosives and various smokeless powders were fired in a closed vessel from which the air had been previously exhausted. The explosions were carried out in a calorimetric bomb of Berthelot's pattern. A. Footnote A. For description of bomb. C. Explosives and their power. Berthelot trans. By Hake and McNabb, page 150. Murray. Table showing quantity of heat and volume and analysis of gas developed per gram with different sporting and military smokeless powders now in use. Underscore 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 underscore. Name of explosive. Calories, permanent, aqueous, total volume, per grm. Gases. Vapor. Of gas at 0 degrees, and 760 millimeters. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 cc/grm 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 EC powder English 800, 420, 154, 574, SS powder, 799, 584, 150, 734, Troisdorf, German, 943, 700, 195, 895, Riflight, English, 864, 766, 159, 925, Bien, French, 833, 738, 168, 906, Cordite, English, 1253, 647, 235, 882, Ballastite, German, 1291, 591, 231, 822, Ballastite, Italian, 1317, 58L, 245, 826, and Spanish, underscore 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 underscore. The figures in column headed coefficient of potential energy serve as a measure of comparison of the power of the explosives, and are the products of the number of calories by the volume of gas, the last three figures being suppressed in order to simplify the results. The amounts of water found were calculated for comparison as volumes of H_2O gas at 0 degrees and 760 millimeters. EC powder consists principally of nitrocellulose mixed with barium nitrate and a small proportion of camphor. Excess of nitrolignin mixed with barium nitrate and nitrobenzene. Troisdorf powder is gelatinized nitrocellulose, Rhyphlite gelatinized nitrocellulose, and nitrobenzene. Cordite contains 58%, nitroglycerin 37%, guncotton, and 5%, Vaseline. Ballastite, Italian, consists of equal parts nitrocellulose and nitroglycerin, and 0.5% of aniline. The German contains a higher percentage of nitrocellulose. Table showing the heat developed by explosives containing nitroglycerin and nitrocellulose in different proportions. Underscore 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 underscore. Composition of explosives. Calories percent underscore 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 nitrocellulose n equals 13.3%. Nitroglycerin 100%. Dry pulp 0 1061 100. Gelatinized 0 922.90. 10%, 1044.80, 20, 1159.70, 30, 1267.60, 40, 1347.50, 50, 1410.40, 60, 1467.0, 100. 1652 underscore 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 nitrocellulose n equals 12.24%. Nitroglycerin 80%, 20%, 1062.60, 40, 1288.50, 50, 1349.40, 60, 1405. underscore 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 nitrocellulose N equals 13.3%. Nitroglycerin. Vaseline. 55%, 40%, 5%, 11343565. 1280 underscore 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 Table of results obtained by Lieutenant W. Walk of the Artillery U.S.A. with Quinnan's pressure gauge. Nitroglycerin being taken as 100. From U.S. Naval INST underscore 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 compression order of name of explosive of lead strength inch. Explosive gelatin, 0.585, 106.17, Hellhoffite, 0.585, 106.17, nitroglycerin, 0.551, 100.00, standard, NG Nobel's smokeless powder, 0.509, 92.38, nitroglycerin, 0.509, 92.37, guncotton, 0.458, 83.12, U.S. Naval torpedo, guncotton, 0.458, 83.12, Stowmarket. Nitroglycerin, 0.451, 81.85, Vosges, NG guncotton, 0.448, 81.31, dynamite number 1, 0.448, 81.31, dynamite Detrol, 0.437, 79.31, emmonsite, 0.429, 77.86, amide powder, 0.385, 69.87, oxonite, 0.383, 69.51, tonight, 0.376, 68.24, GC 52.5%, and BA, no underscore, 3, underscore, 2, 47.5% Bellite, 0.362, 65.70, Rakarok, 0.340, 61.71. Atlas powder, 0.333, 60.43, ammonia dynamite, 0.332, 60.25, Volney's powder number 1, 0.322, 58.44, nitrate naphthalene, number 2, 0.294, 53.18, melanite, 0.280, 50.82, picric acid 70%, and sol. Nitro cotton 30%. Silver fulminate 0.277, 50.27, mercury 0.275, 49.91, mortar powder 0.155, 28.13. Underscore 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 underscore. Composition of some of the explosives in common use. Ordinary dynamite. Nitroglycerin 75%, Kieselguhr 25. Amvis. Nitrate of ammonia 90%, chlorodinitrobenzene 5. Wood pulp 5. Ammonia nitrate powder. Nitrate of ammonia 80%, chloride of potash 5. Nitroglucose 10. Coal tar 5. Celtite. Nitroglycerin 56 to 59 parts. Nitrocotton 2 to 3.5. No underscore 3, 17 to 21. Wood meal 8 to 9. Ammonium oxalate 11 to 13. Moisture 0.5 to 1.5. Atlas powders. Sodium nitrate 2%, nitroglycerin 75.0. Wood pulp 21.0. Magnesium carbonate 2.0. Dahlin. Nitroglycerin 50%, sawdust 30. Nitrate of potash 20. Vulcan powder. Nitroglycerin 30%, nitrate of soda 52.5. Sulfur 7.0. Charcoal 10.5. Vigorite. Nitroglycerin 30%, nitrate of soda 60, charcoal 5, sawdust 5. Rendrock. Nitrate of potash 40%, nitroglycerin 40. Wood pulp 13. Paraffin or pitch 7. Ammonia nitrate powder. Ammonia nitrate 80%, potassium chlorate 5. Nitroglucose 10. Coal tar 5. Hercules powders. Nitroglycerin 75 to 40%, sugar 1. 15.66. Chloride of potash 1.05. 3.34. Nitrate of potash 2.10. 31.00. Carbonate of magnesia 20.85. 10.00. Carbodynamite. Nitroglycerin 90%, charcoal 10. Gelexite permitted list. Nitroglycerin 64 to 54 parts. Nitrocotton 5 to 4. Nitrate of potash 22 to 13. Ammonium oxalate 15 to 12. Red ochre 1 to 0. Wood meal 7 to 4. The wood meal to contain not more than 15% and not less than 5% moisture. Giant powder. Nitroglycerin 40%, sodium nitrate 40. Rosin 6, sulfur 6, Gur8. Dynamite tetrazoyl. Nitroglycerin 75 parts. Guncotton 25. Charcoal 2. Rhenish dynamite. Solution of Ng and naphthalene 75%, chalk or barium sulfate 2. Kieselguhr 23. Ammonia dynamite. Ammonia nitrate 75 parts. Paraffin 4, charcoal 3. Nitroglycerin 18. Blasting gelatin. Nitroglycerin 93%, nitrocotton 3 to 7. Gelatin dynamite. Nitroglycerin 71%, nitrocotton 6. Wood pulp 5. Potassium nitrate 18. Gelignite. Nitroglycerin 60 to 61%, nitrocotton 4, 5. Wood pulp 9, 7. Potassium nitrate 27. Fursite. Nitroglycerin 49%, nitrocotton 1.0. Sulfur 1.5. Tar 10.0. Sodium nitrate 38.0. Wood pulp 5. The N, G, NC, varies. Tonight no. 1. Guncotton 52 to 50%, barium nitrate 47 to 40. Tonight no. 2. Contains charcoal also. Tonight no. 3. Guncotton 18 to 20%, BA no _3 _270. 67. Dinitrobenzol 11. 13. Moisture 0.5. 1. Carbonite. Nitroglycerin 17.76%, nitrobenzene 1.70. Soda 0.42. No _3 34.22. BA no _3 _29.71. Cellulose 1.55. Cane sugar 34.27. Moisture 0.36. _______________________ 99.99. Roburite. Ammonium nitrate 86%, chlorodinitrobenzol 14. Faversham powder. Ammonium nitrate 85%, dinitrobenzol 10. Trench's flame extinguishing compound 5. Favorite no. 1. Ammonium nitrate 88%, dinitronaphthalene 12. Favorite no. 2. Number 1 powder 90%, amine. Chloride 10. Bellite. Ammonium nitrate 5 parts. Metadinitrobenzol 1. Petrofactor. Nitrobenzene 10%, chloride of potash 67. Nitrate of potash 20. Sulfate of antimony 3. Securite. Mixtures of metadinitrobenzol 26% and nitrate of ammonia 74. Rakarok. Potassium chlorate 79 parts. Mononitrobenzene 21. Oxenite. Nitric acid SPGR 1.5, 54 parts. Picric acid 46. Emancite. Emmons acid 5 parts. Ammonium nitrate 5. Picric acid 6. Bruguera powder. Ammonium picrate 54%, nitrate of potash 46. Designose torpedo powders. Potassium picrate 55 to 50%, nitrate of potash 45. 50. Stoite. Nitroglycerin 58 to 61 parts. Nitrocotton 4.5. 5. Potassium nitrate 18. 20. Wood meal 6. 7. Oxalate of ammonia 11. 15. The wood meal shall contain not more than 15% and not less than 5% by weight of moisture. The explosive shall be used only when contained in a non-waterproofed wrapper of parchment. Number 6 detonator. Faversham powder. Nitrate of ammonium 93 to 87, trinitrotoluol 11. 9 moisture 1. Kyanite. Nitroglycerin 24 to 26 parts. Wood pulp 2.5 to 3.5. Starch 32.5 to 3.5. Barium nitrate 31.5 to 34.5. Caco _30 to 0.5. Moisture 3.0 to 6.0. Must be put up only in waterproof parchment paper, and number 6 electric detonator used. Rexite. Nitroglycerin 6.5 to 8.5 parts. Ammonium nitrate 64 to 68. Sodium nitrate 13 to 16. Trinitrotoluene 6.5 to 8.5. Wood meal 3 to 5. Moisture 0.5-1.4. Must be contained in waterproof case, stout paper, waterproofed with resin and saracen, number 6 detonator. With Nell powder. Ammonium nitrate 88 to 92 parts. Trinitrotoluene 4 to 6. Flour, dried at 100 degrees Celsius. 4 to 6. Moisture 0 to 15. Only to be used when contained in a linen paper cartridge, waterproofed with carnauba wax, paraffin, number 7 detonator used. Phoenix powder. Nitroglycerin 28 to 31 parts. Nitrocotton 0 to 1. Potassium nitrate 30 to 34. Wood meal 33 to 37. Moisture 2 to 6. Smokeless powders. Cordite. Nitroglycerin 58%, plus or 0.75 nitrocotton 37, plus or 0.65 Vaseline 5. plus or 0.25. Cordite M.D. Nitroglycerin 30%, plus or 1 nitrocotton 65, plus or 1 Vaseline 5, plus or 0.25. Analysis of, by W. Mancab and A. Layton. E.C. Powder. Nitrocotton 79%, potassium nitrate 4.5, barium nitrate 7.5, camphor 4.1, wood meal 3.8, volatile matter 1.1. Wallerode powder. Nitrocotton 98.6%, volatile matter 1.4. Kainaka's smokeless. Nitrocotton 52.1%, dinitrotoluene 19.5, potassium nitrate 1.4, barium nitrate 22.2, wood meal 2.7, ash 0.9, volatile matter 1.2. Schulze. Nitrolingen 62.1%, potassium nitrate 1.8, barium nitrate 26.1, Vaseline 4.9, starch 3.5, volatile matter 1.0. Imperial Schulze. Nitrolignin 80.1%, barium nitrate 10.2, Vaseline 7.9, volatile matter 1.8. Cannonite. Nitrocotton 86.4%, barium nitrate 5.7, Vaseline 2.9, lamp black 1.3, potassium ferrocyanide 2.4, volatile matter 1.3. Amberite. Nitrocotton 71%, potassium nitrate 1.3, barium nitrate 18.6, wood meal 1.4, Vaseline 5.8. Sporting ballastite. Nitroglycerin 37.6%, nitrocotton 62.3, volatile matter 0.1. The following is a complete list of the permitted explosives as defined in the schedules to the Explosives and Coal Mines Orders of the December 20, 1902, of the December 24, 1903, of the September 5, 1903, and December 10, 1903. Albionite. Aminal. Ammonite. Amvis. Aphosite. Archite. Bellite No. 1. Bellite No. 2. Bobinite. Britonite. Cambrite. Carbonite. Clydite. Coronite. Dominite A. Dragonite. Electronite. Faversham powder. Fracturite. Gelexite. Halite No. 1. Kyanite. Negro powder. Nobel's Ardere powder. Nobel carbonite. Normanite. Pittite. Roburite No. 3. Saxonite. Stoite. Thunderite. Victorite. Virite. Westphalite No. 1. Westphalite No. 2.